As you can tell, we are working from our homes, so this will be an interesting way to do this for all of us. But I think we're all looking forward to doing Moose this way, and I think we'll get a lot of participation. So um, let's get started. I want to go over a couple of things that we'll talk about here. So first of all, I'm Cody Perman. I'm the department manager for the Moose team, and I'm going to be introducing several of my staff here momentarily. So you should also be able to see Derek Gaston as well. He should be on your screen. Hi, Derek, and he's going to be doing some of the training as well as several others. So let's go ahead and meet the rest of the team. Andrew Slaughter, would you go ahead and turn on your webcam, please?
Yo, hello.
So Andrew Slaughter, Casey Eisenhower.
Hey.
Casey, thank you. Alexander Lindsay. Alex, can you turn on your webcam? There he is. Thanks, Alex. Next, we have Logan Harbor. Hello, Logan. And then we have Fendi Kong.
Hey, Fendi.
Okay, thanks. All right, so let's talk about GoToWebinar for just a minute. You guys should have a control panel, and there's a few things I want to draw attention to in your control panel. First off, there is an ability to communicate with us in a couple of different ways here. So there's a raise hand button, and if you want to look for that, it should be, if you have the control panel up, it should be to the left, kind of like a little window that hangs off to the left there. If you guys want, go ahead and click that now. I can see a couple of hands raising. That's great. That's great. Cool. So this will be a good way to interrupt us while we're doing the while we're talking about things. We have a moderator that'll be in here all the time, and if you guys have a question, want to interrupt us, go ahead and click the raise hand symbol. Our moderator will find a good way to communicate with the presenter, and we'll allow you to ask a question live, turning on your mics if you have the capability to do that. If you don't have a mic or you don't want to talk on the webinar, there's also a couple of other ways you can get a hold of us. There is a chat feature in the GoToWebinar control panel, so you're welcome to just go down there and chat, or you can ask a question as well. So you can see those two panels. So we'll have several moderators watching and asking questions. The nice thing about doing it in webinar is it will be recorded, so it'll be part of the next session when we make this available. I've already been asked if this will be available on our website. Yes, we are planning to make this recording available, so if you can't attend or you have colleagues or other people that want to see it later, they'll be able to watch this. So having those questions captured is a great way of doing it. Let's move along here. I'm going to show my, you can see my web browser here. So this is just taking you to the mooseframework.org webpage. And hopefully many of you have found that if you haven't before, but here it is. A couple of things I want to draw your attention to. If you scroll down just a little bit, you'll see the workshop link where you can sign up. Everybody's either done that through the mailing list already or found it on here. We've recently added a schedule, so you can kind of get an idea of how the next 2 days are laid out. You can see the presenter, the assigned moderators for these sections. So if you can't attend for the entire 2 days or you need to hop in and out, you can take a look at this schedule and get an idea of how things are laid out. Yes, we will be scheduling a full hour for lunch breaks. So you'll have that opportunity to, go do other things, check your emails, or actually eat lunch. That would be great. So that's another way of knowing what's going on.
Hey, Cody, it might be important to point out that all those times are in Mountain Time.
Yes, that's very important. So
US Mountain Time.
US Mountain Time. So you probably understand that, but that's just to be clear, that's Mountain Time. Couple of other important ways. So we have We have the raise hand to get a hold of us. We have the questions. We have the chat. So that's 3 ways right here in GoToWebinar. The other way that I would highly encourage if your questions are a little bit more drawn out, or maybe you need some more advanced help, is to take a look at our Getting Started page here. And if you scroll down through here for a ways, there's this Join Our Community bold here, and you can send messages to our mailing list. So those of you who have not joined our mailing list in the past, this is a very responsive group, very active. So there's a lot of people in the community who can help you there as well.
Cody, just so you know, chat's not available for attendees.
Okay, so chat is not available, but questions are. Thank you, Alex. Okay, so with that in mind, I currently have 8 people with their hands raised. I'm assuming that maybe you guys just haven't. Yeah, let's go ahead. I'm going to go ahead and, or maybe one of the moderators can lower the hands. Let's lower them one more. Let's make sure everybody's hands lowered so that we don't have any false positives. And if there's any questions, you guys are welcome to ask them.
Cody, would you like to discuss Slack?
Slack. Okay, so one other thing that we'd like for our attendees to use is we have created a Slack channel that you can join. Slack is just another chat utility, and one of the moderators will be posting that link here in the chat window right now. So if you'd like to install or use Slack to chat with us kind of more in real time, that's yet another way of communicating with us. So hopefully we have several ways that you guys can interact with us through this webinar. I guess with that in mind, is there anything else I'm missing from any of the moderators that you guys want to talk about? Okay, so I'm going to hand this off to.
Cody, do you want to talk about installation real quick? Like actually getting started?
Yeah, sure, why not? So while we're on the Getting Started page, if you haven't installed Moose before, or you are kind of working through it, this is the right place to go for instructions. So if you're on a desktop or a laptop and you need to get started, our 2 main platforms that we support are Linux and Mac OS. Yes, we support several versions of Linux, and we use Conda now to actually get the prerequisites on the machine. So we have step-by-step guide here on how to go through and get everything installed depending on your platform. So I would highly recommend that you carefully follow every instruction in these Getting Started guides. We do have limited support for Windows 10 if you want to try that. And then there are advanced manual instructions if you're installing on an HPC environment or you're trying to build from source. We do have detailed instructions on how to do that. I would recommend that you don't do this if you're on a desktop or a laptop computer. It's just an unneeded hassle. The Conda instructions really are the right way to go here.
So hopefully you have an idea what Moose is, and maybe some of you have an idea what Idaho National Laboratory is. Some of you probably know better than I, even though I work here. And these slides will just tell you a little bit about INL. It was established back in 2005. It's part of the Department of Energy, and its main purpose is for building world-class energy systems, in particular nuclear energy, R&D to be specific. This is a little bit dated now, even. I gotta go update these slides, but as a few years ago, had over $1 billion budget and pretty close to 4,000 employees. I think we probably have that now. And we have lots of interns. We have hundreds this year. There's probably a whole lot of you listening right now, so that's great. Over the years, there's been at least 52 reactors, and we're working on building a few more. One of the most notable is the EVR1. And that was one of the first to produce electricity, and it even powered a little town here in Idaho. And there's also a really wonderful museum. So usually this is where we, tell people that are visiting Idaho Falls to go out to the museum and check it out. Unfortunately, we can't do that because most of you are not here, and it's also closed. But if you ever do come through Idaho Falls when all this pandemic stuff is over, it's a wonderful museum to check out. You get to walk around the reactor and control room and different things. It's really quite good. And then the reactors that we have running, the ATR, probably a lot of you already know of it if you're in this world, and they use it for lots of different testings. It's been around since the 60s. It's a really, really interesting reactor. So if you want to know more, I encourage you to go look up more information. And then another one that's operational here is the transient reactor test facility called TREAT. This just restarted a year or two ago, and it's another really interesting reactor, and it's for doing high intensity pulses to simulate accident scenarios, and probably among other things. So with that, I'm going to jump into giving you a brief introduction to Moose and what it is and what's the purpose and things like that. So ideally, this is what we do. You guys come to us with some really wonderful equations that are really complicated and impossible to solve, and you write them down and you put them in Moose and you get out these pretty pictures. That's what we're hoping for. And conceptually, that's really what we've designed Moose to be. Of course, in practice, it's not always that easy, but the idea is if you understand your physics, you should be able to use Moose to solve those physics and hopefully get you some good scientific results that you can publish and things like that. So the history of Moose, it's been around since 2008. You met Derek already. He's the one that started it. And then we open sourced it in 2014, which was a really wonderful step for us, and it's really expanded the community. And as I mentioned, it's really designed to solve engineering problems and mainly try to reduce the amount of time that engineers and scientists spend on the software side. So it can easily be extended and maintained. We have testing infrastructure and all kinds of tools to help you build a tool and test it and things like that. And we're going to talk about all these things along the days here. And another big feature is it works on one processor, so you can fire it up your new laptop or even a virtual machine and get it to run. And then you can also go out to a supercomputer and run it on thousands, tens of thousands, and I think even up to 100,000 cores we've had a few goes at. It's something that we'll definitely be talking about more as we go. And the whole object or the whole design of the system is object oriented. If you don't know what that is, it's a programming methodology, and you'll see a little bit of it as we go along. Usually when we do this training, we teach C++ an hour or two. We probably don't have time for that in this a little bit shorter workshop, so we're just going to assume that you understand C++. If you don't let that stress you out. We will the C++ that you'll see is fairly basic, and you should be able to follow along and go brush up on C++ after the fact. And we'll even code a little bit later this afternoon. So the Moose team, you met a few of us. This is the current structure of the Moose team over the past few years. We're going to be adding a few more people to this list shortly as well. So Derek's been here the longest, and then Cody jumped in after him. You didn't get to meet David. He's been on the Moose team for quite a long time, and he works on some applications here at INL. Jason Miller, if you've been on the mailing list or if you've installed Moose, you've been blessed by Jason's hard work. He's responsible for putting all our package together. John Peterson was here for quite a while, helped us a lot with libmesh, and he went and got a new job, but he's still working on libmesh, so we still get to get some of that benefit. We just don't get to tell him what to do, but that's all right. Then myself, Brian, worked on Civet, which is a testing infrastructure that we use. We'll probably show you that along the way here. Fanda, you got to meet. Josh is also an application guy that works with David quite a bit on Relapse 7. Robert, didn't get to meet him yet. He's kind of a catch-all. He does all kinds of really good computer science work and also finite volumes he's adding to the framework. And you met Alex, and you're going to hear from him more, so I'll let him introduce himself too. So at this point too, I'm going to say a little bit more about myself, just so you guys know my background. as the slide shows, I started back in 2013 on the Moose team, but before that, I studied snow and avalanche mechanics for my PhD at Montana State University, and most of my background for my PhD was in studying snow and how it changes and may lead to an avalanche. Highly experimental work and a lot of field research, which was great because I got to go skiing all the time. But along the way, I was kind of teaching myself to write code and do simulations. And then I took a short job as a postdoc at Cornell to continue to write code. Started working with libmesh a little bit and actually started working with Moose. Then this wonderful job here at INL opened up, and I cut my postdoc short and been very happy to be part of the Moose team ever since. And on the Moose team, I work on all sorts of different things. I do a lot of the output system. There's a control system in Moose that I work on, and then do a lot with documentation, software quality, and stochastic analysis. And so these are all things that we're going to talk about briefly, some in more detail than others as we progress through these 2 days. Moose itself really is designed to be this bridge between lots of other wonderful software. So down here at the bottom, we got PETSI. That's our numerical solver. It comes from Argonne National Lab. A wonderful package for solving equations or matrices and doing complicated solver technology. On top of that, we use libmesh, which is where all our finite element magic comes from: elements, shape functions, meshes, and handles some of our equation systems and things like that. And then you have Moose, and then you have you up there in physics. So you come to Moose with a strong knowledge in physics, engineering, science, whatever you want to call it, and you use Moose to leverage all this capability down below. And the point is really that as a scientist or engineer, you might not be interested in computer science and learning how to write some of these more difficult things in code. And so hopefully we handle that for you and let you focus on your equations. So some of the generic capabilities, so this says FEM capabilities. It's pretty exciting that just in the last few weeks, we've added some basic finite volume capabilities. Somebody else might speak to that a little bit more as we go on what's currently available and what's not. It's brand new, as in, like I said, weeks old. So it's pretty exciting that we're going to be able to do that as well. Some of the key features is any code you write will work in 1, 2, and 3D without any changes. It supports continuous and discontinuous Galerkin finite elements, which if you don't know what that is, don't stress. We'll give you a little intro to finite elements. The bread and butter is fully coupled, fully implicit. That means if you have 15 equations, we put them all in the same system and solve them all at the same time. And gives you really good resolution on your problem. We have other modes to solve as well, and I'm sure Derek is going to talk about that more in detail. Another wonderful feature is automatic differentiation. This has been in there for a little while now, a year or so, but recently we've made it much better for the user. It's very easy to use, as you'll see as we go along. All sorts of different meshes for finite elements: quads, tris, tets, pyramids, all the mesh things that you would expect in a finite element package. And really interestingly too is they can all work together as well, so you can have mixed meshes. And you can even do higher order geometry. We have a really nice mesh adaptivity systems. It's almost all automatic. It's very, very unlikely that you'd have to do any programming for the mesh adaptivity. We'll have a whole section on that. I already mentioned the massively parallel with MPI. We also have thread support, so that's shared memory support, versus MPI, which is not shared memory. And we'll probably talk and show you how to run in the 2 modes as we go as well. And another important thing is, just like dimension, the parallelism and your shape functions, your code should work for all of them. So you can write really generic code with Moose. So here's the overall kind of big picture, how Moose is laid out to work. If you look at, you got Moose there in the middle of this diagram, and then surrounded by Moose is kind of this shaded box with all these other little boxes in it. So Moose is a compilation of systems. And so in this picture, we got the physics system, a materials system, auxiliary physics system, boundary conditions system. Those are just to name a few. And those are things that live down in Moose. And those are things that you can leverage and specialize to meet your needs. And so the idea is you'll end up having an input file, and I'll show you. And that input file is just going to be a bunch of blocks, and it's going to take all these little pieces and build a simulation for you. And like I said, we'll see more about that. But the idea is just anything you do in Moose is really quite modular and composed of these little pieces that, when assembled, can give you some really powerful capability. Here's just a little teaser, a little piece of code that we're going to see over and over again. And we're going to talk more about the mathematics behind this slide, but some of you are probably familiar with finite elements and weak forms. So that's what this is showing. So the top part there, the blue, it's called the strong form. This is the equation you would see in a textbook or in a journal article, or that you've been working on deriving and applying to your problem. In this case, it's the heat equation. So what you do is you do some finite element math, which we're going to do for you here in a bit, and you get what's called a weak form. And then once you have your weak form, you can go program up that physics. And this is what's done in what's called a kernel, using the kernel system in Moose. And so if you just look at that circled box there in the weak form, the actual code that you need to write is _k, that's your thermal conductivity, at a quadrature point. We'll talk about that. Then you got the gradient of U, that's the gradient of the temperature in the equation above, and then the gradient of the test function, the ith one in particular. So that's actually all the code you will need to write, technically speaking, for a kernel. Now around that code, you'll see some kind of copy and paste C++ to make it work properly. But generally speaking, you'll be writing a few lines like this in the code that you develop. And it's really important to point out is that this is real C++. So we get a lot of times we get questions about why is it in C++? Why don't you have Python wrappers or some other wrapper? There's reasons, and one of the main reasons is the power of C++, speed and performance being one of those pieces, but also you can do whatever you want in here. There's no restrictions. It's real C++. So that line of code could dial up whatever functionality you need if it so arises. But hopefully, if we've done our job well in Moose, all those little functionalities that you need will be in one of our existing systems, and we'll probably talk about that. We'll talk about that soon. I'll give you a list of all the systems.
Hey, Andrew, you mind if I butt in for half a second?
Yeah, please do.
Can you flip back to that last slide?
Yeah.
So I think that one of the things we need to point out here is just how powerful this line of code is, right? So by writing this one line of code, you mentioned it somewhat, Andrew, but you'll be able to solve this heat diffusion term in 1D, 2D, or 3D on one processor or 10,000 processors using one thread or 4 threads or 5 MPI procs and 4 threads on any shape geometry that you can mesh with any kind of shape functions that make sense, with mesh adaptivity on, with all kinds of boundary conditions. So there's a whole lot of power here in this one line of code, and we really try to boil it down to what is the simplest input that we can get from you that describes your physics. And this is what we've come up with here. And Andrew explained really well why we do it in C++, but all these other things I'm talking about is another reason why we do it in C++, because we get a lot out of writing these very few lines of C++ to describe your physics. So just wanted to interject.
That's good. These are things that when we do this in live, we're usually doing this in pairs, and it's easy for us to jump in, but it's a little bit awkward, and I have no read of anybody's emotions right now. So thanks, Derek. So with that, I'm going to jump to another thing that we take quite seriously is just software quality. As a national laboratory, we have certain criteria that we need to meet in software quality, and that's NQA1 standards. And Moose, follows a procedure that allows us to meet those standards. And in doing that, we've developed quite a powerful system for continuous integration and a testing system, a whole Python-based testing system, and a thing called Civet to run those tests on the fly, and we'll probably talk about that more in detail. I don't want to spend too much time. Basically, we take software quality very seriously. This is our general development practice. It's a complicated graph, but it's generally there. We put this up there for people to ask questions. Some people are really interested in this. The short takeaway from this is most of it's automatic, and we have very little human input. And the main human input is that we review everything that goes into the code, from the C++ to Python for the testing system to the documentation itself. All gets reviewed and tested thoroughly. Another wonderful thing about Moose is we have a really strong community, and we already talked about our mailing list. So you've seen links and how to get to that from our website. And you can see we have, that top list is total posts, so hundreds of, probably averaging close to 500 posts a month, and on around 60 to 100 topics per month. And that's just in the month of, this is over 1 year. So it's really a strong community, and the Moose developers try to answer questions, but what's happening more lately is the community itself is answering questions. So it's really, really quite wonderful. We try very hard to answer everything that comes into the mailing list. And consequently, since we've gone open source, especially, the number of people contributing to Moose continues to go up. This graph isn't super important. There's kind of two different metrics on it. Contributors on the right, and then number of commits, that's changes to the repository. Just two ways to measure what's happening in Moose, and you see those lines keep getting steeper, and the number of unique contributors is going up as well. So people are adding to Moose from all over the world, and it's really wonderful to see. And this graph is basically kind of showing you the same information. The red is additions, or the subtractions. The green is additions, and you can see it's getting more green and more red over the years, and just that there's lots and lots of changes going into Moose all the time. Moose is a multiphysics tool for you to go create a multiphysics code. So Moose is really designed as it's a framework for you to build a multiphysics simulation. So many of you would probably know multiphysics is an important, popular topic, but it's pretty difficult to achieve. There's lots of different ways to do it. Well, you can give up. Is one way, and that's a good way sometimes. Sometimes it's pretty hard. Another way is you have coupling codes. You might have two individual codes that two different research teams are working on, and then you'll write a third code in between them to make them talk to each other. And is there something better? We hope so. We hope it's Moose, and that's really what it's designed to do. And so we've already talked about the modularity of Moose, and it stems more even farther than individual systems. So I mentioned that any given simulation can be composed of a bunch of systems. And at the same time, you can take many different physics applications and make them modular as well. And so we take that idea of systems and simulation tools and to the extreme, and allow things to be really plug into each other, and a lot of code reuse and things like that. And if you've ever written a finite element software before, you know it can be quite challenging when you start putting in shape functions, degrees of freedom, elements, numerical integration, and all these different things. It can be quite challenging. And so what we're really work hard to take that all away from you and put it on us, and then do it in a way that allows you to have the building blocks to make something really powerful. And I've already mentioned these pluggable systems quite a bit, so I'll probably just jump through this slide and talk about the actual system. So this is the current list of pluggable systems in Moose. We're going to talk about probably 10 or so of them in greater detail in the next 2 days, and then at the end of the workshop tomorrow, blaze through a slide or two on all the ones that we didn't cover. So these all have a purpose, and we've already mentioned kernels. That's for doing physics, and you'll see boundary conditions in there. That's also for implementing your physics. And there's all kinds of there's some statistics stuff in there. There's post-processing, all sorts of wonderful systems. So this is really the key to the presentation. or this section is what we're trying to do with Moose. So I'm going to try to play this video and stop it and start it as it goes. Hopefully it shows up for you guys. Sometimes video streaming of a video stream gets kind of wonky in these things. So to kind of set the stage, the goal is we want to make a finite element reactor fuel simulation. That's the title up here at the top. What do we need to do that simulation? And you can, go start getting out your textbooks and things like that and start doing some work, and you realize what you need is you need some linear algebra. That's what's down here. You need MPI. You need some nonlinear solvers, integration strategies. Then you get up in the finite element work. You need to assemble your finite element structure in your mesh. You probably need some mesh adaptivity for performance. You're going to need numerical quadrature shape functions, all those things. And then, well, reactors are fairly complicated, so you're going to need to understand chemistry, mechanics, and how to couple those together. And then you need to go to the actual physics and understand fuel performance and neutronics and all these things. So there's a lot to it. So obviously doing that all by yourself is pretty difficult, so we're not going to do that. We're going to start by, is this going to play? Yes. Start by message passing interface, MPI. It's been around for a long time, so we're going to use that. That's great. And then we're going to leverage some other really good tools. So this is PETSI. PETSI's been around for quite some time now, and it has all sorts of good numerical tools. So we're going to use PETSI. Great. This is getting easier, right? The number of boxes are reducing. And then we'll go to the next step. We got libmesh. We already talked about libmesh. That's where all our finite element comes from. And then Moose. So we got Moose sitting here, and that's trying to help us, like I said before, all these tools underneath. Moose is there to try to help you do your job without having to worry about all the stuff underneath. And the big one is the hybrid parallelism is really important to do these massive simulations that people often want to do, and the modularity there and the interfaces things and physics coupling. So great, we got Moose. Okay.
So
Go ahead,
Andrew,
Derek.
I'd like to point out that, the point is, at this point, you're trying to make this new code, and the only thing now that you actually have to code are things that you know about as an engineer or a scientist, right? They're your physics that you're trying to solve. So by using these other packages, you've reduced the burden of what you actually have to code, right? And that's really the point of Moose, is to keep you as a scientist or an engineer focused on solving your physics instead of how to use all these computational science tools down here.
Yeah, thanks. And we're going to take that idea, and we want to take that even further with Moose, and Moose allows you to do that. So something we haven't mentioned yet, but we will, is that you don't even have to do a lot of the physics calculations coding yourself, because we've done that. There's a chemistry module, solid mechanics module, heat conduction module in Moose. So things that are really popular, like heat conduction, we've asked that the community put back into Moose, and that's in a little directory in our repository called modules. And there's a whole lot of capability in there that the community, people like yourself, have contributed back. So once again, like Derek said, now what you have to do is even further reduce, because you can leverage these existing physics tools that are in Moose. So then now you're really just focused on the really specifics of your application. Nuclear fuel, for example, would be Bison. Thermohydraulics is an application called Relab 7 here at INL, and then Rattlesnake is a neutronics application. So here at INL, those are 3 applications that we develop continually, and they're all by individual teams, and they do a really good job of solving their physics with Moose. But the thing we can even do, since these are all built on Moose, is we can push that line further. Is now we can take those 3 applications that all solve different things and put them all together in a new code, essentially, but is leveraging all the existing tools there, and build this reactor simulator. So really, we can have a 4th team that uses existing Moose tools to build yet a more complicated simulation that's across timescales and physics and all the complexities for coupling go away, because all those tools were built with Moose, and now we can put them all together and do these really large scale. I think we even use the term multi-physics, because any individual code like Bison is multi-physics itself, and then you you put multiple together, so you get multi-physics. It's a really powerful tool, and that's how we're going to close out the workshop at the end of tomorrow and show you how to do that. Derek, is there anything else you want to add to that? Is that about right?
No, that's right. Yeah.
Okay. So I briefly mentioned the physics module, right? This is community-driven tool set for you to use. So every Moose-based application has access to all this. You can turn it on pretty easily in the Makefile, and we'll probably show you how to do that. And you can see really common thing: heat conduction, chemical reaction module. There's even contact for stuff coming into contact. So currently, this slide is just for fun. Usually gets a laugh out of people when I'm in person because it's this big spider web. So Moose is it's a big beast now. Moose itself has all these physics as a framework, and on top of that framework, these are all the applications that we test here at INL. Some of them aren't developed at INL, but these are all the ones we're testing against because we've deemed them to be important. So every change in Moose, we test against all these applications, and it's really quite amazing. And we do our best, to keep all these applications working as we go throughout and develop the code in Moose. So it's really a wonderful community, lots of capability, and we'll probably show you as we go a little bit more of our testing infrastructure that allows this type of testing. Okay, somebody needs to mute. I can hear people typing. Who's typing? It's Alex, probably.
Oops.
Okay, this is a good chance to ask a question now too, if you want. We're going to kind of jump into the tutorial and introduce what we're going to be talking about for the next 2 days, essentially. So this is a good quick spot to ask a question if you have one. Okay, I'm not seeing any hands. So this is great. I mean, there's 165 people right now sitting here listening to us, which is at least double what we've ever done before. So this is really great. So thanks for all of you for trying this out with us. So problem statement. What are we going to be doing? Oops, click the window. So a few years ago, Derek and myself and I don't know who else was involved, we decided to come up with revamp our training around the time we went open source. And we found this paper, and we decided to make a Moose-based application to kind of mimic this experimental setup. And that experimental setup is 2 pressure vessels with different temperatures that have oscillating pressures inside that are connected by a pipe. And inside that pipe is a bunch of spheres, little steel spheres packed. And the fluid, based on the pressure and temperature of the vessels, will flow through that differently, as you might expect. And so we decided to try to simulate that. And what we're going to work on is that pipe portion. We're just going to simulate a porous media between 2 pressure vessels. So the governing equations are fairly basic. We'll do conservation of mass. So we're assuming incompressible flow, so that equation breaks down to grad dot u equals 0, which is grad the velocity is the divergence of the velocity is equal to 0, which you're fairly familiar with. And the conservation of energy, transient heat conduction equation, which you probably fairly familiar with. It also has a convection term here that couples in the fluid velocity, so I guess it's convective heat transfer. And then for modeling the porous media, we're just going to use Darcy's law, which is just a way to model a porous media based on porosity and permeability and viscosity. And it's pretty common to do in porous media calculations. So those are our governing equations. These are the basically the strong form that we talked about. And we do a little bit more work to simplify things. This pipe's going along the ground. It's a pretty small pipe, so we're just going to neglect the gravity term. So that makes Darcy's equation a little bit simpler. And then we're going to take Darcy's equation and put it into the conservation of mass. And at the end, doing that mathematics, you get 2 equations. So these are the governing equations that we're going to be working on throughout the next 2 days. So we got one steady state equation and then one transient equation for the heat conduction. So we're going to solve for two things. We're going to solve for pressure, that's with conservation of mass in Darcy's assumption or Darcy's equation, and then we're also going to solve for T, for temperature. So that's what we're going to try to solve, and we're going to set it up to mimic this experimental setup. And along the way, we're going to need some information, and this is a porosity dependent porous media, and so you can the material properties, density, heat capacity, and thermal conductivity can be set up in what I would call an effective manner. So you got the effective density, effective heat capacity. That's going to be some function of the heat capacity of the fluid and the heat capacity of the solid, and that function is dependent on the porosity of the system. So pretty normal thing to do for when you're looking at a continuum approach, but with multiple materials. We'll see these later on. And then this is just some material properties that you're going to see pop up as we go throughout the lectures here. And you'll see these numbers show up, and I think we'll have comments and like, oh, this is from the paper, this is from the paper. And they're just summarized here. So we try to mimic what's happening in the paper as closely as we can, and these numbers you'll see. So here's an overview of everything we're going to do and more, because we're not going to cover every step, or definitely have no plans to do the final step there, but I'll mention it briefly here. So it's basically 10 steps, and what we're going to try to do is present to you a, the methodology to create your own custom simulation tool. So I've already briefly mentioned this, that Moose itself is a framework. It doesn't really do anything by itself. It's intended for you to come along with your physics and your problems and to make a standalone simulation tool to meet your needs. And to do that, we really encourage you to think really small and take baby steps. So if you have a system of equations that you need to solve, and there's 15 of them, and they're all tightly coupled together, please don't go try to code all 15 equations and hit go and hope that it works, because it won't. It's far too complicated to get right in one go. And so what we really encourage you to do is, so you have 15 equations, pick one of them, and even more so, pick one term in that equation and make sure you solve that properly. And then we'll move to the next term, make sure you solve that properly. Put those two terms together, make sure those solve properly, and go all the way through your 15 equations in that manner. And then when you get to the end, you'll know that everything's been working because you've tested it and verified it along the way. And that might seem like it's a little bit too much work to do that kind of approach if you have hundreds of terms, but trust us, that's the way you should do it, and you'll get much more robust code, and you'll be very comfortable with the answers you get in the end, and you'll understand the problem to great detail. So that being said, that's what we're trying to show you how to do here in this tutorial. We're going to start stupid simple based on those two equations that we did, and just slowly add complexity. And when we get to the end down there in step 10, we're actually going to have fully coupled thermal mechanic simulation that's running across timescale and include microstructure calculations within it. And we're just going to build up to that as we go. So hopefully that makes sense to people. So like I said, we're going to start simple. So if you go back a few slides, let's jump over to these equations. These are our equations we're solving for. And this is what we call a diffusion term. So that's what we're going to start with in solving. And we're even going to start simpler than that and forget that coefficient. Let's just see if we can get this little diffusion operator to go through. And this thing shows up in just about every differential equation you can imagine. So we just call it simple diffusion or diffusion problem. And it's where you got the divergence of the gradient of some unknown. So then in the next step, we're like, all right, now we got that working. Pretty confident. We understand the moose a little bit. Now let's add this coefficient. And so we got, what's big K? And that's permeability, I think, right? Yeah, permeability over viscosity. And that's going to just be a coefficient that goes into the diffusion equation. So that's gonna be the second step. We're gonna add that, and we're gonna add that in a very simple way where you just, just type in a value in an input file and run, just constant. Then in the next step, we're gonna expand upon that and make the system a little more flexible and introduce the material system. And this is a wonderful system that we have, and it's probably one of the most powerful that we have for doing multiphysics. And we're going to take that equation with that take that coefficient and make it super flexible, that it can be, it can change with space and time. It can include coupled variables from other simulations and things like that. And then we're going to, in step 4, introduce the auxiliary system. This system has lots of uses, and we'll just kind of show one of them here. And it's basically to do a post-processing step. So we're really interested, we're going to solve for pressure because the assumptions we made using Darcy's equation, but we really might be interested in the velocity in that pipe. So we're going to use the auxiliary system to calculate the velocity based on the pressure. And then in step 5, at this point, we have solved that first equation for pressure, and now we actually want to move on to temperature, and we're going to use the heat conduction module to do that. So we're going to fire up and solve a simple heat conduction problem without that velocity term, so uncoupled at this point. Make sure we can do heat conduction. And then we're actually going to work on putting the two equations together and add that convective term to the heat equation, and then actually couple the two equations together in this step. And then at that point, we basically have the system of equations solving that we were interested in, but we're going to try to improve it a bit, and we're going to introduce mesh adaptivity to help our solve, and then we're going to introduce postprocessors to get some aggregate data from your simulation on the fly. So maybe average temperature or things like that might be of interest to your simulation. And then step 9 is like, well, geez, that's all working really well. Let's just throw in some mechanics. Maybe you want to show off for your advisor or your boss and show, hey, I did the problem you asked, but I also, threw in some mechanics as well. So maybe you'll get a raise, or he'll let you graduate, one of the two. And then finally, this will be the last step we probably cover in this training, is the multiscale simulation. I already briefly mentioned this, is where we're going to take that mechanics, thermal hydraulics solve, and we're going to add a multi-scale dimension to it, where we're actually going to compute thermal conductivity on a microstructure type scale. And then step 11, if we have some extra time, we can maybe toss this in. And it's a question we usually get a lot in the training, is can we do custom syntax? And you'll understand what that means as we actually see an input file. All right, so there's another good little stopping point here. We've got about 15 minutes left in this first session, and that's going to be about right for me to demonstrate the first step, to show you how to do this simple diffusion operator and introduce you to the input file and how to actually run Moose, or run a Moose-based application. So I'll pause for just a second, get a drink of water, and if you have a question, please raise your hand. All right, everybody's asleep, so I'll just keep going. It's fine, I don't know it that they're asleep, that's all right. So step 1, we've already introduced this quite a bit, and we're just going to solve the strong form. We're going to solve is that diffusion term, this little guy here, and we're going to simplify it really quickly, and we're going to say this unknown u is 0 on one side and 1 on the right side, and all other places the gradient of u with the outward facing normal is 0. This is called the natural boundary condition. And then we're going to do some weak form or finite element manipulation to get a weak form, and that's what we have here. So
Andrew, we actually have a Christopher has his hand raised.
Oh, I don't want to answer his question. No, just.
I figured not, but we'll try anyways.
Yeah, I'll try. Hi, Chris. Go ahead.
Hi, I'm just pointing out that those boundary conditions don't match the input file. That's all.
Okay. No problem. I'll stumble across that when I get there. Thanks, Chris. So that brings up a good, so Chris is an intern for the Moose team, and he's working on improving all of our training materials. So that's why he knows that. He probably knows this tutorial better than any of us at this point. So hopefully actually in the next coming weeks, we're gonna have a whole lot more really great information about about this tutorial and building up your simulation on our website in much more in a long format that you could read, because the slides that we are showing here are really meant to be presented in person, or I guess digitally now. So there's lots of discussion that go with the slides, and we're gonna kind of basically write a little mini book about this tutorial as well that you can follow along. So look forward to that in the coming weeks to months. So thanks, Chris. So at this point, I'm going to quickly introduce our input file. Oh, I was going to say one thing here. Don't worry about all the finite element math. We don't need to write any code for this first part, and you're going to see how to do the finite elements and get a good explanation of finite elements with respect to Moose in the next section. So this is just to show you that Moose does do something, and we can show you how to run some stuff, and you can start playing with it as we go if you're interested. So Moose, it runs on input files. If you've used other tools such as Phoenix and other open source finite element tools that use Python, you'll write a little script to build your simulation, which is great and really quite powerful. We do a little differently in Moose, and everything, all the capabilities that exist in the simulation package or simulation application that you make, all are compiled into one executable, and then you use the input file to dial up which pieces of that capability are going to run for a given simulation. So if you create a Moose-based application, it can have lots of capabilities, and it can solve hundreds, thousands, all the equations in the whole world if you want. And then your input file will tell you which equation or equations to go solve for any given run. And so we do that through the HIT format, hierarchical input text. It's a format that we've come up with. It's based on some other formats. We've kind of taken ownership of it, and we call it the HIT format. You'll see it as a .i file for input in most of our within the repository. And it's this block structure, and we like the structure. It's really quite easy to read, and it also kind of mimics the block structure that we have in Moose. So you'll see kernel's block. This is one that shows up probably in just about every single Moose-based application input file, because that's the physics you're trying to solve. And you notice this has a capital K. We use capital letters in syntax that is provided by Moose. So capital K kernels means that Moose is expecting certain things inside the kernel's block. This name is a keyword for Moose to recognize. When you see a lowercase, this is the name that you're assigning. So within the kernel's block, we're creating a kernel, and we're naming it Diffusion. This name is arbitrary. Just write something in here that's useful to you. This type equals line, you're going to see this a whole lot, and that type equals AD diffusion. This AD diffusion is actual C++ piece of code in Moose for solving the diffusion term using automatic differentiation. And then variable equals pressure, this is the variable that you're solving for, and we'll see that a little bit more next. So that's the basic structure of our input files. And for a pretty standard Moose simulation, will require 6 pieces or 6 blocks in your input file. Mesh, that's the geometry, your finite element mesh. Variables, that's the thing you're solving for. Kernels, the equations that you're going to use to solve that variable. Boundary conditions, they fall along with kernels, that defines the boundary pieces of your physics. The executioner block, how you actually want to solve it. Is it steady state? Is it transient? What's your time step? Maybe with some solver options and things like that. And then finally, outputs. How do you want your solution to show up to you? So that's what I'm going to introduce here briefly. So this is step 1. This is the input file. I'm actually going to go run this in a few minutes, but we'll step through it here quite a bit. And we're going to introduce all these input file blocks, and then the rest of the 2 days gets super repetitive because you're going to see the same input file over and over and just small pieces of it being changed. But that's okay. By the end of the 2 days, you'll be experts in our input file syntax and hopefully understand how to build up your simulation piece by piece. So to start with the mesh block, the meshing system in Moose is getting more and more powerful. This is the simplest setup you can have. And so type equals generated mesh here, that top line. Generated mesh is a C++ object, and it's made for making lines, squares, rectangles, and cubes. And in this case, we're going to make a rectangle because we're going to do this problem in 2D, and we're actually going to do it axisymmetrical. I'll show you that in a minute. So 2D, this means dem equals 2. This just defines the mesh, the dimension of the mesh. We're going to have 100 elements in the x direction, 10 elements in the y direction, and then we're going to give it some dimensions as well. So the x coordinate goes to 0.304. That's the length of the test chamber, comes from the paper, and the radius of the temp in the y, 0.02. That also comes from the paper. And it's important to point out that y min and x min default to 0. So this is going from 0 to 0.3, etc. Next, the variables block. We want to solve for pressure. So capital V variables, that means that that's a block that Moose defines. And then we're defining this name pressure. Use a name here that's useful to you, like, pressures, we understand what that is, right? If you just use P, it could be a little more difficult to understand later down in your input file what P means. So we like to use words if possible. And by default, it's going to set up a linear Lagrange finite element, and you're going to see what that is this afternoon and know a little bit more about it. And now you go look at the kernels block. So this is the physics we're going to solve. You've already seen this. This is my little example for introducing hit. It's the same. So AD diffusion, then variable equals pressure. The key here is this pressure now, this string is not arbitrary. It exactly corresponds to the name that you gave here. So now this equation is set up to solve for this pressure variable. And then you take that concept down to the rest of your physics on the boundaries. I mentioned the inlet and outlet boundary conditions. So like Chris warned me, this boundary condition isn't exactly what we had written in the slides. We have to fix that. And we're setting up the boundary conditions here to mimic closely to what the paper is. And so those two pressure vessels, one of them had a pressure of 4,000 in one scenario, and the other one had a pressure of apparently 0. And they actually oscillate back and forth in the end. So this is just kind of setting the stage for doing the problem more realistically as we go. And then we have a problem block. I actually didn't mention this in the basic things that you'll see in an input file because this often isn't there. By default, you'll set up what's called an FE problem in Moose, and you don't even need the problems block. But for our case, if you want to change your coordinate system, and we're changing it to be axisymmetric, so to mimic a tube, and to do that, those settings are in this block. So we set up the coordinate type to be RZ, and then we're doing the radial direction to be X, which is along the long axis of this tube. And then finally, we get into the executioner, and this is a steady state solve, and we're going to use Newton to solve it, and we're going to give it some PETSI options. We're going to talk a lot about these in the next 2 sections, so don't worry about that. And then finally, we're going to output it in Exodus format. It's a really nice finite element format. It's open source and gives us some really nice capability that, again, we're going to talk about that in more detail. And we're going to talk about all these sections in more detail as we go. So I got 5 minutes. This is working out pretty good. I'm going to actually go run this. So I'm going to have to figure out how to change my screen. Do my main screen. Hide that. Okay, now you guys can probably see. Hide that. Hopefully you can see my terminal. Is that big enough for those who have Alex or whoever's listening? Can you guys see this?
That looks good, Andrew.
Okay,
Pretty.
thank you.
I feel like it's a little small, but probably okay.
So the problem with doing this on really nice big monitors is that it doesn't transition well.
Yeah, on a laptop screen, it's just a little bit small.
Okay, I can go huge. So this will give me a quick moment to.
That looks good.
Okay. So I have a really nice fancy terminal. It gives you all kinds of information. This, you might see this. This is my Conda environment. This is who I am, and this is my GitHub, my Git branch that I'm on. You don't have this information, but and then this is the current directory that I'm working in. So so that's Moose. I've cloned Moose, got it all set up. It's all compiled and ready to go. If you do a listing in there, this is what if you went to GitHub, you'd see this. And then to follow along, you go into the tutorials directory and then Darcy ThermalMech and do a list in there, and you'll see all the steps. So how we have this tutorial set up is that each step has a folder, and you can go in there and compile and run your application, our example application, so you can follow along. But in practice, you wouldn't want to keep folders like this. You would use versioning control, in particular Git, to manage this. And you can imagine every single step that's in this tutorial would be a commit to your repository. So you're adding capability as you go, and you're just doing it all in one place, and you're using version control to do that. We have the separate folders here to just for demonstration and allow us to step back and forth between the steps. So that being said, we can talk more about that if people have questions. We'll go into step one. So if you've already followed our getting started instructions, you might have already seen this kind of stuff. This is a Moose-based application. So this is a little, I guess we'd call it an animal. We didn't give it an animal name, but to solve our equation that we're going to work on. And I've already compiled it, but I'll double check again. I'm going to run make. That's standard compile way to compile our code in Moose. And the -J4 just says use 4 processors. I can you probably should use whatever your system has. And then we set up this example to have a problems directory, and that's where we're keeping all of our input files. And there's a little bit of cruft in here, but this is the input file we want to run, step1.i. That's what we just did. And to run that, actually, I'm just going to do it in Peacock. So Moose comes with an application called Peacock, a little GUI for helping us run. And if you follow along, this is the executable you're running. It's in Moose, Python, Peacock, and then there's an executable called Peacock. That's what you're running, and you give it a -i, step1.i. And you hit go, and it's going to take, if it's the first time you run Peacock, it's going to take you, might even take a minute or two to run the first time, because it's actually Python doing its caching. And the second time you run, it'll be much quicker. And it'll fire up this cool little video or a screen. It's going to show you your mesh. It's going to give you a tree view. You can see there's check marks here. So these are all the pieces within your input file that are enabled. And so if you can click on boundary conditions, you can expand that and say, let's look at the outlet. It'll highlight the outlet boundary condition. This is probably pretty small for guys. So I'm just going to go. We can hit run. It's going to go run the problem, and it'll give you a terminal output here, and then you can see the result. And we have a nice linear gradient that you'd expect that goes from 0 to 4,000. So we solved diffusion, really, really good. We got this huge massive code base, and we're able to solve the diffusion equation, which is really quite nice.
All right, let's get started here. So I'm just going to go through some basics on the finite element method. The idea here is not at all to completely teach you the finite element method, but to give you at least enough of an idea of how we think about finite elements so that you can use Moose to solve your problems. And you know, this is trying to distill down at least a semester, if not 2 semesters worth of finite element class into what, an hour or hour and a half or something like that. So don't be discouraged if you don't understand every concept here, but hopefully this gives you some idea of how to relate to some of the objects in Moose. So let's dive in here. So before we get started on finite elements itself, let's talk about something somewhat related, just to kind of motivate where we're headed. So I think everybody's probably done polynomial fitting before, right? You have some data, let's say some experimental data or some XY points in general. And what you want to try to do is fit some sort of function so that it optimally goes through those points. And there's a lot of different ways to do that, of course. But one of the options is polynomial fitting. And you can see that here in the form of f of x here, where we're going to try to find an a, b, c, etc. To optimally fit our data. And in this kind of form that I have it written here, f of x is the function we're solving for to try to fit our data. A, b, and c are scalar coefficients that we will actually solve for in order to find f of x. And you could think of 1x and x squared here as effectively basis functions. They're functions that are going to make up our final solution, which is this function that optimally fits our data in some way. So the problem then is to find a, b, c such that f of x goes optimally through the points, but we do know with polynomial fitting that we can make it go directly through the points, right? So we can also more generally write f of x like this, where it's the sum of coefficients multiplied by x to the ith power basis functions. And even though finite element shape functions typically don't look this way, this is actually a valid set of finite element shape functions. They're called the monomials. And you can actually use them in Moose, and we do use them for some things. So this is fairly relatable. So the problem here is that we want to find f of x, and we know that it's unique and interpolary if d plus 1, with the way this is written, is the same as the number of points that we need to fit, right? We all know this. And what happens is that defines a linear system that needs to be solved. So here's our example. We have our 3 data points here, our XY data pairs. And what we're going to do is write down our generic form here of the equation that we're looking for and substitute in each of the positions here from the XY data points. And by doing that, you put the Y values on the right-hand side and you substitute in the X positions here to get what goes into the matrix here. And you end up with a little linear system to solve to find A, B, and C, right? It's pretty straightforward. So you solve that and you end up with this as your solution vector. And so, yeah, so then you take these coefficients and you put them back into the f of x form and you end up with your function that's going to go optimally through your points, right? And there's a few things to point out here. So even though we had discrete points, these xy positions here, what we end up with at the end, of course, is a continuous function, which is what we wanted, because we probably want to do things like evaluate it in between the points, evaluate its derivative so that we can get some gradient information. We can even extrapolate with it, right? I mean, this is probably a fairly poor fit for extrapolation, especially kind of over here, but it might be a decent fit for extrapolation out here, let's say. So we can extrapolate from it. But the point is that what we solved for in our linear solve were these coefficients, but the actual solution to our problem was this function, okay? And this is really important in the way Moose works with finite elements, because there's a linear or nonlinear solve that's happening to solve for coefficients. But our solution is always actually the function that's made up of those coefficients multiplying their basis functions. So let's talk a little bit more directly about that. So the coefficients themselves that we solve for, the A, B, and C up there, they're just numbers. They're actually meaningless by themselves, right? So the solution to the problem is not the coefficients, but it's the function, like I mentioned. And when those coefficients are multiplied by their respective basis functions and summed, that's how we get the actual answer to our problem, the f of x that we wanted. As I mentioned, you can evaluate f of x anywhere. So to evaluate at x equals 2, for instance, we can use this form of f of x and put in each of the CI coefficients here, and 2 goes right here where x was. and we can get the solution. More generally, instead of having x to the ith power, we can write this as some GI function that's evaluated at 2. And so now in this form here, this is a really generic form where we can change out what kind of shape function we're actually solving for. So this is polynomial fitting, but it's very, very similar to what goes on in finite elements. What we're going to be solving for in finite elements are the coefficients to basis functions. And those basis functions are, the reason why we're solving for them is to build a function that is a solution to a partial differential equation. So one of the important things to always keep in mind about finite elements is that what we're solving for are functions. We're trying to find a function that optimally fits a partial differential equation and boundary conditions, instead of trying to find, in this case, a function that just fits xy data. So we have a different kind of constraint in finite elements, but it's the same basic idea. So try to keep this in mind as we go through this. I find it helps in understanding what we're doing here. We will also actually fill out a linear system of equations that we'll need to solve to find those coefficients. So it's very, very similar. All right, let's talk about the finite element method directly. It's a method for numerically approximating the solution to partial differential equations, as I just mentioned. We have shape functions that work like those basis functions that we were talking about just a moment ago. Both of those words are fairly interchangeable. And we typically utilize the Galerkin finite element method. I think we won't get into exactly what that means here. It's not important. And we view it as different from finite difference and finite volume methods because the output is a function over the whole domain that we can evaluate anywhere within the domain. We can evaluate its gradient anywhere within the domain. And you're not making it up in between. It's actually something you solved for. You solve for the value everywhere within the domain. That's very different, for instance, from finite difference, where you actually are only solving for discrete values at points. And then you have to do some sort of interpolation in between them if you want values in between. With finite elements, there's not actually interpolation in between points. You actually know the solution in between the points because you solved for it. So just as in polynomial fitting, we can evaluate it everywhere. The reason why we went with the finite element method, why we use it, is it's really applicable to a huge range of PDEs, and it's supported with a really rich mathematical theory with proofs about accuracy, stability, convergence, and uniqueness. So when we're looking at, wanting to solve this huge plethora of partial differential equations on different scales, etc., finite element method really makes a lot of sense. Now, as was discussed earlier, we have added finite volume capability to Moose 2. And that finite volume capability is really there mostly at this point to help us out with some of our flow equation stuff, just to utilize some of the technology that's been created in the finite volume world. So we are adding some finite volume capability also to Moose at this point. All right, so to utilize finite element method, what you need to do is form what's called a weighted residual. There's a lot of other terms for this, like a variational statement or a weak form. If you're a mathematician, I'm sure there's a few of you on here. First of all, I need to apologize to you because I'm going to commit all sorts of mathematical crimes over the next hour or so. So maybe just try to shield your eyes during those moments. This is a very applied way to think about finite elements. So we're going to take a few mathematical shortcuts here and there. If you're a mathematician, these three statements, weighted residual, variational statement, or weak form, might actually mean different things to you. In the general Moose parlance, we don't tend to actually differentiate these things. So I'll treat these phrases as all the same for the purposes of talking about Moose. We do tend to use the words weak form though to describe this. So don't worry if you don't know what these are, and I'm talking about them incessantly. We'll go through how to generate a weak form. That's what we're going to do over the next few slides. But let's see. And to do that, we're going to go through a set of steps here. And I skipped a little bit. So the important thing about the weak form is that it provides some flexibility, both mathematically and numerically. And I don't really want to get into that, but it allows us to solve these problems, is the easiest way to put it. So to generate a weak form, we view it as having 5 steps. The first step is to write down the strong form of your PDE. That's just straight up to write down your PDE. We usually like to write it in kind of a dimension agnostic form. Using gradients and divergences and things like that, because that tends to translate into Moose a little bit better. This might seem like a really easy step, but this might be the hardest step. If you don't know what your PDE is, then it might take you years to figure that out before you can use Moose. But hopefully you either have an advisor that's telling you to solve a specific PDE, or you already know it because you're an expert in the field, so you can write it down. That's the first step. The second step is to rearrange all the terms so that 0 is on the right-hand side. So just literally take everything to the left-hand side. Super simple, easy. Multiply the whole equation by a test function, which we call psi. And this is where I'm going to start committing mathematical crimes, because there's a whole bunch of restrictions on psi that we don't care about because we're scientists and engineers trying to get stuff done, right? But the mathematicians should all be crying at this point. And then we're going to integrate over the whole domain. We'll always use omega as the domain. I apologize for that if you like omega for other things in your equations, but you have to make some choices here and there. So integrate the entire equation over the whole domain, and then integrate by parts. And typically we view this as using the Gauss divergence theorem to basically lower the derivative order of some of your derivatives. And we'll see exactly how that works here in a moment. So before we actually go through those steps on a real PDE, this is just a refresher on the divergence theorem. If you don't remember quite how it works, it's been a little while since you took this. And the idea is that if you look at the chain rule, you end up with this kind of construction here, where the divergence of a scalar by a vector ends up giving you these two pieces here. And then you integrate over the domain and you end up with this construction. And then you can actually turn that volume integral into a surface integral using the divergence theorem. Okay, so we can take this piece right here that was a volume integral, and turn it into a surface integral by using the divergence theorem. And then that ends up giving us this piece right here. So this is something that's going to show up a lot in our PDEs, the divergence of a vector field. It'll often be the gradient of one of our variables. And then we can use this construction here to basically turn it into a integral over a surface minus the integral over the volume. And the important part about this is that it will lower the differential, it'll lower the derivative order of the derivative on the function that we're trying to solve. Okay, that's all fairly abstract at this point. We have this slide in here mostly so you can come back and reference it. So don't worry about actually understanding this perfectly. You'll see how we apply it here in just a moment. Okay, so here's our example. So we're just going to talk about a simple advection diffusion problem. And the strong form of this equation looks like this. And what we have here is effectively some diffusive term here, where we have the divergence of k grad u. This k here could be something like a thermal conductivity or a permeability or lots of other things. So this is a very common term. This kind of diffusive term shows up in a lot of physics and a lot of PDEs. And then we have this advection term here. And what this is going to do, beta here is going to effectively act as kind of a velocity term, and this is going to move material around within the domain effectively by this velocity field. Okay, so this is beta.grad_u is the way to read this, and then f here is just some generic forcing function that's over on the right hand side. So this is our very simple strong form PDE equation. Again, note that we like to write it in dimension agnostic form here. So instead of having derivatives with respect to x, y, z showing up all around here, it tends to be simpler to write it here with divergences and dot products and gradients like this. Okay. Hopefully this kind of this mathematics is at least somewhat familiar to you. But yeah, just to read this out again, this is the divergence of k grad u plus beta dot grad u equals f. Okay, this is the way to kind of read that. All right, so now that we have our equation, that might have taken us years of research to figure out what equation we want, or somebody might have given it to us and told us to solve it. The next step is to rearrange to get 0 on the right hand side. So that's literally just taking f to the other side of the equation. That's it. So nothing really complicated there. Then we're going to multiply the entire equation by what we call the test function. And in this notation, we're using psi here for our test function. And so psi will just hit each one of these terms. So we'll just have psi times this, psi times that, and psi times f. Psi times 0 is still 0, so we're good to go there. All right. The next step is to integrate over the domain. So our domain again is omega in this notation, and we're just going to integrate the entire equation, both the left and the right hand side, but the right hand side is 0, so it's just 0. But integrate the entire equation over the domain, and that gives us these three terms again, but now integrated over our domain, right? So nothing complicated there. Now here is the one step where you actually have to finally do some math. So we're going to apply that little divergence theorem piece that we were looking at a moment ago to lower the derivative order on our unknown u. Okay, so right here in this notation, we have the divergence of k grad u. If you were to write that out in 1D and assume that k is constant, for instance, just to make it easy, what you would end up with is a u double prime there, right? So this is a second derivative effectively on u. And that second derivative is problematic for a lot of reasons. And one of them is that in order to find a function to approximate u with, which is what we're trying to do in the finite element method, we would need to find a function that can be differentiated twice, okay, that's twice differentiable. And that's going to basically limit our choices on function spaces that we can try to find the solution to this problem in, okay? So if we were to remove one of these derivatives and lower the derivative order here, that would free us up to actually choose a lot of other simpler shape functions to solve this problem with. So that's one reason to do this. I'll hold off on talking about other reasons. So let's take a look at this term real quick. So we have psi times the divergence of k grad u. So this k grad u is effectively our vector field that we were mentioning just a moment ago. So if I go back to that other slide, we have our scalar function here multiplying the divergence of a vector field. And what we end up with is one surface integral where we take our vector field and dot it with an outward facing normal from the surface of our domain. And then an opposite sign from what this sign was, volume integral, where we have our vector field dotted with the gradient of that scalar function. And yeah, so if we go back down here, we can see that playing out right here. So we end up with our, we've written this in the opposite order here. So the second term is our surface integral, and we're going to denote that with d omega. And notice that it keeps the same sign as the original term. And we have our vector field here, k grad u, dotting an outward facing normal here from our surface, okay, k grad u dot n. And then our volume integral is right here. And what we have is the gradient of that scalar function dotted with our vector field, which is k grad u. And then note that the sign here has been flipped so that it's the opposite of this sign, okay? So you can go back to that divergence theorem slide and work your way through and show that we did the math correctly. But ultimately what you end up with is this little rule that allows you to lower the differentiability of even order derivatives within your PDE. And so what we've really kind of done here, if you look at this, is that in this form right here, u is kind of doing all the work, right? We're taking one derivative of it here and another derivative here, and this test function psi is just kind of coming along for the ride. Like he's getting off easy, right? So what we're doing instead is we're going to take one of these derivatives and effectively move it over onto psi and get it off of u, and that's what you see right here. So now each of these things, our test function psi and our unknown function u, each only have one derivative on them. So they're kind of doing equal work if you want to think of it that way. That doesn't actually mean anything other than that's kind of a way that I think about it in my head. But what it comes out to mean in the linear algebra that we will ultimately do later is that this term right here can actually generate a symmetric matrix, for instance, all right? So that's one reason to apply this, is that this term would actually not be a symmetric matrix, and it has to do with the symmetry in the derivatives here between psi and this other term. Whereas here we have kind of this symmetry between grad psi and grad u that will generate a symmetric matrix. That's one reason to do this. Ultimately in Moose, we don't care much about symmetric matrices because the problems that we're solving are very rarely ever generating symmetric matrices. But classically, that's one reason to do this. The other reason is that, another reason anyway, is that it also generates this boundary term here, which is very, very handy. So k grad u dot n should look pretty familiar to you if you've taken many engineering courses. K grad u dot n, if u is temperature here, that's going to be a heat flux, right? That's the heat flux leaving your body or leaving the surface of your body. And what we can, in general, this is the flux of whatever u is representing, leaving your domain. And so what we can do is we can manipulate this term here in order to apply flux boundary conditions, or what we call Neumann boundary conditions. So that's another reason to apply this, is the generation of that boundary term is very handy for applying boundary conditions. So when we get to the boundary conditions section, we'll actually talk about how we manipulate this part of the problem to impose boundary conditions. The rest of this kind of just comes along for the ride. So we have our other two terms here. They just come down. And then this whole thing here in 5 is actually our weak form, okay? So that was all the steps. We started from our strong form. We moved to residual form by putting everything on the left-hand side. We multiplied by a test function. We integrated over the domain, and then we applied this little rule that we get from the divergence theorem in order to lower the differentiability requirements on our unknown function u. And then we have our weak form. And this weak form, as it's written right here, is good enough to go code and start using Moose. So everything else that I'm getting ready to talk about for probably the next hour is actually probably unnecessary, but it's going to give you some background into what's going on the inside of Moose. But if all you're really interested in is plugging some equations into Moose and getting a solve, this is really the place where you can stop. And you can go code up each one of these terms here as an object to plug into Moose. And doing that process, creating objects to plug into Moose to describe your equations, is what we're really going to talk about for the rest of today and all of tomorrow. And that's really, the meat of how you use Moose. Now, sometimes we'll write this in what's called like an inner product notation here. And so you'll see this around in some of our documentation, et cetera. So it's worth talking about. Volume integrals we represent with parentheses, and surface integrals we represent with these angle brackets here. But all this means is the left thing multiplied by the right thing integrated over the volume. So it's just a little shorthand syntax. And as I mentioned, each one of these things will become an object that you'll create and then plug into Moose. And the volume integrals become what we call in Moose kernels. The boundary integrals or the surface integrals become boundary condition objects within Moose. And these are volume integrals, so they will each be kernels. When we were doing the polynomial fitting, we used some what I call basis functions at that point that were really simple, 1x, x squared, etc. And as I mentioned, we can actually use those as finite element basis functions, although it's a little funky to do that, but it is possible. But in general, we use some other functions here to support our solution. And we're just going to talk about some of these real quick that are important. So a basis function is, or we kind of go back and forth on basis function and shape function, but effectively a basis function is a small function that is generally represented by something that can be multiplied by a coefficient very easily by a computer. And the idea is that a really complicated equation, a continuous equation that's really complicated, like some fifth order polynomial with exponentials and et cetera, is difficult to solve for by hand. So instead, what we can do is try to represent a discrete form of that equation by adding together a whole bunch of simpler equations that will then represent an approximation to the function that solves our PDE. Okay, so that's kind of being shown over here on the right, where we have each of these little pieces of basis functions, and then if you put them all together and you multiply by their coefficients and you add them together, you'll end up with a piecewise continuous solution in this case. And that's kind of what it looks like in 1D for linear Lagrange shape functions. And then we have something here in 2D showing you what's kind of commonly referred to as a tent function, where it's 1 at one point and it's 0 everywhere else within the domain. And that's a really important quality of basis functions. The basis functions that we use tend to have this, this quality that we call local support, where it's only non-zero in a very small area of the domain, and then it's 0 everywhere else in the domain. And that's a really important property. One of the things that it gives us is very sparse matrices to solve. Okay, so this isn't actually required. We could have shape functions that go way outside of where their support is. It could even span the entire domain. And there are methods that utilize shape functions like that. But within Moose, we tend to utilize these functions with this local support so that we can generate sparse matrices, which is what PETSI is really good at solving in parallel. All right. So what we're going to do here, so we had our weak form just a moment ago, and in that weak form, we had a U sitting there. And I mentioned that U is the thing we're going to be solving for, right? We need to find some function U that satisfies that PDE given the boundary conditions. And as I mentioned, you can just go off and start using Moose at that point, but actually there's some more mathematical rigor to understand what's really happening. So in reality, what we need to do is discretize everything in that weak form to make it easier for the computer to solve it, all right? Because the computer, I'm sure you've all used like Maple or Mathematica or something along those lines to try to solve an ODE or a PDE before, and you know that it's fairly cumbersome and doesn't work very well. It's not what you want to use for engineering calculations, where you have like millions of PDEs effectively that you need to solve simultaneously. So what we need to do is discretize every single piece of that weak form. Can I go back to that? Yeah. So we're going to kind of systematically walk through here and discretize each piece of this in order to make it more amenable to solve it using a computer. And the first thing we're going to do is change from that continuous function u, that's a continuous function over our entire domain, and we're going to change it into this piecewise function that we call that's an approximation of u, that's built up out of coefficients uj multiplying shape functions phi, right? And if you look at this right here, this is the same sort of construction that we had on polynomial fitting earlier, right? Where our function was made up of coefficients multiplying basis functions, and it's the very same idea. We're going to use a slightly different system of equations to solve for those coefficients, but at the end we solve for a set of coefficients that, when multiplied by basis functions and summed up, they give us an approximation to our actual function that solves our PDE. All right, that's our game plan here. So those phi guys are what we call basis functions, and when they're used here to support the solution that we're looking for, there's a little bit of terminology. We will call them a trial function in that case. So if you see trial function hanging around, just remember that it's a basis function. It just happens to be used in the approximation of the function that we're solving for. And this n up here is the total number of functions that will appear within our discretized form of the domain. And that n can be really, really huge. So for linear Lagrange shape functions, they will have a coefficient effectively associated with every node in your domain. So if you have 1 million elements and 1 million nodes, you're going to have 1 million coefficients to solve for. Okay, so this can get rather large. Some of the largest meshes and problems I've worked with in Moose are in the couple to a few billion element range on 20 to 100,000 processors. So you can get to fairly large problems with Moose. So the gradient, let's see. So let's continue here. So we have this UH, which is great. But what we really need in our weak form over here, we have a lot of these grad U's showing up. So we need to have a discretized form of grad U. And using this construction, it's really easy. Grad U, we can approximate with grad UH. And what happens when we hit this thing with a gradient is it goes right through this scalar coefficient and runs into our shape function here. So in order to evaluate the gradient of at any point within the domain, we can evaluate the gradient of the shape functions at that point in the domain and multiply by their respective coefficients that we've solved for and get back an approximation to the gradient of the function that satisfies our PDE. Okay, so it's really handy that we can compute the gradient really easily as well. All right, we are going to talk about Galerkin finite element just a little bit. So the piece of this that makes it the Galerkin finite element method, I mean, there's a lot of different views of this, but this is kind of my view anyway, is that we're going to use the same basis functions as both the trial function, which is forming our solution that we're solving for right here, and the test function, which is psi, that we multiplied by earlier when we were constructing our weak form. So at least in my view, a Galerkin finite element method will utilize the same basis functions for both the trial and the test functions. But I'll just say that there's lots of different views out there, but that's my interpretation there. And so if we do this now, our test functions then is not just one continuous test function. It's actually every function. This test function, when we generated our weak form, was actually, it should have said for all test functions, like for every test function in the universe, with some restrictions, as I mentioned. But what we're doing here now is we're saying, well, it's going to come, the test functions are going to be the set of all of the basis functions that are forming that we're also using in the in supporting the solution to our problem here. Okay, so we end up with, again, if we have 1 million nodes and we're using linear Lagrange, we end up with 1 million test functions to go along with that, one that's kind of associated with each node. And what that generates then, if we rewrite this weak form with this stuff substituted back in it, we have our grad UH coming in here, which we know we can compute. And then we have our psi I and our grad psi I showing up here. And what this means is that now, instead of just having this kind of one equation, we actually have one of these weak forms for every single one of these test functions. So this is for I equals 1 to n. So again, going back to this million case, if you have 1 million nodes, you end up with 1 million of these equations, one for each test function in your domain. Okay. And you need to solve all those equations simultaneously. They're related to each other by how much the shape functions overlap. And so you end up with a system of equations that you need to solve in order to solve for the coefficients that are buried within these UH statements here. Okay. All right. So the left-hand side of this equation is what we call the ith component of the residual vector. All right. And we'll refer to that as this kind of big Ri, and it's a function of the current state of our problem, UH. This is a vector. It's a long vector. It's going. The length of it again is going to depend on the number of coefficients that you're solving for. Okay. This is a little bit of a recap. So shape functions are functions that get multiplied by coefficients and summed to form our solution. Individual shape functions are restrictions of the global basis functions to individual elements. You can think of shape functions like those x to the n guys that we were using earlier. Just to give you an idea of some of the names of shape function families within Moose, we have Lagrange, which is by far the most popular. They're very simple, very handy. Lots of people use them. There are lots of other ones built into Moose, though, including Hermites, hierarchics, monomials, Clef-Toscher, and even a few others past this. And different shape function families have different properties that make them more or less amenable to solving different PDEs. We don't want to get into all that at this point. But there's a rich set of literature around why you would use these different shape function families for different PDEs.
Might be worthwhile to mention that we now have support for vector basis functions as well, like Lagrange vec and even monomial vec, and then Nedelec 1 for doing E&M, which is what Casey will be leveraging for his stuff.
That's a good point. Thanks, Alex. Okay. Yeah, Lagrange shape functions are the most common, so let's take a look at those. So in 1D, we have linear Lagrange shape functions here on the left. And what we're really showing here is kind of the definition of the basis function within what we call the reference space, xi. And you can kind of think of this as one element going from -1 to 1. And on that 1D element, you're going to have these two pieces of shape functions, psi0 and psi1. And each of those pieces will be 1 at one end of the domain, which is one node, and it'll be 0 everywhere else in the domain at all other nodes within the domain. So that means it has to go down to 0 here at the other node on this element. And then the other shape function will have the same property, but at a different node. So it'll be 1 at this node. Sorry, is my pointer showing up, by the way? I'm pointing with it. Alex, is that?
Your mouse cursor is showing, yeah.
Okay, good. So it'll be 1 here at this node, and then it'll go down to 0 at every other node in the domain. All right, so those are linear Lagrange shape functions. When you're using them, what you end up with is a piecewise linear function, at least in 1D. that you're solving for. There are higher order Lagrange shape functions, but again, they have that same property where they're going to be 1 at one node, and then they'll be 0 at every other node in the domain. So if you're using quadratic Lagrange shape functions, they look like this. This one here is 1 at this node, and then it goes down to 0. It actually goes negative here and then comes back up to hit 0 again, right? So it has to be 0 at all other nodes in the domain. And then your middle bubble function here is 1 at the middle node, because there will be 3 nodes on this second order element here. So it's 1 at this node, and it'll be 0 at the other nodes on the element, and 0 everywhere else in the domain. Okay. So those are Lagrange shape functions in 1D. Here's a look at cubic Lagrange on the left, which we do have support for in 1D, but not past that. I don't think we have cubic in 2D or 3D. And then the cubic Hermite shape functions are interesting, and they're here on the right. And Hermite shape functions, what's interesting about them is that you end up effectively solving for a coefficient for the value and a coefficient for the gradient. So you're actually solving for the gradient of your function directly. And this is important because it can guarantee C1 continuity, meaning that you have a smooth gradient across element edges, which is important if you're trying to solve a higher order PDE, like something with like a 4th order PDE or something along those lines. You need more differentiability then, and Cleft-Toscher elements can give you those, or cubic Hermites, both of those. And so you end up with one function here at this node that has a value of 1 and then goes down to 0, just like with Lagrange. But you also have one function here at this node that has a gradient of 1. This green one here is the only one of these functions that has a gradient of 1. And then it'll go and have a gradient of 0 at every other node in the domain. And then on this node, you have a similar thing where you have one function that has a value of 1 and one function that has a gradient of 1. And so you'll have a coefficient, you'll have this element will actually have 2 coefficients at each node, one to solve for the gradient and one to solve for the value effectively, if you want to think of it like that. So they're very interesting shape functions, very useful. All right, let's move on and look in 2D. So in 2D, this is what some biquadratic shape functions look like. So we have our square element here, and then we're showing kind of the elevation map of a few of the different shape functions for the second order or quadratic or biquadratic Lagrange shape functions here in 2D. Okay. Let's see. I think that's all we have on shape functions. Are there any quick questions on shape functions? I know we need to keep moving. Okay. Let's keep going. All right. So up to this point, what have we done? Let's go back to our weak form here. Where are we at? I said that we needed to discretize everything in this equation, right? So how much of it have we done? We turned U into UH. That was a good first step. So now the thing that we're solving for is made up of these discrete shape functions that are multiplied by coefficients. And that's something the computer can compute really easily, right? So that's good. We discretize psi so that it's not every function in the entire universe. It's actually just going to come from this discrete set of functions that are also the same functions that we're using as our basis functions in U, okay? Because it's handy. And one reason to do that, by the way, to have these have the same underlying shape function is, again, that symmetry. If psi and U are made up of the same functions, then this term here, again, generates symmetric matrices, right? So that's one reason to do that. Another reason is that you only have to evaluate one shape function and then you get the value for both of these things instead of having to evaluate 2 shape functions. Anyway, that's kind of beyond. So we've discretized U, we've discretized psi. So we're doing pretty well here, but one of the main things left to discretize are these integrals, right? So let's Right now, these are continuous integrals, something we would do with like Mathematica or Maple, or at least I would. I wouldn't try to do them by hand. But we want something that can be done by the computer and that can be done quickly by the computer. And so that's where we go to numerical integration. And the way that this works is that we're going to, instead of looking at the integral over the whole domain, we're actually going to break this up into the sum of integrals over each of the elements, which is completely valid. Our elements tessellate our domain space. And so we can compute the integral on each one of the elements and then sum them up to get the integral over the domain. So that's a valid thing to do. And what we're going to end up with eventually is that we're not going to want to do this integral within the physical space of the domain. It's much easier to do that integration in what we call a reference element and then map that integral back to physical space. I don't want to get into all the reasons why. It's just, it has to do with mathematical efficiency of the quadrature. But you end up with this form here where you have what's called a Jacobian of the map sitting here that's going to map you from the reference space, which is in exi space here, back into the physical space. All right, that's all I'm going to say about that. It's not really important for Moose. So I guess this is a pictorial of the difference between physical space here on the right, where we have some distorted element in our mesh. And then the reference element is always this really perfectly shaped square, in this case for a quadratic, for a quad 9 element in 2D. And so this shape here is easier to integrate over. So we actually do the integral here and then map it back into physical space effectively using that Jacobian. I'm not going to get into it. All right, let's keep moving on. No, not really that important to using Moose, but it's good to know what's happening underneath the hood. Okay, what you need to know is how to do those numerical integrals. Okay, like how is Moose actually integrating these things at all? And so if we have an integral like this where we're integrating f over our domain omega, what we want to do is find some function. What we want to do is formulate something on the right hand side here that gives us an approximation to this integral. And we're going to do it by evaluating that function f at particular points within the domain that we call quadrature points, and multiplying by particular weights, one that's associated with each one of these quadrature points, and summing them up, and then that will give us a really good approximation to the integral of the function. So the important part here is that these weights, WQ, and these points, XQ, are what we call a quadrature rule. And they're given to us. We have thousands of them within Moose, honestly. So you can use lots of different quadrature rules. But the most common quadrature rule is called a Gaussian quadrature rule. And the reason why we like it is that it has this property where it can exactly integrate polynomials of order 2n minus 1 in 1D, at least, of order 2n minus 1 with n quadrature points. So that means that we can integrate a, let me see, do a little bit of math. We can integrate a polynomial with order, what? Order 3 with only, how's that work? Polynomial of order, I always forget this. Polynomial of order 3 with two quadrature points. Yeah, thanks, Vandy. Yeah. Trying to do the math there real quick and failing at this point, very publicly, but that's okay. So yeah, we can integrate a third order polynomial with only 2 points, a second order polynomial with only 1 point, which is a really handy thing. And the reason why this is important is that we have a lot of polynomials. So our shape functions are generally polynomials. And when we use a Gaussian quadrature rule, we can actually exactly integrate those polynomials just by evaluating that polynomial at particular points within our domain and multiplying by particular weights and summing up those evaluations, we can get the exact value. So this won't even be approximate, but we can get the exact value of this integral. Now this property that you don't need very many quadrature points and that you can do this exactly is one of the things that even makes finite elements possible. I often think about this because if we didn't have this ability to do numerical integration so exactly and so quickly, we wouldn't be doing the finite element method, because we need this ability to quickly and accurately integrate over our domain, right? It's inherent in that weak form that we created. We have those integrals that we need to do everywhere. So the fact that this works, that we can have really accurate numerical integration with only a few evaluations of our function within each element, that makes all the difference. That's why finite elements is a thing, and that's why we're all here talking today and learning about Moose. Okay.
Derek, so
yep,
we're scheduled for a 15-minute break at 10:30. I don't know where you want to stop at, but
I think we're almost, yeah, we can stop here in a second. So let me just finish up the quadrature section here. So if we take this construction idea here and we substitute it back into that Jacobian mapped element integral that we had just a moment ago, we end up with basically this double loop where we're looping over elements, and then we're going to loop over quadrature points on the element. We're going to evaluate whatever function we want to integrate at points within that element, multiply by associated weights, and multiply by a Jacobian map here in order to get out our integral in physical space. Okay. And that's all well and good. It's very technical. This is, technically correct and everything, but for Moose, this is way too much detail, quite honestly. What you need to get out of this slide is that the thing that you're going to be providing is your weak form, right? That's what F is here, is your weak form. That's the thing that we want to integrate over the domain. And so your responsibility as a user of Moose is to evaluate your weak form at some particular point within an element. That is the basic piece of code that you need to write, is the evaluation of your weak form at a point within an element. Moose will do all the rest of this for you. It's going to multiply by the weights, it's going to multiply by Jacobian maps, it's going to sum over quadrature points, it's going to sum over elements, etc. It's going to do all those things for you. Your only job is to evaluate F, which is your weak form, okay? Yeah, so that's what you really need to get out of this slide. Kind of similarly here, this looks fairly messy when you write it all out like this, all the math, but the important part is that this guy right here, if you kind of squint your eyes and ignore everything else, this thing right here is your weak form. Grad psi I dotted with k grad u plus psi I beta dot grad u minus psi I f. This piece right here is exactly the same thing that we generated right here, right? With, I guess, even more directly, you can look at it here, and it's each of these volume integrals here just summed together. So again, there's all this extra stuff that's going on that Moose is doing, but all you need to do is evaluate your physics. And that includes your material properties, everything else that goes into this equation here is up to you to evaluate and give to Moose. And then Moose will do the rest of this, okay? And the same goes for boundary conditions as well. We have a different set of quadrature that will allow us to integrate on the surface of our domain so that we can integrate flux boundary conditions. Okay, I think that's where we're supposed to have a break. So I'd say let's stop here. Andrew, how long do you want to stop?
Just 15 minutes. So come back at 10:45 Mountain, US Mountain Time.
Okay, Sounds good. When we get back, we're going to talk about how we actually solve this system of equations that we're generating here. All right, so let's get rolling here again. We need to keep moving. So I was thinking during the break that I wanted to make this a little bit more explicit for those of you who either haven't had finite elements before or haven't thought about it in a while. Like what is actually happening here? Okay. So first of all, I wanted to explain just a little bit more about what a shape function is in Moose. So this right here is a set of two elements. Okay. So we have element 0 and element 1, always counting from 0, of course, like we're supposed to. And so we have two elements, 0 and 1, and here we're using linear Lagrange shape functions. And this is our entire domain. From here to here is our entire domain, okay, for this problem. And we're going to use linear Lagrange shape functions. And what that means is that we're going to end up with, in this case, one full shape function, which is phi1 right here, and two kind of half shape functions, phi0 and phi2, okay? And this is really the way that we like to think about it. You know, back in the slides, it showed kind of each one of these pieces left and right as being separate shape functions. There are a lot of people in the finite element community that view it that way. And then they view kind of tying these two pieces together as part of the process. But if you really think of this as one shape function right here, that's spanning these two elements, and it has a separate gradient on either side of that node. So these are our three nodes here, 1, 2, 3. And we have one shape function here that's 1 at this middle node and goes down to 0 at the other nodes. We have one shape function here, phi0, that is 1 at this node and goes down to this node. And the other piece of phi0 is missing. It's basically cut off by the edge of the domain. And then we have kind of a corresponding shape function on the other side of the domain that's missing one half of it as well. So these are our three shape functions. And the reason why I like to say it's three shape functions is because we're going to solve for three coefficients. And so if we write out what UH is in this case, we can say that it's the sum of UJ phi j. And am I using the right terminology here? Yeah, it's the sum of UJ phi j. And somebody correct me if I'm wrong. Is this supposed to be I or J right here? Alex or somebody? I'm getting mixed up on just a second. Anybody?
I think it's I.
Yeah, I think
J
you're right.
is for test function, right?
Yeah, I don't know why I chose J here. I don't want to do this wrong, and you'll see why. This is important, actually. So I'm going to rewrite this UI phi here.
I mean, you can use whatever index you want, but in terms of Moose notation, we would probably index this with J.
Yeah, I don't want to confuse people, so let's make sure that we use I when we're talking about the function we're solving for. So this is the sum of UI phi, and in this case, there's three coefficients and three shape functions. And so I've literally written those down explicitly here so that you can see what this equation, what this function is ultimately going to be. It's going to be phi0, this linear function right here, multiplied by this coefficient u0. And then it's going to be this function phi1, which is this guy right here, multiplied by a scalar coefficient u1, and this function phi2 multiplied by this scalar coefficient u2. And when you sum up these coefficients times their shape functions, what you're going to end up with is a piecewise linear function. So you're going to take each of these linear functions and scale it effectively, scale it, and then add them together, okay? So down here, I made up a fictitious kind of solution vector here of U0 being 1, U1 being 3, and U2 being 2. And then here, this is showing what UH actually is, what the function actually is. So it'll be 1 at this node here. It'll be 3. This is 3 here. Okay, it'll be 3 at this node, and it's going to be 2 here at this node. Now that's a property of Lagrange shape functions. Not all shape functions are so easy to just write down what the solution would look like by using their values effectively as the value of the function at the nodes. Why does it work that way? Well, it works that way because the Lagrange shape functions, there's only one of them that is non-zero at any one node. So when you multiply phi1 here, for instance, by 3, every other shape function is 0 at that node. So the value of your function then is then 3 at that node. And that's the reason why the Lagrange shape functions are used a lot, because they're just really simple to understand. And the solution vector is really easy to interpret as well. So this right here, this whole thing is our actual solution, all right? It's our function. It's piecewise linear. It's continuous over our domain. And it has a discontinuous gradient here at this point, okay? All right. Any questions on that before we move on from shape functions and what they do? Or anybody else want to chime in from the Moose team on this? Okay, so let's move back to the presentation. All right, so this gets us into our next topic here, which is Newton's method. So what we've generated so far is this residual vector, and we're doing it piece by piece by, we did it by discretizing each piece of that weak form. And what we ended up with, again, is this residual vector, where the entry in that vector, every single entry in that vector is an integral of our discretized weak form. Okay, that's what's in here. Now, what does the residual tell us? Like, why are we forming a residual? What does the value of it mean, right? The value of the residual is, you could think of it effectively as the misfit between your current guess at UH and the PDE and boundary condition that it's trying to satisfy. So at the point where we actually solve this problem, this UH, when you put it through these operators, these grad operators, and you add up all this stuff and you integrate it over the domain and you do the same for the boundary conditions, when we find the correct UH, this whole thing will be 0. Because if you remember back here, when we generated our problem that we're trying to solve, we want to solve to where this left-hand side is actually equal to 0. So we will have solved our problem whenever this U, or our discretized UH, satisfies this condition, okay? So our residual vector here, if we evaluate it with a current guess for UH, which is what this is showing right here, every entry in there represents somewhat of kind of the misfit between the UH that we need, or the misfit between the function that we currently have from our current guess or our current values for UH and our constraints, which are the PDE and our boundary conditions in this case, okay? So that's what's in the residual. So we have this list of equations, one equation per entry in this residual vector, and we need to solve for all of them to go to 0. We need to find the coefficients inside of UH such that it will satisfy these conditions here for every entry in that residual vector and make the entire thing 0. And once we've done that, we know that we have the correct function, the correct discretized form of the function that solves our problem. our discretized problem at least, okay? So what we're looking for here is to turn this entire residual vector into 0 by solving for the coefficients within here that satisfy our constraints, okay? That's our game plan. But how do we do that? How do we solve? We have effectively this enormous system of equations, and they're related to each other because, as I showed just a moment ago, the shape functions span multiple elements. So the coefficients of one shape function impact the integrals for adjoining elements, for many adjoining elements. And so these equations are not independent. They actually have some dependence on each other. So we end up with this large system of equations that we need to solve, all right? And in Moose, that system of equations is almost always nonlinear. Why would it be nonlinear? Well, it could be nonlinear because, for instance, k might be a function of u. It could be nonlinear because f is some nonlinear function of u. Beta might be some nonlinear function of u. There's a lot of ways to make this nonlinear. K being a function of u is very common. If we again think of u here as being temperature and k being thermal conductivity, it's super normal to have thermal conductivity dependent on temperature, right? So that's a very easy way to end up with a nonlinear equation here that we need to solve. So if we have nonlinear equations, we have a system of nonlinear equations. We need something to solve that system of nonlinear equations. And what we're going to do is use Newton's method. And the first thing we're going to do is look at Newton's method for one single scalar equation, and then we'll talk about the system case in a moment. So Newton's method, I'm sure you've heard of it, is a root finding method. And what it does is it finds the zeros of some nonlinear function, right? It finds a zero of a nonlinear function, which is exactly what we need. Our residual vector can be thought of as a nonlinear function. It's a function in a vector space, but it's a function. Yeah, it's a function that generates a vector, but it's a function. And so we can look at one particular equation. So let's think of one single scalar equation, and we can write down Newton's method like this. What you do is you start with some initial guess, x0, at where the root is. And then what you're going to do is you're going to evaluate f at that point, which is this part over here. You're going to evaluate the gradient of f, or in this case, the derivative in 1D, right? The gradient of f at that same point. And then you're going to, quote unquote, solve for this update, xn plus 1. That's going to give you your new guess at where the root is for the nonlinear function. And I've written this kind of in update form, which is totally unnecessary here for one single scalar equation, because we can actually just substitute this in up here. But it's useful to write it this way because this is the way we're going to think about it in a moment. So to quote unquote solve for this update, we would just take this to the other side, right? And then we could just compute our update directly in this 1D case. But anyway, we get our update, and then we could take that update and we add it to our existing guess to get our new guess, and then we iterate back up here again, and we evaluate f at that new guess, the gradient of f at the new guess, and we solve for another update to move us to the next point, which is our new guess at the solution. So let me draw a little bit here to kind of explain what's going on. So what you end up with, let me get a, sorry. What you end up with is, if we look at just a simple 1D XY plot here, let's say we have a function that looks something like this, okay? So it's nonlinear, obviously, and we want to find a root, right? Now there's two roots, right? There's this one and that one. Which one of these do we want to find? Well, It depends on the equation that you're solving. Both are valid roots, right? But typically in finite element land, we're solving something to do with the physical world. And often this U is going to get fed back into the material property system or something along those lines. And usually what we're looking for here are positive values, right? So if we're solving for temperature, negative temperature doesn't make any sense. So usually we're looking for this root over here. Now that really has to do with physical constraints, but that's typically true in our finite element case, that we're typically looking for the positive roots here. And there might even be more than this, right? In a very more complicated nonlinear function, which we will be solving with Moose, you might have many roots, even positive and negative ones, okay? So what we want to do here is use Newton's method to try to find this positive root. And the way that this works is we're going to take an initial guess, which I'm going to call x0, and just put it here, all right? And then what we do, as I showed in that previous equation, is we evaluate f at that position, and we evaluate the gradient of f at that position, and then we use that to find the update. Now, what does that look like pictorially? What it looks like is that you basically use this to shoot back down here to find this position. And this distance, this distance from here to here is our delta x. It's how much we're going to move from our current guess to our new guess, okay? And so we have our new guess now, and this becomes x1. I won't put a 1 there because it's going to get sloppy. So this becomes our new guess, and then we're going to go up here, and we're going to evaluate f at that new position, and we're going to evaluate the gradient, and then we're going to use that to, again, shoot back down here. And this is our new update from here to here. You can see that it's smaller. That's a good thing. And this is our new x right here. We evaluate f again. Of course, my hand wasn't completely steady here. So, and the gradient, and then we go back down. We keep doing this, evaluate f and the gradient, go back down, f and the gradient. And you can see what's happening here is that this is basically circling in on the root, right? As you move around here, it's getting closer and closer to the root. And as you go through the iterations here, it will eventually get to within some precision of the root, right? So this is how Newton's method works. It's a method for finding roots in general. It's very powerful. The major property of Newton's method compared to other methods for solving nonlinear problems is that by using this gradient information and using it to move to the next guess, we gain speed in the order of convergence. So Newton's method has what we call quadratic convergence, which I don't want to get into, but let's just say that it converges more quickly than something with like a Picard iteration or something like that, like a fixed point iteration, which only has linear convergence, okay? So Newton's method converges very quickly on the root, if it converges, okay? And another thing about quadratic convergence, it only gains that quadratic convergence once you're within some distance of the actual root, which in a complicated nonlinear landscape, we'll say is within what we call a ball of convergence around, around the root that we're looking for. Once you're within some distance of the root you're looking for, that's when you actually get into the quadratic convergence realm for Newton's method, and it converges very quickly to the root at that point, okay? So that all sounds great. But the problem is that there are issues with Newton's method. So if we go back here and we draw our function again, there's all sorts of things that can go wrong. First of all, the initial guess that you take actually makes a big difference, right? So up here, I guessed this as my initial guess, and you can see that it ended up swirling around here until it'll find the root right here. But what if I take a different initial guess? So for instance, what if I guess over here? we go up here and we evaluate f and its gradient. And it shoots us over here. Now what happens? Well, we evaluate f and its gradient, and we go down here, evaluate f gradient, f gradient, and it looks like what's going to happen is we're going to find this root. So we actually took here a positive guess over here that ended up generating a solution with a negative value, all right? And in our finite element world where we're doing engineering calculations, this is typically death. What this means, actually, even all the way back here on this first step, where we find this guess right here, what this means is that we'll probably have something like a square root or something in one of our material property evaluation routines, and square root of a negative number is going to, you know, bomb out with not a number, and our whole simulation is going to grind to a halt. Okay, so Newton's method is very dependent on the initial guess that you give it, and this is a really important aspect for using Moose, because your initial guess is set in Moose by your initial conditions. And the initial conditions are a system within Moose where you can actually plug in initial conditions. And you always need to make sure that those initial conditions make sense and are a good starting point for your problem. If you put in non-physical initial conditions for your problem, then you're going to end up in trouble like I did here, okay? This might have been, let's say, like a temperature that's way outside of the range of our problem, like 1,000,000 degrees or something like that, something that doesn't make sense in terms of our problem. And so we ended up finding some non-physical answer because of that, okay? So that's one thing that can happen. We can also, there's lots of ways that this can go wrong. So I'll just draw another one here real quick. If we guessed here, we could get a slope of about 0, and this could go off basically to infinity. That's really not great. We'll end up, again, blowing up our nonlinear solver. Our whole solve will go to a stop, okay? What this really comes down to is two things. One is taking a good initial guess is important, and two is that sometimes we might need to recognize that, wait a minute, we don't want to have a negative solution. So let's just not let the update go into a non-physical area, all right? So we can actually truncate our update in order to stay in a physical regime. And sometimes that's actually important in really, really difficult nonlinear problems. And in Moose, we have a system that actually you can plug into to give it what the physical bounds are of your problem in order to keep the nonlinear solver on track. It's the, what's the name of that system? Somebody, I just blinked. Anybody?
Bounds. It's
What's
just
that?
bounds.
Is bounds?
Yeah.
The dumping system, possibly
Yeah.
they're talking about.
That's what I was looking for, the damper system, the damping system. So we can do a damped Newton's method in order to make sure to keep the nonlinear solver within a physical regime, okay? And we have other things too. Alex mentioned bounds. That's a way of solving a constrained PDE with bounds. That's a slightly different idea, but similar. Having similar purpose sometimes.
Damping
all right.
just usually reduces like the Newton update. It doesn't, depending on the damper, it doesn't necessarily preclude you from going to an unphysical state.
If your damper won't let you get to a non-physical state, but that's the only place that you have a root that's nearby, then what will happen is your nonlinear solve will stall because you're not allowing the Newton solver to get to the root that it wants to get to, and it'll just keep butting up against your damping scheme. So damping doesn't actually, how do I put it? It won't force your solution to be the physical solution that you want. A really good example of that is you can't use damping to remove spurious oscillations, like what you would get when you're solving like a pure advection problem with continuous finite elements or something like that. Damping isn't going to help you because the solution, the literal solution to the discrete problem, actually has those oscillations in it. And if you don't let the solver get to those oscillations, then you just won't get a solution. So damping isn't a solve-all. It doesn't fix everything. There's other technology to use to fix those kinds of things. But damping can help. If you know that your temperature should only ever be between, let's say, like 800 and 2000 degrees, then it's valid to put a damper in to keep it within that, so that you don't accidentally run into any of these kind of scenarios. So it is a valid piece of technology. There's another thing that's related to this. It's called line search. It's basically a more mathematical way of doing damping effectively by inspecting your solution landscape here and trying to make better guesses about where to let the updates go. I don't want to get into line search too much. Honestly, for the really complicated physics problems that we're solving here, we've really found over the years that line search often hurts more than it helps. So I don't want to get too much into that. Okay. Anybody else want to say anything else about Newton's method here? I missed something. Anybody have any questions either? Oh, there's something here.
I mean, what I want to mention is Newton algorithm actually is derived from Taylor expansion. So when we're talking about the quadratic convergence, that means we truncate the term with the second derivative. So the quadratic convergence in terms of update norm.
Yeah, that's a good point. Yeah, the updates shrink. Yeah, at that rate. All right, let's unmute Ben here. Benjamin Ramirez, you're on.
I think you were mentioning the fact that Newton method is local conversion, and you try to make it global conversion with something like line search, right?
That is one way to view it. Yeah. Mm-hmm. I don't know if you want to say anything more about that, Fandy, about line search. Yeah, that's what line search is supposed to do, is kind of give you it should expand so that you can find the root more easily. But
one problem with the default line search algorithm in PETSI is that it doesn't allow you to tunnel through a hump. Like if you're stuck in like a local minimum, but your root has to basically go over a hump in the function, like a backtracking line search algorithm won't allow you to do that, because your residual is actually going to have to increase at some point before you reach your solution. And cubic backtracking won't allow that to happen. But if you have no line search at all, you can actually get through that hump.
Yeah, so if you have a solution that looks like this, and you end up taking an update, let's see, that's not a good one. Let me try again. And you end up, let's say you're over here and you take an update that will, no, it's here.
I liked your first one.
Yeah. Anyway, you guess here, you take an update that takes you here, and then now your function value is here. This is technically larger than your last residual, and many line search algorithms will fail on that. But that's actually what you need to happen here. The residual needs to increase, and then you will ultimately swirl down and find this root here. So line search methods often keep you from being able to do that. And we have that all the time in Moose. There are lots of non-smooth problems and extremely non-linear problems in the problems that we solve. All right, let me turn off Ben's microphone here. Thanks for chiming in, definitely appreciate it.
Okay, I kind of hear some people talk about a global solution. So for Newton, you always look for local solution. So which local solution you get is depend on which initial guess you pass in. So line search won't help you get a global solution. They just get you reach a solution faster if your function is smooth.
Yeah. Okay, let's see here. Anything else here? I think we're good. Let's go back to the slides here. Thanks, Fandy, for chiming in. I appreciate it. All right. So back to the slides here. So what we've done so far now is we've looked at Newton's method in 1D for one single scalar equation and how it can find the root. And we talked about the importance of an initial guess. But what we have is not one single scalar equation, right? We have a system of equations. We have a whole vector full of nonlinear equations that are related to each other and coupled to each other. And so we need to solve this system of nonlinear equations. And what we're still looking for, though, is to find the root, right? We want to find where our residual goes to 0, and that's when we will have solved the problem. And so we need to do that by solving for these coefficients, uj. And for this, what this ends up being is if we take this 1D form here and look at it for the vector form, the right-hand side, which was just the evaluation of f, becomes just the evaluation of our residual here, right? So this is something we can do. We just spent the last, what, hour and a half, hour or whatever, coming up with a discretized form of our residual specifically for this purpose so that we can evaluate it for the right-hand side of this solve, all right? So this is our residual vector here, and we can evaluate it. We can do numerical quadrature, we can evaluate UH, we can evaluate our test functions and sum them all up over our domain and actually compute this residual vector. What this thing is over on the left, if we look back again at the scalar form, it should be f prime. So what this guy is the derivative of the residual with respect to all of the unknowns, okay? And so what you're really going to get out of it is every row is going to be the derivative. So you have n equations, and then you're going to take the derivative of each one of those equations with respect to every unknown in the problem, and that generates this matrix of entries, all right? So this is a matrix. And then that means that our update here is going to be a vector, because what we're going to do is actually solve for an update to every single one of our coefficients in our problem all at one time. We're going to move them all to try to find where the entire residual will be 0. So our update will update every single coefficient in our system. So this right here is a matrix vector, matrix times a vector equals a vector. So this is a linear system of equations to solve, right? AX equals B here. And we can evaluate B, we can evaluate J, even though we haven't talked about it, we can evaluate it. It's expensive, it's sometimes difficult to form, but we have a lot of capability in Moose for helping us there. But we can evaluate J, and then we can give this linear system of equations after we form it over to a solver like one of the ones in PETSI, and it can solve and give us back this solution vector, okay? In an ideal world, hopefully it works that way. And then once we have our update, we take and we actually update the value of every single one of our coefficients simultaneously. And we get our new guess for all the coefficients across our entire domain. And then we cycle back up here and we do this again. We evaluate our residual at our new guess and our derivative at our new guess, and then we have a new linear system of equations to solve. So every single iteration of Newton's method within Moose is actually going to need to solve a linear system of equations, all right? And this is where things can kind of get complicated, because to solve that linear system of equations, we typically use an iterative solver, right? Like GMRes or CG, or any number of iterative solver methods. We can also use direct solver methods as well, like just Gaussian elimination, etc. But we typically use iterative linear solvers. And what that means is that you'll have your nonlinear iterations, which are trying to find the root to your residual function. And within there, you'll have linear iterations, which are trying to solve this linear problem, okay, to find the update to move to the next guess, okay? So it's a double iteration, an iteration over nonlinear iterations, and then within there, an iteration of linear iterations trying to solve this linear system of equations, right? So that's a normal thing to see when you're using Moose. So J is the Jacobian matrix. It can be evaluated. It looks like this, where the ijth entry in our Jacobian matrix is the derivative of the ith residual, the ith entry in the residual vector, which is an equation, with respect to the jth coefficient in our problem. So you do literally take the derivative of every single entry in the residual vector with respect to every degree of freedom in your problem, and it generates this matrix. I don't want to get into more about that right now. It turns out that operation, the derivative of every residual with respect to every coefficient, is, as you might imagine, a fairly expensive undertaking. Now, we have a few things that help us out. The local support I was talking about earlier means that the derivative of the, let's say, the 8th residual entry won't probably be coupled to the 30th or 40th coefficient or the 1000th coefficient, because our shape functions have limited local support. That means that there's only going to be a few of these derivatives that are actually non-zero at any one time, and that gives us a sparse matrix, right? A sparse pattern in our matrix. So that means that this thing is often, like most of the time, computable within a reasonable amount of time. You can technically store it. It will take a lot of memory, but usually we can store it. It depends on how big the problem is, etc. We can spread it out in parallel, which helps a lot as well, on the storage and on the computation. But it is a beast. You have to do a lot of derivatives in order to, a lot of manual derivatives and a lot of coding of derivatives. And sometimes it's even difficult to actually take those derivatives. Like if you have piecewise data for a material function or something like that, you know, taking the derivative of a bunch of xy points can be tough. So sometimes the derivative doesn't even make as much sense. So all of this is a way of introducing this idea of Jacobian-free Newton-Krylov. And this is something that Moose was kind of founded on. And the reason why is because this is pretty critical for extremely large multiphysics problems. And by large, what I mean is many coupled equations. So if you have multiple coupled equations like heat conduction and solid mechanics and chemistry, you end up with this huge residual vector that has the coefficients for every single one of the functions that you're solving within it, okay? And whenever you take the Jacobian matrix, you have to take the derivative. To find the Jacobian matrix, you have to take the derivative of every equation with respect to every unknown. Okay, so you have to take the derivative, let's say, of the weak form for the temperature with respect to the displacements and with respect to all the chemical components. So as you go up in the number of equations that you're coupling in your multiphysics solve, this Jacobian can quickly get out of control, both in terms of being able to write down these derivatives and also in terms of computing it and storing it. And so in that landscape where the Jacobian matrix is an extreme burden, there's this idea of Jacobian-free Newton-Krylov. And the way that it works is recognizing that a Krylov method, which is one set of methods, one set of iterative solver methods for solving that linear system of equations. A Krylov method is made up of these steps where you're iteratively updating and moving to the next guess, the next iterate in your Krylov method. And I'm not going to go through everything about Krylov methods here, but the important part is that the Krylov method works by taking successive Jacobian vector products. And it turns out, which you can see right here, and it turns out that we can capitalize on this fact by effectively approximating that Jacobian vector product in a way that we don't ever have to actually form the Jacobian matrix, all right? So J itself, the actual Jacobian matrix, doesn't show up in the Krylov vector. Only the action of J on a vector. And so what we can do is we can actually approximate this Jacobian vector product. Because we know the Jacobian is made up of derivatives, we can actually use a discretized form of the derivative, right, that we all learned in Calc 1, where we just evaluate our residual function at two different points that are slightly apart by some tiny epsilon, and then we divide by epsilon, and that gives us an approximation to this Jacobian vector product. Now, I'm not going to go through the full derivation of how we get to this form. There's some really good Jacobian free Newton-Krylov papers out there, one in particular by Dana Kernel, that goes through the derivation of how you actually arrive at this form. But you'll just have to trust me that we can approximate this Jacobian vector product using basically two residual evaluations. So again, everything we've been doing today is to evaluate the residual. And so we can do this. We can evaluate the residual at this perturbed point. We can evaluate this residual at this point. And then we can divide all the entries by epsilon in order to evaluate this Jacobian vector product. And then we can do that over and over again in our iterative solver in order to solve this linear system of equations. And the advantage here is that we don't actually have to do any analytic derivatives to form J. We also don't have to take the time to compute all the entries in J. And we don't have to take the memory space in order to store J either. So there's a lot of really important things about this that enable some of these really extremely complex multiphysics problems, like more than 30 or 40 coupled nonlinear equations. And we have some applications that literally solve thousands of coupled nonlinear equations, okay, where forming the Jacobian matrix is literally not possible. There's not enough memory to even do it. And so you have to use something like this Jacobian free method to get there. All right, so this is an important piece of technology. Unfortunately, though, there are a couple issues here. The first one is how to choose epsilon, which I'm sure a lot of you are thinking of right now. My answer to how to choose epsilon is that a lot of smarter people than me, at least, have thought about this problem and have come up with these really handy ways to compute epsilon. And they've coded those things up in PETSI, for instance. So PETSI has several algorithms that can do this Jacobian free approximation. And it's just built directly into PETSI. And the evaluation of epsilon is just a routine within PETSI. And there's a few different options. And you can tweak it slightly if you need to, but for the most part, you can kind of ignore this epsilon thing. That's not exactly true. There are things to do with scaling, et cetera, but I don't want to get into all that right now. But effectively, epsilon, let's assume it can be chosen by an algorithm that computes an optimal epsilon for us. Even outside of that, there are issues. So if you've ever used a Krylov solver, you'll know that it actually needs this thing called preconditioning. And preconditioning, what it does is it helps the Krylov solver converge. So a Krylov solver, if you look at the math of it, is guaranteed to converge in, if we have infinite precision, if we're working in an infinite precision continuous space, a Krylov solver should converge at least the very most iterations it should take is the same number as the number of unknowns in your problem. Now, that's a really bad bound, right? I said that we're going to be solving problems with millions of unknowns. It would be really terrible if our linear solver took millions of iterations. We would never solve the problem. So we hope that we can do better than that, but that's our mathematical bound. That's our maximum. That does, for one thing, tell you that as the problem gets larger, you should expect that Krylov solver will take more iterations to solve. Okay, so that's an important piece of Krylov solvers, is that as the number of unknowns goes up, in general, the number of iterations needed to solve will also go up. But one of the ways that we can fight against that is using preconditioning. So another thing about Krylov solvers is that their convergence rate is highly dependent on the I'm blanking here. It's highly dependent on the condition number, I'm sorry, on the condition number of the matrix. And it will, basically, the better that condition number is, the smaller it is, the faster the Krylov solver will converge, okay? And so one of the things that we can do, one of the games that we can play is to manipulate our matrix in order to improve the conditioning of our system, the condition number of our matrix. And that will allow our Krylov solver to converge faster. There's a lot of other things to do with preconditioning as well, but that's the basic idea, is that we want to manipulate the matrix in some way in order to let the Krylov solver solve faster. Does anybody else want to say something about that? Okay, we'll keep going.
Good summary.
All right, good enough. So one of the important pieces, though, is that even though Jacobian-free Newton-Krylov does not need a Jacobian matrix, it's still a Krylov method, and we still need to do preconditioning. So we don't get out of this just because we don't have a matrix. There's still kind of an inherent condition number in that Jacobian vector product, all right? And that's kind of a bummer, because preconditioning is typically done, as I said, as kind of a manipulation on the matrix, and usually it's done using at least an approximation of the Jacobian matrix. So even though we said we were going to do Jacobian-free Newton-Krylov, in reality, we still actually need to form some sort of matrix to help with preconditioning so that our Krylov solver can solve the problem, all right? So let's look at one particular type of preconditioning here. Within Moose, there's two major options for preconditioning. There's right preconditioning and left preconditioning. And it literally has to do with what side you're multiplying your matrix by your preconditioning process, basically, right? So this is right preconditioning, so we're multiplying on the right. Left preconditioning happens on the other side, and you do kind of a slightly different manipulation to your problem here. But right is pretty easy to talk about. So what we've done here, if you look at this M inverse M right here, if you just squint for a moment and look at this, we basically multiplied by the identity matrix, right? We haven't actually changed our problem. M inverse, where M is some matrix, so I haven't said what it is yet, but it's going to be our preconditioning matrix. If we multiply by M inverse M in the middle of our left-hand side here, like this, we've multiplied by the identity. And so we're not actually changing this problem at all, right? The solution to this problem will be the same as the solution to the original linear system. And what we're going to do is kind of group terms in a very interesting way, though. If we kind of group this M over here with our update vector that we're solving for, you can agree that this is a vector here itself. So we can treat this as a vector to solve for instead of just solving for this. So if we look at this as our entire vector that we want to solve for, that means that we can use this M inverse to basically manipulate J. And at the point where M inverse looks like J inverse, then we can immediately know what the solution is here, right? Because this will turn into the identity. So that's the game that we want to play. M here represents our preconditioning matrix or our preconditioning process. And if M is somewhat similar to J, and if you do a good job of inverting it to make M inverse, then you can significantly reduce the condition number of your matrix here on the left-hand side, which will allow your Krylov solver to solve in many fewer iterations, right? But we can play a game where M doesn't actually have to be the full Jacobian matrix. It can be some approximation. And M inverse doesn't actually have to be the inverse. It just needs to be enough of an inverse that it reduces the spread in eigenvalues in our in our Jacobian matrix, okay? As long as it's effective at reducing that spread in eigenvalues, then it's an effective preconditioning process. It doesn't matter what you put into M, it doesn't matter how you inverted it. If it's a matrix and it reduces the spread in eigenvalues, then it's helping, okay? And so we can play lots of games about what to put in M and how to invert it, or how much of it to invert, or how well to invert it. And hopefully by putting some approximation into M and inverting it at least partially, we can come up with something that will allow our Krylov solver to converge much, much, much faster than if we had no preconditioning at all. And it turns out that that whole thing with the bound on the number of iterations, I mentioned that that only works works in our kind of continuous infinite precision land out here in the real math land. In the real world, in a computer in finite precision, it can be the case that round off error and many other things can add up so that a non-preconditioned Krylov solve might never converge because it just has enough error that it can't move in a direction to actually find the solution. So preconditioning is not only necessary for speeding up the problem, it's also often necessary for actually even getting a solution for some of these larger problems. So it's a really critical piece of the problem, all right? It's important to note that right preconditioning, for instance, flows very easily into this Jacobian vector product. And the inverse of our preconditioning matrix, or in general, our symbolic preconditioning process here, shows up here in our finite difference form. So we can still do preconditioning even though we don't have a Jacobian matrix. Right? That's what that means. I said it in the positive tone there. We can still do preconditioning, but also there's the negative of that. We still must do preconditioning even though we don't have a Jacobian matrix. Okay. All right. So let's not.
So yep, one important thing is we should make sure M is non-singular, so you can get the right answer. At least, I mean, choice of M is arbitrary, but you need at least make sure M is non-singular.
That's a really good point, and that plays into a lot of preconditioning processes, especially when you have things like rigid body motions and solid mechanics and things like that. You need to be careful with what you put into M and how you treat it as well. That's a good point. You need it to not be singular. Okay. I think we might talk more about preconditioning later. There's a lot to it. There's a lot of capability in Moose for preconditioning. You can specialize and make your own preconditioners. You can plug in your own preconditioning processes, your own way of computing preconditioning matrices. There's a huge amount of flexibility there, but we don't want to go into that just yet. So let's just assume for a moment that we can create an effective preconditioning matrix and we can effectively invert it and kind of move on with solving the rest of the problem, okay? So in Moose, to choose between Jacobian-free Newton-Krylov and preconditioned Jacobian-free Newton-Krylov, which we call PJFNK, you do that in the executioner block. Now, Andrew showed you what an input file looks like, and you have this executioner block at some point in your input file, and you can set solve type equals PJFNK. And what that'll do is it'll use that preconditioned Jacobian-free Newton-Krylov form. It'll form some sort of a preconditioning matrix and apply some sort of partial inversion process to it in order to apply preconditioning. Now, the defaults for all of that are not really great. So normally you're going to want to make some adjustments to what preconditioning process is actually used for your problem. And again, we'll kind of get into that later. If you don't want to do any preconditioning because you really just want to watch linear iterations flow down your screen for all of eternity, you can do JFNK and leave out the whole preconditioning mess. generally, that's not going to work for any decently sized problem. You're going to want to use some preconditioning. Okay. Now, if you have a problem that is amenable to actually forming the entire Jacobian matrix, either you know what those derivatives are, or you can use the automatic differentiation system in Moose to automatically compute those derivatives. And if they're storable, so your problem only involves, let's say, a few coupled variables like 4 to 10 or something like that. So you have enough memory to be able to store the Jacobian matrix. If you can actually form the full Jacobian matrix, then you can use solve type equals Newton and not do this approximate Jacobian vector product thing with JF and K, but actually just do Newton's method as described a few slides before, where we're going to invert the Jacobian, effectively invert the Jacobian matrix and find our update, right? But we'll still do it with an iterative solver, typically like a Krylov solver. Okay. So Newton's method, solve type equals Newton, is really specific to when you know you can compute the exact Jacobian matrix. That is becoming more popular in Moose these days, and that's for a lot of reasons. But one of the reasons is the automatic differentiation system, which Alex Lindsay was primarily working on, and I did some work on that as well. But the automatic differentiation system is helping us compute perfect Jacobians more often. So that's allowing us to choose Newton more often. And typically, I think we've found at this point, it's fair to say, and you can hear the resignation in my voice because I like Jacobian free Newton Krylov, but I think it's fair to say at this point that if your problem is amenable to forming the Jacobian matrix, that's typically a good idea. Does anybody else on the Moose team want to chime in on that?
I definitely agree. I think that if you can, automatic differentiation aside, if you can form the Jacobian and there's not memory constraints, that your problem will solve faster with solve type equals Newton. I mean, with automatic differentiation, there's some overhead costs there, but you have the advantage of a very robust solve system, a solve system that's much more robust than PJF and K because you don't have to worry about computation of a differencing parameter.
Yeah. Yeah, that's exactly right.
If your problem
Go ahead,
is
Fanny.
not complicated enough, you actually can form the whole thing. It's also a good idea to use Newton because you will have really great preconditional solver.
Yeah. Yeah, that's a good point. When we're using Newton, we actually use, we typically use the full Jacobian matrix as our preconditioner as well. That's not necessary. You can actually change that within Moose, but that's the default. There are reasons to use still an inexact preconditioning matrix, even when you're using Newton's method, which we maybe don't need to get into right now. The last thing I'll say on this is that we have published papers over the years that show some of the trade-offs between Newton's method and PJF&K, and one of them is that in JF&K, you have to do these residual evaluations, and you need to do one residual evaluation every single linear iteration in your linear solver. And that's really expensive, but forming the Jacobian matrix is also really expensive. And depending on the number of coupled equations that you have, it might be more expensive to form a Jacobian matrix, like literally to compute the entries in it, than it is to do a bunch of residual evaluations. And that's going to depend on how many linear iterations you have. It's going to depend on the number of non-zeros you have on each of your rows, which is related to your shape functions, and the number of coupled PDEs you have. So there's a lot of things that go into that. But I'll just say that there is kind of a trade-off point. Once you get to a certain number of nonlinear coupled equations, PJF&K can overtake and be faster than Newton, even in the case where you could form the full Jacobian matrix. So that is a thing to look out for. I will say the threshold for that is kind of high. I would personally, from the papers that we've published, put it in the 10 to 20 equation kind of range. So you really need to be coupling together a lot of nonlinear PDEs before before you really hit that trade-off point. But yeah, so I want to point that out. We have a question here from Greg Vernon, so let's turn him on. All right, Greg, go ahead.
Hi, can you hear me?
Yep.
So maybe I missed this too, but just comparing with other codes that I've used in the past, that isn't one of the other really detrimental issues with Newton, just the memory requirements around Newton.
Yeah.
And so I just, have you guys looked at the difference in memory between the two methods? Because I find I'm usually constricted by the memory requirements with Newton, say like in Abacus or something.
Yeah, that's a good question. It can depend. It can depend on not only how much memory it takes to store the Jacobian matrix, but also how much memory your inversion or approximate inversion process takes as well. So if you're using, for instance, a direct solver, like is often the case in Abacus and many other solid mechanics solvers, those will tend to use a lot of memory themselves. So not only does the Jacobian itself take a lot of memory, but its inversion takes a lot of memory as well. So using a Krylov solver can help there, because it will use often less memory, definitely less memory than storing the fully inverted matrix. So that's one thing. And then you are absolutely right, though, that's another reason to use PJF and K, is to certainly save on the amount of memory. There are many, once you get up over a certain number of coupled equations, and depending on how much memory you have on your computer or on your compute nodes, it just might not be feasible to actually form the full Jacobian matrix. So that's a good point. Greg, I'm gonna put your hand down. Hopefully that answers your question, but feel free to put it back up. All right, we have something else. Shrinath, you there?
Can you hear me now?
Yeah, we can hear you.
Just wondering if there's going to be any possible support for quasi-Newton methods where you can choose how often you want to reform the Jacobian.
Yeah, so that support is already in there. Whenever we say Newton's method, we almost never actually do an actual just regular Newton method as it was written down on those slides up there. We're always doing things like truncating the linear solves early so that we can get to updates faster, many other processes. We play around with Newton's method a lot. So one of the options is definitely to delay Jacobian evaluation. You can turn that on even just right on the command line using some PETSI options. I don't know, Fandy, if you want to say more about that.
I think it's fine. You already answered the question.
Yeah. So
yeah, just Google PETSI lag Jacobian.
Yeah, that's a good question. Yeah, whenever we're talking about these things in the training, we're typically, simplifying things to try to explain what's going on, but there is a whole lot of mathematical machinery going on the inside of Moose to help solve these really complicated nonlinear problems. All right. Let's see here. All right, so I think we got to be getting close to finishing here. So JF and K, the only thing that you need to do in order to drive a nonlinear solve with JF and K is compute the residual. And in Moose, what that means is that the kernel objects that you make, which represent the volume integrals in your residual, you only need to override the function called compute QP residual. And that QP there stands for quadrature point, and that goes back to the numerical integration that I was talking about earlier, where your job is to compute your residual at one particular quadrature point at a time. And you do that within this function called compute QP residual. And so if you fill out the compute QP residual, which is a required function to fill for every kernel, then Moose can use JF and K to approximate this Jacobian vector product and solve your nonlinear system of equations, if everything else works out well, okay? To get to some amount of preconditioning, historically, the way that you would do that is by also overriding this function called compute QP Jacobian, where you actually input the derivative, or at least an approximation of the derivative of your the weak form of that term, okay? And so that's literally analytically doing the derivative of your weak form with respect to the unknown that you're solving for, okay? And there's two functions that go along with that, because we typically compute things like the block diagonals separately, because they're really important for preconditioning, and then often we'll do things like leave off the off diagonals. So there's compute QP Jacobian and compute QP off diag Jacobian. And in the off diag function, that's where you're going to take the derivative of your weak form with respect to other variables in the problem, all right? I know that this is very hand wavy right now. We can get into specifics later. For Newton's method, you really need to fill out these compute QP Jacobian and compute QP off diag Jacobian methods. They need to be exactly right for the most part in order for Newton to be able to solve and get to the right answer. Yeah, so you really need to do out those analytic derivatives and code them into your kernel object. However, the automatic differentiation system will help, because it will do this for you automatically. I think we have some slides on that here in a little bit. All right, so let's look at a summary. Finite element method is a way of approximating solutions to PDEs. Remember that those solutions are always functions. That's what we're actually solving for. And we're solving for those functions by finding coefficients to a discrete set of basis functions that whenever we add them all together, they give us back a function that satisfies our PDE and our boundary conditions, okay? Integrals can be computed numerically using quadrature, and we can use Newton's method to solve a system of nonlinear equations, and we need preconditioning to help us solve that system, the linear system inside of Newton's method, to help us avoid explicitly forming the Jacobian matrix. We can do that with JF and K, or we can do preconditioning with the full Jacobian matrix with Newton, okay? Let's see. I think I'll hand it over to Alex here to talk about automatic differentiation, but before I go, does anybody have any other questions right now? I know it's super fast. All right, let's hand it over. Alex, do you want me just to keep the slides going here and you can talk for a moment? Does that work?
Yeah, I would say that's ideal, because I don't actually have the website open right now.
Sure.
Yeah, so as Derek has referred to, we now have support for doing automatic calculation of derivatives and consequently Jacobians in Moose. In order to do that, we leverage a third-party package called Metaphysical, which is actually originally created by Roy Stogner, who is also an important libmesh developer. And then we've added things as we needed them in order to get things working as we'd like in Moose. So all of the tutorial code that we're going to show today uses the new automatic differentiation capability. So you're not going to see in the objects that we show, you're not going to see any compute QP Jacobian or any compute QP off diag Jacobian methods. All you're going to see is compute QP residual, because that's all that's needed with AD in order to generate the Jacobian, because the derivatives are computed automatically using operator overloading in metaphysical. If you are using AD with the solve type equals Newton, you can typically expect that your simulation will run about 1.5 times slower than it would if you provided an equivalent hand-coded Jacobian. But what we've typically found, and what I've found, a lot of our application developers have found, is that the amount of slowdown you experience when running your simulations with AD is vastly outweighed by the reduction in time taken to develop your applications, especially if you're coding up very nonlinear physics with complicated material properties. It's very easy to make mistakes when hand coding a Jacobian. Even when writing Jacobians for linear problems, it can be tricky. It's easy to make a sign error somewhere and mess up your Jacobian, and you might spend days trying to debug where you introduced that sign error or where you accidentally took a misstep in your analytic derivative calculation. So, as indicated by how we've moved our tutorial, we highly recommend that our users employ AD going forward.
Yeah, Alex, so I think I'll add a couple things there. One is that that performance envelope is always changing, right? We still have lots of technology left to implement. We're trying new things all the time to speed this up. And it's an important capability for us going forward. So there's still a lot of ideas on things we can do to speed this up. But the other thing is that I think overall it's fair to say that we found that even though AD itself, when compared to a perfectly hand-coded Jacobian, would be slower, compared to a real application where they're using probably a fairly imperfect Jacobian, your overall solve will be faster. And the reason why is that getting a perfect Jacobian is really difficult in a real application, something with contact, something with super nonlinear material properties, all these things, right? So a lot of applications will settle for an imperfect Jacobian and either use that for preconditioning for JF and K, or even use that for Newton's method and just deal with the fact that you don't get perfect convergence rates because you no longer have the correct Jacobian. And so compared to what goes on in normal large Moose applications, AD will typically be faster because it's forming the perfect Jacobian and you get a really great preconditioner out of it. So there are trade-offs here in all the directions, but definitely for getting started with Moose, AD is a really good idea because it reduces your burden in having to get up and running. There's no doubt about that.
Yeah, I would, and yeah, just reiterate on it again. I think in my experience, I'd much rather have a method that I can rely on to converge robustly every time and have it maybe be a little slower on a per iteration basis. If I know that the number of iterations may always be less than if I tried to code it by hand. Let's go to the next slide, Derek. Yeah, so we continue to support manual computation of Jacobians, and I think we always will, although sometimes we discuss this. As I said, all of our tutorial objects will be using AD, but there are plenty of examples of hand-coded Jacobians throughout the framework, throughout our modules, throughout our test objects. So you can just go sift through our code base and look at some of the traditional hand-coded kernel objects if you're still interested in pursuing a hand-coded Jacobian route. If you are doing hand-coded derivatives, there's some important identities that you should know. Derek spent quite a bit of time going through how we approximate the finite element solution. So if you're ever, calculating the derivative of the finite element approximation with respect to individual degrees of freedom, it's very nice and simple calculations. Just that you can be aware that the derivative of the solution with respect to any given degree of freedom is kind of the Kronecker delta function. So with partial UH with respect to partial UJ will always just be phi of J. And then same thing for the gradient partial of the gradient solution with respect to uj is just grad of phi of j. So the grad with respect to the associated shape function. Do you want to?
Usually we don't even. This is just there in case questions arise in our live.
I think it's worth pointing out for a second though. So this is just really quickly going from our strong form here to our weak form residual, right? We already did that for this equation, so that should be straightforward at this point. Note that like we skipped all the steps of actually discretizing everything. We're just going to consider that these are numerically calculated integrals and that these are discretized UHs and all that. We can just assume that that's what's happening here. But if you wanted to actually hand code that Jacobian, it would look like this. And the reason why is because of product rule. You have to deal with things like like the derivative of k with respect to unknowns, right? So if k is a function of temperature, you have to be able to take the derivative of it with respect to temperature, for instance. And so you end up with these product rule calculations. So you get kind of this explosion of terms. And this is only for one single scalar PDE, right? This situation gets much, much, much worse once you're coupling 5, 10 nonlinear PDEs and they're all interdependent on each other, and you're taking the derivatives with respect to all the unknowns in the problem. It can get to be very, very messy very quickly. So getting this computed automatically is pretty great, I gotta say. So that's really the takeaway from these final slides. You can go back and review them later if you want to learn a little bit more about manual Jacobian calculation, or we could have more discussion on it later, but I don't think it's worth going through at this point.
So I'm actually a PhD student at North Carolina State University, and but I also work at INL on the Moose team. In a role, I'm called a INL graduate fellow. So I was brought here to INL to work on implementing electromagnetics capability as a module in the Moose framework. And so that's what I've been doing here as part of my dissertation work. So moving on, let's go into step 2, where we're going to implement the Darcy pressure equation, including our permeability and our fluid viscosity. So in step 1, we used a built-in kernel object diffusion, or AD diffusion, in order to create an input file that contained the basic form of this equation. But now we want to make it a little bit more complicated. We want to be able to add some extra parameters and to just kind of build up this problem step by step. So as you've learned so far, a kernel is a Moose class, a C++ class, which represents the a volumetric integral in your weak form. In Moose, a kernel inherits from Moose object, and that's used under the hood by Moose to accumulate all of your residual terms in your PDE statements. So first, we'll start with what is a Moose object. So everything in Moose that's user-facing derives from Moose object. So this is kind of a backbone object in Moose. So it allows for common structure and then modularity in the framework. So if let's take a look at a basic source code outline. And so for this custom object that we've made, or we have custom object.h, we start with this pragma once line here. That's a compiler directive that keeps the compiler from including this header file more than once. In order to, we made this custom object and we based it on some base object.h. So we need to include the base object header file so that the custom object is aware of it. Since we have a class derivation list here, where we have our name of our class, custom object, and it inherits from this base object class in a public manner, which means that custom object can see all the public and protected members and methods of base object and can use them. So as far as public and protected methods here, there's also a third type, private methods, which only custom object could see. If we were to inherit from custom object and had some private methods that child class couldn't use them. But moving on, we have a static valid params method here that enables the creation of an input parameters object. So this is where we would implement what parameters our custom object would need in order to function. We have a constructor here, which takes in those parameters as an argument. And then we have for our protected methods, we have a virtual function. And a virtual function is a method or a virtual method is a method that is declared originally in the base object here. But we are overriding it so that custom object has a custom implementation that is specific to custom object. And then finally, we have a scale parameter. The scale parameter is, well, you'll see it's defined as a result of your input parameters. And you'll notice that it is a const, real type, and then a reference. It's good practice in general if you're defining a parameter and you don't intend to change it or write to it, const keeps you from modifying that after you've defined it. And this reference it means that scale is referring to a value or another variable that is at a particular location in memory. So the combination of const and reference is useful for the control system in Moose, which we'll go into in some advanced topics, I believe, later on. So that's our header file.
Hey, Casey, you mind
if we look at the custom object?
Something here real quick.
Yeah, go ahead.
I just wanted to point out that this basic template like this is what you're going to see over and over again. So for the rest of today and tomorrow, we're going to be looking at how to use each one of the systems, and they will all look exactly this way. So this same basic pattern of inherit from an object, override a virtual function, have parameters, is something you'll see again and again. So that's why it's really important to go through it like this. And once you learn this one template, everything in Moose will start to look similar on purpose. So that's all I wanted to add.
All right, thanks, Derek. So I've been told that I'm going to cut my video, so you won't see me anymore. I think there's been some stuttering in the connection. So I'm going to shut off my video and see if that helps with the audio. Okay. So now let's move on to the source file for custom object. So first, we want to include the header file associated with this object. So the header file that you just saw. The register Moose object method here is telling Moose that the name of this custom object, as well as the app that it's associated with. So if this is internal to the framework, you would see something like Moose app here. But if you had your own application, so in this case we have a Moose application called custom, the name here is custom app. So let's move on to the implementation of valid params. First of all, so we have our input parameters object params, and we're starting off by calling the valid params method for base object. So this initializes custom object with all of the valid params from base object that it should need as a child of base object. We have this params.addClassDescription method. This is for documentation purposes, and I'll go into this in a little bit with a little bit more detail soon. But this is just a class description, human readable class description of what this custom object is doing. And then we have, we want to add a parameter of real type called scale. Scale will actually be seen in the input file. So you can redefine this. Scale equals, another number, but we've defaulted it to 1. And then we have a documentation description of what the scaling factor is that's human readable. The default here allows you to exclude this from your input file, and it will default to 1. And I believe that Peacock will also show this default and this description if you're actually doing development in Peacock. If I'm mistaken, I think somebody can correct me. In our custom object, we're taking in the we have an argument here for the parameters that we've created, and then we're also initializing that with our base object into constructor with those same parameters. And then finally, we're actually defining that scale variable that we saw in the header file by getting the param that we added above, and we're calling that based on the name we gave it, which is scale here. So finally, we need to define that do something method. So we're saying that we can do any sort of calculation here, and the name you give your function, probably won't be do something, but it can be representative of some action that you need to perform in your custom object. So we can do some sort of import calculation here that needs a scale factor. In this case, we're keeping it pretty simple, and we're just going to return the scaling parameter or scaling factor that we added here. So this should give you a good idea of the basic structure, and I'll show you some more specific examples as we get going. But does anybody have any questions about this before I move on?
Casey, I'm gonna add just one thing to what you said with this valid params. So this function is how you add input file syntax, and you're going to see more of that. So like the scale parameter, that would be inside this block. You'll have the option to set scale equal to something. So that's kind of the left-hand side, and then that 1 would be the default for the right-hand side. You'll see more and more of this function throughout the next few days, but that's what it's all for. If you didn't say that, you might have said that, Casey. And if you did, I'm sorry for repeating.
Oh no, it's fine. I think I said it, but it's always useful to make it super clear for people. Apologize if the connection's a little bit stuttery. So I'm going to move on now to a discussion in general of input parameters. So as Andrew said, every Moose object has a set of custom parameters that's used to construct that object, and we create that object for each Moose object using the static valid params function. So here's the standard declaration, which you saw earlier. In specific, we have something here for convection, some convection object or convection kernel. And then inside of that definition, we have a initialization from kernel. So we start with the parent class and pull in its set of input parameters, standard input parameters. And so we want to add a couple more. So we've got 2 different add param functions here. One is add required param of a given type, and this is a parameter that is, as the name of it alludes to, it's required. So if you do not provide a value for velocity in your input file and try to run that input file, then you'll have an error on your console output. And so you won't be able to run that until you correct it. Meanwhile, a general add param is not required. So if you don't provide this coefficient here, then the input file is not going to complain. But you may want to define it, or you may not want to define it, depending on that. But you're not requiring a user provide that in the input file. Oh, one more thing. Most often for add params, if you're not requiring it, usually you do have some sort of default, and it could be something as simple as 1 or 0 in the case of a real type parameter. but usually you have some sort of default there, but that's not required. So we have inside of that input parameter object, we have a few more methods to talk about. That add class description method, that's just that human readable description that the documentation, you can generate documentation in Moose, and that's the method that that description is pulled from. And like I said before, we do have some optional parameter ability here. So if we had this add param for year, maybe we default that to 1980. So say that's the year I was born and my default year is 1980. Then if I were to call this or use this object, this comes from an input file. So we have an object named date, and we have our user objects block. This is a custom user object. And then we have on the second line, we have a human readable name that we've given it inside of our input file, so date underscore object. For type is a common parameter of all objects in Moose. That's where you put the name of the object that you're using here. So in this case, this custom class is called date, and then we provided an alternative year. So instead of 1980, we put down 1990. So the input file will read in 1990 for year, not the 1980 that you provided as default. But if you removed that line, then it would default to 1980. So required parameters, like I said, those must be supplied in the input file. Here we have that same object, and we're saying month equals 6. And now if we removed that line and tried to run this input file, we would get a Moose error, and it would tell you that you needed to provide that as a parameter. Another method to couple in variables is called the add coupled var method. And so you can add variable coupling to your objects doing this. In this case, we have two examples. We have add coupled var for temperature, and then we have an add coupled var for pressure. In the case of pressure, you can see that we provided a constant default here. So this capability is important. So in the cases when you're building an input file or a problem bit by bit. So say you are solving for temperature in a simple version of your input file, but you don't yet want to couple in pressure. So you can use that default in order to substitute in for the value couple variable for your pressure. And Moose will understand that and use 101.325 as your pressure variable in your residual calculations for this object. So in this example, we provided pressure, but if it's not provided, then it'll use that default, like I said. So within the input file, the parser that we use to parse in the input file and use it in Moose is pretty robust. So you could provide a variable name, a constant value, even a function. Now that function has to be very, very simple. So based on spatial coordinates or time. And you can also provide a postprocessor name. And we'll talk more about the latter two later. But this capability allows you to build your input file in chunks. So starting simple and getting more and more complicated as you add terms to your PDEs and add equations to your problem. So let me see. I don't see any hands raised. I thought I saw something. Okay, so further, we do have some range checking ability. So you can restrict your parameters to a range of values that's automatically checked. And so here we have a growth factor param. So we've add range check param called growth factor. We have a default of 2. And so if that we were saying here that growth factor needs to be greater than or equal to 1. So in our input file, if we try to set growth factor equal to 0, then we'll get an error associated with that mistake. So if you want to learn more about the syntax for this, it uses the same syntax as our function parser system, and there's a quick link to that that you can look at if you wanted to learn more. So as I said previously, that add class documentation line is for the purposes of generating good or human readable documentation about the source code. And so you can generate documentation from this function in a few different ways. If you wanted to use Peacock, then all of that documentation and class descriptions are displayed there. You can use the command line flag --dump or --dump with a search string, and then you can find information about documentation that way. If you wanted to see documentation related to what's specifically in a given input file, you could run the command line --show input, which generates a tree. So if you notice that our input files are in kind of a tree-based structure, and it'll generate a readable output on your console based on that input file structure. And we've also got a online link on the mooseframework.org website where you can look at a summary of syntax and some user-friendly documentation for every object that's currently in the core framework and the modules. So I'm just going to breeze over this really quickly, but you have multiple types that you can use to define your parameters. So reals, ints, even vectors. And then we've got a few more that are related to Moose, so like a point vector of spatial coordinates, or a real vector value, real tensor value, or various IDs. So you've got a lot of flexibility here in terms of the C++ types that you can support for your input parameters. So one thing to be aware of, I've mentioned a couple times about Peacock, that some of the strings can be, there are multiple string types that allow Peacock to be more context aware about what you're doing. So if you have a parameter that requires a string, say you're taking in a particular file name to do processing on it, or a function name, you can use these types, and you can treat them just like real or int in your add param function, but it'll make Peacock more aware of what you're doing and give you some context-specific help when you're using it. So you can see a complete list of this in the moosetypes.h header file inside the framework, and the location is at the bottom of this slide here. So we've got a new utility. So go ahead.
I'm gonna interrupt, and there's a question about quotation marks in input file.
Sure.
Do you want to comment on that, or do you want me to comment on it?
Well, so I know that quotation marks in the input file were pretty flexible there. I think you can use both quotations and single quotes, right?
Yeah, that's correct. But for some inputs like vectors and things like that, if you're inputting a vector of numbers, for example, you need to put those in some sort of quote, either single quote or double quote, and then they're space separated. Other than that, like if you're just inputting one number or a string, the quotes are optional. They're really only required for a vector, or maybe if your string has spaces, then you would have to put the quotes in.
Right. Then I think if you're trying to put in a tensor, then you would use the same quotations and with space separations for each row, but then you'd have a semicolon to denote when you're moving next row in your tensor. Is that right?
Yeah, I think that's correct.
Okay, thanks, Andrew. So Moose has a new utility called moosenum that works for integers and strings. So this is a way that we can signify multiple options in a given parameter. So in this example here, we have this moosenum called option enum, and we have first, second, and fourth as options. And a user can provide, because of how we set it up here, a user can provide first in both first as a name and then 1 as a number, or fourth or 4 as a number. So in this way, you can set up flexible parameter lists. We have a default here. The second argument supplies the default for this enum. So if you don't provide anything, or if you didn't provide anything where this enum was used, then it would default to second here. So when we use this in an actual object, like I said, we use it when we want a specific set of named options. So you could have proper error checking and parsing without having to actually put that code in. Moose will just handle it for you behind the scenes. So here we have Moose enum for component, and the components we have are spatial components. So we have X, Y, and Z. We've not supplied a default here, and so if you don't provide it, it won't default to anything in particular. So you'll have to. That's why we have it as an add required param here. You have to provide that, and then we have the name, the user readable name on the input file. The enum that it refers to goes in that second slot. You would normally put a default, and then we have a description of that input parameter. So in Peacock, you'll actually see this as a Dropbox. If you're working in a plain text editor and working on your input file, then you'll need to remember or look up what your components are. Though if you're using Atom, there are actually a few plugins that allow you to be able to use as the Moose executable to pull out the components that are, or the enum options that are available to you if you have it set up that way. So in the case of multiple ordered options, so for example, if my object here had something to do with meshing, for example, we might want to transform a mesh in multiple ways. So we might want to scale it or rotate it or translate it. So multi-Moose enum enables you to put in a long list of options. So if we want to perform 3 scales, 2 rotates, and 2 translates in that order, we can do that by using a multi-Moose enum in order to outline our possible options there. And so we'll see in the terms of transforms, we would be able to make a list, space-separated list of all of the options that we would want in this parameter. Okay. So let's move on to the kernel system in general. So as said, this computes a residual contribution from a volumetric term within your PDEs using the finite element method. And the kernel object represents one or more terms in the PDE, and you have to fill out the compute QP residual method in a kernel object to compute a residual at a particular quadrature point. So we have a few object members that are available to use. And one thing I want to make sure I underline here is you have U and grad U here at the top. And U is the value and gradient of the variable this kernel is operating on. U refers to variable equals in your input file. So if you say variable equals pressure, then U here refers to pressure. So it will always refer to the variable that you're operating on in that kernel. Now you can create names for coupled variables, and you can name those whatever you want, but you always know that U and grad U refer to the variable that you're operating on in your input file. We have your test functions here, your value underscore test and the gradient underscore grad underscore test of the test function. The value and gradient of your trial functions are underscore phi and underscore grad phi. Quadrature points for q underscore q point, underscore I and underscore j for your indices for your test and trial functions, and then underscore qp for the current quadrature point. And you'll see all this in action in a moment, but I just wanted to outline in one place that all of these object members are available to you by default, and many, many more, but these are the base ones that you're going to be using most often. So we have a few kernel base classes here. The top one, AD kernel, is the one that you'll be using most often, we'll be using most often in this tutorial. But we do have a couple optimized versions of this. So in your weak form, if you have a term computed in your PDE that's multiplied by the test function only, then you could use AD kernel value for that. So you wouldn't have to type in the test function. You would just type in the rest of that line. And this is a slightly more optimized version of AD kernel specific to those cases. Likewise, AD kernel grad has a slightly more optimized version specific to terms that have a grad test in the weak form term. So we'll be touching on this later during the hands-on portion, but for now, just know that they exist, and we'll be operating off of AD kernel. So when you can use this regardless of the residual term in your weak form. Sorry about that. So for a quick example, I'm going to go over a diffusion problem and show you what that code looks like in Moose. So if you recall a steady state diffusion problem, we have the divergence of the gradient of u equals 0, negative divergence of the gradient equals 0 in our domain. And if we translate that to the weak form, then we have this volume integral of grad test and grad u equals 0. And then if we actually translated that term into Moose code, we have addiffusion.h here, and you can find this in the framework. As you saw before, we have that same structure that we saw with custom object.h. In this case, we are inheriting from AD kernel grad, so you'll actually get to see the slightly optimized version of this. So we have we're overriding the pre-compute QP residual method instead of the compute QP residual method like we would if it was AD kernel by itself. In our source code, we have our parameters, and the only parameter that we have here, because we don't need to have any constants like constant of diffusivity or anything like that. We just have an add class description. So this is going to be the same as your standard diffusion in terms of the residual and Jacobian, but then the Jacobian itself is computed using AD. And so if we get down to where we implement the pre-compute QP residual, all we have to provide here, because we're using AD kernel grad, is that grad u at a particular quadrature point. So grad u bracket QP. We don't need to provide the grad test because it's already it'll be provided as Moose accumulates the residual for this term. Okay, I don't see any questions, so I'm going to go ahead and move on. So if we go back to the problem that we're trying to solve here, pressure kernel, we want to implement a new kernel object. We're going to call that Darcy pressure, and we're going to inherit from, in this case, there's a little typo here. We're going to inherit from AD kernel, and we're going to use the input parameters for specifying so that the user can specify permeability and viscosity. So for our Darcy pressure.h, we're including AD kernel so we can extend it here. And this little comment here isn't always required, but it's usually useful if you want to give an extra note about what your object does, and this is useful. You'll see these descriptions in our Moose Doxygen syntax pages, but this is just an extra little bit of documentation for you and Doxygen. If we go down to our protected class objects, then we need to override compute QP residual here. And because this is an AD object, we have a special type called AD real here. And then we want to have variables associated with their user provided permeability and viscosity. And so we have const real references to both permeability and viscosity here. And those will be defined in our Darcy pressure.c file. So we're registering this with our application. So our application in this tutorial is called Darcy Thermomech app. We're registering that as Darcy pressure. And for our valid parameters, we're initializing it with our AD kernel valid params as a baseline, and then we've added our class description here. To pull in our permeability and our viscosity from the input file, we're going to add permeability as a required parameter, so the user is going to have to determine this or to give this every time. And so the permeability here is going to be required by the input file, and we have a quick description of that. So it's going to be the permeability of the fluid. Notice in this documentation that you can use some LaTeX here. If you want to put in a little equation or some mathematical terms, you can do that. Moose will understand it when it's parsing the documentation for Peacock and the documentation for console output, or not console output, but for website output if you're trying to create a website. For your you have another parameter, viscosity. So this we're actually giving a default, so 7.98 times e to the -4, or times 10 to the -4, and we have another description for that. So the user won't have to provide that, but it can be overridden if the user decides to. So we're in our constructor, we're going to get params for permeability and viscosity. So we're defining our parameters, our class objects, permeability and viscosity. And then in the compute to be residual, we're going to define the residual statement. So in this case, our weak form is grad u times grad test times permeability divided by viscosity. And so you see that here. So let's build an input file with this object. And so if we wanted to create a mesh based on, and I believe this was in the last example, so we've got a mesh based on our paper. We've initialized a variable pressure that uses the default, which is going to be the Lagrange family with a first order. And we've got our custom object here. So we've got our kernel block. Go ahead.
Can you comment on that syntax for variables / pressure? Because that's not in the first input file, I don't believe so.
Oh, okay. Okay, sorry about that. So so this is a little bit of a shortcut or shorthand for defining a variable. So normally you'd have this block syntax, just like say kernels here, where you'd have an object with a name. So in this case, our variable is named pressure, and you have some parameters under that name that help define that object. And so for a variable, you would normally have family to designate the basis function family, an order to designate the basis function's order, and then other parameters based on what you need. You have the ability to set initial conditions. You have the ability to set what block in your mesh that the variable is active on. But if you just wanted to have the defaults for everything, then you have a couple options. One is this notation here, variables / pressure. Another is variables as a block, and then underneath is pressure without any parameters. So, and I think you might see that, or there's some other examples in the Moose framework where it shows you that other shorthand. But all this is saying is that we're using default values for pressure, and pressures are only variable in this case.
Casey, can I add a little bit to that too? I want to be clear about what the defaults are, right? The defaults for a variable are linear Lagrange shape functions. So we haven't shown yet how you can change shape function families, which we talked about earlier, but you do it there in the variables block when you define the variable. And this is something somewhat unique here, where the shape functions for a particular variable in a Moose-based application are not hard-coded. You can just change them right in your input file and use higher order shape functions or whatever it is that you want. So this will invoke linear Lagrange shape functions as it's written right here.
Thanks, Derek, for the clarification. So if we're continuing on, we have our Darcy pressure kernel. This is the only kernel that we're simulating here, since our right-hand side is 0. And it's associated with the variable that we created, pressure. And we're defining the permeability to reflect the permeability in the paper that we're trying to model. So for our boundary conditions here, we just have 2 Dirichlet boundary conditions. Again, our variable here is pressure, and we're telling Moose what boundary on our mesh that this is associated with. And I'll go into a little bit of discussion of mesh generation later on in this section, but for now, we'll have these user-readable boundaries for this case, so left and right. And we have values, pressure values for those. then I believe this will be gone into later, but we have our FE problem as Andrew described earlier, and then some basic execution and output options. So we'll go into outputs a little bit later, and also some PET-C options later on as well. So that's not really important right now, but just to give you an idea of a standard input file setup. So if you wanted to run this, you have a couple options. One, you could run it and visualize it with Peacock. So if you were to navigate to the directory that the tutorial directory that this input file is housed in, you would navigate there, make your object, or make your executable, your Moose application, and then find the input file and run that. So peacock-I and then step 2. Alternatively, you could run that via the command line. So you can make it, and you can make your application, go to the problems directory and run it. And so if you were to do that, then you can use whatever visualization you want. I tend to use ParaView, but Peacock is a really, really good platform for being able to do both your input file creation and your visualization. So if you wanted to visualize this within Peacock, you would call Peacock with the -R flag, and then add the Exodus output file that this input would generate after it's run. So after you make this, then you're probably going to want to make a test for it. So I'm going to share real quick, if I can actually get this to work correctly. I'm going to share this particular case. So I believe everybody can see that. And so I use Atom as my editor, so that's why everything looks the way it does. But if we want to take this input file, which I would just walk you through, and make a test for it, we would need to have a tests file. And in a little bit, I'll go over our testing system. But long story short, what we're doing here is we're comparing some known good output, Exodus output, and we're comparing that using exodiff with an output that is generated when we run our testing system. And so if we create this test spec file, and then when we run a test, let's go back to the terminal, and I can show you how to do that and run that input file. So does everybody see my terminal, or did I need to make it larger? I think I probably do. Everybody see that well?
Yeah, you're good.
Okay. So if we navigate to the Moose directory, and we'll go ahead into this step in the tutorial. We have our Darcy Presser application, and I've already built this, but I want to show you real quick how we would construct a test for this. Move this panel out of the way so I can actually see what we're doing. Okay, so we have two tests here. One is a simple diffusion test, and that's a default test for any new Moose object, any new Moose application. You'll see that a lot. But the test that we're wanting to look at now is here. So in this test directory, we have a test spec file. So that's called tests right here. I've highlighted that. And that's the spec file that I just showed you that has information about the test that we're running, what kind of test it is, what input file we need to use for it, as well as what output file that we want to reference against, an input file name that we want to reference the output file generated by our test. And so we have our darcypressure.i, which is the input file that I just showed you. We have a little bit of cruft here because I ran this earlier. But let's go ahead and remove that so you'll see what it would look like to you if you hadn't ran any tests on this yet. So we have our input file, a gold directory. So this is a known good output file that we've created previously, and we put in here to use as our gold standard for our test. And then if we wanted to actually run this test, we go back out to our Darcy Presser application directory. We would just run that test. So our machine was able to run that test and verify that nothing in our copy of Moose or in our system has changed, and that would change that test. So you want to get in the habit of, if you create a new input file, you want to make a test for it, so you can ensure that the functionality that you've added, in this case, we've added this new custom object with its permeability and viscosity parameters. We want to make sure that that can be verified in the future as being correct. So let's go back to the slides real quick. Okay. So in a little bit, we'll be doing the hands-on Laplace-Young example, but I'm not going to go into that right now. So I'm just going to skip over this slide, and Andrew will cover that when we get to that part of the presentation. So right now I'm going to talk about the system for defining our finite element mesh. And so for complicated meshes, as others have referred to, we usually use Qubit from Sandia National Lab, but other mesh generators work as long as they can output a file that libmesh reads. Sorry about that. And at a basic level, if you were to create a mesh from an outside program, then file mesh is a default in the mesh block. So in this case, you do not have to put in a type, but you do need to provide a file name, so sample.mesh in this case, and in this case, they're providing a dimension for that sample mesh, though I'm not necessarily sure that dimension is always necessary for a file mesh. I think it can be just read in with the file. Somebody correct me if that's wrong. But I do not believe you need to put in an explicit dimension if you have one outlined in the mesh file. But that is another parameter that's used in the mesh block. So you can go ahead.
So Casey, it depends on the file format.
Okay.
I don't know, for instance, for Gmesh, whether we can automatically determine the dimensionality or not. But
you can for Gmesh, because that's what I predominantly use.
Okay.
Maybe if you had a simplistic mesh, you might have to, but I've not run into that.
Okay, but yeah, usually we can determine it automatically, but the dimension option is still useful because sometimes you'll want to read a 2D mesh into a 3D space, for instance. So it's a useful thing to know about, but yeah, usually the dimension is determined by the mesh file.
Sure. So this is just a list of all of the extension or the mesh file types that we can read in. Mostly, in my experience, you see a lot of people using the .e or Exodus file format. And that's the same file format that we actually use for our outputs, but you can use it to hold a mesh. And .msh here for Gmesh, which is an open source generator that you can use. But as long as your mesh generator software can create a file with these extensions, Moose will generally be able to read it. If you wanted to generate your own, and you can use some built-in mesh generation systems, and at its most basic level, you can have something like this, where you have your mesh block of type generated mesh. So generated mesh is for implementing basic lines, basic rectangles, and basic rectangular prisms. And you can define your dimension, your mins and maxes in terms of X, Y, and Z, and your number of cells in those directions. In this case, we've got a -1 to 1 X and -1 to 1 Y direction size square with 4 cells total, or 2 in each direction. And we're specifically saying what element type our generated mesh is going to be. So by default, generated mesh is going to label the sides in a logical way. So for 1D, we have a left side and right side. For 2D, we have bottom, top, left, and right. And for 3D, we'll have bottom, top, left, right, front, and back. And those have human readable names in Moose, but they also have numbers. So here you have kind of the code for what the numbers translate to in terms of the human readable names. That's all done by default. So if you wanted to create very, very simple meshes, then you could use this syntax and create very simple lines, rectangles, and prisms. But in these slides, I don't think we have a coverage of the mesh generator system. That is a newer mesh generation system in Moose that allows you to make more complicated meshes in stages, and you can get pretty complicated with it. And we don't have any slides for that here. But Derek, do you want to elaborate on the mesh generation system or mesh generator system while we're here?
I think I mentioned enough about it earlier for right now, but you should know that this kind of shortcut syntax for the mesh block like this with generated mesh is more of an exception than what's recommended right now. We really are moving over to using the mesh generator system more and more instead of using this syntax. But this syntax will probably always continue to exist because it's just so simple and easy for these really simple meshes. So that's the only thing I'd like to point out there. So.
Right. Thanks. So I think we might have a hand raised.
Yeah, thanks.
Let's see, how do I get that to show up?
Here, I can do it for you, Casey.
Oh, thanks, man.
All right, Benjamin Ramirez, go ahead.
So I was wondering if your mesh is able to read point sets defined already on meshes that are already done. You know, like you do there in your slide. You define left, right, bottom, up. But let's say I already have my mesh and already defined those surfaces or sets.
Yeah. So if you pull in a mesh file that you've already made that has user-defined names for the side sets, then you will be able to use those in your Moose input file. So these names that I have on the screen here, those are only in the cases where you're generating a mesh inside of Moose, and Moose is going to try to help you out by renaming some side sets to make it easy. But when you import your own mesh, you need to know either the names that you've given your side sets or the ID number associated with those in your mesh file. So your mesh software should be able to tell you that, but you can name these whatever you want.
Yeah, so Casey, you're spot on there. The one thing I'd like to add there, though, is Benjamin, you mentioned point sets, and this is a good point to talk about side sets versus node sets. And in Moose, we highly prefer using side sets instead of node sets. That has to do with the way node sets handle adaptivity, which is to say not very well. With a side set, we can implicitly know that new nodes generated on a mesh boundary through mesh adaptivity should be part of the side set, where we don't actually know that with a node set. So in general, we highly recommend that you use side sets in your mesh generator whenever possible. If it's not possible to use side sets at all, and your mesh generator only has the ability to generate node sets or point sets, there is a capability in Moose for basically inferring side sets from a node set. So it will basically, you can turn it on in the input file, and then it will look at all the nodes on a side and determine that they're all in the same node set, and then generate a side set from that. So that is just kind of an important thing about Moose to know is prefer using side sets. Only use node sets when you really need to call out just a particular node or a couple of nodes that aren't really going to be like an actual surface. So. That's all I had.
All right, Casey, we got one more question from Will Gardner. I'm gonna unmute you now. Go ahead, Will.
Yeah. In your input files, there's frequently empty open close brackets. Can you just explain the significance of that?
So in an earlier iteration of our input file syntax, this was kind of organized in a file tree sort of manner. So for your block here, your mesh block, you have these open close brackets at the bottom, and what was the remind me what the format that we kind of based the input.
Don't worry about that, Casey. That's just the end of the block. It's just like your end statement.
So it's just the end of the block. I mean, if you were to put in, if I were to go back for a second, and
so you're indenting levels as you add the blocks with names in them, and that's your outdenting effectively.
Yep.
Yeah.
Okay.
Yeah, that's the ending of the block. Casey is right. It does somewhat come from, I mean, it's just the signifier for the ending of the block, but there did used to be something in between those brackets as well at the end, which was a ... And you might see that in some of the older Moose input files. And basically that's just kind of like, just like in a file directory, that's like returning the scope to the outer scope, basically.
Right.
But now we just use the open close brackets with nothing in between it to signify the end of the block.
Right.
Okay, that clarifies it. That's what I had seen previously with the ... and I was wondering why it was different. So it's just a different way of achieving the same effect.
A slightly simpler syntax. I think it cleans things up just a little bit.
Yeah.
Thank you. All right. So as we were talking about in those questions, we can assign human readable names to blocks and side sets and node sets throughout an input file. So if you have a parameter that requires a boundary, for example, then it will accept either those names that you've given or that Moose has given the object, or the corresponding number, an ID number for that boundary. And so you can, to ease maintenance, you can assign those names, those IDs, and make things a little bit easier to work with. Okay, so in this case, we're taking in a file called 3block.e, and Moose will read in this Exodus mesh file, and we have a few parameters that we can use to kind of help us out in terms of readability. So we know in this file that we have 3 block IDs, 1, 2, and 3. And so we have this block ID parameter, and by using block ID in conjunction with block name, we can change 1, 2, and 3 into correspondingly wood, steel, and copper. So later on in the input file, we have this material down here at the bottom, and we're applying that material to 3 blocks, wood, steel, and copper. We don't have to provide 1, 2, and 3 because Moose already knows that we've translated that ID and associated it with a human readable name. Same for the boundaries. 1 and 2 becomes left and right. And then in our boundary conditions, we can signify left and right boundaries. And so this is actually a good opportunity to look at some of that old syntax that we were just talking about. So in this case, we do have /left and /right with .. to close each of those blocks. But these aren't required anymore, but you will see them around just like you're seeing them now. So we have some things to talk about in terms of meshes and running them in parallel. So by default, when you're running in parallel, you will use what's known as a replicated mesh. So a complete copy of the mesh is made for each processor that you're running Moose on. But you can also distribute your mesh and break that up across the processors that you're working on. Especially if you're working on a large machine and your mesh is very, very large, you might want to split that up to read it in and operate on smaller chunks of it. So in order to do that, you need to use the split mesh flag to split the mesh into pieces before you actually run your full input file. I think you need to use, do you need to use split mesh in conjunction with mesh only in order to do this initially on a larger machine? Anybody who's used distributed before?
No, you don't. it should be mentioned actually that also distributed mesh isn't necessarily only accessed with split mesh either. You can run with distributed mesh even without pre-splitting. So there's three kind of levels. There's the default, which is replicated mesh. Like you said, the entire mesh exists within every MPI process. That's done for simplicity. But then once your mesh gets a little bit bigger, you can go to distributed mesh, which you just turn on using what you have there, parallel type equals distributed. And you can still continue to read that same single mesh file though, and what it'll do is it'll read that whole mesh file in on every MPI process, and then it will remove all the pieces of that mesh that are unnecessary for that MPI process. So that's a case where you can read your mesh in on you have enough memory to read the mesh in on every MPI process, the full mesh, but maybe your entire problem is using too much memory. So at the point where you actually go to solve the problem, you would run out of memory, right? And then the third is once you get to a mesh that is so large it could never be read in on any one of the MPI processes, that's where you use split mesh. And for that, you'll want to typically, the way that works is you typically need to either find a big memory machine, because you do have to read the full mesh in once, or you can run, if you have a cluster, you can run and just put like one MPI process on a few nodes so that one MPI process has access to the entire memory of the node. That way you can read that really huge mesh in and split it. It's important to note that this mesh splitting capability is parallel, just like everything else in Moose. And if you have a really big mesh and you need to do splits for like 20,000 or 50,000 processors or something like that, make sure you use like 1,000 processors or so to split your mesh so that it doesn't take forever. Also in those cases, it's really important to use your high-speed file system that your high-performance computing center might have for you. So make sure to check into those options. Just to give some rough numbers here on when to use these things, we are recommending at this point that meshes over about 1 million elements, you start looking at parallel type equals distributed. You could start even at 100,000 to 1 million, somewhere in there is when we recommend that you probably choose parallel type equals distributed. At 100 million or so is probably where you need to be using split mesh. But it could even be earlier than that. But by 1 billion, there's no capability for reading that in without doing a split mesh first. So
thanks, Derek.
I posted the documentation links on Slack and then also on the chat too for mesh splitting. There's actually some good documentation, so people want more.
So I think we have a quick question before moving on from Benjamin. Let me see. I can't unmute him. Andrew, do you know how to do that?
Yeah, it should be good now.
Hi. I was wondering if with this new feature, then you are able to read multi-section mesh files.
Can you describe
Yeah, like what you just said, Derek. Like when you have a huge element and you basically mesh each part of the this model, separately.
Okay.
So you have each part has its own mesh and its own ID for elements and stuff like that.
So split mesh is kind of slightly different than that. It's for breaking apart a single mesh, whether that mesh has many disconnected pieces in it or not. Is for breaking that apart into pieces that will be read in by multiple processors. So it's not breaking along like logical parts of the mesh or something like that, it's using a mesh partitioner to split the mesh up for optimal computation reasons. To read multiple parts of a mesh in from multiple meshes, you can do that in the mesh generator system. You can read multiple meshes and then you can combine them. You can heal them back together, like if they have a surface that needs to be, like if you're reading in two pieces of a mesh and they actually share a surface that you want to be continuous across there, you can heal them back together with that capability. So yeah, in the mesh generator system, you have complete flexibility. You can read as many meshes as you want and combine them however you want.
Great. Thanks, Ben. Thanks, Derek. So the final mesh configuration that we have is displaced mesh. So you can enable displacements of your mesh or changes in your mesh by providing a vector of displacement. And these displacements you'd be calculating as part of your input file. So these are variable names, and you can provide that as in a displacements parameter in your mesh block. And particular objects can enforce using the displaced mesh by setting a Boolean parameter, a true-false parameter called use_displaced_mesh. And so if you set that to true in your objects, then they'll use a displaced mesh if there is one. So I want to move on real quick to the output system. And so you've run your input file and you want to be able to see your information or your solution variables. So we have the output system for producing that data to either the screen or files. So we can make a very, very flexible output system for any input file that we want, because it's very modular and expandable overall. So you can make outputs for specific time or time step intervals. You can create outputs for custom subsets of variables that you have, and even various other file types. So there is some shortcut syntax here, just like a lot of other Moose blocks. So if you just had a simple outputs block with exodus equal true, then you would get an output file whose name by default is going to be the name of your input file, and appended an _out.e to that. And so alternatively, you could have your outputs block with a subblock named out and type exodus. So both of this syntax will generate the same thing with the same defaults. So we can also have the concept of common parameters. So in this case, we have one subblock called all of type exodus. And so, but we do have some common parameters here. So we want to output on every 10 intervals and have exodus equal true. So every block will have these two parameters, these two type parameters enabled. But then inside of these subblocks, we could have more specific parameters that override those common ones. So in this case, we have an exodus block, subblock that has an interval of only 1. So this is overriding the interval from the top level. These common parameters are most useful when you have multiple subblocks, but we're just showing that functionality in a simple way here. So we can also change those output names from their default using the file base parameter. So the default naming scheme, like I said, utilizes the input file name with a suffix. So the _out suffix is used for outputs created using the shortcut. So if you actually had a subblock though, that syntax would be _other instead of _out in this example case. Or if we wanted to make it even more custom, we have this other subblock called base of type exodus, and our exodus file is going to have a file base of out. So the output file that we would see here is just going to be out.e. So the use of file base anywhere in the outputs block is going to disable all default naming behavior. And so just be aware of that as you're using it. We've got various types of output formats. Most commonly, you will see the Exodus file format be used. So it's the most common one in Moose, and it's the most well supported. You also have another common one that you'll see is CSV files for your postprocessors. We'll go into postprocessors later, but you can generate simple comma-separated scalar value files for the outputs for those. Another notable one that I can't remember if we're going to be talking about that tomorrow. I think, yeah, we will. Is the checkpoint output. So this is an internal format that we use for restart and recovery, and we'll be going into restart and recovery tomorrow. So let's get back to our problem. So we want to take our Darcy pressure object that we made, and instead of the user passing in parameters, we want to have the material system supply those values. So we have the same equation as before. So we're just adding the ability to calculate the permeability and the viscosity via material. So we'll start by discussing the material system. So we can define material properties to be used by multiple systems and allow for variable coupling in those as well. So the material operates with a concept called producer and consumer. So material objects will produce properties that Moose objects will then consume. And that's a very important concept. So when we want to produce a property, first we need to declare it. So each property must be declared to be available. So we'll declare, we have a method called declare property where we provide the type and the name. Then in each custom material, we need to override a virtual function called compute QP properties. And then we override that in order to compute all of the properties that we've declared given a single quadrature point. In our objects, in our kernels, for example, if we want to consume a material property, then we're going to have to call a correct method. So we have two in this case. Oh, let me go back real quick. So this was missing here, but when we're producing properties, we have two options. We have a declare property and we have declare AD property. So the distinction is a material property that is a quote unquote regular property, and then a material property that is associated with the automatic differentiation system. Accordingly, we get methods for get material property and get AD material property. Note that you cannot mix these. So if you declare an AD material property, you need to get that property using get AD material property. In previous versions of Moose, you could mix and match these a little bit, but we've recently stopped that. And so you need to make sure you're consistent with your declare and your get methods. We evaluate material properties as they're needed at the quadrature points. So you might have multiple material objects that are defining the same property for different parts of the subdomain. So you might have a material, you might have a block 1 and a block 2, and you might have a material that calculates a property for block 1 and then a property for block 2 in completely different ways or with different values. Material properties can also be stateful, like other objects in Moose. So when you enable stateful material properties, you can access older calculated versions of that material property. So I think old is 1 time step back and older is 2 time steps back. And occasionally it can be useful to have old values of material properties, such as in solid mechanics, plasticity models. But and traditionally this is called a state variable, but in Moose they're called stateful material properties, just to get the naming convention correct. And then this will require more memory because you are needing to store more values of the material property over time. So we also have defaults here. So when you add a parameter that's a material property name, for ease of development, you can give it a default, whether that be a constant or something else. But you can give it a default for if you're building something and know you're going to need a property eventually, you can give it a default and run your input file, and then replace that with an actual name when you get that material developed. So we can actually output material properties by enabling an outputs parameter. So in this case, we have two materials, output test materials in block 1 and block 2. And we want to output these into our output file so we can take a look at them. And in this case, we use that outputs parameter, and we set that equal to the name of the subblock in our outputs block. So in this case, we're still using that shorthand, but remember that shorthand is equivalent to having a subblock whose name is Exodus. So in each of our materials, we can use outputs equal Exodus, and these material properties will be output into the Exodus file that we're enabling at the bottom of the file. And so we can support real values, material properties, vector valued material properties, as well as tensor valued material properties for output with naming conventions as follows. So for real, if our variable name was called, material property name was called prop, then we would output a variable in our output file called prop, or prop1, prop2, prop3 for vectors, or prop1, 1, 1, 2, and etc. for a tensor valued material property. Okay, so another thing that we'll need will be a function system. So we'll need to use the function system for this, a system for defining analytic expressions based on spatial location and time at its most basic. You can create custom functions that take in other variables and other parameters that can be used to calculate a function value, but at its most basic level, it's going to rely on space and time. So we can create a custom object by inheriting from the function class and then overriding the virtual method value, and optionally other methods as well, but mainly value. And then you can access functions in Moose objects by calling get function, and the name that you provide will match what you've given in the input file. So as you look through Moose objects in the core framework, you'll find quite a few objects that utilize functions. And these 4 are listed here as an example, and they're not the only ones. But each of these objects has a function parameter that you can set in the input file, and that controls when a function object or which function object in the input file is going to be used for those. So if you wanted to create simple functions, you can actually create parse functions to allow them to be defined by strings in your input file. So here we have sine and cosine defined by the parse function system using the value equals parameter. In this case, we're not using quotations around these, but you can. But the parser will understand what you're doing for simple functions if you don't include them. So you can use sine x or cosine x, and the parse function system will understand. As you can see below, we have a third parse function where we set the value as some string s over c. We're telling Moose that we have variables in this parse function s and c, and correspondingly what their values are going to be. So you can have parse functions that are defined based on other parse functions or other custom functions. And you can use scalar variables for these as well, couple those in, or even post-processor values with your function definition. It just depends on what your needs are. So in an object, whenever you're adding those in, you can provide a default for ease of development, or you haven't made a function yet, a custom function yet, but you will, and so you're kind of putting in a placeholder for it. So in this case, the first case here, we have a function name for pressure grad, and in the meantime, we're going to give it a default of 0.5. So if we don't put that in the input file, then at least we'll know that there's going to be a default of 0.5 there. If we have another default, say for power history, then we actually have a full parse function based on time and the y position variable. And so we can use a parse function to default for a function name, just like we can use a constant. Let's see. Okay. So now that we've covered these systems, let's jump into. I thought I saw a question, but I don't. Let's jump into continuing this development. So we want to create a material that represents the packed column in our original problem. And so we need to produce 2 material properties, permeability and viscosity, and for consumption by our Darcy pressure object. So we're going to compute that with a single material object. And in the reference article, permeability varies with the size of the steel spheres. So we're going to use 2 points as from our reference article, and then linearly interpolate those and define the property that way. And so you'll get to see some utilities and tools that are available inside of Moose to do things like linear interpolation. So in our header file, it's the same structure you've seen before. We're overriding here compute QP properties. So this is where we're going to actually compute the values of the properties that we've declared. We have a function, a constant reference to a function called radius or underscore radius, and this is where we're going to define the radius of the spheres in the column using this. We have an input viscosity, and that input viscosity variable is going to, that's where we're going to store the value of the viscosity that we've taken in from the input file. We've got a linear interpolation object that's going to be the linear interpolation of the two reference points that were given, and we're going to use that to compute permeability based on the radius. We've got our 2 material properties that we're going to compute. So we've got permeability and viscosity here, and these are both AD material properties, and so their type is a templated type AD material property real for both. Notice here that we don't have const references because these will need to be modified and rewritten as they're needed. So we don't have, these aren't const, unlike some of our other variables. So in the source code file, the standard structure we've seen before, here we're adding a parameter called function name, that's our radius. We're defaulting that to be a constant of 1, but this can be added, changed by the user in the input file. And then we have a real parameter for our viscosity for a default of 7.98 times e to the -4. This is the same default that we were using in the previous step. It's just now we're calculating that inside of we're defining that inside of the material. We move on to the constructor. We're going to be actually defining the values of radius and input viscosity. We're going to get that function that we've defined as radius, and we're going to get the parameter, the real constant parameter for viscosity, and define radius and input viscosity respectively. Then we'll use declare AD property to declare permeability and viscosity, and then we'll be defining those in our compute QP properties method. So in the constructors, we're going to actually do this linear interpolation. So from the table, we have 2 reference points. So for sphere sizes 1 and 3, we have particular permeabilities. And we're going to use the set data method inside of linear interpolation. So in order to use this method, we're going to have to include, let me go back one step, I forgot to mention this. In our packed column.h, we're going to need to include linear interpolation.h. So this is a helper class that allows us to do that linear interpolation. And so we're going to use that here. So our permeability interpolation, linear interpolation object, we're going to call the set data method inside of linear interpolation and give it the sphere sizes and corresponding permeability, and it'll perform that linear interpolation for us. So now we'll get to the point where we can actually compute these properties. So for a given value of our radius, so we'll call the radius function and request a value of that function at a given time, so underscore t, at a given quadrature point. So we have underscore q underscore point at a particular qp, and that'll give us the x, y, and z coordinate vector that we need to calculate the value of radius. Now we have a range check here, so we have a Moose assert, and I believe this will be discussed in more detail later. But this is checking to make sure that the value given by radius, in the case of a user-provided function, is within the applicable range of our linear interpolation. So if it's outside of 1 and 3, then you'll get an error or a warning on your console output letting you know that you might need to adjust this. So finally, we're defining our viscosity. So our viscosity is based on the input viscosity variable that we got from our input file, and our permeability is based on that interpolation. So we're sampling that interpolation at a particular radius defined by value. So now that we've created this material, go ahead.
Can I jump in for a second?
Sure, man.
You can go back. So something really important in Moose World is that material properties live on quadrature points, and they're evaluated on the fly on quadrature points. So this method, compute QP properties, is called with each value of underscore QP, and it sets these values on the fly as needed by other kernels. So it's just important to note that in Moose World, like I said, that properties live on these quadrature points, and that's why this is compute QP properties. That's all I have to say.
Oh, thanks, man. Okay, so now we've created this packed column material, and we're going to be using the existing kernel uses input parameters that the user provides. So now we need to update that to consume the material properties that our new material is producing. So we have our new Darcy pressure.h, and the modifications that we've made are here at the bottom. So we have these AD material property protected members for permeability and viscosity, and we're going to define these based on the material properties that we're consuming from packed column. Otherwise, this kernel remains the same as what you saw before. These are the only changes that we need to make. Moving on to the .c file, now that we've noticed that we've removed the parameters associated with permeability and viscosity because we're now getting those from material. So permeability and viscosity, we need to call the get AD material property for each of those. And for the name here, we need to make sure that this name is consistent with the name that we've given those properties in packed column. Then we compute the QP residual as before, except now permeability and viscosity, we need to know what those are at particular quadrature points. So we have permeability and viscosity at a particular QP. And so we've modified our input file a little bit.
Can I say something about that last slide real quick?
Sure.
So one important thing, we haven't talked too much about AD yet, but I think this is a good point to point out that since this is using AD, just to clear something up, getting an automatically differentiated material property will mean that even if that material property is nonlinear and depends on other variables in the system, or maybe even depends on this variable, the Jacobian of this weak form here, where you have permeability over viscosity times grad test times grad U, will be computed correctly. So the interesting part here is that this kernel doesn't know how permeability or viscosity are actually computed. And they might just be constant values, or they might be nonlinear values made up of multiple variables, etc. But no matter how they're computed, the derivative of this kernel will be computed correctly. So that's a really great thing about AD.
Thanks, Derek. So we do have a question I'm seeing. Unmute that. So Srinath, I think I'm sorry if I mispronounced your name, but I think you're online.
Yeah, hi. So just related to Derek's comment here regarding AD, so the inheritance is continued through every declared AD object for a given kernel. Would that be a correct assumption?
So you're asking if you're inheriting from an AD object, that your custom object is also AD compatible? Is that what you're asking?
No, my question is, will the derivatives be inherited? So I have an AD object that is then related to another AD object that's then put into a kernel. So will the chain rule be properly applied to every AD object that the kernel needs is the question.
It will, yeah. If you let's say pull in multiple variable values in the material system and you combine them into one number. And then you take that and combine it with something else, and maybe another variable value, and store that as another material property. By the time it gets all the way out here to the kernel, and the Jacobian is computed using the AD system, it will take all of that into account. The complete chain rule all the way back to the variable values that you started with is maintained.
Perfect. Thanks.
Thank you. So now that we've made these changes, the modifications that we need to make to the input file are adding our new material. And so because we have defaults for viscosity and defaults for our permeability, or we're linearly interpolating that based on reference points, we don't have any parameters here. We just have materials block with a sub block of column with a type of packed column. Then we can modify our Darcy pressure kernel block a little bit to remove our permeability that we defined earlier. So then we just have our block with type Darcy pressure and variable pressure. So again, we can run and visualize this with Peacock, and I'm actually going to run this in just a second and show you what the output's going to be. But I'll do that on the command line. And so here's the command line version of running that. And so if we run this, let's go to step 3. We can go into the problems directory and run the step3.i.
You got to switch to your Windows.
Oh, yeah, sorry about that. Thanks.
So for those following along, this is about time we get a break, but I think Casey can show us how to run this for a few minutes, and then we'll take a break, and we might review this a little bit before we show off the hands-on.
Yeah, there's a little bit more about the testing system, I think, if we wanted to touch on that before we move to the hands-on. If you still wanted to do that.
We can decide after the break. Maybe we can do that in the morning too. We'll see.
Sure, that sounds good. I want to give as much time as possible for the hands-on, I know. So let's go ahead and run this. So we have our Darcy thermomech. In this case, I'm running in devel mode, but you'll see in the slide that they're using OPT mode. I'm using the -i flag to signify that we're providing an input file. And then I'm going to be running step3.i. And so in this case, our output on the console is going to give us some information regarding our Moose versioning, libmesh versions, and PETC and SlipC versions, timestamps for when we actually ran the file, and just some information about how we're running this in parallel. In this case, I'm running it in serial. What information about our mesh, information about our variables, our nonlinear system, and some execution information about whether doing steady or transient, and some solver modes. And then we'll have our linear and nonlinear residuals as it converges. So that's what we'd see on our console. If we were to run this, let me switch back to the slides. If we were to run this and then take the output and show that in Peacock, you would get this result. So if we were to move and change this and say, okay, we're going to vary the sphere size from 1 to 3 along the length of the pipe, then we could modify that pretty easily by changing the radius function. So instead of having a default size for a radius, we can put in a parsed function here that changes the radius as we move along the pipe. And then if we run that file, then we'll get a slightly different result in terms of our pressure. But you see on the bottom that our permeability is now changing as we move along in the X direction in our 1D pipe.
With that, I'm going to put up a problem statement. And so just ignore the tutorial for now. Just take a break from it. You know, we've dumped a lot of information on you, so we're going to go back and just kind of start fresh. And what we're going to do is go through the process that a lot of you have probably already done by following the getting started instructions and create a moose-based application. And within that moose-based application, we're going to solve what's known as the Laplace-Young equation. And it's this little equation here where you got a diffusion term with a coefficient k. So we've basically already seen how to do this. And then another source term with kappa u, where u is our unknown. And this k function is defined, this coefficient k is defined as 1 over the square root of 1 plus the gradient of u squared. So this makes this a nonlinear equation. And then we have just a constant value for kappa and a constant value for sigma, which is our Neumann boundary condition, which is defined here. So we're going to code this up. And this is also a point where we actually show you how to do the weak form on the board. And unfortunately, I don't have fancy writing utensils like Derek does, so I can't really do the weak form. So I'm just going to give that as homework, is take this equation and give the weak form, and hopefully it ends up being the same as the equations as that I type in. And when I make a typo, I'm hoping somebody will jump in and correct me, because all this math stuff makes me nervous, especially doing it in front of people. So I'm going to switch over to my terminal. I'm going to try to just switch windows on the fly here, hopefully give you a little better resolution. So for those watching, is that big enough on the screen?
That's great, Andrew.
Okay. I'm also drinking coffee. keep me on my toes here. All right, so we've already shown you quite a bit on the command line, and I'm going to keep showing you and try to talk to things as we go. And so hopefully a lot of you have got Moose compiled. I think lots of you have. We've got helping a lot of people on the mailing list or on the Slack to get people set up. So, and anyway, you have Moose installed. You do a list, you see this in Moose, and most of you have probably gone into the test directory and run a compile command. I'm going to do J4 because it's already compiled, but you can use whatever kind of horsepower you have. And then I'm going to run the test, and then I get to show off my really nice workstation here that has 56 compute threads. So, and it's going to go through all the tests, and this is what we do in a day-to-day developing of Moose. We run the tests, and you should see lots of OKs. You probably see some skips. That's okay, because we have, certain tests only work on, certain configurations. Maybe only work on Linux or with a debug build and any number of other minor configurations. So on my really nice workstation, this doesn't take much more than a minute. But when you're sitting here waiting for it and people are listening to you, it seems like forever. So this is the testing system, which Casey alluded to, that we're going to talk a little bit more about tomorrow morning as well. After we review, we'll show an example of why this testing system is so important. And it's something we take very serious. And we put a lot of development in this, mainly Jason Miller, which a lot of you are interacting with on Slack and on email. So anyway, this is just an indicator that Moose is working well. Hopefully that's about done. I can always quit it. I like to finish. I want to show off how many tests we have. But I'm impatient, so I'm going to quit. So that's great. It's all well and good. So now we need to make a Moose-based application. And in our getting starting instructions on our website, this is what we explain to do. And what you do is you run this little application, a little script called Stork. And Stork is good at delivering baby animals. That's what the Stork does. So to do that, you go outside of Moose. So I'm in my projects directory. Generally, a lot of the Moose developers have a directory called projects where we keep all of our Moose stuff in. If I do ls, you see all the random Moose stuff I have in here, and non-Moose stuff even. So anyway, so to run Stork, so I'm going to run the command that's in scripts Stork. So what this is doing, if you're not familiar with Unix, is the / means this current directory, and then go into Moose, go into scripts, and then run stork.sh, and then give it a name. So this is where you get to name your application. This is a super fun part. You can call it frog or dung beetle. I'm going to get all hip with the current news and call it murder hornet. Apparently in the western United States, we get these crazy big hornets that arrived from Asia, and they're going to take over the world. So we're going to make an app for that. And hopefully that worked. So now I just created Murder Hornet, and this, when you run the script, it gives you all kinds of information. It's kind of big on the screen here, but basically what we've done is initialized a Git repository with your animal called Murder Hornet in this case. So we're going to cd into Murder Hornet, and notice that the directory name is all lowercase with underscores. That's just what we like to do in Moose. So we don't like capital letters and stuff like that in directories. So we change your camel case, capital M, capital H, in put underscore in between the letters and lowercase everything. But it's important to note that the case that I use for Murder Hornet will be important later on. You'll see where you know, you got to kind of keep track of the case that you use when you created your applications. So at this point, if you do a list, you'll see something kind of similar to Moose, but this is a basic Moose-based application. What you start with, got a make file, readme files, a documentation directory, include and source, that's where we're going to be working, even a scripts directory, run test application, and even a tests folder. So at this point, we can actually compile Murder Hornet. Shouldn't take very long. There's not much to compile, just a main file and a few other little things. And now we have a working application. So you have your Moose-based application is already done, and it's working. And we even give you a simple test. And that test is this simple diffusion, which we've basically been beating to death over this first day. And that's basically the same thing we did in step 1. And we ship the test with your application. And like I said, we'll talk more about testing tomorrow. So at this point, we're ready to add our own kernels. So I'm going to switch back to the presentation real quick. So we got this equation. This is the strong form that we need to implement. Pretend I did the weak form and have it here for you. Basically, we're going to create two kernels, one for this diffusion guy and one for this source term. And the boundary condition is already covered because we know that's a Neumann boundary condition that exists in Moose. So that's all we're going to do is go create these two kernels. Switch back to my terminal here. So at this point, we're going to do something that often I think sometimes confuses people, but hopefully I can explain it and it won't be confusing. So when you create a Moose-based application, your application has all the power of Moose and all the power of modules. So you should never have to copy something from Moose or from the modules into your application to use it. So that it's already compiled in. I guess the modules you have to go turn on. We can talk about that more later, and we will talk about that more later. But so if you see, for example, if you're want to do heat conduction, you want to use a kernel that's in the heat conduction module. You don't have to copy it into your application or nothing. It's already there. It's already compiled and linked in. But what I'm going to do here is I'm going to copy something into my application, but I'm going to copy it for the sense of as a starting point for writing code. And we mentioned already that you're going to kind of see this basic structure of Moose code over and over and over again. And so rather than type a whole class from scratch, we're going to pick something that's close to what we need to do and work from that to create our custom class. So the first part I'm going to do is that diffusion term. So it's the diffusion with this nonlinear coefficient. So if you hear small children screaming in the background, that's just my kids getting amped up at the end of the day. Told them to be quiet, but I don't think they care. So where do we start? We're in our application, and at this point we usually talk a little bit about C++, but this is a little bit condensed. So in general, we store all of our C++ files in two directories: include and source. The include is going to have our headers. Source is going to have the C file, the implementation. And there's reasons for doing that, but we don't need to talk about those right now. So the first step is we need to create a place to store these objects we're about to make. So I'm going to go mkdir, that means make directory, and source kernels. So inside of Moose, in the framework, in the modules, we generally create folders inside the source and include for each object that we're interested in. So this is going to go create a kernels folder inside that source. So you can do ls source after I do this, and you see I got kernels, and you can look, there's nothing in that directory at this point, which is what I expect. And then like I mentioned, I'm going to just grab a file from Moose for a starting point. So framework, source, kernels. And I know this is a diffusion equation, so I'm gonna well, probably AD diffusion is a good place to start. And we're gonna do all this with AD. But I'm gonna rename this, oops. Let's see if I spelled that right, diffusion.c. So I'm taking a file from Moose, copying it over to my application, and renaming it to Laplace-Young diffusion. And again, this is just a template. If we want to use AD diffusion, we can go use it. There's no reason to copy it. This just gives us a starting point. All right, and then we can go back up, check out kernels, and yes, now we have Laplace-Young diffusion. That's wonderful. We need to do the same for the include. I'll create the kernels directory just to keep things organized. It's optional, but we highly recommend it so you know which is which. And then copy from the projects, use framework, include kernels, AD diffusion.
Andrew.
Yeah.
You already have a great question. Someone asked you why you didn't name that AD Laplace-Young diffusion.
Because I'm lazy. You know, that's up to you. It's a really good question. So you can name it AD Laplace-Young diffusion. The reason maybe you're not is you plan to use AD for everything in your application, so you don't need to, put that prefix. But if you plan to have AD and non-AD versions of your tools, maybe you want to have that AD prefix. It's really up to you. For my own applications that I work on, I'm working on putting everything in AD, and I'm not going to have it because I'm just going to use AD. So it's a personal preference. Thanks. So now we got this, we get these two files, a header and a source file. Now we actually need to go edit them, right? Because right now they're direct copy and they're completely worthless for our own application. So I'm going to use Emacs to edit these because that's what I use. You can use Atom, gedit, WordPad if you want to. I don't know why you want to do that, or any other text editing tool that you're comfortable with. Feel free to do that. And I'm going to use Emacs, and I have a little shortcut set up for my Emacs. So I'm just going to use that, and it's going to fire it up for me. And then I got to switch to it, and then make it bigger. And hopefully you guys can see that. How's that look? Is that okay?
Yep, that's good too.
All right. And so we're going to go modify this file. Like I said, this is a template. And Casey already introduced this template essentially with that custom object. Everything in Moose really looks almost the same. And so the first thing I'm going to do is well, I don't care about Moose's header here because I'm going to use my own license, and I'm just going to delete that for now. If you want to use the same license, you might take that header and make it suit your needs. But for now, we're just cluttering up things. And then pragma once. This is where I'd ask a question to the audience what pragma once means, but that's a little difficult. All this does is it's a C++ compiler flag essentially that tells the compiler only include this once. If somebody's already included Laplace-Young diffusion.h, don't do it again. It keeps duplicate symbols and things like that at bay. And so we're gonna inherit from AD kernel grad. And so if you remember, we've already talked about AD kernel in the actual tutorial, and then Casey also mentioned this AD kernel grad and AD kernel value. These are just optimized kernels to do your physics. And if you want to get into more details, we can maybe talk about the optimization that's actually done, but it just kind of saves some calculations inside one of the loops when we're assembling everything. But we know that this term, I would switch to it, but it's kind of a pain in the butt, but that diffusion term, when you do the weak form, it's only multiplied by the gradient of the test function. So we're going to use that AD kernel grad because that's what it's set up to do. So first thing we need to do then is we need to change the name of this file, or change the name of the class in this file. So likely you have some sort of find and replace mechanism in your text editor. I just did what's called replace string in Emacs. I probably can't see it down here at the bottom, it's pretty tiny. But I'm going to replace AD diffusion with Laplace Young diffusion. And it's going to do that in a few places. So that looks great. Let's see. I think that's all I need to do in this function. So now I got my new class, Laplace Young diffusion, which is really good. Anybody have questions and stuff yet? I'll probably take some nice awkward pauses just to keep, let people to catch up and see what we're doing. Okay, so now let's go to the source file and actually do the implementation. I have a little nifty thing that switches between the files pretty quickly. So whatever text editor you're using might be able to set up to do that same thing. Hopefully that's big enough. And again, we're gonna remove the header. And the first thing we're gonna do is do that same replace. And we'll have to do a few other things. And so we're going to switch AD diffusion to Laplace Young diffusion. It happens in 3 or 4 places in here. Save that, and then, so when you're in your implementation, your C file, you always want to include the header for the class that you're working on. So Laplace Young diffusion.h, that's correct. And we're going to see this over and over. And Casey talked about this registration. We don't want to register this class with Moose. We want to register it with murder horn it. And this is where the capitalization is important. So you want to use whatever capitalization you used when you created your app, you want to use it there, and then you add capital A PP for app. Hopefully that makes sense. It's just a convention we selected. There's no really important rhyme or reason to it. And then we want to update some documentation here. This isn't right. So diffusion term for Laplace Young equation. Something simple, meaningful. And then what else do we got to do? We just got to update this. So what do we need to put in here? This is where I also would love that you don't have people give me some feedback, but again, that's difficult to do. So I'm just going to type. So AD real K. So this is actually going to compute that coefficient K. We're just going to compute it right here on the fly. And the reason is that it's a function of grad U, if you recall. So 1, put a decimal point there to make sure that we know that this is a double precision number. That's really optional. Oh, great, my phone's ringing right in my. I still have a phone that rings, believe it or not. So 1 plus, what is it? Grad underscore U P. I think that's that K equation. And then what do we do here? Pretty simple. K times grad U. And why don't we have the test function? Well, this is one of the benefits to using that optimized class. So anything in the AD kernel grad, that pre-compute QP residual is automatically multiplied by the gradient of the test function. So we really only need to return whatever is going to be multiplied by that gradient of the test function. In this case, it's just K times grad U. And so in Moose land, is the thing that's getting computed is K times grad U times grad test. And one thing that's really important to point out is the type that I used for this K. So this is an AD kernel. And so this K, I want to compute as an AD real, so that the derivatives of doing whatever calculations happening in this function flow through this coefficient K. So this can be arbitrarily complex, and all the derivatives will do the right thing coming from those grad u's.
Well, Andrew, I just pulled my webcam on and everything to tell you the same exact thing. You just had the same question, you beat me to it, and now I'm standing here with my webcam on, so I had to say something.
Okay, that's good. I like it. Thanks.
So distinguishing between the 80 types basically, and also asking, you know, why not 80 float and 80 double? Well, because those don't exist.
Yeah, you can try that. It won't work. So the name real comes. It's just a type def in C++ land to double from libmesh. But theoretically, you could go recompile libmesh to use something else for real, and everything would still work. I don't know if anybody's ever done that, but that's what it's there for. Okay, so I think that is it. I'm gonna try to compile this, I guess, and see what happens. So let me switch. Oh, a good homework assignment actually is to go do the same thing, but just don't use AD and compute. Go ahead and compute the Jacobian terms and stuff for it if you really want to understand this. Computing the Jacobian for this 1 over square root term is really not the most fun thing to do. Oh, I just cheated. I use MK. That's my little script that automatically figures out my make command. I'm not used to do. Oh, look at that! I did it. So I ran, make -j something, and it's gonna go compile. And usually I make a typo. I practiced this last night, so that's probably why I didn't so far. So that's one kernel done. And let me pull back up the presentation again real quick. So that was the weak form of this guy. And now we need to do the source term, which is even easier. So let's just go do that real quick. And again, we're gonna start with something. And this time we're just gonna start with what we already did. So copy Laplace-Young diffusion to Laplace-Young source. And let's go to our again, we're just doing this for template, just a nice starting point, and we're gonna open this in Emacs. And I'll make it bigger again. And I gotta turn that back on. Hopefully this is working for you guys watching me do this. So what are we gonna, I like to do the header first. Let's go to the header. So again, it's all the same kind of stuff, but let's see, what am I gonna do? So what's different in the source term is now, if you recall that equation, this piece, when you do the weak form, is actually going to be just multiplied by the test function, not the gradient of the test function. So we're going to use the other little optimized thing. So I'm going to go do this by hand here rather than find and replace just for funds. More likely to make a mistake, but that's okay. Where else do we got to change it? There. I think that's the 2 spots. So we're just inheriting from that other kind of optimized thing. And when you do that, you actually this pre-compute QP residual only returns an AD real because that's how it operates. And if you go check the math, you got gradient versus non-gradient terms, and so the return type differs because of that. So hopefully that makes sense to everything. Oh, there's one thing I missed. Hopefully somebody caught it and was like, oh, you gotta switch this. So we already did Laplace-Young diffusion. We need to make this now source to match up. And one thing I'll point out to as I'm sitting here doing this is, you notice that I have a file name called Laplace-Young source.h and .c, and inside that we have a class called Laplace-Young source. That's purely convention for Moose, is to have a kind of one file per class, and the file name to be named the same as the class name. It really just makes it easy to find what you're looking for, and just consistency helps. But it's certainly not a requirement from C++ or anything like that. So let's jump over to the C file now, and we're gonna make all these same changes. Like I said, I'm gonna do this by hand just to slow myself down, and you guys can watch my Emacs skills, which are not the best. See where else we got to change it here. And you can see why find and replace becomes important for some of this stuff. And this is important here. So you always want to call the valid params function from your base class. And in this case, the base class is AD kernel value. So make sure we make that change. And we're just going to change this to source term for the Laplace-Young equation. And look at all these diffusions. I should have done find and replace in this one instead. Source. But again, the core structure is all the same, right? The constructors all look the same with input parameters. Pass that input parameters down to the base class, and then you override something. And in this case, we're overriding pre-compute QP residual. And in this case, we're just going to return kappa times underscore u at the quadrature point. So what's underscore kappa? People are like, well, you didn't define underscore kappa. You can't just type it in. You're right. So if I go compile this, maybe I'll do that. So like I was just typing, I wasn't paying attention. Let's see what happens. Switch to my terminal. Give it some. Whoops. Got to go back down to your base application. That's where the make file is. So you run make from there. And if it compiles, I'll be amazed. No. As you accept undeclared identifier kappa, and that's where you're like, oh yeah, I forgot to do that. So jump back to Emacs, and let's do kappa. So what we're gonna do for kappa is we're gonna add a parameter in our input file. So params, add param. This is just a real number, kappa, and I believe the slide had the default to says that kappa is 1. So we're just gonna set the default to 1. And this is the coefficient to the Laplace-Young source term, and add that. So that's the parameter, but now we need a place in the actual C file to store that parameter. So switch back to the header, and we're going to add a local member variable, constant real reference kappa. So this is going to be a place for us to store that value coming from the input file. And there's all kinds of questions that will probably pop up here, and I'll see if I can head off a few of them. First of all, why a real, not an AD real? Well, there's no derivative information coming from the input file, so there's no point of populating an AD real here because there's no derivative calculations that can be done just from a scalar value coming from the input file. If this was a material property, that would be a different story. And that's kind of another homework assignment, is maybe change this kappa to be a material property based on what you learned from Casey. The other thing is, why is this a constant reference? So this const means you can't change it. This is a reference in C++. If you don't know what that means, it's probably worthwhile to go look it up. The reason being that this underscore kappa is going to reference a value from the input file that's stored somewhere else in Moose. And if you do it as a constant reference, it opens up some flexibility to leverage some of the other systems, namely the control system, which we don't really talk about in this tutorial. But in order to use that system, you want your parameters to be references. So just a little information. That's why we do it. So if you can do it, it's probably worthwhile. And then so that's a reference. You always have to initialize a reference. They can't be uninitialized, and you do that in an initialization list. And so in C++, that's kind of some special syntax you do in the constructor here. So I'm going to just realign things so they make viewing a little bit easier. So in your initialization list, you can do a few different things. First, you call your constructor of your base class, and then you actually do your initializations, and you're going to do underscore kappa, give param, give it the type, and give it the name. So that's what you need to do to get kappa into your system from an input file. And you can see these functions, these add param and get param functions, they're what's called template functions in C++, and this just gives you the type. So real, it can be vectors of reals and tensors and ints and all sorts of things. And all this is doing is in your input file, you're going to have a block, and you're going to define a Laplacian kernel. And if you don't give a value of kappa, this get param is going to just pull this default one. But if you do give a value of kappa, it's going to pull the value that you provided in that input file. So at this point, I think we should be able to compile this guy. So let's go do that by switching back to the terminal and run make again. All right, so that compiled. So Murder Hornet now has 2 new kernels. They don't do it, we haven't used them yet, but they're there compiled, ready for somebody to use. So I think I'll pause for just a minute and have a drink. And if people have questions at this point, please speak up, and then we'll, if not, we'll move on to the actual make an input file and go use these things that we just created. Any questions out there, Logan? Nothing, nobody cares. They're all left. It's okay.
Yeah, we're just having a design discussion now on AD Real, so you're in a good place.
Oh, good. I like it. You guys completely digress.
You had a question on where are the files that you created already?
Okay, we can show you. So in my application, I do a listing. This, yeah, you guys are seeing this. Is that big enough, Logan?
Yeah, that looks great.
Okay. And excuse me, you have these 2 directories, include and source. So let's just go into include. So in the include directory, we have this kernels directory. Excuse me, I'm regurgitating some coffee for you guys. Inside this kernels directory is something that we created, this kernels directory, and that's where we put the file. So let's go in there. And there's Laplace Young diffusion.h and Laplace Young source.h. And you can go back to the source in the kernels directory there that we created and do a listing. And you see Laplace Young.c and Laplace Young source diffusion.c and source.c. These other little squiggle 1 thing, that's my editor. Those are some temporary files that's saving automatically for you, so you don't actually accidentally like delete something. So you probably won't have those, or you might have something else if you, depending on what editor you're using. So I guess we have some time. I think this is going pretty quick since nobody's actually complaining about anything because everybody's sleeping or who knows what. Or maybe it's just brilliant and everybody gets it. But we can talk a little bit about Git. So I mentioned when we created Murder Hornet that we kind of initialized a Git repository. And if you don't know what Git is, it's a version control system that most software projects this day use. It's what we use in Moose, and we use GitHub, which is just a kind of an online management tool for the for the Git system. And if you run Git status, you can see what we have here. So all the things in green are what when I ran Stork, it created all these files and set up things for us, and it actually staged them for saving. So I actually probably should have done this. There's a good chance that this is going to not work for some crazy reason. So I'm going to commit these. That means, you know, save them off. So everything that's green, I'm going to put into a commit and just give it a message created Murder Hornet. Yeah, and for, I don't know what the heck this is. My Git on my machine is broken. So just pretend that worked, and now you would have a commit. I have no idea what this is. If anybody can fix this, that'd be great.
Did you initialize?
We do that automatically in Stork. They can try again. Sure? Reinitialize Git repository.
Yeah, it's initialized automatically, or it should be.
Yeah.
Because if you scroll up, you had something similar when you first storked.
Oh, really?
Yeah.
Yeah.
I don't know if that history still exists.
Yeah.
There might be something wrong.
I'm sorry about this. Everybody who's watching me suffer through this. My computer is just not. Something's wrong with it. So maybe I can try to fix that, and we can go back over that tomorrow.
It looks like there might be something wrong with your hooks.
Yeah, could be. Oh yeah, that's what it is. I know. I have like this crazy hooks thing set up. Okay, so just pretend that works. I saved all those changes. It's brilliant. Get status. I'll just talk my way through it. You wouldn't see any of this green stuff. Those would all be saved away in some Git world, and you could upload those to your remote repositories and all the things. And then at this point, I would probably git add include, git add source, and then you would get status, and you would see that now you have, I'll highlight them here, you have include kernels and source as well. Where's,
hey, Andrew.
Yeah.
You have a question again about possibly looking at the kernels again. Do you want to maybe go to the summary and show the summary again and name what kernels you created, and then go look at the source again really quick for people?
Yeah, what do you mean by the summary? What are you talking about?
The problem statement, just
the problem statement.
the equations.
Sure. Okay. So yeah, just to review for those.
Yes,
let's go back
about quickness with the kernels, so it might be nice to go refresh them really quickly.
So we're created two kernels, one for this term and one for this term. And the way Moose works is we automatically, as we'll see as we create the input file, each kernel you had, we just add them. I think there was already a question on Slack earlier about this. They're just additive in nature. So those are the two things we computed. This one on the left-hand side here is Laplace-Young diffusion, and then this is Laplace-Young source. So we can go look at those again. So here's Laplace-Young source. We have an H file, and I'll just go through it again since we have a little bit of time, I think. Pragma once, this is so you don't over-include things. You can always include the base class you're inheriting from. This is C++ magic. And this is the class I'm creating, Laplace-Young source. It's inheriting from 80 kernel value. You can go back in the slides and you can take a look at what that does, but it's this optimized kernel for when you only multiply by the test function. And then you have your valid params. This is how we're going to get parameters into this thing. Standard constructor for all Moose objects that we have. This is the one thing that we have to do in this class, pre-compute QP residual, and then a little member variable here for storing that input parameter. And then in your source file, again, this is all going to be boilerplate. You're going to get really sick of seeing this stuff over the next day. Include the header we just looked at, register that object with your application, so murder hornet app, and then Laplace-Young source. This is the class we just created or are creating. Input parameters, this is your valid params function. Always start off by getting the valid params from your parent. And then I'm adding a simple one parameter here. So we're gonna have kappa equals to something in our input file for this object. And then added a little class description. And then the actual constructor, they all look the same. So you always have one input to your constructor for the parameters. You pass that down into the base class constructor. And then in this case, we need to initialize this reference to underscore kappa with whatever parameter is coming from the parameter system in your input file. And then the weak form is kappa times u. This is what we just saw in the slides. And then automatically, because this is that optimized thing, we're going to be multiplied by the test function. Okay, and then let's go look at the diffusion. It's going to look really similar, and like I said, it's all very repeated. So again, pragma once at the header file, and then include your base class. In this case, it's the grad version, so that optimized kernel for when you're multiplying by the gradient of the test function. This is the thing we're creating, Laplace-Young diffusion, inheriting from 80 kernel grad. Declare our valid params function that we're going to fill out. Declare the input or the constructor, which all looks the same, the class with input parameters, constant reference. And then this class is pretty simple. We're going to do one thing in this pre-compute QP residual. This is that optimized bit as well. So whatever returns from this is automatically multiplied by the gradient of the test function. So if you go over to the implementation and the source file, again, you always start by including the header that whatever class you're working on, register it to your application, so murder hornet app, class here that you're creating, and then you have your valid params. In this case, we don't need any valid params, but we do want to make sure we have this function that adds some documentation. So again, always get the valid params from your parent, add a class description, and then make sure you return the parameters back so other objects can inherit from that. I guess that's something maybe to point out is we do all this, and so that somebody else maybe in your research group or some other research group like, wow, that Laplace-Young diffusion kernel is really close. Maybe I just need to add a new multiplier to it or something. So they can actually inherit from your code and specialize it even further, and hopefully not repeat physics if we can be avoided. So the constructor, again, is all the same. The class that you're defining here, input parameters gets passed in, and then you call your base class constructor and make sure you pass in parameters to it. And then the one thing we actually need to code up is basically these two lines in that optimized compute QP residual bit. Define that coefficient k. So this k is a function of u, in particular the function of the gradient of u. And we're doing AD, so we pass in the proper derivative information along the line for having grad u in it. It's 1 over the square root of 1 plus grad u squared, which we got here. And then we return k times grad u, and then automatically, because this is again that optimized thing, the grad test is getting multiplied by this behind the scenes for us. So hopefully that clears out that question. And now let's switch back, and I think it's about time we'll do the input file now, and then we'll have plenty of time for questions. Yeah.
Okay. Well, people are asking about how to enable like module objects in their applications, but we can do that after you do the input file.
Yeah, that sounds fine. Remind me if I forget. Okay, what do I got to do? I got to go to terminal real quick. So anyway, sorry about my broken get. I should have kind of knew that was going to happen, but forgot to fix it. We'll have some time to go back to that potentially.
Yeah, I also told someone that we could put these on GitHub at some point and post the link in Slack. You can figure that out offline and post it later this evening.
I can certainly do that. And one thing to look forward to as well is, like I already mentioned, Chris Wong is really working hard on making a lot of this stuff way more documented on our website. And I think we'll probably even include a complete repo of our tutorial, and maybe we'll even add this one as well. So a lot of this stuff is hopefully going to get much clearer over the next week or month or so. Anyway, so we need to create an input file. We need to test this. We want to run this problem. We got all these cool new physics. Let's go run it. And we're going to do that in a problems directory. This is just another convention that we have in Moose. Is like when you have kind of complete input files that for solving a problem, we put those in problems directories. Certainly don't have to do that. So go create a directory, and let's go in there. And I'm going to use my Emacs thing to go create a file. So let's just call it Laplace-Young.I. And I'm just going to write this input file from scratch. If I can make well, that's going to be huge. A little bigger, I think. Okay. Oh, I got to switch to that. So I opened my Emacs, and now I got an empty file in there, so there's nothing in it right now. And then we're going to start typing. So if you don't have an editor and you're glutton for punishment, please learn Emacs. It's brilliant and maddening all at the same time. Many of the Moose developers use Emacs, and then I guess probably a better choice if you're just starting off might be Atom. It's a really good editor. A lot of people are using that, and we have all kinds of nice tools and stuff that use Atom to help do autocomplete for your input file. So once in a while, I actually fire up Atom to make an input file, but I'm not going to do that here. Maybe Logan or somebody could post a link to the Atom instructions to Slack or something as I talk.
Yeah, I will. And I'll use Atom some tomorrow as well.
Yeah, you'll see it. Casey already showed it, but for those interested, it's well worth your while. All right, so we've already seen a lot of this stuff. It's a lot of boilerplate. So this might be a little huge. Take it down a notch. So we need a mesh block. So I'm going to create the mesh block, and then we're going to fill in some stuff. I think there was a question about indentation somewhere along the line. It's merely convention. You can actually do all this stuff on one line, even if you wanted to. But for readability, we tend to indent with a few spaces. So we're going to use that generated mesh again. I think that's spelled right. And nx is the number of elements in the x direction. We're going to set that to 20. And y equals 20. So this, we're just going to do a rectangle domain, a unit. I think it's a unit square that this thing's defined on. So 0 to 1. And let's put, we've got to put dim in this. I like to put that up here at the top. I don't know why, it's just me. So a really simple generated mesh in 2 dimensions, 20 elements in each direction. No big deal. And okay, what do we need? We got to solve for something. So variables, u. This is a handy little syntax for if you're creating a variable and just doing one variable. It's really quick to do something like this. This is exactly equivalent to doing this. So it's up to you how you want to type, create a variable, and if you're not setting any parameters in it, it can be nice to do a little shorter syntax or not. And the next block we need, let's do our kernels. This is what we're actually here to use. So we have a diffusion kernel equals Laplace Young diffusion. So this is what the name that you put here on the right side of type, that's the actual C++ name of your class, and it's the name that actually is registered in that register moose object macro that we have in the source file. And the only thing that we need to do is define the variable that this thing operates on. And this is actually coming from those base classes. So it's really important that you include the valid params from the base class, because that variable input parameter shows up and we leverage that. So this Laplace-Young diffusion equation is going to operate on the variable u. And now we're going to add another kernel. So these are just added together. This is how Moose works. We're going to add the source term, type equals Laplace-Young source, variable equals u, same equation, and then let's set kappa on 0.9, even though the problem said 1. Let's change it just because why not? Life on the edge here in Idaho. Okay, so what else do we need? Somebody said boundary conditions, I'm sure of it. So let's add some boundary conditions, and we're going to do all of them because they're all the same. And we're doing AD, so we're going to use AD Neumann. Did I spell that right? Is there 2 N's? 2 N's or 1? Anybody? Anybody? Didn't hear that.
There are 2 N's.
Okay. I was right the first time. Should have went with what they got. So this is that Neumann boundary condition. I guess I'll switch back to the slides real quick for this. So this is that flux term. So when Derek talked about the finite element section quite a bit, this flux term shows up in your weak form by doing the divergence theory of this diffusion term. And we're just setting the flux equal to some constant value, sigma, and it's 0.2 in this case. Really common thing to do. And we'll talk about it more and more, I think, as we go on. Where am I at? Emacs. That's what we're doing here. And then one thing you got to do in boundary conditions is define which boundary or boundaries it's using. And this is, I named this block all for a reason, because this is on all boundaries. And in 2D, we got left, right, top, bottom. And then executioner. This is a step. There's no time kernel in this. We'll talk about time kernels later. So type equals steady, so let's go with that. And then outputs simple x this equals true. And that's it. I think that's everything. We'll see what happens when we run this. So at that point, we'll go back to the terminal. And do an ls, and you can see that we got laplaceyoung.i. That's the file I just created, and we got my temporary file from my Emacs editor. And to run it, we already compiled Laplace-Young or Murder Hornet application. So we're gonna run Murder Hornet opt-i plus young.i. And it's gonna go and solve, and it's gonna take a whole bunch of iterations, and it looks like we did something. Let's see, I'm gonna fire this up in Peacock. So I have the location, the Peacock executable, it's in my path environment, so I can just type Peacock. And I'm actually just gonna do a shortcut and just look at the output. So give it a -r that stands for results, and laplaceyoung_out.e, that's the default output file name, and let's fire that up. And you're not going to see it fire up because the way we're sharing. But if I switch to Peacock, maybe it won't be so small this time. I can't switch to Peacock. It won't let me. That's sad. It's not
Andrew,
giving
don't forget to tell them if they haven't added Peacock to their path, don't forget to use the command when you don't have it added, just so they know where Peacock is actually located.
Yeah, I did that earlier today, but I can do that again.
Oh, I'm sorry. I didn't realize you did.
That's cool. I don't mind. So apparently Peacock cannot be shown with GoToWebinar as a window. So I'm actually going to try pair view real quick. Well, I guess let me do what Casey suggested. So I did this earlier today, but let's do it again. So projects, Moose, Python, Peacock. That's the thing I'm actually running, but I have that Python Peacock path kind of set in my bash profile, so I can just type the final executable Peacock, and we'll do it again, plus young out.e. So that's all that I was doing. So that's fired up. But that doesn't work. So I have pair view set up with a little command line thing as well. So it's called pview pv. See if that works. See if I can. Yeah, pair view seems to be okay. So apparently Peacock is not webinar acceptable. Is that showing up, everybody? Seen that? Looks like it.
Yeah.
Yes, sir.
Pair view is a wonderful tool. Has a lot of capability, and a lot of people use it. And it's kind of more intended for. So Peacock's meant to give you a quick view of your results and your input file, where pair view may be a little bit more professional to make higher quality plots and things like that. The downfall is that you have to click a lot to actually see something. I gotta rescale it. Is that the right one? Get to the time. I gotta rescale again. And that looks like what I'd expect. So that's kind of a solution to Laplace-Young. And what's this equation will give you it's used for like modeling the meniscus of a fluid and things like that. And so homework is to play around with the terms a bit. So yeah, is there any questions with that? I'll give it a few minutes. I actually think I made
some parallel runs, Andrew.
Yeah, I can do some parallel. I also think I made a mistake.
Doesn't look right.
No, when I was typing it up, I was realizing something. I want to see if anybody else picks it up. Even the brilliant Moose developers, see what you say. So if I pull the slides back up here, that's not the slides. That is. So what might be different about what I programmed versus what's on the slide here? Anybody catch it? No absolute value, someone said on chat. That kind of happens naturally with the squaring, but that's a good response. So there's another thing. It's in the first bit. This guy. Nobody? Really? Man, people are sleeping. Let's go back and look. What am I missing here?
Are you looking at all the questions, Andrew? In
What?
we say sigma, negative, negative sign.
Okay, yeah, okay. I can't see all the questions. There's too many. This
That's
go
okay.
to webinar puts about 50 windows on top of stuff. So
There were a few about the negative sign.
yeah, so we're gonna put the negative sign in. I'm pretty sure that's what a lot of people probably
And
notice.
all over Slack as well.
Yeah, okay. So people are paying attention. That's good. So let's go back to the terminal then and let's see what looks different. Oh gosh. I'm just gonna kill my pair view. No, I'm not. So we gotta recompile. So that gives you the change that we just made.
And while that's all running, you have someone asking about, you know, the number of linear and nonlinear iterations. If you want to make a quick comment on the fact that we're not preconditioning anything.
Yeah, I was gonna let Alex do that in a second. I figured that question would come up. Let's take a look at pair view. So we got, this is going from 8.6 to the blue to 9.6. So let's see what changes here if we rerun this. It looks about the same, and let's see what happens. Oh man, how do you, there's a way in this to like reload it. Where's that at?
You right click on the Exodus file.
This guy?
out.e and just reload.
Oh, there it is, reload files.
In the Pipeline browser.
Reload existing files? What does that mean? Let's do that
I can't tell exactly what you're doing, but you right click on the +young out.e in the Pipeline browser and click reload.
So it did change the solution.
There you go.
Which is good, I think.
Yeah, now it's going the other direction.
Yeah. Is that right or not? I don't know. Whoever's an expert in the Laplace-Young equation might know. Regardless, I think we're definitely getting close to something.
You're applying
so Alex,
negative diffusion now. So.
What's that?
That's definitely the wrong sign on the kernel now.
Why is that? Oh, because
when you integrate by parts, you lose the sign.
You're right. See, I had it right the first time.
Yeah.
Thanks. Okay, that's a good homework assignment. So I did have it right the first time, and I shouldn't have second guessed myself when I did this last night. If you go back to the slides Derek covered this morning, when you integrate by parts, you switch the sign. So the positive was right, which when you go look at the picture, you might expect. So I mentioned that this is good for a meniscus problem. You'd expect that the corners would go up, right? And now the corners are going down, so we actually made it wrong. And I think some of you already pointed that out in the Slack too, that I was just making it worse, which is fine. I do that all the time. So I'm gonna go switch that back. Alex, you want to talk about the conversions here? Because you have some experience in that department.
Did you have, what's your solve type?
Let me, I can show you. So let me show you the terminal.
Just put a nice view in, and then we have all details so we can explain that.
Hold on. Let me switch this really quick and then go back to the input file. So there's my input file. I didn't do anything.
Okay, so you use PGF and K by default.
Yep.
So, I mean, one thing I would say is that we should encourage people using AD not to use PGF and K.
So you want to do that. Solve type equals Newton?
Yep.
So let's see what that does for us. Oh, let me recompile. Since I fixed it now after my mistake. So that mistake was good. Just make sure you do your weak form on a piece of paper and write it down in front of you. Don't do the math in your head, at least if you're me. It's a bad idea.
So could you put us in this view so we can know all detail if we audience want to understand?
Yeah, I can. Let me, what is it, dash SNES
_view.
So this is a one way to get PETSI options into your executables. You just put them on the command line, and we'll probably see more of this as we go along. But this is going to give us some more information.
As well.
So the iterations look about the same to me. What was this telling us, Fande?
How many unknowns are in your problem?
1.
I mean, DOFs.
I got it's 20 by 20, so 400, 441.
Yes. So we're using preconditional ILU. So I mean, we can talk about this thing a lot, but we probably don't have time. So if you switch to different solver, you will get a different converge, possibly better.
Let's do that real quick. Let's put it in the input file here. We got a few.
I mean, you can try different one.
So what is it?
Right now it's default.
PETSI. Is it PETSI options I name, right?
That's correct.
And what should I do?
You could try Boomer AMG.
PC tab.
Oh, yeah, is it
dash?
PC. Is it like this?
Underscore.
Yeah. Boomer AMG, right?
No. You know, PC option underscore value.
Oh, yeah. Sorry.
You don't need to say anything about the Boomer MG, just say hyper and enough. Default is Boomer MG. Just a hyper. H.
That one?
HYPRE.
Yeah.
YPRE, yeah. Okay.
Default is AMG, so it's fine.
So you guys should explain what this is doing, because this is the algebraic multigrid stuff while I go run this.
And do you want to talk about multigrid?
Oh, it's beautiful. Beautiful convergence.
I can't see it.
I guess, I mean, that's,
yeah.
So this is really good. This is some of the stuff we would usually kind of cover in the preconditioning section that we did this morning, but we're trying to condense things a little bit. And those settings that we just saw with the PC type hyper is kind of where you want to start, and it's really works really well for diffusion heavy problems, if I recall correctly.
Yeah, work for elliptic problem.
So, Alex, do you want to re-repeat why we switched to Newton instead for AD? That was one of the questions that's in there.
Sure. So go ahead, Alex.
So there is so most of the computational cost. So there is some overhead to do AD calculations even when just computing residuals. So you want to try, if you're already forming a perfect Jacobian, you don't need to approximate it using finite differences. But if you were to go ahead and use PGFNK, you'd be incurring some additional AD cost for every linear residual evaluation. So in general, if you're using AD, you will find that PGFNK would run quite a bit slower than Newton.
So just to kind of say it in more layman's terms too, for if you're using PGFNK on this, and each of these linear iterations, you're going to be going through and computing that residual over and over and over to estimate what the Jacobian is. But when you switch to Newton, you can do that Jacobian calculation up front and then use it for each of these linear iterations. So you don't have to do those residual calculations on each of these linear lines. So that's where the speed up comes from. I hope I said that right.
Yeah, if you're doing PGFNK, you have a residual callback for every linear evaluation. But if you're doing Newton, you don't have any callbacks during the linear solve.
So you can get a lot there. So I guess one thing that Logan asked me to do is do some MPI, which we'll do. We got 7 minutes here, so let's do that. So to run with MPI, it's pretty easy. Spell it right. That's first. Let's do 4, and we're still running Murder Hornet. I Laplace Young. And this is a pretty small problem already. It's only 400 some odd degrees of freedom. So I'm going to actually make the problem a little bit bigger. Mesh, uniform, refine. We haven't talked about refinement yet, and we haven't talked about the syntax I'm showing you, so I'm going to do that briefly now. So the input file syntax that we've been showing you so far, we've kind of already talked about being folder structure. Let me pull it back up here quick. So what I'm doing is on the command line, I'm saying this mesh block, and I'm giving it a slash uniform refine. That's the same as typing in uniform refine equals 2 here. So all I'm doing is from the command line setting that parameter. And so this is that kind of nested folder structure that our input file follows and allows us to do this kind of stuff. So let's go back to the terminal. So I'm going to run this problem with 4 MPI and uniform refine twice. And it's still pretty quick. So, but you can see now we have, where's the elements has gone up to 6,400, and we got 65, 61 degrees of freedom. So quite a bit larger problem. What we're doing with MPI, and you can play around with this. You can go nuts on it. And this is going probably a little too much. Generally speaking, we recommend that this number, where is it? This number, the local degrees of freedom is what, on the order of 10,000 to 20,000? Is that what we recommend?
Correct.
Yeah.
For good scaling, yeah.
So if you go smaller than that, you tend to do too much parallel communication. It can actually make your application slower. So you want to keep 10,000 or 20,000 in this local degrees of freedom number.
One thing that we should say is it probably doesn't make it slower, but if you're trying to make a beautiful scalability graph, then you should keep it 10, 20,000.
Sure. Okay. What else do we mention about this?
Oh, I guess I should qualify that. Typically, like if you're using some types of preconditioners, the more you spread out the problem, actually the worse the linear convergence can be.
Yeah. We don't have time to demonstrate that. It's something else we usually do as well, and when we do these in 3 days, but unfortunately we can't do that right now. So we got like 4 minutes left. I think we'll call it. All right, people are still trickling in, but we're gonna get going here. So what I'm gonna do for the first few minutes this morning is just do a quick review of what we've done, and then I'm gonna talk a little bit about testing for just probably 5 or 10 minutes, and then we'll continue on with the tutorial from step 4 with Logan. So if you recall, we were going through this Darcy problem where we see. Actually, I should probably go back to the equations. We're going to solve these 2 equations. We have a pressure term that comes from conservation of mass and Darcy's equation, and then we have a conservation of energy equation that gives us the heat equation for temperature, and it has a convection portion of it that couples to this equation via pressure and the velocity relationship. So just to go through the summary of the steps. Step 1, we showed you a real simple, just pure diffusion problem. We call it simple diffusion in the Moose. It's what we did in the hands-on section as well, just by putting coefficients in this type of term. And then in step 2, we did that coefficient step. We added the permeability over viscosity coefficient, and we just did it with input file syntax. And then in step 3, we introduced the material property system to make that a little bit more generic. And so that's where I'm going to jump to, and we're going to go back over that code. So now that you watched me write some code, and some of you have also written the code following this Laplace-Young hands-on example, hopefully this pressure kernel will make a little more sense. Material system. So yeah, this is the code. So if you remember, we created a material object, and the material object's responsible for producing or computing properties. And in this case, there's 2 properties that we need to produce. It's the permeability and viscosity. And we're going to do that a little more complicated than just setting a constant value to make it a little more interesting. And we're also leveraging the function system and some linear interpolation. But if it's go to the top, this is a standard header file for Moose. This is what you see all over the place. You got the pragma once, so you don't include too many times. Include the base class, which you're inheriting from. And then we also have this little include for linear interpolation. This is just a utility for us to convert the radius, which you'll see. Then we create our new material class, packed column. You inherit from the base class publicly material. You got your valid params function here so you can pull in input file syntax or create input file syntax. Standard constructor, where it's got a constant input parameters object. And then you got this one virtual function that you must override, and that's for material objects. You have to compute QP properties. So again, we're producing properties at a quadrature point. That's the job of the material. And then we got some things in here to help us do that job. So a function object to get the radius, and the viscosity that's supplied via the input file, we're going to store it. The linear interpolation object, and then finally the two properties that we're going to produce, and make sure that these are references. So we go to the source code. Always start by including your base class. This thing is using a function object, so you got to include that guy as well. Register Moose object, Darcy Thermomech. This would be your application. So yesterday for Laplace Young, it was Murder Hornet. And then the class name that you're actually registering. Then your valid params. And this one's pretty straightforward. We have one function called radius and give it a default value of 1. So if you don't use radius on the left-hand side, radius equal to something, it's just going to use 1. Or you can supply it a different value or a function name or a parse function, which we all talked about a little bit yesterday. And then another parameter, viscosity, and we're going to give that a default. So in the constructor, there's an initialization list. After calling the base class constructor, you're going to initialize the radius with get function. And so that's going to go grab the function, whether it's a constant function or some other function that you passed in the input file, it's going to grab it. And then you're going to get the input viscosity and then the permeability, or then declare AD properties for the permeability and viscosity. And take note of these names. These are important. They're not arbitrary at this point. These are the names of the material properties that other objects are going to have to use to get access to them. Then in the actual body of the constructor, we do that little set up the linear interpolation object with the 2 permeabilities and 2 different packed sphere sizes. And that comes out of the paper. And then we'll actually do the computation, which is pretty simple. So first of all, let's go get the radius, and at this time and at this location. So underscore Q point indexed with the QP index is going to give us a point in XYZ space, and underscore T is the time. All the functions in Moose take these 2 things as arguments. And then we do this Moose assert. This is to make sure that the value of that radius is in between the data that we have, 1 and 3. And a Moose assert will only run when you have compiled in non-optimized mode. So in like debug mode or devel mode, which we haven't really talked too much about, but that's okay. The key feature is this compute QP properties loop runs on every quadrature point in your mesh. So you think you have millions of elements, and you have several quadrature points at each element. This is going to get hit lots of times. So when you're running in optimized mode, this piece of code won't be there. And it might help your speed a little bit to not do these few comparisons. And then we actually update our material properties that we're computing in this object. So the properties that are being produced. And viscosity is pretty simple. It's just going to be constant based on whatever you put in the input file. This will get better as we go on. And then permeability is a little more interesting, where we're actually doing that linear interpolation with the radius value received from that function. And then we just got to go quickly update the Darcy pressure kernel to use those properties instead of from the input file. So in the header file of the pressure kernel we made in step 2, we just get permeability and viscosity as AD material properties of type real, and they're constant references. And the constant's important because this is a consumer. We don't want the consumer to change the value of the property. That would be could be potentially bad. So always make sure you put constant on the consumer end. And then with respect to the C file, it's pretty simple. We actually take out the parameters from the valid parameters because we don't want the user to be able to give them there, and they're coming from the material property system. So you use get AD material property type real, and then these names here are matching exactly with the names that are declared in the material property object. And then this line doesn't really change except for you now have to index into those with the quadrature point index, because material properties are given as a little vector indexed on quadrature point. So hopefully that helps show you what we're doing. It's pretty straightforward. So I'm going to jump over to a different window really quick. And we haven't really talked too much about testing. So I'm going to do that now for the next 5 minutes, and then we'll be back on track. So what we've been doing along the way in these steps, if you go look at the steps in our folders, you will notice that each step adds a test. And the reason to doing that is to make sure we don't break anything. So in step 2, we made a little test that was testing our kernel, our Darcy pressure kernel, and it worked great. We did a bunch of verification and all that stuff, and everything was wonderful. And then we came along in step 3, and we made a new material. We even go make a test for that material object, and now we're all done with making this new material and making this new test, and we want to make sure that everything's in a good state. So we want to run our test. So this is in step 3 of the Darcy tutorial. If you can hopefully see that on my screen. And I'm going to compile it. I already did this, hopefully I did. Then I'm going to run tests, and run tests you can also give some J to if you want. And then it fails. So what happened? So let's go look at the output of this really quick. This final test results is a quick summary. So this is the test that gets shipped with your application. I believe this is the test from step 1. This is the test that we created for this step 3. We're testing that material. I think this is also maybe from step 1. And then this test is from step 2, and it's broken. And if you scroll up, you can see the reason. Material property permeability requested by Darcy pressure is not defined on block 1. Let's go look at the input file and see if something about that message helps us out. So this is the input file from that test. And remember we made this in step 2, and this is where it asks the audience what's changed, and that is this, right? When we first made Darcy pressure kernel, we had to prescribe the permeability. It wasn't something that was in the material property system. So we got to update this test, and there's lots of ways to do that. We can maybe add that packed column material. But we don't really want to do that because this test was designed specifically to test just the Darcy pressure kernel. So we don't want to add complexity to the test by throwing in a material object. So we actually have a little helper material object for doing this type of thing. So we can go down here and create a materials block. Just call it mat type equals generic constant material. And I need to, all the Moose team people, what's the syntax for, is it values and names?
Prop names and prop values.
Oh gosh, you're all talking, I can't hear.
It's prop names and prop values.
Okay, so prop names, permeability, viscosity, I think that's right. Prop values, we'll go grab that guy. Get rid of this line. And what was the viscosity? Does anybody know? Or should I go look it up here?
It's 7.98 e to the -4.
7.98 e to the -4. So all I'm doing here is, this is the up and down syntax, which you've seen a few times in.
Sorry,
Moose.
typo.
What?
Prop values, not prov values.
Oh, you want to let me fail? Thanks. So prop names is permeability. It's going to give a value of this 0.84 e to the -9, and then viscosity 7.9 e to the -4. And so these are just constant values across your domain and with time, but they're doing a direct replacement for this Darcy pressure, which is now expecting material properties by the name permeability and viscosity. So if I did my job right, I'm going to go run this, and it still fails, so I didn't do my job right. Ooh, AD material.
Throw
Oh,
up
you
your
guys can
terminal.
see.
Throw up your
Yeah,
terminal to show what the error was.
This is a good question for Alex. I actually don't even know the answer to this. So my terminal says, requested AD material property permeability is declared as a regular material property. Either retrieve this as a regular material property or change it to AD.
So prefix generic material, generic constant material with AD. So AD generic constant material.
Okay, so we do have this capability, so that's good. Alex thought of this. So I just needed to update and spell it right. Whoa. Oh my Max is all wonky. There you go. Update. Wow. You guys are watching me struggle here with Emacs. All right, so that fixed that hopefully properly, and go back to the, not Slack, the terminal, and run it. And hopefully now that passes, yeah. So we fixed the test. We didn't add any complexity to the test. We didn't re-gold anything, which, well, I haven't talked about what that means, but I will here in just the last minute. So a couple more minutes, and then we'll move on. Let me switch to the presentation. So as you seen, as we've run tests in kind of a couple scenarios yesterday and now today, we have a whole testing system in Moose. It's pretty powerful. It's all written in Python, and it's a way to test your objects. And generally speaking, if you go create a C++ object, you should do your best to make a test that is specific for that object, and try to minimize the test complexity as much as possible. It'll help you debug problems like this when they do fail. Like the only thing that really could be wrong is something with this little object, not 10 different objects that you're trying to test all at the same time. And the test setup looks pretty similar to other things you've seen in Moose. We usually have we put all our tests in what's called a test directory, and then we'll put other directories underneath to help us understand what that test is doing. So we'll have like kernels directory. We'll have tests for all our kernels, and then maybe my kernel test would be, for this one would be, what is it, packed, or I guess this is Darcy pressure. So we have a Darcy pressure folder, and then inside that you have some more information, maybe an input file, input mesh, input file, the actual test specification. We'll show you that in a second, and then a goal directory where you'll keep known solutions that are have been inspected and are known to work. That's what you're going to compare against. And this would be like the output file of the actual running this input file. You wouldn't want to save that in the repository. So a test specification is using our HIT format. And so they all start with this kind of global block, capital T tests. So that's syntax we're looking for. And then you can add any number of arbitrary named blocks underneath it. This is doing exodiff, so it's going to compare. It's going to go run this input file, which creates this output file, and it's going to compare it against the same name of output file in the goal directory. And if they're the same, the test pass. And if they're not, you're going to get an error. That's what we were seeing. This is the kind of test we were just running, but it actually errored out before the comparison. We also have run exception tests, which are useful just to test for actual errors, to make sure that those are being thrown when you expect them to be. And here's a list of some of the other ones we have. So just make sure something runs. Exodiff is what I just said for comparing two Exodus files, CSV file and VTK, compare those types of files. Run exception, it's checking for errors or even warnings. Check files will check for if you have files that are created or potentially not created. image, if you want to compare two images, we can do that as well. And then if you have Python utilities you want to test, you can run Python-based unit tests. There's a whole framework for unit testing in Python. And then we have some Jacobian testers that if you're working on non-AD objects and you want to verify that your Jacobian is correct, or I guess AD objects as well, you can use those utilities. Run test, we've already seen how to do this. Test, yeah, and you can dump all the available test objects and stuff just like you can for Moose input file syntax. That's what's on that slide. And then finally, make them quick. Less than 2 seconds, hopefully, even faster than that. You can see that in Moose, we can run about 2,000 tests on our workstations in just over a minute. And so we have a whole lot of tests. And on our testing system, we're testing 10 million plus, running 10 million plus tests a week. So millions of tests a day. And so you want to test as much as you can. So that's pretty quick, but I want to try to get us back to the actual workshop, which is what Logan's going to do. So is there any hand raised questions at this point? We're going to strongly encourage everybody again to use the Slack channel. I think it's way better for us as answering questions and for you seeing the questions of other people and things like that. So if you have a question, you can use Slack or raise your hand as well. So at this point, I'm going to switch over to Logan, if I can. Holy moly.
Faith in you, I'm not going to do it.
Oh, I got you. Yes. Oh, you already did it. So
Well,
Logan, you should
we do have a hand raised, by the way.
We do?
Well,
Yeah, let me.
I'll do that and I'll switch over.
Okay, here you go. Now you're in charge.
All right, Srinath, you're online.
Quick question, guys. I mean, your unit test framework is great for most C++ error checking, but what about fancy material models? Do you have any recommendations for tests? Non-linear material models. Clearly, those tests will not run in 2 seconds. I want to know if you guys have any recommendations.
We do have folks that are using the test system for larger validation models. I don't see if there's a reason why you can't use it for something that would take longer to run. Is that what you're asking? Just
no, I just want some general recommendations. I've been using Moose for a little over 6 months, 8 months now, and I have several nonlinear plasticity models that I have developed, and clearly the unit testing framework, for every change I make, I usually wait for a while before I can validate whether my model works or not.
So I can make a recommendation. So certainly always test. If you can't make your test faster, it's better to have a test than not, because it'll break otherwise. And you can, and for like your casual developing, you can mark a test as what's called heavy, and so it won't run when you just do run tests without a flag. So if you run test -- heavy, this test would run. But if you're just doing like casual development and you're trying to make sure you're not messing up most of your stuff, you could run tests and it would skip those long ones. But then when you actually want to deploy, you want to make sure you run all those heavy tests before it actually gets maybe merged in to your repository. And if you have an automatic testing system, you would want to run the heavy tests with that. So we do have some things that do that already, exactly for this case.
Got it. Thanks.
all right. With that, everyone, good morning. My name's Logan Harbor. I am a graduate fellow here at INL. I'm still a student at Texas A&M studying nuclear engineering. I was here for an intern for a few summers and moved up here full-time starting last May. I've been working alongside these Moose guys for quite a while and have had quite a bit of experience with Moose, so I'm glad to be here today to explain some of this content. What I'm going to start with is kind of a general overview of what the remaining steps we have for this problem are. So as Andrew discussed, so far we have created a general diffusion problem. We have created the pressure kernel, And we have created that pressure kernel and kind of extended it a little more so that you can use materials with it, which allow for all kinds of great things like spatial dependence and AD and all of that. What I'm going to work on first is computing the velocity field as a result of the pressure field. And with that, we'll introduce the aux system in Moose. After that, we're going to focus on the heat conduction portion of the equation, which will begin first with solving steady state heat conduction. And then we'll also add the time term. And with that, we'll go into time integrators and time stepping and all of that in Moose. After that, we'll discuss the coupling of these two equations, which occurs in this term here with epsilon in it. And then we will discuss mesh adaptivity in Moose and how it can apply to this system with a traveling wave. And more importantly, it makes really pretty pictures to look at in this kind of context. Then we will focus on postprocessors, which produce scalar values for solutions or for problems like average temperature and also average or line source or line values and things like that. And then lastly, we'll discuss thermal expansion and its relation to this problem. So with that, I'm going to continue on to producing a velocity field from the pressure field that we've created so far. Of course, the velocity is our primary variable of interest, and it's computed using the permeability tensor, the viscosity, and the pressure. So with that, we will introduce the auxiliary system in Moose, which is a system for computing directly other value or other field variables of interest. An important distinction in Moose is that a nonlinear variable in Moose is something you're solving for. It's something that is in the solve directly and is used in a kernel or a boundary condition, for example. An auxiliary variable is used and computed outside of that primary loop. It can be before a solve, after a solve, and whatnot in order to actually compute auxiliary properties. And in specific, those are only computed with aux kernels is our direct definition for that. Now, aux variables are defined similarly as regular variables are with just an aux variable's syntax in the input file block. They take the standard inputs like order and family, and their default follows the same as first Lagrange. Now, similarly to regular variables, you have element and nodal options for these variables. Standardly, whenever we use element values for aux variables, they're constant, so a constant value on each element. And then nodal, of course, like I said, the constant we have, or the standard default we have is linear Lagrange. Now, I don't know if we discussed this earlier, but all variables in Moose, aux and nonlinear variables all have old and older and even older states if you want, with a simple enable flag in a few systems. So as you're computing these in time, you will also have old and older copies of them for use in things like time integrators. Now, elemental auxiliary variables, here we have an example of how to define an aux variable called aux that is constant on each element. In other words, it is a constant monomial aux variable. These can couple to nonlinear variables that are both nodal and elemental variables. I'll go more into that and what can be coupled with what in a second once I go through all of the variable types. Nodal aux variables are similar to nodal standard variables, of course, where they are defined at the nodes. And like I said, they are defined similarly to standard variables in that you have an order and a family to define them. Now, something important to note is that aux kernels that are nodal aux variables can only couple to other other nodal variables. And this is because the evaluations are done directly at the nodes. So if you couple to a nodal nonlinear variable with an aux kernel, you're doing the evaluation at those specific nodes, not at quadrature. However, with elemental aux variables, you're doing that evaluation on quadrature points. So you can actually sample the solution using the nodal basis at quadrature points, which is what allows elemental aux variables to be coupled with both elemental and nodal standard variables or nonlinear variables. And of course, these aux variables are all coupled with one another as well. So we can create some kind of dependency, and some aux kernels which produce aux variables can depend on other aux variables. Now, aux kernel objects are another standard object type in Moose, in which we produce values by overriding the compute value virtual function. In order to maintain simplicity and consistency, this function is used for both elemental and nodal auxiliary variables. Like I said, whenever you're calling compute value for, or whenever you're computing a value for a nodal aux variable, the operation happens on a node. Whenever you're doing this on an elemental variable, it operates on the element, within the element, essentially. With that, the basic members, which are the variables you have available when you're in these compute loops and aux kernels, first of all, are u and grad u, which are simply the value and the gradient of the variable that the aux kernel is operating on. You have the physical quadrature points. You have underscore QP, which is the current quadrature point. Now, if you have a nodal aux variable, this quadrature point value will always be 0, and it will represent the 0 index for whatever you're working on, which is just a node. So for example, if you have an elemental aux variable, this could vary from 0 to 3, for example, but for a nodal aux variable, this will always be 0. And lastly, you have a pointer to the current element that is being operated on in the case of an elemental aux variable, and the node that is being operated on if it's a nodal aux variable. Now, vector aux kernel objects and vector aux variables are also an option, and that's simply, in this context, you have a first Lagrange variable for each dimension for x, y, and z, and it's a simplification for if you choose to have a vector value represented. You could also represent most of this similarly by having a variable for each x, y, and z, but just for syntax and objects and operation, it simplifies things a lot if you have a vector value that you want to compute an aux field for, to just use one of these vector types, which is actually what we're going to do in a moment. Okay, are there any questions about the aux system before I jump into actually using it? Okay, great. So in our problem, the primary unknown, which what we're solving for, is the pressure, and it's a nonlinear variable. Once we have that pressure, we can have we can have our aux system compute and output the velocity using the pressure. This is below. We have another recap, of course, about the two flavors we have for nodal and elemental aux variables. And what we're going to end up using is a nodal vector aux variable to represent the velocity, so that we can get an x, y, z component and a magnitude for easy output, essentially. Now, and this is really important again, and this happened, actually a question came up about this in the Slack channel not too long ago, about how, again, nodal aux variables, they can't couple to gradients of nonlinear variables. Let's say you have a linear variable on an element. That means the gradient is a constant value on the element. So if you want to compute the gradient then for a nodal aux variable, which is the value at a node, that gradient is not well defined at a node, because if you're thinking about 4 simple quad elements and you're at a node in the middle of them, you don't know which gradient to use. You have a gradient over here, down there, and down there. So of course, we don't support that kind of coupling because that behavior isn't very well defined. And a recap on what I said earlier about how those elemental variables can couple to both, can couple to gradients of nonlinear variables, because the evaluation for an elemental aux variable happens within the element, and the gradients of the nonlinear variables that are being coupled to are well defined inside the element. All right, so with that, I'm going to introduce the Darcy velocity aux kernel. It's actually a vector aux kernel because we're producing a vector variable field. And of course, what we're trying to produce here is the velocity computed with the pressure, which is the permeability tensor over the viscosity times the pressure gradient. So of course, we have our standard pragma once at the top of every object to stop us from including this object more than one time. We will include the base class that this derives from. Now, in this case, aux_kernel contains a class for both a vector aux_kernel and an aux_kernel, which is why the name for this is separate from this. So we're going to create Darcy velocity vector aux_kernel. We have our standard input parameters, so we can define input parameters and pull on input parameters from the objects we inherit from. Our standard constructor, which simply takes a set of input parameters. And now we would discuss what needs to be overridden for an aux_kernel. And what we said earlier was that we have the compute value function, which is what is overridden here. Now, in this case, the comment here says compute value is called on every quadrature point, but of course, we're doing a nodal field here. So that means that this compute value function is called on every node that it is defined on. Now, of course, the values that we need to produce the velocity are the pressure gradient, the permeability, and the viscosity. So we will couple in the value from the pressure, which of course this is const because we're simply reading a value and creating something else from it. So we have a variable gradient, which is, as it says, the gradient of a variable, which we will store from the pressure. And we need two material properties, which are the permeability and the viscosity. And this is pretty similar to what Andrew just went over. Those are also const as well, because those are material properties that we need to only read. And with that, I will continue on to the source. So significant things to note here, input parameters. Now we need to couple to a variable. Well, without any extra information, we don't know which variable we're coupling to. In this case, we don't know what pressure to use. So with that, we have a method in parameters. It's called add required coupled var. And what that does is it says to the parameters object that we need, and we must have, it's required, a coupled variable, and we need a name for the coupled variable. So the user now will supply pressure equals and the name of a variable. Important thing to note here, although in this context we're coupling this to an actual variable, this required coupled variable could also be an aux variable that will be supported. But it's important to note that because we're creating a nodal aux variable, of course, that we can still only couple to other nodal variables. Now with that, we go to the constructor for this object. So this is something that we haven't seen before. So pressure gradient, as we said before, has a type of variable gradient. And how we grab the gradient of that variable is through this coupled gradient interface. And what that does is this string of text called pressure. First, it looks to see if you have anything called pressure in your input parameters. And if you do, it will grab whatever that points to. So let's say someone says pressure equals variable in their input file. That will then grab the coupled gradient of the variable called variable. And this is also supported, this syntax is pretty similar for other types. So you can also have coupled instead of coupled gradient, which will just get the value. You can have coupled old, which will get you the older value of it, and so on. This is quite extensive in terms of what different kinds of values you can get from variables in terms of gradients, time, and whatnot. Now, we have done something similar to this in the past where you need to grab the material properties for both the permeability and viscosity. And as Andrew said, this is really important. This permeability string is the same thing as it is in the material object that is defining it. So we're specifically grabbing the permeability and the viscosity from whatever decides to name something called permeability and viscosity. Now we'll come down to the compute value method, which is where we actually do the computation on nodes. Note that we have a return type of real vector value because this is a vector aux kernel. So we're actually producing a value for both x, y, and z. And let me read this. So this is actually some older comments that probably shouldn't be here anymore. So pressure gradient is a vector value, correct? It is it's just a standard vector value. Permeability in this case is actually an AD real, and viscosity is an AD real. So at this point, this operation will return an AD real, but we're returning a real vector value that is a non-AD value. So in this odd case, metaphysical raw value essentially strips that AD real of all of the AD information associated with it and just gives us a standard real. So essentially what we have here is we have a real value multiplied by a real vector value. So we're just scaling the real vector value here. Other important things to note here is that even though underscore QP will only ever be 0 for a nodal aux variable or nodal aux kernel, we keep it in just to allow for consistency between objects. So in this case, permeability will be evaluated at the node, as will viscosity. Any questions about that? I see one up from Benjamin. All right, Ben, I can.
Okay, I know you do, but I was just curious on how do you make sure that the I guess the object is I guess because you have this pressure gradient on the return that you calculate.
Yes.
So that's on your constructor, right? So you make sure that you construct your object before, I guess, calling compute value.
Yeah, correct. So this coupled gradient here, this will perform a callback to basically make sure that that variable even exists. So this object will get created a long time after all the variables are defined and things like that. So we define variables way up front so that all the objects that need them can make sure they exist before they do any work. So at this point, if we cannot find a variable for this, we'll get an error.
Okay. Thank you.
Of course. I think I've got another one. Yep.
So the AD distinction to get the raw value of the real value of the AD variable is only restricted to material properties, or anything else we define as AD, because presumably the pressure is also some kind of automatically differentiated quantity in this instance.
So it's not just necessarily material properties, it's really any kind of case where you have to convert from an AD object to a non-AD object, which happens here. And pressure gradient here is actually not an AD quantity, it's actually just a solution value. If you go up here and look at the type of pressure gradient, it's simply a variable gradient.
Okay.
So, and what one of these values actually is, so if you take pressure gradient 0, it's just a real vector value. So you have a real vector value here, and then you have an AD real here that you need to strip the AD contents for. Otherwise, C++ is it's a typed language. It'll not be happy and won't know what to do with it.
I have a slightly, maybe not exactly a related question. You said earlier on when you were discussing aux kernels that there's no well-defined gradients at the nodes for some of these elemental quantities. But there are techniques in finite elements like patch recovery, etc., which give well-defined gradients at the nodes. Is there any such capability in Moose?
Could someone else answer me on that? I'm not sure if there is. I'm pretty sure I don't think we've actually had it implemented. Alex?
I feel like there's a nodal patch recovery aux kernel, if I'm not mistaken.
Okay.
Yeah, there definitely is some patch recovery capability, but I would say that's an area that could definitely be enhanced still. And there are larger stencil-based physics that are being done for flow that kind of have some of that patch recovery flavor as well. So I wouldn't say it's a strong suit of moves to have patch recovery, but we have some in that area.
Yeah, Srinath, if you look in the Ox kernel source, there is indeed a nodal patch recovery object.
All right, thanks, guys. I'll look into it for sure.
Hey, Logan, you have a question in the questions area about raw value. Could you go into that just a little bit?
Yeah, so I'll reiterate that again because that is kind of odd out there. So the type of pressure gradient quadrature point is a real vector value. Pressure gradient itself is typed as a variable gradient. So what that means we have here is we have a real vector value here, which is basically just, it's a vector with solutions, or it's a vector with values for x, y, and z essentially. Now permeability and viscosity are AD reals. And why those are not reals instead? First of all, they're AD material properties, which means they contain additional information that is needed to do a differentiation on them for the sakes of computing derivatives in the Jacobian essentially. So the issue is that this type is an AD real. Now, C++ is a typed language, so it's very specific to having the correct types for everything, or else you won't even be able to compile. And it needs to know what to do with certain types versus certain types, which means in order to get this real vector value return type, we have a real vector value here, and we have an AD real here inside the parentheses. So what raw value does is it strips this of all of the AD quantities and just gets us the real value. So essentially, in this statement, we now have a real value. And a real value times a real vector value is a valid operation. It's just scaling the real vector value. So it's essentially typing to make sure that we can get a real vector value out of this. And that is it.
Thanks, Logan.
Yep. So with that, I'm going to continue to an example input file for how we actually use, how we actually compute the pressure. So at this point, up at the top, nothing much has changed. We still have a mesh. We still have a pressure variable. I'm going to ask you to please avoid looking at these just for the sake of, we prefer that we instead use this vector value for the velocity. So we've defined a velocity aux variable of type constant monomial, and it's a vector value, which means we have a constant value on each element for each direction, essentially. Now, this is kind of an older style that, it's not an older style, but it's a less simplified style that we used in the past, where you actually create a separate variable for each x, y, and z dimension. So at this point, we have an aux variable called velocity of type constant monomial, and it is it's a vector constant monomial. So again, we have a vector value associated with it. Pressure, we still have our standard pressure kernel we had previously. Now, something that is new is an aux kernel. So again, aux kernels operate exclusively on aux variables. So this Darcy velocity object that we created takes first by default, all aux kernels take a variable, which is the aux variable they are operating on. So we want to fill a value into the velocity aux variable. Execute on, we'll go into that more a little bit later. But what this says is that I'm going to execute this after every time step. And lastly, if you remember, we add an additional parameter called pressure, which is a way for this kernel to grab the value of the pressure. So we're saying the pressure variable we want to use is called pressure, which if we scroll up to our primary variables, we have our pressure variable here. Now, this syntax here, or these objects are simply, I'm not going to go into too much detail for them, but they're grabbing a component of the vector aux variable and putting them into the non-vector aux variable. So we're grabbing the x component, putting it in velocity x, the y component into y, and so on. All right, okay. And everything else down here is remain the same. We have some Dirichlet boundary conditions on the side, using our same packed column material, and so on. Now at this point, we're going to go ahead and run. We're not running with Peacock today because our software doesn't support it very well for video conferencing. But I'm going to go ahead and run this in the command line. So I'm going to switch over here to my terminal. We're going to go to tutorials, Darcy Thermo Mech, step 4, velocity vector aux. And we're going to go ahead and make this Shouldn't take too long. We're going to move into the problems directory where we're going to go ahead and do a list. And of course, we have a step 4 input file. So standard running in Moose, we're going to go ahead and grab the executable, which is back one directory called Darcy thermomech opt -i, just note which input file we're going to run. We're going to run step4.i. Right, so if we look up here at the top of our run, we have our standard nonlinear system, which has our pressure variable, but we also have aux variables. So we have those individual x, y, and z velocity variables, which are of type constant monomial. And we also have the vector monomial, which is the constant value that holds values for x, y, and z. I believe this is, yep, visualization. Okay, so we're gonna go ahead and visualize this in pair review. So I'm on a Mac, so I have this nice open syntax. You might have to open it, I'm not sure, other machines, but I'm gonna do open. And I'm not sure if we discussed this earlier, but by default, all output is named the name of the input file _out. That's the default. So we produce step4out.e. So I open that. I'm going to switch over to pair review. We're going to enable this. And we see our velocity field here. I'm also going to enable pressure. So we're going to show first our pressure field, which hasn't changed. It's the same field that we had in the previous problems. But what is new is that we have this velocity value. We also have, I'm not sure why this nodal value is here, considering we're using constant monomial, so I'm not going to go into that. If someone wants to interrupt me, they're welcome to. So what we have here is we have a magnitude of velocity over all of the elements. So this is just the magnitude. Now what you see is a relatively constant value of 0.014, and this is expected because we have a constant pressure. Or I'm sorry, a pressure profile like this, I'm sorry. So also note that we have that this is a vector quantity, which means up here in pair review, and this also exists in Peacock, we have a few options. We have the magnitude of the value, we have the x value, the y value, and the z value. First, I'm going to switch to z value, which we should see no contribution because it's a 2D problem, which is good. We have a 0. We'll go to y, which we also shouldn't expect. And of course, this is negligible. And if we go to x, we'll see that all of the velocity is in the x direction, which is good. That's what we expect. If we compare x to magnitude, it's the same thing, which is good. That's exactly what we would expect. And I actually don't need to rescale. Hold on, someone said I need to rescale. Yeah, this is just an artifact of the values being, close to within some precision, so you end up with all this static. Okay, any questions about that? Okay, and let me switch back to Firefox.
Logan, just to be clear, the velocity there is constant, right? Which is the reason why it looks that way.
Yes, yeah, exactly. You mean the
pair review is trying to show a constant value that was solved numerically, so there's noise around.
It's within 7 digits of noise. So at the very bottom, of course, we have a more simpler visualization of this without actually showing how to run it, but running it's the way to go. And we also produced a more fine solution. All right, with that, we've now figured out how to solve for the velocity field, but now we need to add in the heat conduction component. And we're gonna start that by focusing just on the steady state part. So we have a time dependent part right here. We have our coupling, and we have just standard steady state heat conduction on the far right term. So like I said, that's what we're going to start with. We're going to look at just standard steady state heat conduction, which is kind of something we've done a lot. It's a diffusion style thing. Now for simplicity, without having to write a bunch of new code, we're going to use an object called AD heat conduction, which is the heat conduction term with AD support, with the thermal conductivity. So this already exists. This is the header file for the AD heat conduction kernel. As you can see, it inherits from AD diffusion. This is pretty standard because it's a diffusive term with a constant on the outside of it. And the value we actually need, the additional information we need on top of standard diffusion, which we will define, is the thermal conductivity. And that's exactly what this is. This is a real value. It's an AD value for thermal conductivity. With that, we continue on to the source. Now, of course, we need to define that thermal conductivity. So what this does is this, of course, says I need a material property that the user is going to give to me with a thermal conductivity equals in the input. We're going to default it to the name of thermal conductivity. And of course, just a standard definition. Displace message support, this is separate, but it exists for this object, which is why this is being set to true. If we skip down to the constructor, of course, the only thing we actually define in the header file is the thermal conductivity, and it's a constant reference, so we absolutely need to define it in the constructor. So with that, we'll grab the AD material property called thermal conductivity so that we can use it further on. Now, as we said before, we have lots of objects that are optimized for certain physics, right? So AD diffusion, for example, this does the bulk of the work, which is, the gradient multiplication and whatnot. So that's what this pre-compute QP residual is from AD diffusion. And we're only going to modulate it, modify it by the thermal conductivity. And of course, pre-compute QP residual is a quadrature evaluation. Material properties exist on quadrature points, so we're going to grab those properties using the standard _QP syntax. Now with that, as for a simple example, we're going to use this AD heat conduction kernel along with a generic constant material, which it should be an AD generic constant material, as Andrew learned earlier on today. What a generic constant material is, or an AD, is it's simply an easy way to define in input a set of properties by names and values, as Andrew showed. And we're going to run, as I said, a simple steady state problem with Dirichlet conditions at the inlet and the outlet of 350 and 300 degrees. So as Andrew used earlier, the input syntax for generic constant material is simply a list of names that you want to define and the values for those. Now we will move on to the input. Of course, we have our standard mesh definition. We have our standard, or we now have a temperature variable that, again, by default is the first Lagrange variable. Our only kernel is the heat conduction kernel that we just discussed that exists already in Moose. We have an inlet and outlet Dirichlet boundary condition at the left and right on the variable temperature. We must now define a thermal conductivity for the AD heat conduction object. So something needs to define something called thermal conductivity for this object to use, which is what we're doing here. So what we're saying is that go ahead and create a material property called thermal conductivity and give it a value of 18, and it will be constant everywhere that this object is defined. Standard problem with our coordinate transformation. Executioner is not changed, and we're going to do some excess output. Okay, so now we're going to go ahead and run this as well. I'm clear. And while I'm doing this, feel free to jump in for any questions as compiling takes a minute. We're going to move into step 5. We're going to make it. Now, something of interest that I should note here that we discussed earlier or yesterday was the use of modules. Well, some of these objects actually come from modules, and what I'll show briefly while I'm here is the simplicity of enabling other modules in your application. So your standard make file for your application exists in the base directory for your application. So in this case, we have an application, the step 5 heat conduction module. So if I look at that make file, we have a listing of modules and enabling a few of them. So in this context, we need the heat conduction module. We even have a comment that says that we need it for step 5+, because that 80 heat conduction object actually comes from the heat conduction module. So this is how simple it is to enable the use of modules in your applications. Now, of course, because those are there, actually, I'm not even going to that. Disregard what I just said. So now I've made my application. I'm going to go into problems, and we're going to go ahead and run that steady state problem. So again, we're going to go grab that executable. We're going to run step 5a steady.i. All right, now as we expect, we have a temperature variable we have a first Lagrange variable called temperature, and that's all we have in this problem. So we're going to go ahead and open that file. Open step 5a steady, and of course, like I said, all output by default is suffixed with _out with the input file name in the beginning. So we're going to go ahead and open that. I'm going to switch over to pair view. Now, of course, we have our temperature variable that we would expect. We're going to go ahead and view that. And in this case, we would expect a linear profile. And what I'm going to do to show that we get that is we're going to go ahead and do a plot across the line. I'm going to go ahead and plot across. I'm going to plot the temperature in a line across the bottom of this. We're going to go ahead and apply that. And what do you know? There's the profile that we expect, with 350 on the left and 300 on the right, as we define with our Dirichlet boundary conditions. I'm going to go ahead and ping Will, since it looks like I have a hand up. Will, I just went ahead and unmuted you.
Yeah, thanks. Sorry, I was going to ask this while you were waiting for your compile, but
no problem.
And sorry if I'm asking you to recap something you already did, but when would you choose to use an auxiliary, an aux variable aux kernel versus integrating into your main?
That is actually a great question. So we'll actually we'll look at that later, because actually one of the equations we need to solve has a velocity in it, right? So you can either compute that velocity directly, implicitly in a kernel, or you can compute it in an aux variable. Now, why you'll want to do it differently is really depending on if you want it to be implicit or not, is kind of one of the reasons, right? Because if you compute the velocity ahead of time, it's going to be lagged. So it's not going to be implicit in the kernel itself. Does that make sense as to why you would use one versus the other?
I can maybe add a little bit more to that. I think that's a good explanation, Logan, for why you would choose one or the other if you have a choice.
Yeah.
The basic difference is an auxiliary variable is something you can directly compute. A nonlinear variable is something you solve for. So if you have a direct closed form expression for how to compute something, then you can do that in an auxiliary variable. If you're trying to actually solve using the finite element method for a nonlinear for a variable, then it needs to be in the nonlinear system.
Okay, so you would calculate the aux variable and then feed it in for the next time step.
So that is the thing that Logan was talking about, that there are trade-offs to utilizing the auxiliary system in that way. Usually, I'll say right now that you don't want to do that, and the reason why is accuracy. When you use the auxiliary system in the way that Logan was just using it, you're basically getting an average value for the velocity on each element. And that's not usually what you would like to couple to in your actual solve. Yeah. So in this case, this velocity that Logan is computing is really just for visualization purposes, and so that we can see what the velocity field is doing in the output file.
Okay, so then that's clear. If it's coupled into the equations and there's a feedback effect between velocity field and the rest of your physics, then you have to couple it in. But if it's just something you're looking to get as, I guess, an auxiliary variable that you want to view, then you use it as an auxiliary. Okay.
Yeah, and the auxiliary system is really flexible. It's used for a lot of different things. Another very normal case for the auxiliary system is to read field data in. So let's say you have something like a permeability map for a chunk of rock or something like that you've gotten from some sort of a scan. You can read that into an auxiliary field and have a different permeability in every element, let's say, something like that, and then couple to that and use it in your material. But typically you don't want to go through the round trip of nonlinear variable you're solving for into the auxiliary system back into the nonlinear system. That you're going to lose derivative information, you're going to lose accuracy.
Thank you.
We do actually have an example later on too, where we kind of decouple some of this, and in our kernels that rely on on the velocity vector, we can actually pass in directly this through an aux kernel like we discussed. And of course, it's not really, if you can actually compute the real thing in a kernel, then you should pretty much always do it, because the cost is probably going to be pretty little if you already have the material properties available anyway.
There's another question, Logan.
Yep, I see it.
But in just on the same note, but in solid mechanics, the stress is a derived quantity, and yet for many things in solid mechanics, the common way is to use the stress and its derivative with respect to some other variables. So would you recommend then just reformulating the problem, a complex multiphysics problem in terms of the displacements, rewriting all the equations, and then use the displacements to solve the problem, or would the auxiliary variable system can be used in that situation?
So I think maybe Alex wants to chime in here, but I'll say real quick that typically for all the things for solid mechanics, the computing the stresses and those sorts of things, you would do that in the material system. So that's where you can compute a high precision stress at each quadrature point, that sort of thing. So they wouldn't really involve the auxiliary system.
Got it.
I guess I'll say, like, you do have a choice in a displacement-based formulation or a stress-based formulation. We've done both within Moose, but I think the current implementation is a displacement-based implementation. Is that true, Alex? You would know, or somebody?
I would definitely not know.
I actually know the answer to that. It is displacement based.
Okay.
Okay.
So,
perfect.
and yeah.
Good. Thanks.
Okay. I'm going to continue then. So our next step is to add in the time derivative term and get rid of the steady state nature of what we were running earlier. Similarly to how we have an AD heat conduction kernel for the heat conduction term, an AD heat conduction time derivative also exists, which, if you can see, also requires a value for C. So with that, we need some more information about kind of transient systems and time integration and all that in Moose, so that we're going to go ahead and make a jump to that before we actually solve this problem. So what we'll start with is the executioner system in Moose, which you guys have seen so far. Usually in most blocks, we have executioner with a type equals steady for a steady state executioner, and then some kind of solve parameters that we've changed, but we kind of have a default set that we use for most of these problems. So the executioner system is basically just a system that dictates how the simulation will solve. Like I said, what you've seen mostly or completely, I think at this point, has been the steady state executioner, in which case we can solve the system multiple times. We can also adaptively refine the mesh even in the steady state case. Now, even more significant is the transient executioner, which of course just involves just solving at multiple time steps. So the most standard default parameters that are used the most, of course, are dt for time step size that you start with, the number of steps that you want, the start time, the end time. Now, these aren't all used in combination, of course, because you can't provide or maybe they can. Anyway, I think I just complicated myself. I'm going to back up on that. And then lastly, a scheme, which is just the scheme for the time integration. And we'll discuss time integration after this little section, what the options are and how that system is extended. What also comes with the transient executioner is a steady state detection, which is simply a system to quit the solve whenever it thinks that it's achieved a steady state. By default, of course, this is set to false, and it's controlled by the steady state detection parameter. And the steady state tolerance parameter is just a tolerance for when it thinks the solution has met a steady state. So by default, if you set steady state detection to true, it'll quit once the compared difference in solution vectors between now and old time step is 180 to the minus 8. Other common executioner options which are involved in the solve are things like linear tolerance, the max linear iterations, and tolerances on the nonlinear solve, as you can see here. Oop, that's the wrong way. Okay, now with the transient system in general, now you need time derivatives. So we have a specialized kernel that acts on time derivatives, or acts as a time derivative, and those are called time kernels. So those gain access in addition to the standard variables that you would get in a kernel object like U and quadrature point and whatnot. You also now have access to the time derivative that's stored in U dot and the derivative of that with respect to U, which is in du.du. Now, of course, these interact otherwise like standard kernel objects where you have a compute QP residual that you need to store and whatnot. Now, similarly to how we have things like AD kernel and AD kernel value and AD kernel grad, we have the same thing with time kernels. The standard base, of course, is time kernel or AD time kernel that has a compute QP residual that you would override. Now, we also have time kernel value and AD time kernel value, which is something similar to what we've been using so far, where you will override pre-compute QP residual. And you can see the use cases for these on the right here that I'm not going to read through, but they're similar to as we had in the previous classes with just kernel value and kernel grad and whatnot. Now with that, we have an executioner that can support transient operation. We have time kernels that we can use for our time derivatives, but now we need to define how we're going to integrate in time. And with that, we have the time integration system. I hope you understand now at this point that Moose is just these massive culminations of systems that can be plugged into one another, and that's kind of the beauty of what's been created here. With that, the standard schemes that are typically used, we have backward Euler, BDF2, Crank-Nicholson, Dirk, Newmark Beta. These are all common time integration schemes. Of course, others have implemented more. We have some other methods that are kind of in development for more structural mechanics and whatnot, but these are kind of the standard that anyone starting should have some knowledge of or should expect us to have, I guess is what I should say if you're working in the transient sphere of things. Now with that, we jump into where this time integrator object actually goes. It's a subblock in the executioner system. So here we have a transient executioner that's going to start at time 0, and it's going to take 6 steps of dt of 0.1. Now we also have a user-defined time integrator in here, which now takes a time integrator block inside the executioner block, like I said. In this case, we're using Newmark Beta with a user-defined beta and gamma value for time integration. Now we're going to consider this is kind of standard across the board, showing convergence rates for things like for time integration. We're going to consider the test problem you have here, and we're going to choose F such that we have a known exact solution. And we're just going to go ahead and look at the convergence rates to make sure with the schemes that we have defined previously that we get the convergence rates that we would expect. And this is quite self-explanatory. You see first order with explicit Euler, second order with midpoint and the Dirk methods, except for of course Dirk 3, and near third order for Dirk 3, second order for Crank-Nicholson, and and whatnot. So, you know, you get the order of occurrence that you would expect from these time integrators that are used everywhere. Now, if you're new to, you know, working in the transient verse, it's also really important to take note of these convergence schemes and the positives and negatives to each of them. But of course, that's past what we will discuss today. Definitely feel free to ask about time integration on the user group if you need to figure out which object to use, though. We started with the transient executioner, different time integration schemes and how to apply those. And now we're discussing the time stepper system, which allows the user to create objects that will change the time step size you're taking. So with that, similarly to how the time integrator was a nested block inside the executioner, the time stepper is also a nested block inside the executioner. In this case, we are using an iteration adaptive DT time stepper. This is basically a time stepper that attempts to set the time step size to create an optimal amount of iterations, both linear or nonlinear. Now, some standard built-in time steppers, constant DT, of course, it's just a standard constant time step. Solution time adaptive DT is one that tries to use solutions to set an appropriate time step. Iteration adaptive DT, as I said, is the time stepper that allows you, it attempts to set a time step to create an optimal amount of linear and non-linear iterations. Function DT is one that takes a function, so someone can create a function that, you know, depends on t and can ramp up, or, you know, the solution or the possibilities with that are endless. But typically we use it for setting a parsed function as a time stepper, like if you want to ramp up time within a certain period and whatnot. Postprocessor DT, we haven't discussed postprocessors yet, but they're scalar values that can be created using, you know, be created anyway, and this basically creates a time stepper that is based off of that postprocessor value. DT2 I'll explain in a second, and time sequence stepper is a time stepper that allows you to just kind of basically provide a set of a sequence of times that you would like to run. Oh, and we have another description here. So like I said previously, iteration adaptive DT grows or shrinks that step based on, you know, an optimal level of iterations that the user provides. In this case, we want a ratio between linear and nonlinear iterations of 1, and we want to shoot for 1 nonlinear iteration optimally. And we want to start with a time step of 5. DT2 is an adaptive time stepper, and the general process can be described here. I'm not going to go in detail too much for this, but you end up creating error estimates using different time step sizes to create an optimal time step size. Derek, if you want to comment on this at all, I think you had a better explanation for it, if you find it to be fitting.
I mean, I don't think it's really necessary to go into detail.
Perfect. There was so much here, I just wanted to make sure I wasn't missing something.
It's simply, yeah, using a more exact time integration step and comparing it to a less exact time integration step, and using that to predict error and predict the next time step size. So
perfect. Thank you. Like I said, time sequence stepper is a stepper in which a user just provides a set of times they want to include, and DT is generated as such. And interestingly, with most of these, if you have some kind of solve failure, there's usually some fallback. In this case, if you have 2 times that you must include, it will fall back by inserting an extra time step in the middle of your current time and your next time in the sequence. Okay, so with that, we have all the general basic building blocks to start running transient problems, which is the transient executioner, time kernels, a way to integrate in time, a way to change time steps, and so on. So with that, we'll continue back to our problem. What we're going to do is we're going to work on a simple transient heat conduction case. Remember, we already discussed the steady state, which is just this right term here, and we're going to add in this time-dependent term on the left. And like we said in the past, there's an object called AD heat conduction time derivative that actually already implements this in the heat conduction modules. We're just going to go ahead and use that. So just to show you what this time derivative, what this object looks like, this is in the heat conduction module. So we said previously that now we have these time kernels. So AD time derivative is the base class for that case. Now, in addition to that, we need to be able to get the material property C in there somehow, which of course is the specific heat times the density. So with that, we must override pre-compute QP residual as we have done in the past, which is where this override is coming from. And we need two material properties. We need the specific heat and the density, which are both going to be AD material properties. Reminder again, they're const because we're just going to be reading into them, and they're references because they're pointing to some other system that owns this information. Now into the source of this, we have a description in the input parameters object. Of course, per usual, we take the base class, which is time derivative, and we add on additional parameters from the base class's parameters. We have a simple description, which I won't go into. We allow displaced mesh use. More specific to us is that we need to be able to get a material property for the specific heat and the density, as I discussed previously. And we're going to default the specific heat name to specific heat and the density material property to density. So if the user does not provide specific heat or density name, they will default to these values. And we will look for material properties with the name specific heat and density. In the constructor, remember that we defined two new member variables, specific heat and density, so we need to fill those in the constructor. We're going to go ahead and grab the material property called specific heat and the material property called density name. Now remember that the system's smart where this density name will look back to the parameter called density name, and then we'll look to what that's pointed to. So if the user sets density name equals G or foo, this will appropriately grab the material property called foo. Oh man. And now we also need to override pre-compute QP residual, which actually does the computation of, it does the residual computation that we need to override. So of course the AD time derivative has the standard derivative term in it. So we're going to go ahead and grab the method from the base class, and we're going to multiply it by the constants that we need, which are the specific heat and the density to grab big C. Of course, standard nomenclature, we're indexing in through QP because this evaluation is done inside an element on quadrature points. So we're going to grab those material properties at quadrature points. And they are AD properties. This function will return a type of AD real. This is an AD real, and this is an AD real. And conveniently, we return AD real. Otherwise, C++ would not be happy. With that, we continue on to the input file. Our mesh has not changed. Variables, we have a temperature. Something new here is an initial condition. There is a separate initial condition system, which will allow you to do much more complicated things for initial conditions. But in this case, we also have a really simple input parameter that is initial condition equals, which sets the entire field equal to a scalar value. Now, this is important in time-dependent cases because we need an initial value for it at whatever the starting time step is. So in this case, we're going to set the initial condition to 300. The AD heat conduction kernel existed already in our steady state problem, and now we're going to go ahead and add an AD heat conduction time derivative kernel, which also acts on the temperature variable, and that's going to introduce our derivative term. Now, if you remember, this took inputs called, I think, specific heat and density name. We did not define those there, which means they're going to revert to their defaults of specific heat and density name. We have our same boundary conditions. We're going to enforce 350 degrees to the left and 300 degrees to the right. Now, we also must add the additional properties that are needed by the time derivative kernel. So thermal conductivity we already had. It's a constant value of 18 everywhere. Now we're also going to add a value for specific heat and density, which are required by the time kernel that I just talked about. We're setting those to 0.466 and 800. The problem hasn't changed. We're still working in RZ coordinate system. The executioner has absolutely changed. So this used to be type equals steady. Well, now we're working on a time-dependent problem. So we're using a transient executioner with 10 time steps, and the solve parameters for each time step have stayed the same as it was previously. So now we should expect to run 10 time steps with an initial condition of 300. And those are the changes for the time-dependent problem. So with that, we're going to go ahead and run this. So I'm going to switch over and run this really quick. We're going to go ahead and go back into the step 5 folder. We already made this, so we shouldn't have anything to do here since we're already working on this. We're going to go into problems, and we're going to, per usual, get our executable, which is Darcy thermal mech opt -i to pick an input file, and we're going to run step 5b transient.i. Now, okay, differences in output. Let's scroll up to the top first. We see we have a transient executioner now. That's good. We expected that. Now at time equals 0, we don't have a solve because we set initial conditions. Now the step to time step 1, we've now advanced with a dt of 1. We're now at time 1 and physically at step 1. And we do our standard nonlinear solve. And we do that for every step up until we get to the 10 time steps that we expected and we asked it to run. So we're going to go ahead and open that file. Like I said, all outputs by default are the input file name, which is step 5b transient, and then our suffix by _out. So we're going to go ahead and open that. I'm going to switch my view to pair view. All right, things to note here. Now we have 10 time steps. That's good. We have output at every iteration, and that output, when it happens, this isn't discussed now. We can also change when that output happens, so we don't output all the time if we don't need to, or if we have massive simulations, we don't want to output at every single time step. So I enable temperature. I'm going to go ahead and pull this up. I prefer to show the line view because I think it shows better than the propagation, but we're going to play this anyway. We're going to step through in time. Of course, at time equals 0, we have our initial condition of 300 that we set. And then we will see the propagation through time. And then I'm going to go ahead and also plot this over a line because, like I said, I think that it's a little bit easier to view than looking at a field like this. So time equals 0, you see that the fun of precision, everything's 300. This is just numerical precision here, but our initial condition worked as we would expect. And we're gonna go ahead and march through in time. We're gonna watch that front move along, and we're actually gonna get to steady state, or somewhat of a steady state as we would expect, with 10 time steps, which I don't know if it was on purpose, but if it was, whoever picked 10 time steps did a good job. Any questions about that simple transient run while I'm here and while I'm shifting things around? Nope. Okay, perfect. Okay, we're going to go ahead and shift back to the slides. Now, we're also going to do a run and show the creation of a separate boundary condition than the Dirichlet boundary conditions that we've been using everywhere. And we're going to go ahead and model the output or the exiting condition as a no BC boundary condition, which is in this paper that we discussed here. And you can see the boundary term here. And we need to implement this next. But with that, we're going to go ahead and do a quick dive into the boundary condition system, because at this point we've only used Dirichlet boundary conditions. So we want to give a nice overview of what the basic boundary condition types are in Moose, and of course how to use that to your advantage and build additional objects, which we will end up doing for that no BC boundary condition. So with that, boundary conditions, of course, compute a residual on boundaries, or also internal slides if you so want them to. There are two flavors of boundary condition objects: nodal boundary condition objects and integrated boundary condition objects. So integrated boundary conditions, as you would expect by the name, are integrated over a boundary or internal side, and should inherit from 80 integrated BC or integrated BC, depending on your flavor. the structure for these is very similar to kernels because you're doing an integration. So to preserve consistency, you will also override things like compute QP residual or pre-compute QP residual, which are per usual residual contributions at a quadrature point, which is exactly what you need to do when you integrate along something. Now, 80 integrated, that's some good spelling. The members that we have available in these 80 integrated boundary condition objects, in addition to integrated boundary condition, depending on if you're using 80 or not, we have the standard U and grad U, which are the value and gradient of the variable, just like you do in kernels. You have test, you have the gradient of the test function, just like you do in kernels. Same thing with phi and grad phi. And also the same thing with I, j, and quadrature point, where you have the index of the test function, the trial functions, and the quadrature points. Other things that don't exist in kernel objects that are a little different, you have normals because you need to sometimes know the outward normal for certain boundary conditions. You have the ID of the boundary you're on. And you also have, in addition to the current element that you're working on, the current side that you're working on, which is the side on the boundary that you're working on at the moment. Now, non-integrated BCs are boundary conditions that set the residual directly on a boundary. And these are nodal boundary conditions. And again, to preserve consistency, we still use this compute QP residual form. Now, object members on nodal BCs and 80 nodal BCs. Of course, you have the value of the variable you're operating on, underscore QP, which again, remember for consistency, all the nodal objects we have, we still use underscore QP for consistency, but in this context, underscore QP will always be 0. And it's just to allow for consistency between all the interfaces. You'll also have the boundary ID the node is on, and you'll have a pointer to the actual node that you're operating on for nodal boundary conditions. Standard Dirichlet BCs, which we've been using the whole time, are of course just setting a value on a boundary, and those exist as Dirichlet BC and 80 Dirichlet BC. What this boundary condition object actually looks like is, so we inherit from Dirichlet BC base, and of course, I'm going to go ahead and we need to override a compute QP value, which will actually produce the value at that point. And of course, this value option is an input parameter that will allow the user to set the value appropriately. And it's const, of course, because the user provides it, and it's a reference so that other objects in the future could possibly change that value using the control system, which may be discussed later today. So for Dirichlet boundary condition, like I said, we will ask the user for a value for the boundary condition. As I discussed the control system, this declare controllable basically tells the control system that this value can be controlled by it. Now we will grab that parameter, so now we have a value, and compute QP value will simply return that value, and that is the value we want to oppose to the quadrature point. Integrated boundary conditions, as we discussed, are actually integrated over faces. In the case here, we have the Neumann, or no, we don't have the Neumann boundary. We have the general form. And of course, if we have this condition right here, the boundary integral is 0, and we end up with the natural boundary condition. But this is just here to show that we end up having a integration along the boundary in this form for integrated boundary conditions. Neumann boundary condition, we'll go ahead and show the source for that really quickly. So as I said, these objects, per usual, we have the normal syntax, pragma wants, have some input parameters, we inherit from some object, we have static input parameters, we have a constructor that takes those parameters. So at this point, you should pretty much be looking for, okay, what is different down and protected? In most cases are the things we're doing today, because that's where most of our overrides are going to happen. In this case, we're going to go ahead and override compute QP residual. Like I said, we're keeping that in order to have some kind of consistency between objects. So compute QP residual is pretty common for residual contributions at a quadrature point. And again, we're going to have a user parameter called value so they can set the value for this Neumann boundary condition. Just as we did in the Dirichlet boundary condition, we're going to ask the user for a value. We're going to default that value to 0. We're going to say that value is controllable so the control system can use it. We're going to add a class description just for the sake of all kinds of different syntax use. Just as we did in Dirichlet boundary condition, we're going to go ahead and grab that user inputted value. And with an Neumann boundary condition, we end up having the test function times the value that the user provided. And this is the most basic you can find. Any questions so far? No, I'm going a little fast. If that's an issue, please let me know. And lastly, we also support periodic boundary conditions that work in all dimensions with mesh adaptivity. We can restrict them to specific value or variables, and they also support arbitrary translation vectors for defining periodicity. And we won't be using any periodic boundary conditions in these examples, but we just wanted to make aware that they are available. Okay, with that, if you recall, our preface to discussing the boundary condition system was to add a no BC boundary condition on the outflow for our pipe. So now that we have that information, we're going to go ahead and work on implementing that boundary condition. So this is the boundary condition that we need and that we will be implementing. Of course, in the notation we have here, this is integration over the surface. And the normal here, of course, is the outward normal on said surface. We have a material property and our standard variable and test. And now we're going to go ahead and work on that outflow condition. So the base class for an integrated boundary condition, which is what this is, that we integrate along quadrature points in the boundary, is with AD, is an AD integrated boundary condition. Have our standard valid params and constructor that you would always expect. And we must override compute QP residual in order to accumulate that integration on the boundary, which is why we're overriding this. Of course, it's of type AD real because this is an AD boundary condition, so we can have proper derivative propagation through all these values. And then we also need the material property that I talked about, which was K. So we're going to go ahead and grab a const reference, and we're going to store some material property in thermal conductivity, which is what we need. Into the source file. Input parameters, the main difference is here, of course, per usual, we will grab the input parameters from the class we inherit from, which is AD integrated BC, which will contain all the information for variable equals and which boundaries to apply to and so on. And we're just going to go ahead and add a description. At this point, we actually don't give the user an option to name thermal conductivity or to give the name of the material property. And by that, I mean, we're assigning the material property thermal conductivity with something that has the name thermal conductivity, which means that whenever we create this object, we need to make sure that we define a material property that is titled thermal conductivity. We'll continue into how to actually compute the contribution, which of course occurs in compute QP residual. So if we look back at this form, let's see, yep. So we have K times the gradient of our variable we're operating on times the normal times the test function. So if we come down to the residual, we see that. We see the test function here multiplied by the conductivity, the gradient of U, which is in our case the temperature. Remember that grad U is simply the variable this kernel is acting on. So keep that in mind, because in our context, this is the temperature, the gradient of temperature, and of course times the normal. And all of these are indexed in a quadrature point as you'd expect, and we all have the proper AD values so that we can propagate derivatives with this object. With that, I'll continue on to actually using this object. Our mesh is unchanged, our variables are the same, we still have the same initial condition of 300. We have the same two kernels. We have the time derivative term and the heat conduction term. Now what varies in this input is primarily this outlet boundary condition. Now instead, we're going to apply our newly created heat conduction outflow object on the variable temperature at the right boundary. And if you remember, this heat conduction outflow needed a material property called thermal underscore conductivity. And luckily, we've already created an AD material with that name and given it a value. Otherwise, we're using the same problem, same execution or same 10 time steps, and we're going to use standard output. So with that, we're going to go ahead and run this really quickly. Make sure the boundary condition looks like we would expect it to be. So we've already made in step 5 heat conduction, and we're in the problems directory. So we're going to go back. We're going to grab that executable. We're going to run step 5 C outflow.i. All right, we see the same 10 time steps that we expected to run. Not really too much more information here compared to what we had previously. So we're going to go ahead and open that input file and see what it looks like. Step 5C outflow is the input file name. And as I will keep hammering down, the default output is suffixed with _out and the file type. So we're going to go ahead and open that. I'm going to switch over to pair view. And instead here, I'm just going to jump straight to showing a line plot. Oops. Oh man, now you guys get to watch me struggle with pair view. Nope. Delete on temperature. Go ahead and set this to 0. We're going to look at a line plot along the bottom of it. See our same temperature profile at the beginning of a constant 300 that we would expect. We're going to step through in time, and we're going to watch this front propagate. Right, and then now we deal with that. We see that no BC on the right that we would expect, that outflow condition, where now we actually have the front propagating, and these values won't change at all until the front reaches the end of the pipe. So our boundary condition works. I'm going to go ahead and close out of this. Any questions there while I'm fixing things around again? Feel free. All right, now for the bread and butter of Moose, the coupling of variables. So if you remember correctly in our problem statement, what we've implemented thus far is we have a Darcy pressure kernel for this term right here. We are using AD heat conduction for the heat conduction term here, and we're using AD heat conduction derivative for the time kernel. Now at this point, that we don't have any coupled equations. Without this term right here, both of these equations are independent. So we're going to go ahead and add in the coupling, where epsilon is a porosity, u is the magnitude of the velocity. In this case, we're using I'll get there in a second, and t is our temperature variable. So like we said here, we've created all these objects, and we're only missing this. So we're going to create an object called Darcy advection for this. And what's really important to note here is that we have multiple variables. We have u, which will actually come from the pressure. And for the question that was discussed here previously, we have an aux kernel that will actually define the velocity for us right now in terms of the pressure. But we're not going to use that aux kernel because it'll introduce, it won't be implicit in nature. We have a direct definition for what u is in terms of other variables. So when we create this Darcy advection term, we're going to actually substitute in u for what we know it to be exactly in terms of these variables. And with this, we also need a much more sophisticated material object in order to get the effective properties for epsilon and u, basically, which include things like densities and porosities, and I'll go into that here. Actually, I have another slide ready for that moment, hopefully. Problem statement? Yeah, here we go. So now we need to define these properties in terms of, we have fluid properties, we have solid properties, and we need to define these effective properties for the region. And what's really interesting to note is that these are all going to be super nonlinear, not super nonlinear, these are going to be nonlinear. And we're also going to make them be dependent on temperature, or allow them to be dependent on temperature. So we need to define all these new properties. We need to define K, C, and rho for each of the different material types at this point. Let's see, where was I? Oh yeah, I was right here. Okay, so first we're going to work on the Darcy advection kernel itself. We're going to talk about the material properties in a second. So I'm going to scoot back up here and see really quickly. So we need a definition for these properties for this property, u is going to be the superficial velocity, and we need the gradient of temperature. So in the header, let's see what kind of additional information we need. Of course, we need to override pre-compute QP residual to actually do the computation. We need the pressure, we need the gradient of the pressure, and then we need all of these material properties in order to properly compute the C times the porosity times the superficial velocity. And remember, these are effective properties in the fact that they are a linear combination of the properties from the fluid and the solid in this kind of context. So in our material, not only do we need this information, but we also need to be able to define these quantities for the specific states, solid and liquid in this case. So our Darcy advection kernel is going to inherit from AD kernel value. We're going to grab all the necessary parameters from that. And we also need to add in another coupled variable. If you recall back to how we got the pressure in the variable aux kernel, which created the velocity field, it's the same kind of syntax. Add required meaning if the user doesn't provide this, we're going to get an error. And we're going to add a coupled variable. So we're going to grab the value of whatever variable the user sets pressure equals as. Excuse me, the gradient. If we come down here to the constructor, we actually need the gradient of pressure. This is simply asking for variable name. So we're going to go ahead and grab the AD coupled gradient. So the AD compatible gradient value of whatever the user provides as pressure. And we're going to grab all the material properties that we're going to define in a moment: permeability, porosity, viscosity, density, and specific heat. Now, when we come here to actually compute this, in the context of the problem we had earlier, the superficial velocity represents u, so the magnitude of the velocity, which is going to include these properties. And you see here what I was discussing earlier about how we computed the velocity using the pressure field. Well, that is this computation right here. So we actually did the same computation in an aux kernel. But in this case, we're not going to use the aux variable value of velocity, because those values, that would not be computed implicitly here. Those aux variable values are computed at the beginning or the end or at various times. We're not actually computing those implicitly if we use those here. So we're going to grab the current properties, the current pressure gradient, and use them to compute u. And then we're going to get the superficial velocity, of course, by multiplying by the porosity. And then, so the superficial velocity here, of course, is the porosity times the velocity. We have the gradient of temperature involved, and then we have big C in terms of the density times specific heat. And these are all at quadrature points. It's important to note they can all be spatially dependent. And even more importantly, we propagate all of the derivative information through them. All of these are AD reals or AD vector values, which is why we return an AD real here, and we use their raw formats here, so that we can propagate all the derivative information through the system. Any questions there? I know that's kind of a big one. Okay. Now for the bigger thing.
Morgan, sorry to stop you, but
Yeah.
You have a good question in the question box saying, can you please point out the differences between heat outflow BCs and Neumann BCs?
Heat outflow BC. Where did we use heat outflow BC? Someone else want to jump in on that? I'm at a stuck point right now. If anyone else has it quicker than I do, please let me know.
Yeah, he's just talking about the one that you showed up there, the heat conduction outflow.
Yeah. So
and the difference is, rather than setting the quantity for that surface integral, you're actually computing that gradient term.
Yeah, where did we actually discuss what? Yeah, it's this.
That guy.
Right? Yeah.
So yeah, right there in that boundary term, negative k grad t dot n.
This is the boundary condition instead of the standard Neumann boundary condition.
So yeah, rather than replacing that k grad t dot n with a known quantity, that's the Neumann boundary condition, we're actually just going to let that integral, be part of the residual statement, and that integral needs to be satisfied on the boundary.
Correct.
So you're actually just computing that term. Now the physics and what that means physically behind that, I'm not a good expert on it, but I think it's pretty common in fluid flow problems. Alex, I don't know if he's listening. He might have a comment on that, but that's the difference.
Thanks. I thought it might be useful for that to be stated.
Yes, thank you. And there was another question I saw on there about operator splitting. In this context, everything is solved fully implicitly. So there's different ways you can do operator splitting in Moose, including grabbing older values or setting things as explicit. But operator splitting is available. In this context, everything is fully implicit. And that is something that I noted here as well, that, for example, this computation of the velocity is fully implicit, as in we're using the most up-to-date value.
The multi-app system also allows you to solve different physics with different
Correct.
settings if you wanted to do that.
Yep, you can do different operation orders if you so desire, grab older values. There's lots of options. If you have a question about how to, solve something in a specific order with different physics, please, that's a great question for us at a later date. We're going to revert back now to our packed column material, which now we need a lot of extra properties for both fluid and solid. And we're also going to add in temperature dependence on these properties if possible. And we're also going to correctly propagate the derivatives from any temperature dependence. So at this point, previously we had a radius and a porosity input. Now we're going to add a bunch more stuff. So in order to add in temperature dependence, this material property needs to know about the temperature. So this is a coupled value to the current temperature available for the material property, or will be whenever we define it in the constructor. We're also going to introduce an interpolation, permeability interpolation was already there. We're now going to introduce all of the different parameters for both the fluid and the solid, which include viscosity, thermal conductivity, density, and specific heat. Now, the listing for all of these is the same up to this point. So I'm just going to go ahead and discuss one of these of the 4 properties for each kind of state. First of all, we're going to have a use property interp, which is simply a Boolean that says, are we going to use an interpolated value, as in something that depends on temperature, or are we just going to use a constant value given? The constant real in this case is going to be the said value. And then for 80 linear interpolation, we're going to create an interpolation object for each material property that will allow us to essentially provide a list of CSV comma separated values for a value for the property and a temperature. So from that point, we're going to have a set of properties, a set of values for each property and temperatures that we can interpolate on depending on whatever temperature is at the time this is computed. So with this simple subset, what we get for the fluid viscosity, for example, is the ability to pass in a known set of values, interpolate them from whatever the current temperature is where the property is being evaluated, and also propagate properly the derivatives from that using the AD linear interpolation. So this is a really powerful thing.
I'm gonna add to what you said. You said it fine, but I just want to knock it home. So that first Boolean, that's going to be a flag, and that flag is going to tell this material, should I use a constant value, which is that real thing, fluid underscore mu, or should I use basically a table lookup like Logan said? And so that is getting some flexibility into this this material object to do one of those 2 options, and it does that same switch for every single property for both the fluid and the solid. So this adds quite a bit of, adds a lot of complexity to what we're doing, but it also is, adding, a lot of realism to this. So the data that we use for these interpolation functions is, looked up off of the web.
Yeah,
for,
and while I'm also at that, I will go ahead and switch really quickly to show you guys what some of that looks like. So in the problems, in the step 5 heat conduction, step 6, we're on step 6, right? I think we're on step 6, I hope we are. If I'm not, someone can tell me that we're not. Problems. Okay, so in step 6 heat conduction problems, there's a data folder. And we keep talking about all this interpolation that we can have. Well, we have interpolated values for all of these different properties. So for example, water density.csv is simply a listing of temperatures and density that we can interpolate between. So by providing these CSVs, we introduce temperature dependence, and even cooler, we also still get derivative information from interpolation. So this is really powerful in a really simple method, and like Andrew said, it introduces a lot of complexity, but also a lot of realism to simulations, and can be done in a somewhat reasonable sense. Okay, I'm going to switch back to packed column. So we've now discussed that this is a flag for a specific property, if we're going to use interpolation or not. We've discussed that this is the constant value if we do not use an interpolation, and we discussed that this is how we get the interpolation if we are interpolating. Now with that, remember that these are properties for the specific states. Now, our kernels will only see an effective property, which is, this viscosity, thermal conductivity, and so on, which is computed as such here as a combination of the fluid and solid state properties, which is why we're doing extra computation here, but we're actually only showing to other objects these effective properties, which is why we're defining all of them. They're standard AD material properties that are real. They're a single value, and they include, temperature dependence and also porosity dependence. With that, we'll continue on to this packed column source file. It's definitely gotten a little more complicated. Up front, in order to do any of this interpolation with temperature, we need to get the temperature value. So first thing the user needs to find is, hey, give me some type of definition for the temperature, which is the variable for the temperature field. With that, we will now add in, I'm going to focus on only one subset of these, because if you see here, this section and this section, they're quite similar. They're just for a different property. So for each one of these fluid and solid properties, the first thing we're going to ask for is a constant value in case the user does not want to use interpolation. So for example, here we have the fluid viscosity, and we're going to give a default. And note that these aren't required. So by default, we're going to have a value of this for the fluid viscosity. And we're also going to provide a file name which contains the comma separate, which is the comma separated value for to interpolate this property. So we're going to add a parameter that is a file name. The fact that we make this a file name allows the system to also make sure up front that it actually is a file without having to run and get further down in the run. So for each one of these properties, we're going to provide a default constant value, and then also a file name that is optional if the user so decides to provide interpolation or values to interpolate on instead. Now that is done for all of those fluid and solid properties. So we have that for the viscosity, the thermal conductivity, the density, and the specific heat for the fluid, and then all of the same for the solid. Well, except for except for the viscosity, because solids and viscosities are pretty well defined. So at this point, we're going to get into the constructor. So input radius and porosity were something that has been defined before. Recall that we need a temperature value. So we're going to store in temperature the coupled value of the temperature variable. Now, all of these values are the user defined constant values for these properties if they define them. So these are going to get a default value by default they're going to get a default value if the user does not provide them. So these are going to be filled regardless. The user can of course change them if they so desire by the method of fluid viscosity equals fluid thermal conductivity equals, and so on. And then lastly, we need to actually define the material properties that this object is producing. So these are the properties that the kernels are going to actually use. And if you remember in the past, we had permeability, porosity, and now we're also adding some more properties here that are going to be used in the kernels. And that's what these properties are here. And they're all AD material properties of just a single real scalar value. Now we get into a little more complexity. So this was already here, so I'm not going to discuss that. Everything down here is quite new. So if you remember correctly, these use underscore something underscore interp are flags for if you want to use the interpolation or not. That is, it's a flag for use the real constant value or actually interpolate based on some CSV file. Now, this init input data function, what it does is it checks if the user has provided a file or not. And if it has found a file, it will properly set up the interpolation using that file. And what it returns is if it has actually used an interpolation or not. So essentially, what all of this init input data will do, it will set up the interpolation for a property if the file exists, and otherwise it will do nothing. And it will return if it had created that or not, which means that this flag will be set with, hey, do I want to use the interpolation for this property or not? So if, for example, use fluid mu interp is false, that means that I will just grab the value. I want to use the fluid mu value, which is the constant value the user has provided, or the default value if none has been provided. Otherwise, if this value is true, it means that I should be using the interpolation located in field mu interp or fluid mu interpolation. And that is done for all of those properties. Andrew, if you want to jump in at any time, also feel free to interrupt.
No, you're doing great. I guess the only thing I might add is that init input data is a function that this class.
Yeah,
it's
yeah.
I
was going to have it at the bottom. I'll jump to that right now. So
you probably don't need to go through it in great detail.
Yeah, that's kind of what okay.
So just know that if you want to get more, you can go look at it.
That function exists down here, but for the sake of simplicity, I'm just going to describe that it either sets up an interpolation or does not, and also returns a bool saying use the interpolation or don't. With that, we're actually going to get to the calculation. Permeability, temperature, or permeability and porosity were there before. Something new is that we actually need the temperature value, and we're doing this all in terms of Celsius because all of our information is provided in terms of Celsius. So we're going to go ahead and take the temperature at the quadrature point we're evaluating. We're going to subtract it, and we're going to convert it into Celsius. So now we have a new temperature that is in Celsius. And the reason why is that if we interpolate anything, we need to interpolate it using the correct units. So with that, we're going to come down here to the fluid properties. Okay. So for starters, we'll start with the velocity or viscosity, right? Which only applies to the fluid. So we're going to set the viscosity, and this is a conditional statement in C++, which means that if this evaluates to true, go ahead and set this equal to the statement before the colon. If use fluid mu interp evaluates to false, go ahead and set it to fluid mu. So what we get out of this is we're setting the viscosity based on whether or not we need to interpolate it or not. So if we do need to interpolate it, we will grab the interpolation and sample it at the temperature that we need. Otherwise, just use the default or use the constant value, which is stored in fluid mu. Now that is done for everything down here that follows. It's the same kind of syntax where if you interpolate, grab the interpolation and sample that value at the temperature, otherwise use the constant value. The reason why viscosity is different from all of these is because the remaining properties are a linear combination of the fluid properties and the solid properties. So first we define the fluid properties that are separate from viscosity and the solid properties. And then we create an effective thermal conductivity, effective density, and effective specific heat using the combination of those and the porosity. That was a lot to swallow. What's important to note here, the general takeaway is that our properties are now temperature dependent, porosity dependent, and are nonlinear if you so desire to make them as such.
So Logan, one thing I want to add here is something that was mentioned yesterday by Andrew. One of the things that this piece of code in particular shows is that you're writing real C++. So in a lot of these examples, the properties are so simple, the PDEs are so simple that it might not even look like we're doing much programming at all. But in this one, you can really see that we can run any C++ that we want to in here. We could call out to a third-party function. We could call some Fortran code. We could read something from a file. We could do anything you want to here in compute QP properties. And it's built that way on purpose because we need ultimate flexibility for computing these material properties. So I just want to use this as a chance to highlight that, that you can write complicated C++ in here. So.
Yes. And are there any questions on this? Because this, like I said, is definitely significantly more than we had before. So if there's any, feel free to also raise your hand or ask and jump in. We're glad to answer more on this. But like I said, the general takeaway is that now we are able to get all of these properties. They are temperature dependent if the user wants them to be. They're porosity dependent and all of that. So we're introducing a lot of nonlinearity to the problem. And what's even cooler is that all of the derivatives propagate properly through this system. So you don't have to think about Jacobians or derivatives or any of that for your materials. They also propagate as they should, with a bit of an overhead, but with much more simplicity. Heat conduction outflow. Okay, I gotta remember what this is really quick. Okay. Yes. Okay. So our heat conduction boundary condition. Wait. Yeah, our heat conduction boundary condition has now changed. Actually, no, it has not. I don't know why this is listed in there. If anyone, I'm going to skip through this unless one of the Moose folks tells me that I shouldn't, because I believe we've already gone over this.
I think with our old AD system, it had a change, but I think now it doesn't.
Cool.
These probably need to go away.
Good. That's what I like to hear. Okay, so what have we done now? We've now added the coupled term in the form of Darcy advection kernel, and we've modified our packed column material to account for all the new properties that we need to produce those values. So what's new here? First of all, mesh hasn't changed. Really important change. Pressure and temperature variables now exist at the same time. Previously, we were only solving for one of the variables, but now we need both. We're solving a coupled system that involves a pressure and a temperature. Something to note here, the pressure initial condition is not listed, and by default would then be 0. And the temperature initial condition, again, is still 300. We have included our velocity aux variable just to be able to, like we said, show the velocity in output. We're not actually using this velocity all in the coupled kernel because we are computing the actual velocity fully implicitly in the kernel. So with that, our complicated system of coupled equations is really reduced down to only a few kernels in this simple language. We have, and this is also something important to note, is that now you can really see where the variable equals component for a kernel really matters. The Darcy pressure kernel, for example, operates on pressure. The heat conduction kernel operates on temperature. The heat conduction time derivative kernel operates on temperature. And now we have a heat convection kernel. Now, this term actually contributes to the temperature equation. It's something you need to make sure that you're aware of here, because we have two variables going on here. So this kernel contributes to the temperature equation, but uses a value of pressure. So that's why the primary variable in this is temperature, because this denotes, what U is in the kernel and what residual it contributes to. In terms of aux kernels, we're still using Darcy velocity so that we can output the velocity just for visualization. There's one question here about why there is no file name in the input file for the material data. We will get there in a second. We do not use the temperature dependence in this example, but remember that if a file name is not given in that packed column material, it will default to the constant values that are given in the input file, which are the same as what we defined them to be in the beginning of the problem. So I'm going to go ahead and mark that as answered. In terms of boundary conditions, now you see what it's like to have boundary conditions for multiple variable equation or multiple variable systems. So we have a Dirichlet boundary condition on the inlet and outlet pressure of 400 and 0 respectively. And again, remember, variable equals shows what these objects act on. And it's important when you have multiple variables in the system to make sure that you're aware of the fact that everything's contributing to the right equation. And then now we actually have a inlet temperature that is function dependent. So before, this used to be a Dirichlet BC. So a lot of the objects in Moose have function, not function components, but other function objects. And in this case, a function Dirichlet BC is a Dirichlet BC that accepts a function as the value. So here you see we're actually using a parsed function as that function, and you can use standard statements using this parsed function syntax that's available from another package. In this case, if the time is less than 0, or the inlet temperature is going to be 350 plus 50 times the time. After time equals 0, we're going to go ahead and set that temperature to 350. And this is a really cool way to easily change things in input syntax without even needing to write code when you have simple examples like this. And the outlet temperature, we're going to use that outflow object that we discussed and created previously, the no BC BC, which is the more natural way to do it. Apply to the right side. I'll answer that in a second, Derek. In terms of materials, not much has actually changed here, except for the fact that we've now supplied a temperature. Remember that we now have all these inputs for all the fluid properties and solid properties, and optionally the fluid property file names if you want to interpolate, and the solid property file names. But because none of those are chosen, there are default constant values for all of those properties, which is why a packed column now only has a temperature, which we've required it to have. Now, interestingly, because we're not interpolating on temperature, we're not actually using this, but we've made it a required parameter because we didn't add any extra error checking, and just for simplicity, so that it is always available. Problem type has not changed at all. Executioner has changed. Something important to note here is this automatic scaling parameter. We are about to hit a break, but I will discuss briefly that automatic scaling is it is what it says. It automatically scales different variables to improve solves essentially, and I'll discuss that more in a second. But I wanted to note this is really important for a problem like this. When you have physics that are on different physical scales, you can really improve your solving techniques, or maybe go from not being able to solve something to solve something by enabling something like automatic scaling. That's this new functionality that's really, really important for this kind of problem. Lastly, before we go to break, I'll discuss the time stepper that we've included in here. Note that we're starting time at -1, and we're continuing on with 100 time steps with a time step of 0.25. So I think that the reason why we started with -1 was so that we would allow these time steps to be smaller in the beginning. So this dt equals 0.25 is actually not even used.
I'll jump in. I'll explain what this is doing. So if you remember Derek's talk yesterday about the Newton's method and things like that, and how important it is that your initial condition satisfies your differential equations. That's what all this time stepping stuff is doing. We're basically initially, like the boundary conditions are set such that, and then we slowly ramp up the temperature on one side so that we don't get too far away as we're solving these equations from reality. Because like in reality, changing the temperature from 300 to 350 instantly in a boundary is not a thing. You can't do that. So
It's not natural.
This is a numerical thing that we're doing to try to help our solver out.
Yep. Then lastly, we're gonna let this run until we hit some steady state, or if 100 time steps isn't enough, we'll just end at 100 time steps. Well, I'll preface with where we were before we ended, in which we were discussing automatic scaling and its importance. We figured it was probably a good time for Alex to come in on this, as he's the one that created the system. So with that, I'm going to continue on to the next slide and pass it over to him.
So I guess this is our first use of automatic scaling in the tutorial. And we'll show why on the next slide. But in multiphysics simulations, in real multiphysics simulations where you can have coefficients of dramatically different scales, it can be very difficult for a monolithic solver to try to converge all those variables well simultaneously when they're on those dramatically different scales. So we often saw, particularly in the case of PGFNK, but this can also happen for Newton as well, especially pending the choice of finite differencing parameter. When you perform your linear solve, you might get a very good update for one variable, probably the variable whose residuals dominate, and not a good update for another one. And so if you're not scaling your system well, you may be solving one of your problems very well while, say, like you may solve temperature very well with 1 Newton update, but perhaps you didn't converge the pressure variable very well. And so what automatic scaling tries to do is it tries to alleviate that problem by trying to scale different physics to be on the same order for both your residual and Jacobians. So Logan, you can go to the next slide. So this is, here we are in our tutorial. We're doing just a 2 variable problem at this point, only 2 sets of physics, and we're already running into scaling issues here. So if we just run step 6a coupled.i, and we use PC type SVD, which is a singular value decomposition, a preconditioner that PETC provides, it will actually show us a value for the condition number of the matrix. And if we run this net,
can we just go have you do this? Is that too much to ask? I think it's useful to see this stuff run.
I can also, I have it up if you want me to run it. I can do that too.
Sure. Yeah, I'd have to go compile step 6.
Yeah, that's fine. That's fine.
I was just testing you, Alex, see how ready you were.
All right. Well,
I've got step 9 ready to go, but not step 6.
Dual user problem. Okay. So like we have in the slides, we're going to go ahead and run this. We have step 6a coupled. I believe in the slides, using the command line input, we also refine the mesh a little bit. So we're going to say we're going to have 50 elements in the x direction. Maybe we didn't.
You need a .i there after step 6a coupled.
Oh, yep, that I do. I was just testing you. And y equals 3. Now, it was a transient problem, but we're just going to go ahead and run it with 1 time step. So num step equals 1. And more importantly, there is an automatic scaling. There is an automatic scaling parameter that we're going to set to false. So we're going to show what it's like without automatic scaling. And then what Alex was talking about, if you want to talk about the preconditioner part, I'll start typing.
Yeah, so usually what you would do is maybe you try to solve a problem and maybe the linear solves look really bad or the nonlinear solve looks really bad. Especially if the linear solve looks poor, almost the first thing I always try is to try with PC type SVD and inspect the condition number of the matrix. In an ideal world, of course, it should be 1, but in general, we're never going to get there.
Okay, let's
what happened? How did we get all that?
That was KSP view PMAT.
Okay.
Yeah. This is the important content.
Okay, so the condition number here looks a little better than what we had on the slide, but it's still not great. 3e to the 12, that leaves us about 4 digits in double precision to work with, which isn't ideal.
Hey, Alex, can you rehash what the condition number means?
So Wikipedia has a pretty good explanation of what condition number is, but in general, it's a measure of how well conditioned your linear system is. If it's perfectly conditioned, essentially like the identity matrix, it'll have a condition number of 1. And that kind of matrix is very easy to solve with an iterative method. With a condition number of 1, it should just take 1 iteration to solve. But as that condition number gets higher and higher, an iterative preconditioner will have a tougher and tougher time solving the linear system. So we want to do our best to get that condition number close to unity, as close to unity as possible. So now if we try turning on automatic scaling and running, we might as well turn off the KSP view PMAT.
Yeah, we'll make it look a little more reasonable.
Yeah. And run that.
I think you possibly want to mention the condition number can be computed by using largest eigenvalue and a smaller eigenvalue.
Actually, here, I'm going to go ahead. I'm going to rerun that. Take out that. There we go. Now we have the two choices.
Yeah, so you can see that just by toggling on automatic scaling in Moose, we drop that condition number by 9 orders of magnitude.
Yeah.
And so we have way more digits of precision to work with now than we did previously. And this is especially relevant for PGFNK. Having a well-conditioned system really helps with picking a differencing parameter. But as I'll show later in step 9, it can still matter for Newton as well. And so we recommend that you try to be aware of the conditioning of your linear system. If you see a poor linear solve, it may be because you have a poor condition number. And we recommend, trying to use automatic scaling, or at least doing some manual scaling if you know the scales of your physics. But I'd say by default, try with automatic scaling equals true when you're setting up your applications and running your input files.
All right.
This was kind of a basic example. This problem may have been able to solve even with that poor condition number, but I'll show you in step 9 that if you run without automatic scaling with like a default PC type, you'll actually never converge. And then if you run with automatic scaling, it runs very well. And so we'll show that when we bring in tensor mechanics and have introduce another set of physics into our tutorial.
Great, thank you, Alex. What I'm gonna do at this point is continue on to actually running this problem and showing some results from it, and then we're gonna jump on to mesh adaptivity with Andrew. So, I don't know why I switched to that. We're gonna go run this problem anyway. Clear that. So we're gonna go ahead and run this problem with its standard type. Now we do have 100 time steps here, so we're gonna have a little bit of chatting time. Or I think some 400 time steps. This takes about 1.5 minutes. So if you remember correctly, we'll scroll back up to the input while I'm letting this run in the background, and I'll switch back over once it's done running. We did set this up to have an end time of 100 with the original time steps of 0.1 seconds and the later time steps of 0.25. So we have some 400 and something iterations, I believe. But while that's running, I will skip ahead to an easier to show result before I show the live result. In the case of we have temperature on the top and pressure on the bottom. And if anyone wants to comment on the physics of this too, this is not exactly my specialty, and I'm sure Andrew has plenty of fun stuff to say about this as well. But I will show a line plot in a second once I actually finish running the problem. But of course here you see our couple of variables, both temperature and pressure, kind of the whole purpose of this problem itself. Andrew, is there stuff you want to say on this?
No, that's fine. It's
okay.
Still a relatively simple problem now, but we have.
We're gonna run it this while we're gonna show this output be nice and laggy. If anyone has any questions too while this is running, feel free. We should be good pretty soon. Trying to look around at everything. Okay, well, we're done. Perfect. Okay, so we're gonna go ahead and open that up. Now, something fun to watch here is we actually outputted this at every time step. So if we list this, hold on, where's our output? I guess it all punched it together. Okay.
This isn't adaptivity yet. You're getting ahead of yourself.
That's right. Yeah, I am. Same mesh. So we're gonna go ahead and open 6A coupled out. If I can spell and type, out. Again, reminder that all output is suffixed with _out by default. That's going to open it up in pair view for me, so we're going to switch over to pair view. Now we have our pressure, temperature, and velocity fields available for visualization. So we're going to go ahead and start with one of those. And like I said, I prefer in cases like this, especially where we actually have some symmetry, to just go ahead and plot it by line because it makes it a little clearer. Oh geez, let's not do that. So we're going to go ahead and show both of these on the same plot. I'm going to close out of this, and we're going to look at this as it actually ran. Right. So we see our front slowly moving along in the temperature field. In time, we're about 30-some seconds in. And due to the physics that we have in here, we still have the same most linear pressure that we would expect. And that is the simplicity of this coupled problem. Andrew, do you have any comments?
No, it's great.
Yeah. So it's what we'd expect. And with that, I will switch back to this, and I believe I'm about to pass things on to Andrew to discuss mesh adaptivity. Oh no, we have a prettier case. That's right. Okay, so we're also going to change something. We're going to vary the inlet. Go ahead, Derek.
I want to point out that, I mean, this is the first time we've done any multiphysics, right?
Yeah, true. I know.
I'm sure all of you here are here because
right?
you want to do multiphysics, right? And we finally got there midway through the morning on the second day here. But as you see with Logan just moving on here, it's almost
second nature for us now, right?
Almost second nature. It's not anything. It's not anything special in the Moose world. It's a straightforward application of all the systems and the coupling calls and everything else that we've been showing you for the last 2 days. So multiphysics to Moose isn't a special case or anything like that. It's just something you put in the input file and something you do with your kernels. So
like it was developed.
Hopefully everybody was paying attention. All right, that's all I had.
And 6b here, we're going to kind of introduce some fun periodicity to the problem, and that we're going to introduce a sine function and a cosine function in the inlet pressure, so we don't just have the same Dirichlet constant values on the edge. And remember, this is really cool in that now these properties all also depend on temperature, or can potentially depend on temperature. So we're going to introduce temperature dependence as well with these.
Logan, switch back to your slides.
Oh, geez. Yeah, you're right. Haha. There we go. Okay, so like I said, we're going to introduce a sine and cosine function for the inlet and outlet pressure. Originally, these were just constant values. And now that these are going to be changing with time, other variables are going to be changing with time. So we can introduce the temperature dependence to the properties as well in this case, which is what we're going to do. So at this point, I'm just going to scroll quickly to what our differences are. Like I said previously, a lot of our objects can take in functions, including the Dirichlet boundary conditions. So we're going to create some parsed functions to represent that sine and cosine function. And remember that by default, all parsed functions have available to them x, y, z, and t for time, which means that these functions will get appropriately sampled at time using the variable t. So we have the inlet and outlet functions defined as we had them in the previous slide. And as I said, most of our objects have function variants, so to say, in which we can supply a function instead of a value. So this Dirichlet boundary condition is now actually will sample this function up above appropriately. And then more importantly, we're also going to introduce temperature dependent fluid properties using those CSV files, one of which I showed earlier, which is just a listing of a property value and a temperature. So we can interpolate with different temperatures all of these properties for fluids. And having these file equals define, we're now overriding the fact that we're now not using the constant default for these properties. So important takeaway, now in packed column, we are using temperature dependent interpolated properties for the fluid properties. And we also introduced something, we're using a function time stepper here, in that we're actually setting time steps so that we actually hit the peaks for those boundary conditions perfectly, just so we can capture that in this example. I'm gonna see how long this takes. I don't remember if I should run it or not. Okay, I will switch to that so we can show it really quickly, just as a reminder. Of course, load our executable, or act with our executable -i for input syntax, and go ahead and run the input file, which in this case is step 6b transient inflow.i. Something fun to note here is that you can, if you take a look at the time steps, note that of course before time equals 0 we have time steps of 0.1. If you look back on the slide, which I can't show both. So here, all the way from -1 to 0, we have 0.1, 0.1, and so on until we arrive to a time of 0, or appropriately 0. In which case now we're using the function dt so that our time specifically hits the peaks of that sine and cosine boundary condition, which is why you see time steps as such. And that's exactly what this time is here. Let's see if this can run in a reasonable amount of time. And until then, I'm going to switch back and show the pre-created picture for this input. And we can see the fun oscillatory behavior that we get from this. And mind you, all of these boundary conditions with the sine and cosine functions were really done with just a few lines changed in the input file. Didn't even require to recompile anything, especially with the objects that already exist in Moose. So that is, that can't be understated. It adds a lot of really great capability at fingertips, and prototyping even with stuff like this. It makes for a really great user experience in problems like this. And I'm actually, let me see if I can run that in the case of where it is right now, or pull up my example and show a line plot. So we're going to go back to here. I'm going to show that this is still running, but I'm going to go ahead and open that Exos file and open it as is. So we're going to tutorials, Darcy thermomech, step 6b, or step 06, problems. And we're going to open step 6b, if I can spell, transient inflow out.e. And this is really just to show you the line plot too, because it looks pretty cool. And there's also an added side effect from this, in that we're also outputting the material properties using some simple input. So we also have available to us all of those material properties also as constant monomial values. So we have basically the element average value for all of those properties, which is used primarily in visualization. So I'm going to go ahead and enable pressure and temperature, and I'm going to show those two fields in a line plot. Oh, I can reload because it just finished. Reload files. And now I'm going to set up a line plot. By the way, if anyone has any improvements for my pair view use, please email me. I need to learn. And we're going to look at that lovely oscillatory behavior back and forth and back and forth. And just to show also, I'll go ahead and add some material properties and remove some other stuff here just so you can see what that's like. We'll just add some properties to that to show, I don't know what's actually going to change, but oh yeah, specific heat is changing appropriately at the boundary as a result of that. Other cool takeaway is the fact that viewing material properties like this is great and simple and straightforward. Do you want me to show something, Andrew?
No, I was just going to add a bit of explanation to what you.
Yeah, please. Yeah, just explain the physics.
This is really cool with respect to the heat equation, because you're seeing the two forms of heat transfer, the diffusion and advection. And so the advection piece is what's, the velocity of that pipe, the fluid's going back and forth, back and forth, back and forth. So that's going to push heat forward and back, forward and back. But along those same times, the heat is diffusing, and so that's why you get this slow progression down the length of the pipe.
Yeah, which I will show just that for the sake of not having it look crazy, which is what you see here.
Yeah, so that line slowly creeping to the right overall is your diffusion, and the pumping back and forth is your advection. Well, it's a pretty cool problem. I like this. It's a good plot.
Okay. And the last thing that I'm going to discuss is, and this is kind of relevant to something that was asked earlier, was the decoupling. And I won't actually run this, but I'm going to describe what this looks like. So we're going to instead make pressure an aux variable, which means we're not directly computing it. We're computing it ahead of time, or after a time step or something like that. So now our only primary variables are temperature. Now pressure is going to be defined. Remember how we have these function versions of things. So function aux will fill an aux variable according to some function, which in this case is t times x times x times y. Remember, you can use position and time arguments in this. So something cool about this is with the kernels we had before, the coupling occurs in the heat convection, the Darcy advection object. Remember that before, pressure was a nonlinear variable and was being solved for in the other equation. But we can actually decouple that and still use the same exact objects because of the interoperability of aux variables and variables. So we can now use this approximated decoupled pressure function in our objects and just have one equation, the temperature equation. So this really highlights the interoperability of all of our variables, where you can use primary variables or aux variables. In this case, of course, now we have some approximation for the pressure. And like I said, we still use the same exact kernels. We just stopped solving for one of our equations and create an approximation for pressure. That's a really, really powerful thing that definitely deserves to be highlighted and allows for a lot of prototyping and simplicity and even creating input.
So this is a fun section as well to add capability, and we don't have to write any code anymore, and we don't do a whole lot of code writing. Kind of for the rest of the tutorial, we're just going to kind of show off other systems in Moose. And at this point, we have a fully coupled system of equations, nonlinear with based on temperature and the material properties, and all kinds of really powerful capabilities, including automatic differentiation and stuff. And now we want to step it up another notch with mesh adaptivity. So adaptivity system in Moose is just another pluggable system. You can create custom adaptivity objects if you need to, but thankfully you usually don't have to do that because some of the core ones that we provide work pretty well. And in general, we do what's called H adaptivity. That's element size, refinement, and coarsening. And we do it through two systems within adaptivity: indicators and markers. The indicators basically kind of think of them as like an aux kernel type thing, but it's a standalone system that computes some measure of error. And what that means is, pretty subjective. The error can mean anything that you want it to. And then based on that error, you would use the marker to do something with it. So if the error maybe is high, you would refine, or if the error is low, you coarsen back. And we can see that in practice here with some of the built-in systems. So usually you won't have to program anything. You can use the built-in capability, but certainly can if you really need to for your problem. So what is Moose doing for mesh refinement? When you create a Moose-based simulation, you're going to start it with some sort of mesh, maybe a generated mesh or maybe a file mesh or something else. And that's kind of, that mesh that you load in initially is going to be your level 0. And from that point, we can refine, and we do what's called self-similar refining. So if you get a square, it becomes more square, triangles, more triangles, cubes, more cubes, pyramids, more pyramids, et cetera, all the way down to whatever level you want to refine to. And you can always go refining, but you can never coarsen back past level 0. So whatever mesh you start with in your mesh block, remember that's 0, and you're never going to get coarser. So this is where we usually make the recommendation that if you're using an outside package, especially mesh for your geometry, make sure you capture your geometry really well. Other than that, you probably want to use the biggest elements you can that give you, a good quality mesh. And then you can let Moose refine from there. And even if it's in the case of uniform refinement, if you just want to get a better view or a better solution, you can refine the whole mesh as well, which we've already shown a few times now, I think. So hopefully that makes sense. So now we're jumping into the indicator system. And like I mentioned, this just produces some measure of error. Errors in quotation marks in the slide for that reason. It's not really well defined. And the four basic objects in Moose that we talk about here are the gradient jump indicator. So this is just going to look at the change in the gradient across the elements of a variable. And the flux jump indicator, the same thing, but now we're going to actually, use that physical flux quantity, so it has like a coefficient on it. And then the Laplacian is the second derivative, that same kind of change in the second derivative across elements. So you got to note that if you're going to use the Laplacian, you got to make sure you have higher order shape functions that are capturing the second derivative. So linear Lagrange wouldn't work in this case. You need to use second order Lagrange or something similar. And then analytic indicator, this is generally for testing. If you want to compare against a well-known solution, you can do that with the analytical indicator. And so that, in that case, this is probably a proper measure of error, where these others are maybe a proxy in some capacity. And then markers, generally speaking, we'll use an indicator, although they don't have to do something with that error. We're going to talk more about the error fraction marker, and all that's going to do is look at all the computed error and all the elements, and then sort it, and then take some fraction of the higher error and some fraction of the lower error areas, and coarsen or refining coarsen based on those bins. Another one is error tolerance marker. So if the error gets above some sort of threshold or above some sort of tolerance, coarsen it or refine it or coarsen it depending on that tolerance. And similarly, threshold, you can do the same thing if it's greater than some value. Value threshold markers where you actually look at the variable value. So this one doesn't use an indicator. It's just going to look at a variable. This might be useful for, like, if you're doing a level set type problem where you're advecting some front, and that front can have a value of 0 or 1, and you want to, just refine in that intermediate area where it's a 0.5. Uniform marker, we've actually seen this in practice. That's our uniform refinement shortcut that we've been using with mesh/uniform refine on the command line. You can create a full uniform marker object as well. Box marker is very similar, but put it in a specific region within some subset of your domain. And then combo marker will allow you to combine any number of these markers into one that you actually use. Input file syntax is pretty straightforward. We're gonna show this in practice here, but this is a pretty typical setup, and it's wrong. So I'll highlight that in a minute here. So we have some copy and paste problems. Anyway, we have an adaptivity block, and inside at the top level, you can set some kind of global adaptivity parameters. And so this first one is, initially, when you're doing an initial condition, you're going to take 2 steps. And then every time step, we're going to take 2 steps as well. The marker we're going to use is marker, that's defined here. And initial marker is also marker. So you could have a different adaptivity for during the initial condition than during the actual run if you want, and it's with these 2 parameters. This parameter is really quite important, max H level. So this is how many of those levels are we allowing our system to perform. And this is not going to let us go past 2 levels of refinement. And you probably always want to set this to something reasonable, because if you imagine if you're doing a 3D quad element and then you're doing refinement, every time you do that, you're splitting that quad element into 4 more elements, and then at every level, and so it quickly gets out of control, and you can refine your computer to death and crash your computer with memory because your mesh is just getting so big so fast with this refinement. So generally speaking, you're going to want to set this. So sorry about this mistake. This block got repeated for some reason. You only need one of these top level marks. So this is an indicator block, and we're creating an indicator object. This second bit, this is an arbitrary name. Here, well, I just did a search on my computer. And we're going to set up the gradient jump indicator to follow variable u, and then error fraction marker, same thing. This one of these lines shouldn't be here. And we're going to look at the indicator. So this indicator name here on the right-hand side matches this name here in our block above. And what this error fraction just sorts all the error from the various elements and coarse in the bottom, the lowest error elements, 10% of them, and refine the top 70% of those elements with respect to error. And we're going to go do this so with our problem.
Hey, Andrea, I wanted to mention one thing about that. You mentioned initial adaptivity, but I wanted to be clear about what that is. The initial steps here, where it says initial steps 2, what's going to happen there is we're going to project the initial conditions into the variables, and then we're going to compute the marker that is the indicators and the markers that are called out there as initial marker. And then we're going to refine the mesh based on the initial condition alone before we've done any solves. And then we're going to reproject the initial condition onto the newly refined mesh. And since we have 2 steps of that, we're going to do the process again. We'll adapt the mesh based on that initial condition now. And then after that, we'll reproject the initial condition again. So this is a really powerful capability, and it allows us to do things like Andrew was mentioning phase field simulation. If you have a starting condition that's, let's say, a value of 1 across half of your domain, and then it's a value of 0 across the other half of your domain, and you're going to have some sort of smooth interface in between those. You really want to have a lot of mesh in that area where the smooth interface is, so that you can really capture that curvature of the solution there accurately. And so this type of setup here, where you actually use a gradient jump indicator, it would tell you where that high curvature is in your initial condition and allow you to start with a really nice fine mesh right along that boundary between that 0 and 1, so that whenever you first start your first time step, you already have a really good mesh to start with, and then your mesh will continue to move with that front. So
thanks.
I just wanted to be explicit about what it does. So.
Yeah, that's a good thing to say, because we'll actually do exactly what Derek said in step 10 later today. So thanks. Okay, so now let's jump into our actual problem. So what we're going to do is, I think I'm going to go run all of these on the command line quickly. We're going to have a coarse solution. So let's look at this input file. So this is where we don't have very much mesh, and this is the same problem we've been working on. I think we take out the nonlinear variables here, if I'm correct, but let's find out. So our mesh is the same in general, but now we have far fewer elements in the x and y direction. So this is our coarse solution. We have our same pressure and temperature initial variables. We're still computing the velocity. We have all our kernels for both equations fully coupled, and the velocity calculation. And we're going back to the constant Dirichlet boundary condition. For whatever reason, we're still ramping that inlet temperature, so our solver works nicely. We have a packed column with radius 1. We're coupling in temperature, but we're using constant values here. We're not pulling in the values from the files, but we will again later on in this example. And then the problem's the same. Executioner is I think all the same. We got our tolerances, and we have our time steps set up differently for the ramping phase and the non-ramp, and then the actual solution phase. So that looks pretty good. We'll just go to the next one for now, and then we'll go run these in a minute. And then the fine solution is almost the same, except for I add this line in our mesh, uniform refine. So why did I do uniform refine versus setting these nx and y. And that's for what I said before, is you can't go coarser than your level 0. So this nx and y, that's the number of elements for level 0. And then we're going to automatically use the adaptivity system to uniform refine that mesh 3 times. And so that's going to give us our fine solution, and everything else should be the same in this input file. We can run that, and we will. And then we're going to add adaptivity. So in this step, we're going to kind of start with that fine mesh again. We're going to uniformly refine 3 up front, and then we're going to go to mesh adaptivity, which we have down here at the bottom. And at this point, we could have used what Derek just talked about and done some initial adaptivity and done those projections a few times, but this problem's small enough we can just kind of refine everything up front and let the system coarsen stuff back as it goes, and we're going to see that. So we're just going to run marker. We don't have an initial marker, so we're just going to run the error frac marker at every time step, and we're going to limit this thing to do 3 levels of refinement. And now we got proper syntax for the indicators with the full block, not a shortcut, which is fine. So our indicator is, again, this gradient jump. It's just going to change, just going to look at the change in gradient between 2 elements across the faces, and we're going to scale that error by the flux in this case. That's an option you can use for this. Sometimes that gives you some better results. And then the marker, again, same thing we talked about. Indicator, this temperature jump refers to the name given here. And then we're just going to coarsen the bottom 15% and refine the top 70% of the error on an element by element basis. And you can run and visualize. This is the kind of overall results, but we'll do it. Apparently I was already playing, I was practicing. So the top one is the automatic refinement, fine solution, coarse solution. Great, let me switch to my terminal and let's go play with these a little bit. All right, so we are in now step 7, adaptivity. You can see that here, and make sure it's compiled. And we're going to go into the problems directory. You should see, whoa, let's so don't worry about that command I run. If you're good with Git, you'll know what I did. If you're not good with Git, don't use that command because it can be dangerous. But I just wiped out every every file that's not in my Git repository from this directory. So we see all kinds of fun stuff in here. You're going to see the 3 input files we just looked at: coarse, fine, and adapt. And we'll talk about this one in a bit. And just for people to know that these videos that we have in the presentation come from these Python scripts that are in here. That's what those are, but not important for this example. So let's go run the coarse one. Let's see how long this guy takes. I think it's pretty quick. It's just, yeah, flying through. So that's well and good. And then let's look at the fine one and see what it's kind of, we can kind of look at it. Whoops. So you can see it's chunking a bit slower. So maybe you're like, oh, I need to get a better view of my solution. And so I'm going to do some refinement. Like, man, it seems kind of slow. So one solution would be we can give some MPI. I don't know if that's a good idea or not. Let's go look at the top. We talked a little bit about yesterday. So this already has 12,000 local degrees of freedom, which isn't a whole lot. We're just doing lots of time steps on this problem. So MPI, it'd probably help us a little bit, but generally, like I mentioned yesterday, that's kind of the target number of local degrees of freedoms that we want, but let's do it anyway. And maybe that's a little faster. I don't know. It's hard to say. You can keep going, and that definitely seems a little faster. But if you were actually just to plot this out and show the scaling, it wouldn't scale like you might expect. So another option to improve performance is the adaptivity. So let's go run that one, and then we'll look at it on the screen. I'll just leave the MPI. It works fine. So what you'll notice there is the first bit took a little while, right? Because that was, we had, uniform refine 3, and so it had the fine mesh, and so it took a few steps, but as it's going, it was coarsening back elements that weren't didn't have high error. And then this thing starts really to fly at that point, and it all works with MPI in parallel. And as it goes along, and you get this wider swath of refinement, it kind of slows back down a bit, because up front you only have a few elements refined, because that front we're tracking is on the boundary, and then towards the middle it's quite wide, and then actually towards the end it gets narrow again. So we can go open this in pair view. What's the name? Step C code. So yeah, I'm sorry about Peacock not working. This is actually pretty convenient to look at in Peacock with just the Peacock-R. I actually just go run it in Peacock directly, but for some reason we can't show the windows that well with it. So I encourage you guys to try Peacock out if it's of interest to you. It makes you don't have to do so much clicking. And we're going to show these two. I'm going to make this thing a little smaller, so hopefully that shows up better for you. So we've already seen this. This is our temperature front going through. Looks pretty normal. We've seen this plot lots and lots now. But let's look at our error frac. So this automatically outputs the indicators and markers. You can turn that off if for some reason you don't want it. And this is showing you the error. Let's also put the edges on. So this is a measure of error. This is where we would ask the question, why does it look non-symmetrical, right? Does the temperature front is really looks pretty symmetrical, straight line going through. And what happens is, remember we're doing a coordinate transformation. So the center of this pipe is r equals 0, the radius here, and then we're doing this axisymmetric thing, so you're kind of rotating about that x-axis. So in these error calculations, we're doing coordinate transformations along the way. So the r actually becomes a part of that error. So that's why you get this kind of maybe unexpected shape. And I think more fun to actually watch is the marker itself. Oh no, that's what I was showing. Sorry, I did it backwards. So this is the measure of error. So you can see it's kind of a continuous value in your finite element space. And then the error fraction is actually the marker. So it's value of 0, which means coarsen, value 1, do nothing, 2, refine. And so this is kind of a nice pattern to see, especially down here. You want to have areas of refinement kind of buffered by a do nothing zone, followed by a refine zone. And then you got a little bit of scatter out here, but that's kind of normal thing to see. And if you want, this is a really nice example to go play with. Maybe if you played with some of those error fraction tolerances, you can get rid of these things on the outside and get a little cleaner tracking at the front. But I think generally this is doing a pretty nice job. So as I'm going to switch back to the slides, and we're going to talk a little bit more about adaptivity and introduce something a little bit new as well in the mesh block. So if you have a question, please raise your hand, or again, post to the Slack. I'm going to drink. Okay, so we've been doing this training for quite a few years now, and we keep adding little bits to it, as some of you might kind of notice. It seems like things are, you get an A, B, C, and D steps, and that's because people have asked for certain things, and we add to them. And this is one of those cases. You know, people are asking us about subdomains, and we've already talked about subdomains a little bit in your mesh. And what we do in this example is we're going to split the pipe into 2 domains, kind of a top and bottom, or if you think about an RZ coordinate, it's kind of a center and outer ring. And we're going to use ideally we're using the mesh generator system, but unfortunately we failed to update this example. This is still using what's called a mesh modifier. So the syntax in this is going to go away, and it's going to change to something a little bit cleaner, where all of these this kind of syntax will actually be up in the mesh block. So we're going to have to get that updated soon. So just keep in mind. But conceptually, this is going to show you the same thing. So we're going to start with some sort of mesh. I think this is probably the mesh that we had been doing previous to the refinement steps above. And then we're going to add a mesh generator, even though it says modifier. And all that's going to do is inside of this box that's defined from this corner to this corner, we're going to change the subdomain ID to 1. So inside this box, change the subdomain ID to 1. So that's going to give us 2 regions in our mesh. And by default, the generated mesh object, generated mesh creates everything on block 0, and this is adding another block for this region to block 1. And this, if you look at this, is kind of the halfway up the radius, all the way to up and up, or maybe it's below. Yeah, it's the bottom part. So from radius 0 to radius 0.0125, and all the way along the axes. And then everything else here is what we've been looking at. We got pressure, temperature, computing the velocity. We got all the kernels, velocity kernel, same constant BCs. And then we're going to get down to the materials block. So it's important to note that the BCs area where we're, put our Dirichlet BCs and their function Dirichlet BCs and outflow condition haven't changed. And we didn't change the kernels at all. So those are all the same. They're still applied across the whole domain. But now this pipe is actually split into 2 domains with the mesh. So in the materials block is what actually changes. And we're doing 2 things here to show off a couple different capabilities. The first capability that is probably pretty obvious is that we have this kind of top level syntax. And this is a little feature of our hit format. And it just helps you do some shortcuts. And so what we're doing is, in the hit format, you can optionally define like little variables in your input file directly. So viscosity file equals these file names and the density file, etc. These aren't actually syntax coming from any object, and maybe we should actually change these to be a little bit more different, so it's kind of clear that these aren't any specific syntax. But regardless, this is just kind of a hit variable, and we're going to use that hit variable in these 2 blocks. And I'm going to talk about the 2 blocks in a second, but we're using what we call the dollar bracket syntax. So this little variable, hit variable, is then just being called out here and in another block here. And if you're familiar with like bash, it's kind of that same syntax as you have for environment variables, and make, I think, uses something similar too. So the actual thing that we're really trying to show off is the material system, the power, and why we spent all this time making a material object. Because what it allows us to do is make this real generic capability. The kernels are just looking for a material property. They don't really care how it's computed. So in this case, we're going to use packed column twice in each of the subdomains. So the bottom, or the center of the pipe, block 1, we're going to set a radius to 1.15. We're going to couple in the temperature, and we're going to do that fully temperature dependent fluid properties. And we could have added in the steel properties as well. We just didn't do it for whatever reason. And then in the top, or like the outer ring of this radius, we're going to use that same packed column C++ object. But now on block 0, we're going to set a radius to 1, which is the same radius we had. We're also using the temperature dependent fluid properties. And then we're also going to mess with the porosity. If you remember, if we go back and looked at the packed column material, we allowed porosity to change as a function. So we're going to do that. So on that outer ring, the porosity is going to change and get bigger as it goes down the length of the pipe. So the porosity is going to increase with X down the radius. And we're also going to monitor temperature. So this is pretty neat. So like I said, the kernels didn't change, and the proper material property as computed by these two objects is just going to flow into those on the appropriate domains as they're computing. And you could have very easily, somebody could have said, hey, I came up with a new material model for this system. Can you try it out? And this could be some other material object that somebody else made or that you made, and you're trying it out. And as long as you're supplying viscosity, density, thermal conductivity, etc., as properties to those kernels, they're going to work. So that's why we have this material property system. It allows us to couple things in and allows all of our code for the physics and to be super generic and independent of how material properties are calculated. I hope that comes through. And this is a really cool thing to go run, and we're going to do that. And then everything else looks the same. I think we even left adaptivity in there, and we did. And we also output the material properties here. So this is, somebody was asking about this earlier. This is one quick way to just turn on all the material property output that is supported. We'll show that video in a second. Let's just go run this on the command line and see if we can get something interesting. I'm just gonna close out my pair view there for a second. And I don't know what all that is. What is this? Ha! This is good. So this is telling us that we're using old code. So in Moose, as we develop Moose, especially over the last few years, we're trying very hard to do what's called deprecation. We change things for all sorts of reasons, for performance or syntax or just for simplifications, who knows what. And when we do that, we'll leave the old stuff lingering around, kind of like these mesh modifiers. And we'll give you this warning that says, hey, this code is going away, and it's going away last year. And we still haven't got to actually removing it. So that's kind of funny to show. So hopefully soon this will go away. And so what you would do is we update your application using the subdomain bounding box generator object. Maybe you go Google that on our website and you update your input file to use that. So something we need to do. Or maybe we left this in here on purpose to show that we do deprecation. I'm gonna go with that. So here's our solve. It's going away, going along great. Actually doesn't, kind of breaks down a little bit. It gets kind of harder to solve. This is super nonlinear. We got all the material properties in there, temperature dependent and things like that. Wow, this is what Logan and I were chatting about this last night, and he said he was seeing this, and I didn't see it, but now I am. So now Logan's just laughing. So I guess I'm not going to show this live. This is probably running into some of our scaling problems that Alex is going to talk to in more detail in a bit. For whatever reason that, yeah, go ahead.
I said this is fitting. I appreciate it.
Yeah, because this was working fine for me last night, and some little thing is different. So I don't know what happened. This is the wonders of highly nonlinear problems. Numerics is super important, and Alex is going to continue to talk about that. So I'm just setting you up, Alex. That's what I'm doing. Well, I'm going to jump back to the slides then and pretend that didn't happen, and I'm not completely embarrassed. This is why Logan passed off this section to me. So now let's just go look at the results the way they should run, and this is a really fun thing. So now we have these two domains, kind of the center of the pipe and outside of the pipe. And you remember that on the bottom of the pipe, we set a larger sphere radius. So the fluid's able to flow through there a little faster, as you might expect. So consequently, the heat in the bottom starts to flow, goes along with the flow and goes faster. And then the top, the radius was smaller, but we also remember that the permeability is increasing separately than the porosity along the axis. So this front is actually going to start to catch up to this front because of that change as well. But something else really fun happens too along the way, is that this is a continuous domain, and you imagine you got cold fluid up here, warmer fluid up here. Well, that fluid will diffuse, that heat will diffuse up into that upper region. So that's what you're seeing here. And the velocity, like I said, because the change of permeability is increasing in that top section, so that heat starts to diffuse up and it hits this faster flow, and that starts to carry it out in front of even this front. So this is a really fun little example to play. And so now you can see that top front's kind of catching up because this one is that permeability change as well. or porosity, whichever one it was. I get them backwards. So yeah, this is a fun example. I like to play it a few times because I really like that the heat kind of jumping out in front, coming from the bottom. So at this point, I mean, this is a pretty serious little problem. We got, multiple subdomains. We got nonlinear material properties. 2 equations, fully coupled, fully implicit, all the stuff. Mesh adaptivity. It's really, really quite good. So we got about 15 minutes. I think I can get us through this system. It might take me a slightly bit longer, and that'll get us close to back on track. The afternoon was a little light on content anyway, so I think we'll be in good shape. But I'm going to try to go through postprocessors here a little bit quickly, and I think we'll still be in good shape. So yet another system in Moose, postprocessors, and it's really 2 systems, postprocessors and vector postprocessors. And all these are is ways to aggregate values from your simulation. So for some reasons, lots of reasons, you want to compute some sort of aggregate value for a simulation, like your average temperature or the temperature in some region within your domain. And you can do that with one or two of these systems. The postprocessor system, that's just one scalar value, and the vector postprocessor is some vector of data. But again, it's an aggregate vector for your simulation. So both of these systems are based on what's called a user object. And user object system is a super generic interface for building simulations. So in order to talk about the vector postprocessor and the postprocessor system, we got to quickly talk about the user object system. So that's what I just said. They have postprocessors and vector postprocessors are just special user objects. So a user object is just a place for a user such as yourself creating a simulation tool to kind of define a custom interface that you might want to share with multiple objects. So if you're doing some complicated calculations that maybe are needed in both a kernel and a boundary condition, you can maybe use a user object to help you do those computations if necessary. One example we actually have is this our velocity calculation. We could maybe put into a user object that the aux kernel could use, and then our actual kernels could use without losing any sort of resolution, which we talked about between the 2 systems. But that's pretty simple, so we just kind of repeat the code instead of building one of these. The important part to take home from these is execution. You haven't really talked about this, but you might have seen it in an input file or 2. User objects will execute at certain times in quotation mark, and that's just kind of simulation times, parts of your simulation. And they'll execute on initial and time step n, for example, is pretty common to see. So that's during your initial setup of your equation, and then at the end of every time step, you can run a user object. You can actually run them on linear, nonlinear iteration at the end of a time step, only at the end of your simulation, or even when the simulation fails. And these also can be restricted to subdomains, side sets, node sets, kind of what we were showing in the previous example. And there's a bunch of different types, and the types just specify what the execute part means. So when a user object executes, where it executes with respect to your simulation is dictated by the type. So an element user object will actually call its execute function on every element. A nodal user object, an execute will execute on every node. Side user object, every boundary. Internal side, every internal side of your domain. Interface would be between 2 subdomains interface, and then a general user object will just go one time. It's just going to call execute once. So I guess to be clear, like when you create a user object, the virtual function that you fill out is actually called execute. And so, oh yeah, it's good. I got ahead of myself. That's what I was just talking about here. You also see some other virtual functions. Initialize. You also see finalize, which is in the next slide. So these is actually where you potentially, the user objects and postprocessors, vector postprocessors, where you might have to do some parallel communication depending on what you're calculating there. And the reason we don't do it for you is because we don't know what you're doing, but we'll provide you some helpers. So initialize, this runs one time before all the execute calls. So if you're doing an element user object, it's going to go call the initialize, it's going to call execute on all the elements, and then it's going to go to finalize and thread join. These are ways to do the final aggregation for the two different parallel communications. This is your shared memory parallelization and your MPI, non-shared memory parallelization routines where you can collect values. For example, if maybe you're summing the value across all the elements. So in your execute, you're just going to accumulate values, and then in the finalize and thread join, you're going to add all those values that were computed up and into a single value, which is what a postprocessor might be used for. And we have those, of course. And this allows you to create custom functions and things like that. I'm going to skip past this and jump to this slide. So inside of any sort of object, really, in this case, this is a simple material object example. You can go add a parameter, give it the special type username and user object name, and just like we've done with lots of other stuff, the left-hand side is block average user object, and on the right-hand side, it's going to look for some user object name. And inside that class that's using it, further on down, you're going to actually, this is where we do some nice type casting for you in C++ language. So this block average value is maybe some material, something that you created. This is the actual name of your user object, and you can go get that user object, give it the type, and then the input parameter that you're using. I think that's good enough for the cases of a user object. And here's a simple example how you call that custom interface. So with respect to time, I'm just going to press on so we can show you how the system is used for postprocessors and vector postprocessors. So in aggregation, again, it's the postprocessor system just is going to compute a single value. And we have all the different types, and these exactly mimic the types that I just showed you in the user object system, which is why we have to do it. So an element postprocessor going to operate on each element. So this is where you'd want to do kind of my example, where you're going to sum the values from elements, etc. And all the functions look the same with respect to things you override, initialize, execute, thread join, finalize. And then there's one more that's actually give me the final value. So after you've done all your computation and finalize, what's the value that this postprocessor is actually computing, comes off in the get value there. And then these are the helper routines that I alluded to in the user object. So if you're going to do mins and maxes in parallel, we got some gather routines for MPI. And we have tons of built-in postprocessors. Using them is pretty simple in your object. We have a special type that you would declare as a member variable. Then in your initialization list, you get postprocessor value, where this thing is going to be an input parameter that you define somewhere in your valid params. And we can come back to this if we need to in more detail if there's questions, but people are getting hungry. So Derek actually talked about this a bit, and so did I think Logan, about default values. So postprocessors, they're single scalar values, so they're easy to put defaults in. So if you have add param postprocessor name, you can give it a default, so the user doesn't have to do anything, and it's just going to use 1.2345. You can also then put a function string in there using the parse function syntax, or then you can actually give it the name of the postprocessor if you prefer, or if you want to, depending on what you're doing in your calculation. Vector postprocessor system is very similar. The only difference is you actually do kind of a material property style declaration. So you have a vector postprocessor value, and all this is a vector of reals. And then in your constructor, you declare vector and give it a name. And so then in your actual execute method, you're just going to populate this underscore PID, which is a standard vector, and you can just populate data into it. And then that data then becomes available just like it does for regular postprocessors, but you just use the type vector postprocessor value, and then you get vector postprocessor value. You give it the name of the postprocessor, and then you also have to give it the vector name, because a vector postprocessor can actually declare many vectors. So you got to add a little bit more to it, but it's fairly straightforward. It's really quite a powerful system, a lot of capability in it. So with respect to our problem, I'm just going to breeze through this in the 5 minutes and show you some of the things you can do with it. And if people are really interested, chime up on Slack and we can come back to this. If we need to do a little more information, we'll have time after lunch.
Hey, Andrew, before you get into that, I just want to double down on the fact that we have many post-processors and vector post-processors built into Moose. Most likely, something that you want is already in Moose or is very similar to something that we already have in Moose.
Yeah, I'll make it a couple minutes late for lunch and I'll go show that. It's a good thing to show. So we haven't really showed it off our website. This is something we kind of usually jump into. And unfortunately, it's crazy slow because I guess all you guys are on it and we need to update this computer in a bad way. Holy moly. So there's lots of information on it. We have a Google search on there that can help. And I'm going to go show you Doxygen. So this is kind of in code documentation system for really common in C++ tools. So I'm going to click on that. It's going to take forever. And I'm going to go into it and look up vector post processors. Click on that. And you can see this is the inheritance diagram for all the code in just the framework. And these are all the vector post processors that exist. You can see there's quite a few of them. There's element ones, general ones, etc. So worthwhile to come look at this. You can kind of see what we have. And you can also go to our syntax pages to see them all as well. I'll do that in a sec. And so there's even more regular post processors. So let's go back to another place to view this. So this is maybe more useful if you're going to develop your own. You can kind of see the inheritance and maybe you can inherit from one of these objects. If you go back to our website, which is going to hopefully not take forever to load, it's going to, oh, there it is. And we already showed, we briefly talked about this, but all of our syntax is available on this tab. And so every system Moose is listed here on the right. And let's go to Postprocessors. And then here, this is actually a clickable link. You can click on that, and that's going to take you to documentation about the post-processor system in general, which there's quite a bit on. And then this lists all the post-processors that exist. Don't worry about these actions. We may talk about the action system at the end of the day if we have time. But this lists all the post-processors available in Moose, which there's a lot, and then all of the submodules. So this is Paradynamic submodule, RGG submodule, Navier-Stokes, phase field, heat conduction, etc. And I'm gonna go click on one of these and hopeful that it's documented. Probably won't be. Oh, this one is good. And so each object then should have a summary and description and also a list input parameters. There's not too many input parameters for this one. This is one that's required. This one's optional. And this lists, I need some advanced parameters there. You can expand. And then this list is everywhere it's used in our repository. So pretty useful stuff. And there might also be a list if this object is being inherited from to make a more specialized version. You also see that objects that inherit from it in these lists as well. So there's lots of documentation there. So to jump back to our example to finish up here for lunch, the problem's generally the same. We got all the kernels, all the coupling, aux calculation, back to a single problem, but we have porosity. We put a function in there. It's still changing with along the axes. Oh no, this is in the radial direction. Now we got porosity changing in the radial direction. It's a little bit different. And then we're going to add, this is what we want to show off. We're going to add two post processors. One of them is the average temperature. So this is the element average value of the variable temperature. So it's going to look at the temperature over the all the elements and just give us back our average value. And then at the outlet, we want to get the flux. So this is the AD side flux integral of the variable temperature on the right-hand boundary. So this is just going to be the flux or the heat flux going across that boundary. And in order to make that calculation, you got to give it the activity. as a diffusivity parameter. So this is where you see that material property name thing coming into fruition. So this object, which is living down in Moose, is probably looking for the more generic term diffusivity, which is used for flux in general, but we're talking about heat, so we can actually give it the thermal conductivity in this case. Yep, and then vector postprocessors, fairly similar syntax, but what we're going to do is actually do a line, grab the values in a line along the radial direction. So in pair view, Logan's been showing you that plot over line. This is actually doing plot over line on the fly in your simulation. And there's a lot of reasons to do that. Namely, or one of them is you get that plot will be updating with time in your actual output. And another one is that the line value sampler actually uses your finite element shape functions to perform that sampling. So in Logan's case, it's just doing some simple linear interpolation based on the in VTK and pair view based on your nodal values. But if you had higher order shape functions, especially this becomes important, pair view would miss that higher order geometry, whereas this line value sampler is actually going to use your solution, which is your actual continuous function, to perform this sampling. So you get a much better view of the values across the line. So you can run it in Peacock, hopefully. And this is a nice video too to kind of show you the capabilities that this opens up. I gotta rewind it here apparently. So this video is showing the temperature. You're gonna have that temperature profile. It's progressing across, and remember that the permeability or the porosity was changing in the radial direction, so it's getting easier for the fluid to flow kind of on the outer edges of the pipe. And then down here, we're plotting, on the left-hand side, we're plotting the two postprocessors. One of them's the average temperature, which is just going to keep going up as you would expect. And then also down here is the outflow flux, and this little red line. And they have these little tracers to show you. So the average temperature is plotted on the right, the flux plotted on, plotted on the left, the flux plotted on the right, and the colors match the line. And so initially, the flux across here is 0 because there's no temperature gradient hitting that boundary. That'll change. And then on the right-hand side, so somewhere here, I have to go look at the input file again, but there's a line value kind of going across the radial direction. And so now you're seeing the temperature, which is down here at the bottom, in that radial direction. And we'll just let that play out. And so as you imagine, the temperature is going to go from 300 to 350 on the vertical line in the domain. And now the temperature is getting to the end, so we're actually getting some sort of flux. There's a change in temperature across that boundary. And then as as it goes to steady state, that gradient of temperature across the boundary is going to 0 again, and the flux goes back down. And the average temperature obviously goes to steady state at 350 for the whole domain. So that's only puts us 3 minutes behind. That was a little fast for postprocessors, but I think you get the point, and you're probably following along reasonably well. We can come back to this if we need to. Derek, go ahead.
Yeah, I just wanted to add a couple of things. So the output of postprocessors, you're showing it here, but the basic output is a comma separated value file, right? So it's a CSV file that you can read into Excel or MATLAB or whatever you want, so that you can plot these things over time. The same with vector postprocessors. The other thing about postprocessors is that they're actually embedded, the values are actually embedded into the Exodus file themselves. So when you're using ParaView or something like that, you have access to all those postprocessor values. You can plot them in ParaView, etc. So I just wanted to point that out, that how the output works.
Yeah, thanks.
So we're moving on to step 9, where we actually bring in another module, our mechanics module, and subsequently we're going to make this thing even more multi-physics, 3 physics now. Exciting. So nothing too complicated here, and I should qualify this and say that I myself am by far in a way, not a mechanics expert, but I'll hack through these slides here. We're going to solve very simple PDE. We're going to compute the elastic and thermal strain in the tube, allowing it to expand along the axial y direction as the, actually, I think in our graphics, it will be expanding in the x direction, maybe also in the y direction, but definitely in the x direction. And it will expand due to thermal expansion. Okay. We're going to solve this using one of the built-in modules in Moose, the tensor mechanics module. And before I go into too much detail about the tensor mechanics module and how we're going to use it in this input file and in this problem, I'll give a general overview of the modules that we have available already in Moose. We have a chemical reactions module, which has been around quite a while. It was originally developed as a Moose application called RAT, which we published on in 2013. I think by and large now it's largely maintained by a group in Australia. They use it for a lot of equilibrium chemical type reactions. We also have the contact module, which is a module leveraged heavily by some of our Moose applications like Bison for doing fuel performance problems. And then I think the wider community uses this module quite a bit. Where we model mechanical contact with different algorithms. Mostly mature and widely used algorithms are based on node face constraints or node to segment contact enforcement, although in the last couple of years we've also been working on mortar constraint enforcement of contact. And we have both frictionless and frictional contact implementations. This is something that Fandy put together, this external PETSI solver. It's meant to demonstrate and provide support for coupling standalone native PETSI applications to Moose applications. And then we have a fluid properties module, which a lot of our INL apps use. Which provides consistent interfaces to fluid properties like density, viscosity, enthalpy, and many others. And it also provides derivatives with respect to those variables. We also have the functional expansion tools module, which went into Moose in about 2018. This has been used and is really useful for coupling Moose applications with things like Monte Carlo simulations, where you can use functional expansion tallies to essentially transfer the Monte Carlo results over into Moose and to couple with the finite element Moose application in that way. We have the heat conduction module, which we've been using in our tutorial. We have the level set module, which is primarily developed by Andrew. Which is meant for solving essentially multi-phase problems where you define the interface between phases with the level set equation. We also have the Navier-Stokes module, which currently only has continuous FEM code in there, but actually this summer we're going to be migrating some finite volume code from the Pronghorn application into the Moose Navier-Stokes module. But what's in there right now, we have both compressible and incompressible flow equations. And the incompressible flow, something largely developed by me, we have a AD vector variable implementation, which includes streamlined upwind and pressure stabilized Petrov-Galerkin methods. One module that's heavily used by the community is the phase field module, which is one of the principal developers there is Daniel Schwen, and we have a lot of other great developers at INL who work on this and use the phase field module. Then we have the porous flow module, which is another application which is heavily developed by some of our Australian colleagues, meant for modeling flow through porous media. We also have a reconstructed discontinuous Galerkin method, which is another module which is meant to help solve fluid flow equations. We have the stochastic tools module, which is a module that's growing rapidly and is also developed by Andrew. It's meant for performing stochastic probabilistic type analyses. And then the module that we'll be using in the next step of our tutorial is the tensor mechanics module for solving continuous solid medium mechanics problems. It has implementations for both linear, small, and finite strain mechanics, as well as creep and damage physics. And then we also have support for the extended finite element method, XFEM, which I think is pretty strong support now, and it's also still being developed. So moving on and diving into the mechanics portion of our tutorial here. I don't know if we actually update this material for this step. I don't think that we do. But again, here's the packcolumn.h file that we're going to use for providing our material properties.
Alex, we have to add the thermal expansion coefficient to it.
I see. So that would be this CTE variable.
Yeah.
Thermal expansion here, yeah. So we define the bulk thermal expansion coefficient as a new AD material property, thermal expansion. And then most of this code we've already seen before, but now we have this thermal expansion computation here, which is going to feed into our tensor mechanics equations as an eigenstrain. So here's our step 9 input file. Andrew already touched on this in the previous steps. We got this mesh modifiers block here, which should be converted over to a mesh generator. And actually, I've already done that in the input file that I'll be showing you guys. And then our new important block here is we're adding the tensor mechanics action, which is a nice nice action syntax that our tensor mechanics developers came up with. Essentially, it's this custom syntax written as modules / tensor mechanics / master. And then when you create this subblock here, you automatically generate all the necessary kernels in order to model the tensor mechanics or solid mechanics equations with just a few input parameters. So you don't actually see any tensor mechanics variables in the variables block, and that's actually because we're going to add those automatically with the action via this add variables equals true parameter, and that will add the displacement. That'll add the displacement variables. In this case, we're going to call them disp r and disp z since we're solving an axisymmetric equation. And this is usually an optional parameter here. This eigenstrain names, it's an option for providing additional eigenstrains. So we have the added strain due to thermal expansion. So we're going to make use of that parameter here. And then we're going to use the automatic differentiation version of the tensor mechanics kernels to help improve our Jacobians. And then there's another optional parameter here called generate output. And what this parameter will do is it will lead to creation of aux variables, which are going to hold von Mises stress and then these components of the elastic strain tensor. In this case, we're going to output elastic strain XX, elastic strain YY, strain XX, and strain YY.
All right, Alex, we got a question on Slack. I think you probably should answer it. What are the global params? I think this must have a global params block in it.
It does. Excellent question. So we have this global params block here. And essentially, anything that we put in here, so here we put displacements equals, essentially any block anywhere in the input file that would take that parameter will automatically have this displacements equals disp r, disp v filled in. So actually the mesh block takes the displacement parameter. So by putting global params here for the displacements value, you're automatically adding that to the mesh. And then I believe the tensor mechanics action also takes that parameter. And so by just specifying in that global params block, you fill in for every other block input file, you fill in that value. So it applies to all the blocks in the input file that would take those parameters. You can override. So for instance, if you actually had a displacements definition in the mesh block, so if you had global params displacements equals disp bar disp z, and then the mesh block you put displacements equals disp x disp y, the definition in the mesh would override the definition in the global params. So there are cases where you may want to override a global params definition, and you can do that. Let's see, did we add anything else in this input file? Yes, we did. So we have to make sure that we appropriately constrain the problem, so we don't have any spurious rotation modes. So we apply some Dirichlet conditions to displacement variables. We put one at the inlet, one at the center, and one at the outside. And then we have our materials here. And then importantly, when we're using the mechanics system, we have to introduce several materials. We have to provide something for the elasticity tensor. In this case, we're going to define it to be a AD compute isotropic elasticity tensor. So we have anisotropic elasticity tensors, but in this case, we're just going to use the isotropic one. And we define what Young's module will be and what Poisson's ratio will be. And then we define a stress calculator. In this case, we specified strain equals finite up here, so we have to use an appropriate stress calculator in the material block to correspond to that. And I think the tensor mechanics action does a good job of doing consistency checking. If you made a mistake in the consistency between the material and tensor mechanics block, you should get a helpful error, I think. So here, since we're doing finite strain, we define the appropriate material here, AD compute finite strain elastic stress. And then we're going to provide that strain due to the thermal expansion. And so we add this AD compute thermal expansion eigenstrain object. And we define what its name is going to be, just eigenstrain, and that's fed back in that tensor mechanics block. And then also we have to couple in the temperature variable, which will define the thermal expansion. And I guess at this point, the tensor mechanic module doesn't support a material property, but it will. So here we just define it as a constant. So let's go ahead and run this problem. And I'll actually hopefully demonstrate some different aspects of the solve and like the importance of scaling. So let's see here. So we'll go to the terminal, and let's see what we got. So I'm going to try to run that step 9 input file. I'm going to go ahead and run it with 2 procs. And let's see how we do. So you can see here, the linear solve is really struggling. And maybe let's try to understand why. Let me switch to my text editor here. Actually, I'll show full screen. So we're going to go ahead and watch that linear solve continue to struggle. And let's look at our execution options here. So in this particular case, I'm using solve type equals PGFNK. And you can see right here, as I'm running, I have automatic scaling equals false. And so something that I mentioned is that if you have a multiphysics problem and scaling is dramatically different between the different physics, PGFNK can have a hard time selecting an appropriate differencing parameter. Andrew or somebody, is my screen big enough to see well?
It's fine for me.
You might want to Command plus a little bit based on other issues we had in the past with some people saying it was too small, but it's fine for me.
Okay. So as I was saying, you can have, for poorly scaled physics or physics on dramatic different scales, PGFNK can have a hard time selecting a good differencing parameter that can satisfy both physics. And here in this problem, I've actually used the PETC option, which is called KSP monitor true residual. So you can see here in my input file for PETC options, I put KSP monitor true residual. And what this does is it allows me to look at how, if I actually tell PETC to do an explicit computation of AX minus B, which corresponds to essentially J delta U equals the residual. What we want to see is we want to see that this ratio, this R over B, we want to see it decrease certainly, and ideally it should decrease significantly. But actually what we see here is that over the course of the solve, we actually get farther away from the solution than when we started. And when we reach what the linear solve considers to be converged, we're back, we've partially reduced the residual, but hardly at all. So let's not worry too much about what these things mean, but the linear solve thinks it's reduced its residual norm to 1 e to the minus 8, but actually the true residual norm has only reduced to 1 e to the minus 3, and we started at 2 e to the minus 3. So we really hardly reduced it at all. And not surprisingly, we actually, due to this linear solve, we don't get a great Newton update. So in our nonlinear residual, we only go from 2.7 e to the minus 3 to 1.4 to the minus 3, which isn't a great drop. So we can look at the overall solve. It took us a cumulative 425 linear iterations to solve the problem, and it took us 6 nonlinear iterations to solve the problem. Now, how do we do if we change to use automatic scaling? So I'm just going to append this on the command line here. So this did much better. So now this took us a cumulative 35 linear iterations instead of 425. So over an order of magnitude reduction in linear iterations. And we also halved the number of nonlinear iterations. And if we were to look at that true residual, you can see it's nicely dropping in each linear solve. So hopefully this is a good incentive for automatic scaling. Let's go ahead and turn off automatic scaling again. Now I'm actually going to explicitly demonstrate, why is that linear solve so bad when we don't scale? We talked about the SVD preconditioner before. So I'm going to make the mesh really coarse for this because the SVD preconditioner is very expensive. So I just ran on a 2x2 mesh there, but you can see that without automatic scaling, our condition number is 10 to the 19th, which is quite terrible. And so it's not surprising that without scaling, our real solve really struggled. Let me go ahead and add it back and see what the condition number is with this. And you see it's nicely reduced to 10 to the 5. So hopefully that's a good motivator for using automatic scaling. So that was using PJF&K. We can also see if we use Newton, how does this do?
Yeah, Alex, we got a good question on Slack too about automatic scaling. So what algorithm is used?
So it's a pretty simple algorithm. Essentially what we do is we go through and we look at the, well, it depends on what type of scaling we're doing. The default scaling is based entirely on the Jacobian or the preconditioning matrix. And what we do is we go through and we look at every row in the matrix for a given variable, and we look for the largest diagonal entry for that variable. And we do that for every variable. And then what we do is we choose scaling factors such that the largest diagonal entry for each variable has an absolute value of 1. So if in the unscaled matrix, you know, the displacements had a diagonal of like 10 to the 10, you know, that would be something for like with Young's modulus. Then what automatic scaling would do is it would scale down by 10 to the minus 10 so that the displacements had a Jacobian entry of 1. And so in that way, by bringing all the physics to about the same order of magnitude, you get a much better conditioned system. So I just did a run with Newton there, and you can see that took 4 nonlinears and 68 linears. That was without automatic scaling. So you can see, I mean, the difference here between Newton and PJF&K, Newton's not improved nearly as much as PJF&K is by the automatic scaling, but it still is improved. We halved our cumulative linear iteration count. We went from 68 to 34, and then we reduced our nonlinear iterations from 4 to 3. So not as severe an improvement as when we use scaling with PJF&K, but there's still definitely an improvement, even when using Newton. So that was just one time step of the problem. I think if we actually ran that out to completion, it would take, I think it's like 200 steps or something. So I'm not gonna run that whole thing, but I'm just gonna show you the results if you were to run that input file all the way to completion. You've seen the temperature results before. If you're looking carefully, you should see actually that the domain is growing. On the right-hand side, it's extending out there slowly. So that's the continual movement of the mesh due to the thermal expansion. And then in the bottom half of the screen there, you can see how the von Mises stress changes over time. So something that I love, something that's near and dear to my heart, is the method of manufactured solutions. Being kind of a math nerd, I believe that MMS is critical for actually demonstrating that your finite element method is valid and implemented correctly. And if it's not, then what are you doing? I don't know. So I love using our MMS tools to show that we actually have implemented the finite element method well in Moose. And the MMS tools that we have, you can use to verify and validate any kernels that you develop for your own application. So I strongly encourage you to do that. So let's just talk a little bit about what MMS is. It's a useful tool for code verification. How it works is essentially you assume a solution for your PDE. And when you assume a solution, you run through your strong form and essentially calculate a forcing function that you need to add to your system of equations in order to generate the exact solution. And then you can compare your numerical result to the analytical exact solution, and then you can compare things like L2 errors or H1 errors and see if your method is converging like it should with things like H refinement. So for the example that I'm going to show you here, we're going to use it, basically the simplest PDE, just diffusion, or the Laplacian. So minus del squared u equals 0. We're going to assume, so when picking MMSs, I strongly encourage people to pick a smooth function, but also not a function that can be exactly approximated using your finite element bases. So for example, if you were using like a Lagrange basis of second order, you would not want to assume a solution of second order. You would not want to create an MMS that's a second order polynomial or a first order polynomial, because it could be exactly represented by your finite element basis and your error would be 0. So hopefully. So you wouldn't be able to look at the convergence rates and learn much from that. So with the assumed solution of u equals sine of alpha pi x, if you take the del squared of that and apply the minus sign, you end up with a forcing function of alpha squared pi squared sine alpha pi x. And so then with that forcing function, we now proceed to solve the modified problem in Moose, which is minus del squared u minus f equals 0. And let's look at the input file that we used for solving this problem. We just create some arbitrary mesh on a very simple domain. For these MMS studies, you should probably be using a uniform grid, and that's what's being done here. We do a simple domain just from 0 to 1 in both x and y. In this case, in this input file, we're going to modify through command line options, but for the base input file, we're going to use the first order Lagrange basis. And you can see where we've specified the exact function using a parse function. That's sine alpha pi x. And then I guess for this demo, we actually implement the forcing function using a compiled function. But you could also implement the forcing function using another parse function and just apply it in the input file, just like we're doing there for the exact solution. We implement that negative del squared u term using AD diffusion. And then we apply the F term using this AD body force object. And we supply the forcing function equals force there. You should be applying essentially boundary conditions that derive from your MMS solution. So in this case, we're going to apply a Dirichlet boundary condition, and the values of the boundaries are given by the exact solution. For doing these studies, we need to add a couple of postprocessors in the input file. We need something that's going to compute the element size h, because we're going to be plotting error versus h in our plots. And you can do that using the average element size postprocessor. And then we're going to compute the L2 error using the element L2 error postprocessor. That just shows how you just run that single input file in the command line. But we're going to demonstrate how to do multiple runs with progressive refinements in order to generate these MMS plots. So we do have some MMS tools built into the Moose package. And you can get those into your Python environment by exporting to your Python path. This can also be useful for some other stuff too, although we're only going to be using MMS here. So if you want to get the MMS tools from Moose, you need to export your Moose Python dir, which is just moose/python. So one tool that we have is this MMS.evaluate method, where you essentially, as the first argument, you supply your PDE, and we're doing the Laplacian, so we do negative divergence of grad of u, and then you supply as your second argument what you want for the exact solution. And then you can do there's various printing methods in the MMS package for printing blocks for use in Moose input files or even for Moose code. So let's actually go and run these Python files corresponding to this example. So I'm going to go to the terminal here. This is in our examples. So I think this PPS is actually supposed to be MMS. We should get that fixed up. So let's see. We're going to run the exact Python file. Let's just open it up, look at it. That's what we saw on the slide.
So the PPS stands for, it's actually our post-processor example. So that's how we introduce post-processors, is through this thing in our old training.
Okay. Okay. You could do EX14, PPS, and MMS. Okay, so we ran that Python script, and we got various output to the screen there. We printed what the function parser should look like. The function parser expression, that's if you're entering like type equals parse function in your input file, then you'd want to essentially write this line of code into your parse function, pi squared times a squared times sine x pi a. Parse function syntax uses, caret to represent exponentiation. So like behind the scenes, our MMS Python package converts like star, which is the Python representation of exponentiation, to this caret, which is what the parse function recognizes. And then I also told MMS to print like what the C++ code would look like, and that's the print moose method, and that comes out of C++ code. And we can actually go and see whether whoever made this example function was following what the MMS solution said, and you can see that essentially they did. libmesh pi is probably just I think it's just a type def for the mpi, and then alpha corresponds to a here. So our example function, which we use in our input file, matches the function generated through the MMS Python module, which is good. And then finally, the last thing that this Python script printed for us is what the different input file blocks would look like for the forcing function and the exact function. And let's go ahead. Let's see, do I have that input file? So I guess we're actually using a different value for alpha here in this problem, but you can see that the exact representation matches what's printed out by our Python MMS module, just with a replaced by alpha, and vowels, instead of using 1, we use 16 instead for this example. So this is just this summarizes what this actually isn't totally right. So this is what the L2 error looks like there. It's just the difference. It's how you compute L2 norms. You just do a simple subtraction of F1 and F2, and then there's the Hilbert 1 semi-norm computed there. I believe that should actually include the difference of the function as well as the difference in the gradient of the functions. And so those are the norms that we use behind the scenes in those postprocessors like element L2 error, and we also have an element H1 error as well. I guess maybe the semi-norm does just refer to computing the difference in the gradients, but we have a H1 error standalone, not an H1 semi-error, that also computes the summation of the difference in the function values as well as the difference in the gradients. So we can also now basically just automate a convergence study using the MMS tools that we have in our Moose/Python. We have these run spatial methods, which are essentially going to execute an input file given in the first argument here. So that's going to be our example 14 input file. Then the second argument that this takes is the number of mesh refinements you want to perform in order to generate an MMS plot. So here we're going to perform 4 mesh refinements. And then you can also pass additional arguments that correspond to command line arguments that you want to pass to the input file. So we're going to do 2 different runs here via the script. We're going to run the base ex14 input file, which remember had a first order Lagrange basis. And then we're going to do a second run with that input file, but we're going to create a second order mesh, and we're going to have the basis for our nonlinear variable be second order. And then if you're familiar with finite element theory, the convergence rates that we expect for the first order basis, we should see second order error in the L2 norm for that first order Lagrange basis, and then we should see third order error in the L2 norm when using a second order Lagrange basis. So we can go and actually run that Python script. And what this will do is it will actually go and run our input file multiple times corresponding to the number of mesh refinements that we want, and it's going to do that first order study as well as the second order study. And then we're actually going to combine them on the same plot, and we save it out as this ex14 MMS GNG. So we went ahead and generated that plot, and we saw exactly what we hoped to see. We saw that when we used a first order basis, first order Lagrange basis, we see second order convergence in the L2 error. And then when we use a second order basis, we get third order convergence in the L2 norm. So this is great. Moose is an appropriate finite element code that solves problems like we like it to. So yeah, you can do pretty neat stuff with the MMS package. I thought maybe I'd run one more example for you guys. It's actually something I'm working on right now.
There's a question. It's kind of more taking a step back to what you were talking about before MMS, but what NL reltol and NL abstol is ideal necessary to ensure that we're solving the problem accurately? So I don't think we've actually talked too much about solver tolerances, so it might be good to show them in your input file or something.
Okay. Yeah, so our default tolerances, let's go ahead. Okay, let's look at an input file. Okay. So this was the input file that we were using for our MMS solution. And you can see we don't actually have anything set for like relative or absolute tolerances. So what happens is that PETC defaults end up being used. And the PETC defaults are the numbers that I'm going to type here. So by default, we try to converge the nonlinear residual by 8 orders of magnitude. So we try to drop it yeah, by 8 orders of magnitude. So that's definitely like a fairly tight convergence. I think some of our applications need to solve more loosely sometimes, but I highly recommend that if you can, you try to reach that default convergence for RelTol. By default, we don't even try to use the absolute tolerance, so we set it to some absurdly low number. It's 1 e to the minus 50. So unless you actually change that option in your input file, you're never going to hit it. I guess unless you exactly solve your problem, which would be great. So some people can use absolute tolerance if they have a problem that slowly approaches steady state over the course of a transient. But we actually have other options for that. I think we have like a steady state. We do have steady state detection parameters, and so we generally encourage our users to use those parameters instead of an absolute tolerance in order to detect those approaches to steady state in a transient. We also have, so our option for linear tolerance is just LTOL, and the default for that is 1 e to the minus 5. Sometimes you may also want to loosen that. You may be doing a lot of extra work, especially if you're solving a highly nonlinear problem and you're early in Newton's method. You may not be anywhere close to the quadratic basin of convergence. It may be not wise use of computational resources to tightly solve your linear problem, especially in those early stages. And so some people get away with a much looser linear tolerance. So, sometimes I'll run with even like a 1 e to the minus 2, maybe 1 e to the minus 3. So like 1 e to the minus 2 is still a valid choice for a linear tolerance. So in general, I encourage users to play around with linear tolerance, but try to keep that nonlinear relative tolerance as tight as you can, remembering that if you're using Newton's method, once you get in that quadratic basin of convergence, your nonlinear residual can drop quite quickly. So typically what I found is sometimes some application developers try to stop their solve at like a RelTol of 1 e to the minus 4. When actually, if they kept it at 1 e to the minus 8, they could actually hit that much tighter tolerance if they just took one more nonlinear step. Oftentimes, if you've reduced by about 4 orders of magnitude, you're probably approaching Newton's quadratic basis of convergence. And so it's definitely worthwhile to take 1 or 2 more nonlinear iterations in order to really solve the problem tightly. So that was a meandering discussion. I don't know if that answered the user's question.
I think they probably did, but I think you should add about if you're having trouble with a test that's not, behaving differently on different systems, what the actual solution to that usually is versus what a lot of people tend to do.
Sorry, repeat that one more time.
So I can talk to it, or if you want to. A lot of times you have a test that works well on your Mac machine, but doesn't converge on your Linux machine. What do we recommend for solving that type of convergent problem?
Yeah, so I guess you're referring to like when like something exodiffs on one machine versus another.
Yeah, and I'm referring to like tightening the tolerances rather than loosening them.
Yeah, so something we do for Moose is we do our testing across different platforms, different architectures. We always make sure that when someone submits a pull request to Moose with a test in it, that's going to be tested on Linux, it's going to be tested on Mac, it's going to be tested with a variety of methods. And it's not uncommon, for instance, if a developer is creating their test on a Mac, they solve their problem, they generate like a gold exodus file, and then they try to submit a pull request to Moose, and then they discover that their gold file, when their problem runs on Linux, it actually differs from their gold file, which was generated on Mac. And typically, an often common response to this problem is that the pull request submitter will go and loosen the comparison tolerance for the exodiff. You know, if it exodiffed on Linux, then okay, I just won't compare the solution as tightly. You know, they may loosen the default comparison tolerance for exodiffs is like 5.5 e minus 6. They might loosen it to 1 e minus 4 or something. What the right solution is, and I think, you know, what the path Andrew is leading me down here is that what they should instead do is in their input file, they should tighten their solve tolerances, not loosen the gold file comparison tolerances. So if you solve very tightly on a Mac and a Linux, you are going to converge to the same solution, and your exodiffs will be good on both platforms. So yeah, in general, try to solve as tightly as you can, especially when generating tests, because then it will be work across platforms much better. Yeah, so I guess the last thing I wanted to show you guys for MMS was, you know, we've been working on this mortar method in Moose for a while, and we're making some pretty cool steps with it. And you know, when developing mortar, we want to make sure that the method's implemented correctly. So I have this very simple gap conductance problem with the temperature on 2 different blocks, and the rate of flux on both sides. So the right face of the left block and the left face of the right block is determined. The fluxes there are determined with the Lagrange multiplier using the mortar method. And to make sure that you do the mortar method right, we did it right, we run a lot of MMS studies. And while I was talking, I generated some graphs for the mortar method for different basis function choices. And then these are just some of the plots here. So this P1, P0 is if I use a first order Lagrange for the primal variable. In this case, the temperature, since we're doing a gap conductance. And then I use a constant monomial for the Lagrange multiplier, which is representing the heat flux at the interface. And so what we would expect if the mortar method's implemented correctly with this P1, P0 basis is second order convergence for the primal U and first order convergence for the Lagrange multiplier. And then in the asymptotic limit, you can see that we are approaching that. And then you can also do it for different other choices for the U and primal base, the primal and LM basis. So here we do first order for both, and we say second order convergence for both, which is great. And P2, P0, you actually get error from the flux variable pollutes the primal error, and you expect an asymptotic limit of second order for the primal and first order for the LM, and that's what we would get if we refine this even more. For P2, P1, we would expect 3 and 2. That's what we see. And then finally for P2, P2, we expect 3 and 3, and that's exactly what we see. And all these plots are generated using our Moose Python MMS tools. So I think they're great things to learn. So that was the MMS stuff. So again, I strongly encourage users as they develop things like kernels and stuff to be doing these MMS studies and make sure you haven't made a mistake somewhere and that your kernels are actually going to converge to the physical results that you expect.
There's also tools for doing temporal studies as well, that you're getting the right time conversions.
That's right. Yeah.
I'll put a link on Slack to our docs.
Yeah, good. So the final thing that I'll be talking to you guys about is debugging. And our example here is pretty basic, but I strongly encourage our users to get familiar with the debugger, or I should say our application developers should definitely be familiar with the debugger. You can save innumerable time by using a debugger as opposed to doing print statements. And it's also a great way to learn code, to step through Moose, etc. As I just said, the debuggers, I would contend, almost always more effective than print statements. There's several different debuggers you can choose from. LDB and GDB are probably the most commonly used. Those are the ones that I use. LDB is what I'll use if I'm on my Mac. GDB is what I use on Linux. There's also like TotalView, DDD. I guess there's the Intel debugger, but we don't even compile with Intel anymore, so I wouldn't use that. Let's see. So we're gonna go over a simple example that actually generates a segmentation fault. When you see a segmentation fault in your console, that gives you no clue what just happened. But despite that scariness, it's actually one of the best kinds of errors you can find because it's very easy to trace back to a segmentation fault in the debugger. Like I said here, it's a good error to have. So we're going to run this example 21. Okay, so I won't show the code yet because that's going to be the surprise, why we get a segmentation fault. So let's see, if I run, yeah, so if I run my oprof executable here, all I do, I just hit a segmentation fault. That's not very helpful. What happens if I run it in debug mode? So debug mode is actually very useful. You actually get, we try to put a lot of assertions in Moose. Assertions are things that are essentially code that's only compiled in debugging mode, so that we do all this pedantic checking that if run in an optimized mode would make your code run quite slowly. And so we try to compile it out in optimized modes, but we compile it in for debug modes because it helps track down where errors might be. And this actually gives a stack trace, but it doesn't have line numbers. So in debug mode, so you can compile Moose using kind of this method environment variable. So if you wanted to compile in debug mode, you would type method equals debug, make dash, whatever you want to do there. I've already compiled it, so I didn't do anything. By default, if you don't specify a method, it's the equivalent of telling Moose to compile opt mode. And then I think we've talked about some of the other ones. There's also an oprof mode, which is great for profiling. If you get really good with Moose and you want to speed up your application later on, you might use this oprof mode. But for debugging, definitely compile with method equals debug.
Hey, Alex.
And then that will generate.
Oh, geez, where's my webcam?
Yeah.
I also want to recommend something that Cody suggested to me a few months ago that I've used a lot now, is that develop mode is also an option, and it basically just adds all the assertions without all of the super expensive debug checks, which if you're kind of doing general development and don't want to get rid of all the speed and you're still kind of running somewhat large problems, just if you run devel in general, for most cases, you get a lot of extra assertions and a lot of extra checks without a huge speed cost. So devel is also an option if you're developing.
Do you still get the right line numbers in the debugger?
Yes, you do actually.
I don't think that's true, but
oh,
I use devel mode, and when I hit an error, I switch to debug. So
yeah, that's the same way that I run. I run in devel pretty much by default all the time, unless I hit something bad enough that I can't figure it out and I need to go to debug.
Yeah, so sometimes you get the right numbers, but not all the time. But that's my recommendation. Is devel is great to develop in as well.
Yeah, we definitely get the right line numbers on the error. You may not be able to step, but the right line numbers, I don't think I've ever seen a case where you get the wrong line number.
Okay.
That's fair, yeah.
I like having consistent stepping, so I compile in two modes, oprof and debug, but that's just me. Everyone has their own development strategy.
you guys are all wrong. Do it my way.
All right, so we're going to try to figure out where this segmentation fault's coming from. We already got somewhat of an idea just by running in debug mode. We got a backtrace without line numbers, but now we probably want line numbers. So I'm running an LDB now, and you do that just by actually I'm using an old Moose environment package which provides LDB, but I actually don't like that one, so I use the system installed one. But anyways, yeah, so I specify what LDB I want to use, and then you have to add these dashes here if you're using LDB. If you're using GDB, it would be --args. But this is how you invoke LDB. And then when Moose aborts, it aborts using MPI abort. So we're going to break on MPI abort. And now I'm just going to tell the simulation to run. Okay, so we hit our error. So now you can ask for a backtrace. The short way to write that is BT. I've actually forgotten what the long form is. So this shows a backtrace of where the error came from, and this one's complete with line numbers. So I can step up the stack using up. I think you can even be lazy and press U. Oh, nope, can't do that one. Okay, so I went up the stack. You can keep going up the stack all as far as you want to, and then to go down the stack, you type down. Okay, so I'm getting an error from here. Let me try. So the original assertion error was assertion I less than size failed, access out of bounds in Moose array, size 0. Okay. So I'm gonna try to print this coupled. So you can see that LDB is very thoughtful, even underlines like the call that's happening here. So actually the error comes when we index at QP here. So I'm actually gonna print coupled conf and see what I see. And its size is indeed 0. So if I do any indexing at all on this thing, I'm going to get an out of bounds error, which is exactly what I got. So now I know exactly why my error, or I should say I know exactly how my error is happening. I know that something is quite wrong with this coupled conf. And that's in this example diffusion class. So let me go and actually search. Let me go look at that code. Okay, the C file here looks fine, looks pretty innocent. Don't expect anything wrong here. Oh, wow. Okay, here is the issue. So, like we've seen throughout our tutorial, when we couple in variables or we couple in material properties, we always store those quantities via reference, because things like variables aren't computed in the kernels, they're computed in the internals of Moose. And if you just initialize this thing in the beginning as its own object, that value is never going to change. It's never going to be touched again. Any change that happens to the underlying thing that you wanted a reference to wouldn't be reflected in something that you copied by or created by value instead of caught by reference. And so we caught our error. Coupled conf was created we just initialized it and constructed a brand new coupled conf instead of creating a reference, and so it never got resized, and that's why it was size 0 over here in the debugger, and that's why it caused a segmentation fault. So we have to make sure we store it by reference there, and then I can try compiling again, see whether we fixed our mistake. So something you see is debug mode is quite slow, but look, we don't get a segmentation fault anymore. We fixed our error. and the debugger definitely helped us do that. So again, I strongly encourage our application developers to get comfortable and familiar with the debugger. So these slides, if you kind of glossed over this here, I glossed over this information, but this is how you compile moves in debug mode. Again, with that method equals debug. And we showed how to run it again. If you're using GDB, do dash dash args. LDB just takes that dash dash. We showed how to break. We showed how to run, how to generate a backtrace. And then we saw what was causing our errors. So let's see, how long was I supposed to take? Another 30 minutes. Okay, well, I will talk about restart and recovery. I definitely don't know that much about these systems, but maybe enough to get myself in trouble. So people can hop in if I don't say something correctly. But these are pretty powerful tools. So what the names mean. So restart is where you run a simulation that uses data from a previous simulation using different input files. So this is kind of like something you plan for. You might like want to generate, say, like a flow field using maybe like the Navier-Stokes simulation, and then you may want to feed that in as data into like a transport calculation where you don't actually want to solve for the velocity field during that simulation. You just want to simulate some transport variable u, and you want to use the flow field from the previously completed simulation as an input into that new simulation. That would be a good example of where restart would be used. Recover is like in unplanned circumstances where you may want to resume an existing simulation after a premature termination. I often use this if I'm exploring like a bad solve and it keeps failing to converge and I want to try different PET-C options. I write to a checkpoint file and then I do dash dash recover with those new options. So more names and meanings here. A solution file, that's just a mesh format which contains field data in addition to the mesh. So we may read in solution values from that solution file into our restarted simulation. Checkpoint is definitely used extensively in like recover. That's a snapshot of the simulation. You'd probably also use it in restart. A snapshot of the simulation which includes all meshes, solutions, and stateful data. So it tries to capture everything. There's end-to-end restart. So in an end-to-end restart, what that means is that the number of processors used for the previous and current simulations are the same. And then an end-to-end restart would indicate that you're using a different number of processors between the current simulation and the previous simulation. So variable initialization. So this method is best suited for restarting a simulation when the mesh in the previous simulation exactly matches the mesh in the current simulation. And essentially all you need are initial conditions to initialize some variables, maybe auxiliary variables. This method requires only a valid solution file from a previously completed simulation. And Moose supports a non-matching end-to-end restart when using this method. So here's an example of how you would conduct such a restart simulation. So this doesn't look new. This is something that you should have seen already in the tutorial, is if you're creating, I guess we probably only use generated meshes, but we also read in file meshes. So in the mesh block, you just specify file equals previous.e, and in this case, this previous.e file is, in addition to the mesh, it's going to hold solution data information. And this file could be Exodus. This .e indicates it probably is Exodus, but it could also be an XDA or XDR file format. or it could also be a mesh checkpoint file. So there's the different kind of suffixes for the different IO. So .e for exvis, and then the xg, xtr, and then checkpoint. So we do have, I don't think we've talked about it. We do have different, or maybe we have, we've talked about split mesh. We have support for replicated and distributed meshes, where we essentially, in distributed mode, we've broken the mesh apart, and each process owns a different part of the mesh. In replicated mode, each process has access to the entire mesh. But for this kind of restart, it's only possible with serial replicated meshes. So in this restart context, how we do our variables block is a little bit different. We add these additional parameters. So if we're initializing it from this file, we use the initial from file var parameter, and then whatever we set on the right-hand side should be a name of a variable that exists in previous .e in this case, whatever file is provided to the file input parameter. And then the other parameter that you'll want to set, if you don't set this, I think it defaults to whatever the last time step is that's in previous .e. But you can choose to specify a time step that you want to initialize from. In this case, we're going to initialize it from time step 10. And then we can do this just as well for aux variables and elemental variables. So in this case, we're going to initialize from the variable named elemental, and again, we're going to initialize from time step 10. So this is for checkpoints. So advanced restart and recovering Moose requires checkpoint files, and it's very easy to tell Moose to generate these checkpoint files. So in order to do that using default options, so generating checkpoint on every time step and keeping the last 2 checkpoint files in your current working directory, you just have to add 1 flag to your input file in the outputs block. You just put checkpoint equals true. And once you have that there, you're going to continuously write out this checkpoint data. And then even if your solve was to fail, for example, you can easily recover the simulation from that checkpoint data.
So Alex, I just want to add there real quick that checkpoint might sound expensive, but it's really, really not. We have a great place, a great system in place in Moose for doing the checkpointing, so that we only save the pieces of data that are absolutely critical for recovery, and everything else gets rebuilt. So I highly recommend that honestly everybody just turns checkpoint on all the time. We've even toyed with the idea of making it on by default these days, because even for really huge simulations, those files are really small, it's really cheap to do, and the benefits of having the ability to recover if a node goes down or a solve fails or something along those lines are huge. So definitely highly recommend you use the checkpoint capability.
Awesome, thank you, Derek. So yes, for additional control over the checkpoint system, you can create a sub-block in your input file just as you can for every output type. And then there's different parameters that you can set there. So the interval parameter controls how often you output the checkpoint files. So if I say interval equals 3, we're going to write out checkpoint files every 3rd time step. And then num files tells Moose how many checkpoint states you want to hold on to. So like if I save at time step 1, I save at time step 4, and then I make it to time step 7. If num files equals 2, we're going to erase that checkpoint corresponding time step 1 when we write that new checkpoint corresponding time step 7. And then you can choose to save more if you want, or less. Num files equals 1. Num files equals more than 2. So this is advanced restart. So this is best suited for situations, again, where the meshes match between previous and current simulations, and again, where we want to load variables and stateful data from the previous simulation. This we have support for modifying some variables such as DT and time step when doing this advanced restart. If you don't try to change these, we'll just automatically use the last values found in the checkpoint files. For advanced restart, we only support end-to-end restarts. So doing advanced restart, if you use 4proc, you have to make sure that you're restarting with 4proc as well. And the relevant parameter there is in the problem block. You can specify like what restart file you want to use. So make sure, /latest. You can also specify a number for, if you are running restart, you can go and look at the files that are generated by checkpoint, and you should see like these numbers corresponding to the different checkpoints, and you can specify exactly which of those you want to restart from.
So Alex, I just want to mention, I think that comment there is wrong. Advanced restart definitely works with distributed mesh as well. I think that's probably an old comment, so.
Okay. Nice. Yeah, I think you're right. Reloading data. So everything that we talked about before were for matching meshes, but we can also we can load data from meshes that don't match, and you can do that using some objects that we have in the framework. So solution user object is the object that gives us that capability. So this is recover, not really related to reloading data. If you want to recover, like a bad solve caused your simulation to abort, if you've generated a checkpoint file with that checkpoint equals true in your outputs, then you can very simply pass the -- recover option on the command line, and then you'll essentially begin your simulation from the last successful time step, and then you'll try again.
All right. Good afternoon, everybody, again. Good to see you. I'm glad a lot of you, most of you, stuck around till the very end here, which is really appreciated. So this last topic here that we're going to talk about is multi-scale simulation, but that's what it is in the context of this tutorial, but it's much more than that. The actual system that's going to be used here, the multi-app system, does a lot more than only multi-scale simulation, but it is something that can enable multi-scale simulation. So let's jump in. So from a tutorial standpoint, this is what we want to do. We want to run a full simulation. We want to compute thermal conductivity and porosity from microstructure. So far, in everything that we've done, we've been working at kind of the macro scale, engineering scale, where we've used kind of these blended material properties for thermal conductivity and porosity based on the size of the spheres and how well they're packed, etc. What we kind of want to do now is look at actually doing a simulation down on the scale of the spheres themselves, as kind of a mini test in a way, like a mini experiment that will give us, we can test the thermal conductivity and porosity with the spheres themselves embedded into this geometry. So we're going to have an engineering scale and then a lower link scale where we're actually resolving the spheres and testing the thermal conductivity and the porosity of that microstructure sphere system. So that's the idea here. But to get there, we need to talk about a couple more systems in Moose. The first one here is the multi-app system, and these two systems work together. Multi-apps, they're called multi-apps, and then the next one is transfers. So let's talk about multi-apps first. And it is what it says there, a system for performing multiple simulations within a master simulation. That's maybe a little vague, so let's dig in here. In the beginning, Moose was originally created to solve fully coupled systems of PDEs. I mean, that was its intended purpose. In fact, I guess, the intended purpose was for tackling nuclear energy problems that had fully coupled systems of nonlinear equations that were particularly difficult to solve in any other way. And so that's what Moose was made to do. That's what it's been doing for 12 years. And it turns out, though, that after many years of doing that successfully, we realized that you don't necessarily need to or can solve everything that you want to solve as a fully coupled system of nonlinear equations. It's just the reality. And so a few examples of that, multiscale systems are generally loosely coupled between scales. So you'll have a solve on an engineering scale and then a solve on a lower link scale, and you might pass data back and forth. But solving those as one system, one nonlinear system that's coupled together is a difficult thing to do and not commonly done. I will say that we've actually done some things like that, but it's much more common to do individual solves on the individual scales and pass data back and forth. The other thing is systems with both fast and slow physics. So if you have something that's really slowly evolving in time, coupled to something that is rapidly changing in time, then it might be advantageous to actually split those solves so that you can take longer time steps with the slowly evolving physics and take smaller time steps with the rapidly changing physics. That way you can target each one with the time step size that makes sense for that system. Let's see, simulations involving input from external codes. So this is just a practicality. If you're going to try to reuse some existing physics tool that you don't want to replace with a Moose-based code, then you're going to need to pass data back and forth between this kind of external simulation tool, this non-Moose based, and your Moose based tool that you're creating. And to do that, you're going to need to be able to run these things simultaneously and pass data back and forth. So in order to cover some of these cases, the multi-app system was created, and what it allows us to do is create what I say is loosely coupled systems of fully coupled equations. So let me see what I have on that. So what I mean by that is that in the case that we're looking at here, where we have an engineering scale fluid flow heat conduction problem, and we want to couple that to a lower link scale fluid flow heat conduction problem to resolve the microstructure. At each one of those scales, we're solving a fully coupled system of nonlinear equations, right? And then we're going to couple them together in kind of a more loose fashion, right? So that's kind of what that means. All right. So the multi-app system works on a hierarchy. Let me see if I have a picture. Oh yeah, here we go. So this is an example of a multi-app hierarchy. I'll keep referring back to this as we go along, but just to give you a mental image here of what we're talking about, there's a master application, and then underneath that are what we call sub-applications, and you can have an arbitrarily deep hierarchy of solves and move data back and forth between the levels. So each app is considered to be an independent solve, or each app instance is an independent solve. There's always a master, which is the input file that you actually run on the command line will create the master application. And then that master application can have any number of multi-app objects, all right? And each multi-app can represent many sub-applications. So let's relate this back to our tutorial again. So in our case, it makes sense for the master app to be the engineering scale because there's only one engineering scale solve. And then you're going to want to have multiple microstructure solves within there to sample the microstructure of the packed column. And so that will be just one multi-app, actually. And then within that multi-app, you'll have many sub-apps, and they'll be located at different points within the master application, okay? And whenever we say many here, we really mean many. Multi is very serious here. So we've run tens of thousands, hundreds of thousands. I think Andrew's even run millions of Moose-based apps simultaneously.
We got a billion now. We did a billion.
A billion, there we go. So that multi, we really mean multi here. These things get spread out in parallel across the cluster, et cetera, and they get executed optimally, as efficiently as possible, using all the computational resources that you have. So you can really make some really massive simulations with this. Each of the multi-apps can solve for different physics from the main application. So they can be another instance of the same application, maybe with different boundary conditions or a different mesh or different material properties or something along those lines. It could be another Moose application. So Moose-based applications can actually reuse each other and run each other in this multi-app system. And it can also be an external application, so a non-Moose-based application can fit within this as well. And as I mentioned just a moment ago, this hierarchy can be arbitrarily deep. So a sub-app itself can have its own multi-apps, and then you end up with a multi-level solve like this. So here we have a master application, and there are two multi-apps within it. And this multi-app has two sub-apps, and this multi-app has three sub-apps. And each one of these sub-apps itself has their own multi-apps with two sub-apps each. And so what this does, you could think of this, for instance, as, let's say this is a, let's give a good example. Let's keep going with our example. So let's say this is our packed column simulation that we've been running. And then underneath there, we might have this kind of sphere level simulation where we're resolving the spheres. And then underneath that, we could actually have kind of like microstructure simulations that are looking at, let's say, like the sphere water interface and trying to get the heat flow in and out of the spheres correct. Okay, so you can have kind of multiple levels of solves here. These also don't have to necessarily be on different scales. So they could all be on the same scale. And maybe it's just the case that you want to decouple these solves. So you want to decouple the solve here from the solve here, and maybe a third thing you want to decouple here, right? So it doesn't have to be a multi-scale situation. But it's kind of easiest to think about the multi-scale solve case. Okay. Anything else to say here? Oh, okay. The other thing to say here is that I mentioned parallelism. The sub-apps will all be spread out across the number of MPI ranks that you're currently running on as best they can be. So in this case, if you're using, let's say, 6 MPI ranks, what's going to happen is all the sub-apps from multi-app 1 will get spread across those 6 MPI ranks. So this one will get 3 MPI ranks, and this one will get 3 MPI ranks. And then over here, these 3 will be also spread across those same 6 MPI ranks. So this one will get 2, this one will get 2, and this one will get 2. And at any one time in the system, only one multi-app is executing. Okay, so when multi-app 1 executes, both of these sub-apps actually run simultaneously on the MPI ranks that they're assigned, okay, at the same time. Meanwhile, these are kind of sitting dormant. And then whenever this is done, this one could run. It depends on what execution order we've defined here. And then all 3 of these will run simultaneously using those 6 MPI ranks, okay? Now, if things don't quite fit, let's say you're using 2 MPI ranks to run this problem, what's going to happen is this one will get 1, this one will get 1, and then over here, you're going to have one given to this one and one given to this one, and then this guy here is going to get stacked up on one of the other MPI ranks. So one MPI rank will actually get 2 sub-apps that it has to execute whenever this multi-app executes. So it will try to use your MPI ranks as best it can to spread the sub-apps out. And this does go to massively parallel. You can run it up to, I mean, I don't know what the largest is. What's the most number of ranks you've used, Andrew, for a multi-app solve?
Oh man, that was run by Wen, but I think he was on definitely thousands of cores to do that billion-1.
Yeah, I've used about 6,000, but I mean, I have confidence in it all the way up to about 30 or 40,000. I don't think we tried anything larger than that at this point, but there's no reason why it shouldn't work. So you can really use a lot of compute power this way. All right. As far as input file syntax, how does this work? How do you actually set this up? It's set up in the input file just like any other Moose-based system. So there's a multi-apps block at the top level. And within one multi-app, you have to set the app type, okay? And the app type is the name of the application that multi-app is going to be representing. So I don't remember, what's our app type here? Thermo Darcy app or something along those lines? So
yeah, correct.
Whatever the app name is goes here. Positions is where within, so within the master app, the positions are where the sub applications are located, all right? So in a microstructure sense, that really makes sense because your lower link scale solves need to be associated with some position within the engineering scale space, and that's what positions sets. If you're solving on the same link scale, then most often positions will probably just be something like 0, 0, 0 because there's not really an offset between the domain in the master app and the domain in the sub app. They probably overlap. But you can have all sorts of different configurations. But this is essentially the offset of the sub app to be within or be positioned within the master application. We'll see some examples of this in a moment. Execute on works just like Andrew was talking about earlier for user objects. This controls when the multi-app will execute. So you have choices. You can do things like run the microstructure simulation first, then the engineering scale simulation, or you can do it the other way around. You can run the master first and then the multi-app afterwards, right? And you can control that based on using these guys like time step begin, time step end. And you can even run them, you could even run a multi-app only on the initial condition, for instance. So you could run a multi-app to actually solve for the initial condition and then utilize that in your, to set up your initial condition for your solve, which does happen. People are doing that. Linear and nonlinear is not very popular. I don't know of anybody that's actually trying to do this, but you could use nonlinear to kind of like inject the coupling into the middle of the Newton solve. It will slow down your Newton convergence, but it could actually speed up your overall convergence of the entire system. That's a strange thing, but it is technically possible to do. Okay, input files. So whenever you're setting up these sub apps here, you have a choice. You can either provide one input file for this multi-app block, and that same input file will get used for each of these sub apps, or you can provide one input file per sub app. It's definitely a lot more common to provide one input file for the multi-app that's used for all of the sub apps. And then what happens is the difference between the sub apps is usually where they're located within the master app. So even though they're running the exact same physics and the exact same input file, they'll be getting data fed in from different parts of the simulation. So they'll be running separate simulations, okay? So those are your choices, either one input file or one per sub app. Okay, so this is just an example block here. We're using the transient multi-app. There's the multi-app system itself you can plug into and specialize. That's a very advanced capability that I don't recommend upfront. You'll probably want to use this transient multi-app to get started. The other one that a lot of people use is called full solve multi-app, and that will actually solve a transient sub-app all the way from the beginning time to the end time, all the way through, every time it's called. But transient multi-app is typically what you want. That's going to step along with your master app and solve the physics. Okay. So app type here, yeah, is Darcy Thermomech app. This name comes from the name of your app object. If you go look in the base class, in the base directory, under include base in any of a Moose-based application, you'll see some class that's probably named something like some animal name app, okay? Or if you go look in the tutorial, it'll actually be named Darcy Thermomech app. You'll see a class that's named that, and that's where that name comes from. So this is where we call out what kind of application or which application we want to be running. And then positions, this is where within the master domain each one of the sub apps is going to be located. The other thing that positions does is you notice that there's no explicit definition here of how many sub apps to run. So positions actually defines the number of sub apps that are going to be created as well. So there's 1, 2, 3, 4, 5, 6. So there's 6 positions given here. So that will actually create 6 instances of the Darcy Thermomech app. And each one of those is going to be associated with a different position within the master apps domain. Then you can provide an input file, and here we're choosing to provide one input file that's going to be used for every instance of this application. And then we're going to say we're going to execute on time step end. And what that'll do is that means the master app solve is going to happen first. And then after that, this multi-app will execute every time step. Okay. Another parameter here that you definitely want to know about is you can provide a positions file instead of putting them right in the input file like this. It really is the case. I mean, I've used 50,000 sub apps before, and you don't want all those in your input file. So you can provide a file that has them all listed out instead, if you're running that many. All right, we already talked about parallelism, so I don't think there's really anything new there. So let's continue on. Well, before we continue on, are there any questions just about the multi-app system itself? It's just about running multiple applications in parallel and having this hierarchy between them. But we haven't really said how we're going to utilize that yet.
Derek, there is a question on Slack. You might just go read it rather than me try to explain it to you.
All right, I don't have that open. Give me just a second. You're talking about the question about can you distribute binary apps?
No, in the questions channel, is it Ian has one, and there's another one coming in. There's another one coming in, I think so.
Yeah, so there's a question from Pranoy here. Let's start there. Is there an easy way to create sub apps at QP locations for all the elements? I think currently we don't have a multi-app that's built to do that in Moose, but it would be really, really easy. As is mentioned here in his question on Slack, he mentions the Centroid multi-app. That creates one sub-app located at the center of every element in the master apps domain. So that's already pretty close. If you take a look at how that thing is coded, it would be trivial to set it up to create a multi-app at every quadrature point instead. What I'll say about that, though, is that every quadrature point is kind of insane. There are a whole bunch of quadrature points, especially in 3D. So make sure that you really need that before you're running off to try that, because it's going to create a whole bunch of sub apps. All right. It'd be fun to try, but yeah, it's gonna be computationally expensive. All right, let's see here. What else do we have? Yeah, so Ian was asking about the execution of this tree here. I think I tried to explain, but I didn't really go through what happens with the multiple levels here. So the order of multi-app 1 and multi-app 2 will be specified by either their execute on or just kind of arbitrary order. So if both of these are set to execute on time step end, then the order of execution between multi-app 1 and multi-app 2 is actually arbitrary. It could be this one first and then that one, or this one first and then that one. We don't guarantee an ordering at that point. Once multi-app 1 starts executing, though, this entire subtree will have to execute and finish before multi-app 2 or the master would execute. Okay. So yeah, hopefully that explains it. So when multi-app 1 is executing, it's both of these two sub-apps will execute simultaneously. And these two multi-apps actually don't know anything about each other, and they're running on separate MPI ranks, and so they will actually execute simultaneously, which means that these two sub-apps and these two sub-apps, also all four of these things don't know anything about each other, and they will all execute simultaneously as well. I hope that's clear here. The not knowing anything about each other is one of the powerful things about the multi-app system. This app that's sitting in the middle of this tree here has no idea that it's actually running within the multi-app system. And that's like that on purpose. It's a design goal of the system. And what that means is that we can actually come prune this part of the tree off and actually just run this by itself to make sure that it's working. And then once we get it working, we can link it in here to this larger solve and run the master input file instead. So this entire tree is decomposable here, and you can run any portion of it by itself. So that's a feature of the system. All right, let's see here. What else? Yeah, there's a question here about the multi-app system working with external apps. Andrew, I don't know if we have any of the Moose Wrapped app slides in here. Do you know?
No, we don't have any slides on that. I'll get the website and put it up there, and I think we have a page, but you should say a few words, I guess.
Okay, yeah, working with external apps, the way that basically works is we effectively wrap the external app up in a really small interface that then makes it look like any other Moose-based application to the multi-app system. And so then that external app can just slot in here as a sub-app in one of these multi-apps. And as far as this system knows, and as far as every other thing in Moose knows, it's actually, everything else in Moose thinks it's just a regular Moose-based application. And there's just a little thin layer that does kind of a translation between Moose and what that external app is expecting. And that's a capability that we call Moose Wrapped Apps, or MWA. There's a whole set of interfaces for helping you do that.
There's a hand raised there. Derek, do you want me to get it?
Where's it at?
So just following up on the external app question. So what if the external app was only a serial app? Is there some control for an MPI most application that the sub app can just run on a single processor?
Yeah. So actually, there's a couple ways to do that. Let's see. So what happens is each one of these sub apps ultimately receives its own MPI communicator and will be executed on those MPI ranks. And typically we're dealing with an external application that is parallel, and so we can give it that MPI communicator to use, and so we can actually run external apps in parallel using this system as well. But if you have an external app that is just serial, actually in the input file, you can actually restrict the multi-app to just running on one processor. And then that'll execute the sub apps will only execute using one processor each. So there's an input file parameter for like max procs or something like that, where you can restrict the sub apps, the number of processors the sub apps are using.
And if I can just follow up, your MacPy app was supposed to be an interface to LAMP. Do you know what the status is? I haven't seen any updates on it for a while.
I really don't know. I would definitely send an email to the Moose mailing list about that, or contact Daniel Schwinn probably directly. Does anybody else have some information on that? No. Okay. Sorry.
What was the question, Derek? I was reading something else at the same time.
Oh, it was he was asking about the MagPi app. I'm not sure what the status of that is. So
That's open source, so I think you can go to GitHub and look at that, I think.
Okay. But yeah, I would definitely ask questions about that on the mailing list. I'm sure you'll get a few responses. Okay.
Absolutely. Thanks.
Yeah. Let's see here. It looks like everything else has kind of been answered here. So if there's nothing else, I think I'll move on here and talk about the transfer system, because multi-apps by itself isn't actually very useful unless you're going to move data back and forth between these applications. So a hierarchy of applications to execute doesn't actually give you a multiscale solve or a decoupled, loosely coupled solve. You have to move data back and forth. And so the transfer system is what is utilized to do that. The typical way to transfer data is to move data. First of all, the important thing to know about transfers is that they only happen up and down the hierarchy here. Okay, so a transfer can only go up and down. There's nothing left and right. And sometimes that can be a limitation, but you can typically get around it by structuring your tree in a different way. If you're having trouble figuring out how you want to structure your multi-app tree, definitely contact us. The reason for the data movement only being up and down the hierarchy has to do with what I was talking about before, which is that none of these apps even know that they're working within a multi-app system. So this sub-app couldn't go get data from here or even push data to here because it doesn't know that this thing exists at all. And that has lots of advantages, but it has this disadvantage that data must go up and down only. So if there's some data that needs to go up to here, and then if there's some data that needs to go from this multi-app to this multi-app, it typically has to go back to the master first and then come down over here, just to let you know how that works. So the data movement back and forth is usually handled within the auxiliary and post-processor system. So a typical transfer will fill an auxiliary field with data, all right? Similarly, it can fill a post-processor value with data instead. And then applications can couple to that auxiliary field or that post-processor value in order to retrieve those transferred values. Let's see, yeah. Okay, so there's a few different kind of broad types of transfers. The first one is kind of like field transfer. So this is where you probably have two domains that are on relatively the same scale, and you want to move a whole field from one domain to the other. So this is some sort of field interpolation transfer. The way we typically do this is something along the lines of the source field will get evaluated at positions, and then those evaluations will get moved into an auxiliary variable on the receiving end. Let's see here. All the multi-app transfers take a direction to specify the flow of information. The two options are either from multi-app or to multi-app. So a to multi-app transfer that's in the master application will transfer data from the master down. A from multi-app transfer that's in the master application will pull data back up from the multi-app, okay? And it's important to note that transfers target multi-apps, not sub-apps directly. So you say, I want to transfer data from the master to multi-app 1. And what's going to happen is that the transfer will automatically figure out which data to send to all the sub-apps underneath multi-app 1, and that transfer to all the sub-apps underneath multi-app 1 will happen simultaneously. And if you're running in parallel, it will happen simultaneously in parallel, in fact. So all the sub-apps underneath multi-app 1 will receive their data at the same time. Now, again, this makes sense if you're thinking of this kind of multiscale situation where we have our packed column on the engineering scale, and let's say we have a dozen microstructure simulations located within that packed column. What we want to do is just specify one transfer that says, you know, I want to send down temperature from the master app to all the microstructure simulations to inform them of the temperature at the position that they're at in the master app. And so that transfer will actually sample the temperature at each one of the positions of the sub-applications and give each sub-application its own temperature. And it'll do all that simultaneously in parallel. Okay. Let's see here. So that's what from multi-app or to multi-app is about either pushing or pulling data. Looks like I have, it's kind of off the bottom, but so this is what the transfers block might look like. So here we have one transfer that we're calling from sub. We're specifying the source variable. This is the variable in the sub application. The direction is from multi-app, so we're going to actually pull data back from a multi-app here. And the variable option here is the variable that will be filled by the transfer, okay? So this is a variable within the master app that's going to be filled with data from this variable within the sub application. And the transfer type that we're using here is multi-app mesh function transfer. And what that thing does is it's going to evaluate the sub applications field at all the nodal positions by default. Well, if you're transferring to a nodal variable, it will sample the sub-application field at all the nodal positions within the master app, and then pull those values back and set them within this nodal aux variable as its values. Okay. I hope that's clear. Multi-app mesh function transfer evaluates the source field at the destination's geometric points, whether that's element centroids or node points, and then pulls those values back from the source field. And then you need to specify which multi-app you're doing this transfer to or from here. And execute on, this is weird. we should remove this from this slide. You shouldn't have execute on in your transfers block. By default, the transfers will happen at the correct time based on when the multi-app is set to execute on. So if the multi-app is executing on time step end, the transfers to the multi-app will happen on time step end, but right before that multi-app executes. The transfers from that multi-app will also happen on time step end, but they will happen right after that multi-app is executed, okay? So that the transfers happen at the correct time. That's all you have to remember, and you don't need an execute on for them, okay? And then the next one is just an example of, no, it's the same thing. So let's keep moving. So that's one type of transfer, moving a field back and forth between a master and a multi-app. Another one is user object interpolation. I don't think I really want to go through this. This one's kind of advanced. Let's leave that for later. Post-processor transfer, though, is a really important one. This is often used in the multiscale setting. So this is where you're going to have kind of one value, like just one value, not a field, but just one value that needs to move from the master application to the multi-app, or the other way around. If you're taking, for instance, the temperature at the position where the sub-app is, and you want to push that down to the sub-application, that's just one number. And the type of transfer that you'll want to use is probably something along these lines. And what it does is it will sample in the this particular multi-app, this particular post-processor transfers a post-processor value. So it'll actually move the value from this post-processor to this post-processor. But there are other post-processor transfers that will do things like sample a field and then fill a post-processor value on the receiving end with the value of that field. So that's really useful when you're dealing with multiscale simulations. Looks like that's all we have here on transfers. There's definitely a lot more to the transfer system, but the important parts are here. And let's see, what else is next? Okay.
Derek, you have a couple questions that you might want to address.
Yeah, absolutely.
One of them is, if the source variable is an elemental variable and the point, I'm guessing where it's being sent is on the nodes, what will happen? What error, or will it take advantage of values on all the connected elements?
Well, it kind of depends. So let's say the two, let's talk about the most general case where the two meshes on the two different apps are different. Okay. What's going to happen if you use something, and the answer to this is that it's going to depend on what kind of transfer you're using. So if you're using the mesh function transfer like this, it will work perfectly fine in that case. What will happen is, let's say the receiving end is nodal and the source is elemental, like stated in the question. The nodal, what will happen with mesh function transfer is that the field made up of the elemental values will be sampled at the nodal positions for the receiving end. Okay, and so if it's a constant value per element, then that means if the node falls within that element, it's going to get whatever that elemental value is sent back to that node. Okay. I think the question is kind of asking something along the lines of, if you have the same mesh on both levels and you're trying to transfer elemental to nodal, what you get, it will work, but what you're going to get is maybe not what you want. You're going to end up with the transfer will, in this case, the multi-app mesh function transfer will literally just pick one of the elements that's connected to that node and use its value. The way that this works is it uses kind of a geometric search algorithm to find where in the source domain the sample points fall. And so that geometric search algorithm will end up picking one particular element to pull the value from, if you're trying to pull from an elemental field. And so it's going to sample one of those elements' values. So that's what you would get back in that case. And it's going to be effectively random, which means that's probably not a good idea. I would probably revisit what you're trying to do there. But it won't fail. It's just going to do something you probably don't want it doing. Let's see here. There's another question here about, do you lose information when you send data? The answer to that is highly dependent on what data you're sending and what transfer you're using. So if your meshes are exactly the same and you're transferring from fields that are supported by exactly the same shape functions, so let's say a nodal auxiliary field to a nodal auxiliary field, you can actually use what's called a multi-app copy transfer that just directly moves the values from one application to another, assuming that they have the same mesh and that the storage is the same on both sides. In that case, you don't lose any information at all. The source and destination fields are exactly the same. But with many other combinations where you have different meshes in each of the master and sub apps, I don't know about lose information, but you're going to get some sort of an interpolation, or there will be some error in the transfer most likely. That still depends on how you're transferring and what you're transferring, how the meshes line up, etc. But you can definitely introduce some transfer error here. You can minimize that by choosing the right type of transfer, choosing the right type of field on the sending and receiving sides, and also it depends on how your meshes line up as well. If they're nested within each other, you have better options than if they're just completely random and not related to each other in any way. So hopefully that answers that well enough. Is there anything else? Any other questions right now? So this is a really deep capability. It's being used for many, 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 many different things. I'm always amazed at the things people are doing with it. It's really just a thing. You'll have to play with it and try it and use it if you have one of these scenarios. And then contact us on the Moose users list. And there's a lot of people using multi-apps on there, so you can get some good advice on how to set these problems up. All right, I think that's, it does look like we have another question. Yep, go ahead, Srinath.
So just a quick question. What about large deformation problems? So you're defining these sub-apps based on some kind of initial position. So what happens when there's large deformation?
Yeah, I'm surprised I'm missing my slides here that show the positioning of the sub-apps. Maybe I should just go pull the documentation up for multi-app. So there's a little write-up here on the positions, wait, I now forgot the original question. What was it?
Large deformation.
Large deformation, yes. Okay, so what happens there is that the transfers have options for. Okay, let's back up a little bit. In the mesh displacement system that I believe Alex talked about, you specify the displacement variables that are going to be moving the mesh, right? And what happens within Moose is that we still always keep the reference mesh configuration, and then we also have a deformed mesh configuration, right? And those are kept internally within Moose. And you can always access one or the other depending on what you're trying to do. So in the transfer system, you actually have the option of transferring to or from either the displaced or the undisplaced meshes effectively, right? So what happens with displaced domains is kind of up to you. Now, maybe it would be better if I draw it here. I could draw what's going on, but I do want to mention something that's kind of subtle here, which is that if you're transferring from a displaced frame to a mesh that is not displacing, what's happening is that the mesh that's sending data is kind of moving across the mesh that's receiving data. So the actual points that are being transferred from will be changing. If you're transferring from the undisplaced frame, then no matter how the displacements change the mesh, that point that you're sampling from is always within the same element. So the point itself that you're transferring from actually moves with the mesh. It's kind of a subtle thing.
I see. No, I can imagine that that's why I asked the question. It's rather subtle, but if there is the capability, I think I mean I can definitely request more assistance in the most users group, which is totally doable. I had another question, which I haven't looked through the multi-app documentation at all, but do the users have access to this geometric search API in any sense?
Yes. So the geometric search system is a pluggable system, just like everything else in Moose. And there are several objects that you can just grab inside of your own Moose-based objects. So you can get things like the nearest node locator, which will give you like the nearest node on some surface that you specify you want to track. There's also the penetration locator, which will give you like the distance from where you are right now to a surface and various other things. So, and you can pull those objects directly into, let's say, your boundary condition objects or your kernels, if that makes sense.
Yeah, that makes total sense. Thanks.
Mm-hmm. So while I have the positions thing up here, I will just mention that this is what we're talking about when we're talking about the sub-application being located within the master apps domain. So here the blue is the master apps domain, and the green triangle within its own coordinate system starts at 0, 0, 0, and goes to 2, 0, and then up to 1, 0. So these are the local coordinates inside that mesh for the sub-application. But by specifying that the position of this application is at 320, what it's going to mean is that to the transfer system, this application is effectively is going to be located at this position within the master apps domain. So if we try to send a field from the master application down to this sub-application, this area where the triangle is where those field values will come from in order to fill that field in the sub-application. Now, this case where you have non-matching domain sizes that are on about the same scale is fairly rare. Usually if the domains don't match, it's much more common that you're doing a multiscale simulation, in which case the position is just the point, just like the individual point within the master applications domain that microstructure solve is existing at. Okay. But the positions are used kind of implicitly in the transfer. You don't have to say anything else in the transfer. You just say, I want to transfer from this app to that app, and the transfer takes into account all the offsetting from the positions. All right.
I think if we want to show off the example, we should probably switch, and I can do that pretty quick. But
go for it. Thanks for all the questions.
Okay, so we have about 20 minutes left. Derek did a great job at explaining the system. Like he said, this is a huge capability for us. We use it for all kinds of stuff. I do a lot of work with the stochastic tools module, and we're actually using this just as a way to run lots and lots of simulations and pull data in just to do statistics and circuit modeling and different things like that. So it's really quite powerful. So what I'm going to do now is take all that information that Derek presented and kind of show you how we can use this in our tutorial. And this will be a pretty quick run through. So I'm going to skip probably a lot of the code and just kind of show the results of what we're doing. But first I'm going to set the stage. So this first C++ object that just shows up right away is what we're going to do with the problem is we have the pipe, and along the length of that pipe at 6 different locations, we're actually going to do a little microstructure calculation where we resolve the spheres. I guess we're doing it in 2D here, so circles. And given some temperature criteria, we're going to say that those circles, the steel slowly corrodes or disappears away. And the code for doing that is in this random corrosion object. And I'm not going to spend any time going through the code. If you just kind of read the comment here, it creates artificial temperature-driven corrosion. So this is a somewhat contrived, not somewhat, it is a contrived corrosion. There's no physics in this corrosion, so that's why it's called random corrosion. But it demonstrates, what could maybe be a physics process. Maybe sometime in the future we can come up with something a little bit smarter, but this is really just a demonstration. So this is the source code. If you want to go take a look at it and run this example, please do. And the first input file we're going to look at is just on the microscale, and we'll see the results of this. And this is really important, as Derek mentioned, that these sub apps and master apps, especially the sub apps, are designed, generally speaking, they don't know that they're being run by some sort of other application, the master, I guess in this case. And so that this input file can run by itself and it'll give you some data. But it's also set up to run from a driver or a master application. So what we do here is we set up a generated mesh that's with 10 by 10 elements, and it's relatively small, 0.1 by 0.1 in, I think we're in millimeters here, centimeters, I can't remember. And then we're going to add an adaptivity block. We've seen these adaptivity blocks before, and we do this initial marker thing. And we talked about this earlier in the day that we were going to show this initial adaptivity. So we're going to do that same gradient jump indicator and error fraction marker, but we're going to do it all mostly on initial and a little bit as the solve goes along too. And this problem it's a temperature problem. So we're going to solve for temperature, and then we're going to have some auxiliary variables, which I probably won't say too much about, but that's fine. I want to get to the meat of this. And really what this thing is doing is it's performing a heat conduction solve. So just pure heat conduction. And we have a rigid temperature boundary condition on the bottom and a flux boundary condition at the top. And if people are familiar with that scenario, given those two boundary conditions, you can compute an effective thermal conductivity over the whole domain. And that's what we're going to do. So that's what all this problem is doing. And it's important to note here that we're using this post-processor version of the Dirichlet boundary condition. So this is where the data that's going to come from the master is going to come through. So the master application is going to set the temperature in the post-processor, or the incoming temperature in the post-processor, and then this boundary condition is going to use that temperature to enforce the Dirichlet condition. And to do this solve, we actually use our packed column again, and we've made some modifications of that to be able to use a phase variable for porosity, which you could look in the code if you want to see more about that. And then finally, the post processors to really look at, we have the temperature in. This is what's going to the master is going to send data to that's going to use, and if the master is not there, it's going to use 301. So that's kind of the default. And then this is the thing that's going to get sent out of this, or not sent out, that the master is going to retrieve from, and is effective thermal conductivity. And this is a built-in object in Moose, the heat conduction module, already for doing this exact calculation. This is a pretty common thing to do. And the rest is stuff that we've already talked about. But this does actually introduce initial conditions as well. And this comes from the phase field module. So I know this is pretty quick. So again, this is mainly a demonstration. I'm just going to show you the capability of the system. So we can actually go run that input file if we had time. I usually do that. We're not going to do that today. So if you were to run this input file, after the initial adaptivity, your mesh ends up looking like this, where you get 0 equals water. So that's the darker region, and 1 is your resolved close packed spheres or circles. And what happens is over time, we're just going to randomly pick points in the mesh, and it's going to switch from 1 to 0. And so your mesh, the amount of the porosity then obviously changes. And then you can see the result of that change here. So the blue line, this porosity, is going up as material is getting removed. And then the effective thermal conductivity is dropping because heat moves through steel better than it moves through water. And you imagine it's going to kind of reach steady state where it's just thermal conductivity water. So this is what's happening at all the microstructure calculations in this next part. So at this point, I would talk about all the changes we made. The packed column is actually not that many changes. It's kind of these bits here at the bottom where we optionally can use variables to do 2 different calculations. Optionally use a variable for thermal conductivity, and optionally use a variable for porosity. If you're interested in how I do that, please just go take a look. It's really not, doesn't add too much complication to what we already did. And then at this point, we're going to we got the sub application running fine, and you probably want to create a test for that file and that it works properly. And then we jump to our master application, and this is the same problem we finished up in step 9. It's got all the stuff in it: thermal mechanics, it's got temperature dependent fluid properties, all the stuff. And what we add to it now is the 2 multi-app and a transverse block. The multi-apps block is this sets up the multi-apps at various positions along the length of the tube or pipe, and it says go run this input file. This is literally the input file that we were just looking at. So we didn't change anything about that input file, so it works by itself, or it's going to work plugged in here. And we're going to do this at the end of every time step and feedback thermal conductivity. And then the transfers, where you're going to use 2. One of them is going to go, this one gets the K effective from the sub application. So the direction is important from sub application. Which multi-app micro, that's the name up here, micro. What are we transferring to? The variable K effective, that's in this file. And then we're going to get the post processor from the sub application. So what this does is just doing a nice interpolation. So it's going to go grab a post processor, from all those sub-applications and use their position, like Derek mentioned, to perform some sort of interpolation into a k-effective auxiliary field in the master application. And then on the other end, we're going to basically do the reverse with temperature. So as the temperature of this thing is changing, we're going to feed that temperature down into those sub-applications to use it to compute the k-effective. So this temperature that's passed in from a variable, the source variable temperature, gets passed into that receiver post-processor, which ends up getting used as that Dirichlet boundary condition. Simple, right? No problem. We introduce controls. I'm not even going to talk about that. There's some decent documentation on what this is doing. This is just turning things on and off at start time 0, because if you remember, we ramp up the problem from -1 to 0 for the boundary condition, and then at time 0, we actually turn on all these transfers. So with that, we will run this, and we get this really nice result in this video. This image is now famous. We put it in our latest Moose publication, so this is where it comes from if everybody's looked at that publication. So what's happening? In step 9, Alex basically showed you this result here. This is just the temperature part of it. And if you look closely, this thing is actually expanding. This is supposed to be 50, not 500. And this is time progressing. And then these are all the 6 different sub-applications. And you can see they're all dissolving, and or corroding, we will say. And they all are kind of doing it at different rates. As they warm up, so as that temperature field goes across, they become more, it corrodes faster and faster. And this plot down here is the effective thermal conductivity coming from each of those 6 calculations. And you can see they all drop, but they all start to level off at the thermal conductivity of water. So that was, 10 minutes, just a demo of what we can do. We spend a little time going through the code, but honestly, it's probably better that we didn't, because sometimes I think people get a little confused at what's happening in there. It's better maybe to go run it yourself and spend some time with the code and things like that. So at this point, what we really do is, so we're not even talking about custom syntax. This is if you actually want to wrap up syntax in your input file and make it a little more compact, like we've already seen with the tensor mechanics module. We do some of that for this tutorial. Debugging. So now we're basically done with the tutorial, and the last thing we usually do at the end of the day in our trainings is go through all the available systems, which we have seen a bunch. We've talked a little bit about constraint system, control system. We've actually mentioned the damper system. We have a whole discontinuous Galerkin kernel system in Moose. So if you're doing discontinuous finite elements, we have some tools for that. The Dirac kernel system is for point sources. Distribution system, this goes into the stochastic tools. We've seen executioner, we've seen function. Derek briefly mentioned this. We have a geometric search capability that's customizable, and it's a lot of great capabilities. Initial condition we've seen. Indicator is adaptivity. Interface kernels, this is another way to add physics to your system. This is kernels that operate maybe between 2 subdomains, like you have steel and copper, and you need to enforce some sort of physics in between the two. Kernel system, we've obviously seen. Line search system, we've talked about that in the numerical section. This helps with the solver. Markers go with adaptivity. Material, scene, mesh generator. This is kind of the new mesh. This is where you should be looking if you're looking at doing some mesh generation. Don't do that. Multap we've seen. There's a whole nodal kernel system for solving PDEs that are residual contributions directly at a node. Output system we've seen quite a bit.
That's not quite right there. The nodal kernel. I think that's why you got tripped up there. It's for solving ODEs at nodes.
I thought that we had an ODE kernel for that. Is that
that's a separate thing. That's for solving global ODEs.
Oh, okay.
The nodal kernel system allows you to solve an ODE like at every node in the mesh.
Okay.
So they're disconnected from each other, but they're integrated in time.
Okay. Thanks. Parser system, if you actually want to change the input file system, use a different input file format, you can do that. Nobody's doing that. This is for finite. This is for partitioning your mesh. I think we've talked about that in a few instances, that how we partition mesh with parallel versus distributed. You can create a custom partitioner. Seen that. Preconditioner system, you can make your own preconditioner as well. Predictor system, this is again goes with your solve. This can help your selecting the next iterates for your solver and can help do performance. Problem system, we've seen that a little bit. Relationship manager system, oh man, I'm not even going to talk about that. This is for again parallel management and ghosting and things like that of element information across processor. You use this. Sampler system, this goes in stochastic tools. Split system, this is again for preconditioning. You can do different preconditioning and different parts of your matrix for your problem. We've seen time integrator, time stepper, transfer we've seen, user object we've seen it. That's it, easy, done, 5 minutes early. I don't know, Derek, you want to add anything to all that stuff, capabilities that we want to briefly mention to people?
No, I think the takeaway from that ridiculous stream of capability is just that there is a lot more to Moose than what we've told you about yesterday and today. There's so much capability in all these other systems that we just can't even get to in this kind of a training session. So what that leads to is, if you're running into a limitation or you don't know how to do something, definitely contact us on the mailing list, because we can point you to some of those other capabilities, some of the other systems that we didn't get to. We can give you pointers on how to solve those kinds of problems.